we have already seen that we have discussed how one hot encoding works, right? And if I probably talk with respect to different. Hello guys, we are going to continue the discussion with respect to NLP. In our previous video, we have already seen that we have discussed how one hot encoding works, right? And if I probably talk with respect to different types of ways how we can convert a text into a vectors, we had completed already one hot encoding. Now we are into the second, that is bag of words. Now let's go ahead and understand how bag of words actually work. And this is super important because this is the technique which you can do simple tasks like sentiment classifications or whether basically in short a text classification kind of task easily you'll be able to solve. Okay, some of the applications, famous application like whether a mail is a spam or a ham, everything will be able to solve it. Now let's say that I have a data set, okay, and in this particular data set, I'm just saying that this is a positive or negative statements. Now in this particular data set, I have three sentences. Let's say he is a good boy, she is a good girl, boy and girl are good. Okay. Now all these are like positive statements. So the output of all this are ones, right? In supervised machine learning, we really need to know the output also. Now let me go step by step and show you that how bag of words are implemented. So this is basically the step one, right? I have the data set. Now let's go to the step two. Now what happens in the step two is that once I go over here, right? There's multiple steps that actually occur. And initially we should also go with respect to this. The first thing is that if I probably consider two things are going to basically happen. First of all, we will lower all the words, and usually all the steps we will even be doing for all the other techniques also. First, we will lower all the words, and then we will probably apply stop words, right? And this also I've already shown you. Now, when I lower all the words, let's say my sentence one, right? My sentence one now becomes, I'm going to take only this text data. I don't have to worry about the output because later on, once we convert this text into vectors, we can apply it to the machine learning algorithm. So in the sentence one here, you can see as soon as I lower the words, what will happen? This all will become smaller. Now, why I'm doing this because there may be some repeated words. Now, in this particular case, the capital with capital B, you have boy. Here, small b, you have a boy. So both these words are same, but since it is in uppercase, this will be treated as a separate word. So we really need to lowercase all the words. So I'm just going to write lowercase all the words. Now, in sentence one, after lowering casing, so what will happen is that this all will become smaller letters. Then once we apply stop words, now what happens in stop words? These all words like he, she, is, a, you know, it will get deleted, right? Because we don't require this particular word for any kind of task like sentiment analysis. Important words like good boy, good girl is basically required. So this all things will go like and, are will also go. Now what will happen with respect to this? The sentence one words will become only like this: good boy. Okay, I'm showing you step by step with the help of Python. When we do with the help of libraries, when we do it is very much simple. We don't have to worry that much about it. Okay, we just have to use one library. So sentence two, what it will become once the stop words will get removed, it will become good girl, right? And similarly with sentence three, I will be having the specific words, that is boy, girl, good. Right? So all these things are there. I have sentence one, sentence two, sentence three. Perfect. Now what we do is that we go ahead and calculate the vocabulary. Now how many words are there in this vocabulary? We have good, boy, girl, boy and girl, and again it is getting repeated. So if I probably consider how many unique words are there in the vocabulary, so I will be able to write it over. The first word is nothing but good. So I'll go ahead and write good. Good is my first word. And one more thing that I will probably write, that what is the frequency of the specific word? Like how many times these words are there in different sentences. And obviously you can see 1, 2, 3. 3 are there, so I'm going to keep the count as 3. Then we have something called as boy. Over here you'll be able to see how many times boy are there. So in sentence 3 also boy is there, in sentence 1 also boy is there. So I'm just going to make the count to 2. And coming to the next one, which is called as girl. So again, girl word is also there in this vocabulary. And again, girl also you'll be able to see 2 times it is there, right? Now, first of all, you need to see that in this frequency with respect to different vocabulary words. Is this in ascending order? And obviously, is this in descending order? So maximum number of frequency will be put up in the first word, right? Then boy is present 2 times and girl is present 2 times. So this can be moved up and down. But just understand what I've done is that based on this descending order, I have just ordered all these words. So from it is basically from maximum to minimum. Okay. So this is there. Perfect. Now, before applying bag of words, you already have seen that how many vocabulary size, what is the vocabulary size? The vocabulary size is 3, right? And I can see in a bigger data set, I can have this kind of words a lot. So I will be having all these words like this, and frequency will also be there. And one important step is that it's not necessary that you use all the words. This is also there in this bag of words itself. Let's say that over here in the vocabulary, there are 100 unique words. And let's say some of the words are just present once, right? So if some of the words are just present once, we even need not take that. So when we'll be doing the coding with respect to bag of words, we also have an option that we just select the top 10 features or top 20 features, which of the words are getting repeated more and more. And that is the importance of this particular frequency. Okay. Now, perfect. We have till here. Now the next step will be that it is very simple now. Based on the topmost frequency, what I'm actually going to do, I'm going to keep these words as my feature. So good will come over here, boy will come over here, and girl will come over here. Okay. Now you already know what is the sentence one, right? So sentence one, what will happen is that this sentence one has good boy. Now see how this will get converted into vectors. Wherever good is present, that will become 1. Wherever boy is present, that will become 1, and remaining will become 0. So this entire sentence will be able to see that it is getting converted to 110 as a vector. Okay, so this was the text. Now this is getting converted to 110 as a vector. Now similarly, if I go with respect to sentence 2, wherever there is a word like good, that will become 1. Wherever there is a girl, that will become 1, and remaining all will become 0. I'll talk about the advantages and disadvantages why we are doing this. Previously, in one hot encoded, you saw that for every word we are doing this. For every word we are creating a vector. But here, for the entire sentence, this vector is coming. Okay, and there are a lot of advantages when I talk about this, which I'll discuss. First of all, let's understand what more we'll be having in this. So S3, you'll be able to see the sentence 3. Here I have boy, girl, and good. So wherever boy is there, that will become 1. Girl is there, that will become 1, and good will be there, that will become 1. Okay. Now, this is my entire vectors, and obviously I will also have my output variable. The output variable can be 1, 0s, anything as such, right? If you are probably solving the sentiment analysis or something like that. Okay. Now, these are my entire vectors. Okay, and this is the vector for the entire sentence. Okay, entire sentence, and this is how the entire bag of words converts a text into a vectors. Okay. Now, what we can do is that we can take this particular vectors, we can train it in a machine learning model, and we'll be able to get the output. Now, one more important thing that I really want to put. Let's say that I have a word over here, right? Good, girl, girl, right? So let's say if I have one more word like good. Now, in this case, what will happen? Okay, in this case, what will happen? Usually in bag of words, since good is repeated 2 times, so I will increase the count to 2. Okay, in this particular case, so what I'll do, I will increase the count to 2. Okay. Now, there are 2 things. One is binary bag of words, and one is normal bag of words. Now, in the case of binary bag of words, even though the count is 2, what it is going to do, it is going to force it to become 1. So, most of the time the word is present, it may be present any number of times, the value is either 1 or it is 0. And in normal bag of words, I can increase the count to 2, 3, 4 based on the number of words that is there. So, that is the basic difference between binary bag of words and bag of words. That basically means here you'll be having only 1s and 0s, and here, based on the frequency, count will get updated. Count will get updated based on frequency. So, this is the basic difference with respect to this. Okay. So, I hope you have understood like how with the help of bag of words we are converting a text into a vectors. Now in the next video, I'm going to discuss about what are the advantages and disadvantages with respect to this, like how we have actually discussed it, but not encoding. Okay. And first of all, I'll talk about like what all problems are getting solved and all, right? So yes, I will see you all in the next video. I hope you're able to understand it. And just try with some other data set of your own. Just try to create a text, try to perform all the steps, and then try to convert that into vectors. So yes, I will see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to bag of words. Already we have understood the intuition behind bag of words, how it is converting a text into vectors. Now, as usual, let's go ahead and discuss about the advantages and disadvantages. So first of all, I will go ahead and write the advantages, and then I will go ahead and write the disadvantages. Okay. So and obviously we have also discussed about the advantages and disadvantages with respect to one-hot encoding. We'll try to compare with this and we'll try to see that what all problems is getting fixed. Okay. First of all, yes, again, this is easy to implement and it is intuitive. I'll just write something like simple and intuitive. Simple and intuitive. Okay. The second point with respect to advantages. Now here, what will do in one-hot encoding, you see that you're seeing that some important thing is that in machine learning algorithm, right? Okay, with respect to sparse metrics, I'll be discussing. With respect to semantic meaning, out of vocabulary, everything I'll be discussing. But let's consider this particular second topic, which is like for ML algorithms, it gives fixed size inputs. Now over here, with respect to bag of words, any statement. Now here you can see that some of the sentence may be 3 words, 5 words, 10 words. At the end of the day, based on the vocabulary size, you are able to get all the sentences converted into that many number of dimensions of words. So here the vectors is getting fixed, the inputs are getting fixed because here our vocabulary is getting fixed. So this particular problem is getting solved. Okay. In one-hot encoding, you do not have fixed size inputs since we are creating words for every vectors. Sorry, we are creating vectors for every words. Okay. So what we are going to do over here, the second point that you'll be seeing, yes, you have a fixed size input, right? And this will superbly help you for ML algorithms training. Okay. ML algorithms. Now, this is the two major advantages. Now, if I talk about the disadvantage, see over here, the first disadvantage with respect to one-hot encoding is sparse metrics. And I've already told you what exactly is sparse metrics. It is nothing but ones and zeros. Let's say if your vocabulary size is 50,000, then what will happen? Every sentence will get converted into that size of the vocabulary, right? So, still sparse metrics problem is there. So, with respect to disadvantage, again, I'm going to write it as sparse metrics and array or array is still there, and this will actually lead to overfitting. Okay. Now, second major disadvantage again. See, at the end of the day, whatever statement that you have, like good boy, good girl, or it can be boy, girl, good. Okay, something like this. You'll be seeing that based on this sentence, right, and based on this vocabulary, and based on the frequency of the vocabulary, the ordering of the word is changing. Now, see, understand, if in a sentence the ordering of the word changes, and based on that, this vector is getting created. Because see, based on the frequency, we have written all the vocabularies right over here. Good was present maximum number of times, so we wrote it as first. Boy was present in the second number, so we wrote it over here, right? And a girl was present like for two times, and we have written it at the last, right? Now over here you can see that if I probably consider the third statement, boy, girl, good, right? But here you can see that entire word is getting ordered, like it's completely changed, right? The ordering of the word is completely changed. So I'm having 110 for sentence 3, I'm having 111. Now when word ordering is changed, the meaning of the sentences also gets changed. And because of that, some of the semantic information is not getting captured. I'll talk about more semantic information, but here you'll be able to see that ordering of the words is getting changed. This is super important. Ordering of the word is getting changed. Because if this is getting changed, the meaning of the sentence changes, right? Is getting changed. So this was a second disadvantage. If I probably talk about the third disadvantage, okay? Third disadvantage, again, we'll go and see over here with respect to out of vocabulary. Now, what happens if I probably add a new word like boy, girl, good, and let's say I'm going to add something called as school. Now, here you'll be seeing that the school word is not present in the vocabulary. So what it is going to do for this specific word, anyhow, it is going to get rejected, right? It is not all getting considered in this training data. Let's say that for our new test data, in our new test data, we have included a school word. And we need to do the prediction for this particular word with respect to output. So the first step will be that we'll do text pre-processing, and then we'll try to convert this into a bag of words using the same technique what we did in the training data set. But here you see that in my training data set, I do not have a vocabulary which is called a school. So what it's going to do? It is just going to ignore the specific word, and it's just going to see that where good and boy and girl are there. Right? So still, out of vocabulary still exists because this word may be an important word for the sentence, but it is getting removed because we don't have that in the vocabulary. Right? Major problem. So yes, out of vocabulary is obviously an issue over here. Right? This still persists. Okay, OOV. Now this was the there. Now one more important thing: semantic meaning in this is still not being getting captured. Why I'll tell you. Semantic meaning is still not getting captured, and there are multiple things to explain this. Okay. Now first of all, obviously you know that I'm having either ones and zeros. Okay. Now in this particular case, good and boy, they're getting the same importance. Right? For girl, obviously, if the word is not present, I'm getting 0. Small amount of semantic information is getting captured when compared to the one-hot encoding format. But here you say that when we have many vocabularies, either my values will be ones or zeros. One is just indicating whether the word is present or not. But which is the most important word? What is the most important context in that particular sentence? That is obviously not getting captured. And if that is not getting captured, semantic in turn will not get captured. Now the other thing over here is that there's also a very important thing. Let's say that I'm having two sentences. Okay, it is like the food is good. Let's say in my data set I have this sentence: the food is not good. Not good. Now let's say I don't go ahead and remove all the stop words and all. For this, I will be having a vocabulary like one. Let's say all these words are there, okay? And girl is also separate vocabulary, food is also separate vocabulary, is also separate. How many unique vocabulary are there? 4, because not is also there, right? So is will also become 1, not will be 0, and good will be 1, right? So this is how we convert from this to this, right? Similarly from here to here, if I really need to convert, then what will happen? 1, 1, 1, 1, 1, because not is also present, so I'm writing 1. Now let's say this is my vector 1 and this is my vector 2. If we try to find out the distance or how similar this vector is just by plotting some points. Let's say that I've converted this particular dimension to 2 dimension using PC and probably I've plotted it. Based on this, right, only one value is getting changed, is and not, right? So I will get both these vectors very much near to each other. And this we can basically do it through something called as cosine similarity. So let's say this is my vector 1, this is my vector 1, this is my vector 2. So vector 1 is basically present over here, vector 2 is present over here. If it is near to each other, if the angle between them is very near to each other, or if the angle between them is very less, I may say that both the sentences are same, almost same, or similar, right? This is almost similar. But do you think both sentences are almost similar? Because it is the complete opposite of them, right? But since there is only one word that is getting changed, because of that, only one of the values getting changed over here, right? Like zeros and ones are happening. And when we plot this, it is becoming kind of a similar word. But this should not be a similar word. This is completely opposite word, right? So this kind of situation is also not getting handled well with a bag of words. And later on, the techniques that we'll be learning, like word to vec and all, this will be solving all these problems. right? So I hope you are able to understand the advantages and disadvantages of bag of words. Super important with respect to interview. And if your basics of this are getting strong, trust me, you'll be able to understand bag of words, average word to vec. Sorry, you'll be able to understand word to vec, average word to vec in a very easy manner. And there are techniques in deep learning which is also going to come, which is called as embedding techniques, word embedding and all. All those will get solved in a very easy way, right? So I hope you're able to understand. This was with respect to the bag of words. And now in the next video, what we're going to do is that we're going to do some practicals. And we'll try to see with the help of SQL and how we can perform bag of words, right? So yes, this was it from my side. I will see you all in the next video. Thank you. Hello guys, so we're going to continue the discussion with respect to natural language processing. We have already seen in our previous video about bag of words, we have understood the intuition. We have also made sure that we understood the advantages and disadvantages. Now let's go ahead towards the practical part and see that how we can implement bag of words. So over here I have an amazing data set which is called a spam classification. So if I probably open this, right? So this is a data set which is having a label like ham, and then I have a message, right? Then again I have ham, then again I have a message. So here you can see spam, and then again I have a message. So like this I have this entire data set. What I'm actually going to do is that I'm going to basically apply on this particular data set bag of words model, and later on as we go ahead, all the different techniques also will try to see it. So over here I'm just going to create a new Python file, okay? And here let me just go ahead and write bag of words practicals, right? Perfect. So we will go line by line and we'll try to understand everything. And first of all, we'll read the dataset itself. Okay. Now before I go ahead, I really need some of the libraries. So I'm going to import pandas as PD. Okay. And then I will just try to read this messages. So I'll write pd.read_csv. And here you can see that obviously it is present inside a folder which is called a spam classification master. And then it is having spam. So let's see. I'm just going to write like this: spam classification master, and then spam classifier.py. So I have something like spam SMS folder, and then I can basically go ahead and write my dataset name. So inside this, you'll be able to see that I have this SMS spam collection, right? So I'm going to write SMS spam collection. So this is my file. You'll be able to see it. Okay. SMS spam collection. Okay. So this is my data set over here. But remember, as I opened this particular data set, there are two things that you really need to focus. Over here, the space between this dependent and independent feature, that is my text, it is basically a tab. Okay. So I will basically be using a separator, which will be a tab. So in the next step, I will write separator, and this will basically be a /t. Okay. And then along with this, what I'm actually going to do is that I'm going to also assign names as my what all features it should basically get assigned to. One is label, and the one is message, right? So I'm basically providing my own custom column name in chart, right? So once I do this, let's go ahead and execute it. So you'll be able to understand. I'm just trying to read the data set over here. So if I probably go and see the messages, so here you'll be able to see label and message, right? So I've just read this entire data set using a /t, that is a tab separator, and then I've also provided two names, label and message, which is my column name. Perfect. Till here, it's quite good. We are able to see the data set, and clearly we're able to see the data set itself, right? Now the first step, obviously, before applying bag of words, we really need to clean the data. So I'll write data cleaning and pre-processing. Okay. Let me make my mic a little bit straight. Okay, data cleaning and pre-processing. Now, what all things we can actually clean the data about, right? What all processing we can basically do? Obviously, lowering the sentences, applying stop words if I want, applying lemmatization if I want. So there are various ways what all things we can basically do, right? So what I'm actually going to do is that I'm going to import some of the libraries for this. And again, I also need to make sure that any special characters that are present in this particular sentences, I should remove it, because see, this kind of words, it has two dots. So, these are like special words. I will just write nltk.download stop words. Okay. And already we have done the downloading of this particular stop words if you are following my previous videos. But let's say that if I have directly jumped over here, I'm just going to download it once again for you. Okay. So here you'll be able to see I've written S stop. So it is already up to date. All these things are there. Now, the next thing what I'm actually going to do is that I'm going to write from nltk.corpus import stopwords, and I'm also going to make sure that I download from nltk.stem. I import the nltk.stem.porter, import porter stemmer, right? And I hope everybody knows why porter stemmer is basically required. So I'm just going to write it this one, porter stemmer. This is specifically for the stemming purpose. And along with that, I'll also make sure that I'll initialize this. Okay, so I'll write porter stemmer, and I'm just initializing so that we will be able to do this. Okay, I really need to write from. Okay, I'm not going to edit any errors as such. So everything, whatever I am facing the error, I think you should also be facing, or you may be also writing with respect to some mistakes, right? Whenever we are trying to solve this. Perfect. We have imported porter stemmer because we really want to do the stemming. Now what I'm actually going to do is that I'm just going to create a list, which is like corpus. Okay, since I need to clean all the data, right? At the end of the day, after I clean the data, it will be stored in this variable. And let me iterate it for I in range of 0, length of messages. Now, what I'm actually doing is that I will make sure that I go through each and every sentence. I remove all the special character. I lower down all the sentences. I apply the stop words, and then I probably apply stemming. So there are many things that we are going to do. And this task is common and generic with respect to all the use cases. Let's say that later on you want to solve any other use cases, right? You can follow the same approach, and that will actually help you to solve this problem statement. Okay. So what I'm actually going to do over here is that I'm just going to write colon. Okay. And then first of all, let me go ahead and take the review. Right. So here I will say the first thing that I'm going to do is that after I go with respect to each and every review, I first have to remove the special character. That basically means I don't want anything else other than the words or letters over there. Okay. So over here I'll be using RE, and there is a function which is called as dot sum. Okay. Now in this particular function, I will just apply my regular expression. Now, how do I apply my regular expression? You can definitely try out different things, but I'll give a simple regular expression. And there is also a website where you can easily see that what regular expression you need to apply to select those similar kind of words. Okay, so I'll say I'll just give one simple thing with respect to this. I'll say that okay, with respect to only if you find A to Z, okay, or I can also say that apart from this word, like A to Z, that small A to Z or capital A to Z, okay, apart from this word, any words, any special character that you find, just replace it with blank. Okay, I'm trying to use this because there are a lot of special characters in the text which I have basically analyzed. And here what I'm saying is that apart from the text, that is small A to Z and capital A to Z, replace everything by blank. So here I will be having message, and this same thing I will try to apply it. Now messages obviously has all the messages over here, right? But inside this I have a label called as message. So I'm just going to apply that message. And with respect to any index, that is I, I'm just going to apply this. Okay. So review what I'm doing is that I'm just substituting, right? The sub is basically nothing but substituting A to Z, capital A to Z, along with, apart from this A to Z. Any special character that you get, just replace it with blank and try to replace it in not message and store it in a review variable. Okay. This is perfect. Now the next step, what I'm actually going to do, I'm also going to make sure that I lower all these words because I really need to lower this. Okay. If I don't lower this, then again it will be a problem. After lowering the word, what I will do since I will also be having a space things, I will convert this entire review into a list of reviews. So I will write review.split, okay, just to create a list of reviews, okay. And then finally, for each and every words, like let's say if I probably just try to execute this review, okay, how will I get? So print review, okay. Okay, it's okay. We'll be able to see it. Okay. So what I've done is that I've substituted it. I made it lower. I have done a split with respect to each and every reviews inside the sentence. I'll get a list of words over here. Now, after I get a list of words, what I'll do, I will apply the same concept that we did before, right? In lemmatization and all. Same process. So over here, you'll be able to see that what kind of process with respect to these things. Here, same process. I will try to apply the same combination, whatever I did. If it is not present in stop words, then only you try to stem it, right? Like how I did it in text processing. Same thing I will be doing it over here with respect to bag of words. So I will say for word in review. That basically means review has a list of words with respect to a specific sentence. I'm iterating through every word. If not word in, if that word is not present in stop words dot words of English, if it is not present in English, because this is what I showed you with respect to theoretical integration, right? I'm going to take that specific word and I'm going to basically apply ps.stem. Very simple, okay? Nothing so complicated. Whatever I've done, the same thing I've explained you with respect to this, okay? And this I will be taking it entirely into my review variable again, because here I'm basically applying stop words and stemming. I will get all my review variable over here, and finally you'll be able to see that I'll be writing review, and then I'll be joining that all these words into a sentence again, okay? And later on, what I will do instead of printing it, no, the list that I have actually made, I will just add it over there. So I will say corpus dot append, and I will append all this review, okay? So once I probably execute it, you'll be able to see it will take some time. But at the end of the day, we are going to clean it. We are going to make sure that all the loading of the words will happen. And finally, we'll be able to get the entire corpus. Because after this only, we will be able to apply the bag of words. Now, this is perfect. It is completely done. Now, if I probably go and see the corpus, now here you can see everything is basically done, right? And obviously, you know the disadvantage of stemming. Some of the words will not come right, but maximum number of words will come right. If you want to make it more accurate, you can definitely apply lemmatization. And if you also want to make sure that you apply snowball stemming, you can also do that. That will be a task that I really want to give it to you as an assignment, okay? You can try both of them, but I can understand with lemmatization, it will take more time, okay? So this is my entire text, my input data, okay? Input data with respect to all the things. And let's see what will happen in the next step that we are going to basically apply bag of words. Now, let's go ahead and create the bag of words. As you know, I already know what is my output variable. Okay, my output variable is nothing but the spam and ham, the label column, right? And this is specifically my input features. I need to convert this into vectors. So now we are going to create the bag of words model. Now this is super important, guys, how the bag of words model is created. So just go and search for sklearn bag of words. Okay, and here with respect to sklearn, you have a library which is called as count vectorizer. Now this count vectorizer I'm going to specifically use for the bag of words, and here we are going to discuss about some of the important keywords. Okay, and then only we'll be able to understand. Okay, there's so many keywords that we will try to solve it. Okay, and with respect to that only we'll try to solve more of the problem statement as we go ahead. Okay, so let's go ahead and create it. So first of all, I will just import count vectorizer. So I'll say from sklearn.feature-extraction.text we are going to import count vectorizer. Okay, so here what I'm actually going to do is that I'm just going to write something like this: from sklearn.feature-extraction.text import count vectorizer. Okay, so and then I will initialize to count vectorizer. Now you need to understand some of the things with respect to the parameters. Okay, now here you can see that if I probably zoom in, there is also something called as lowercase is equal to true. See, we did not have to do the lowercase manually, right? You can also use this particular library to and make sure that you just put lowercase is equal to true. It will also do for you. Okay, and there are also stop words. You can also apply stop words, but we have already done that, so I'm not going to focus on that. This n-gram range, I will talk about it in the upcoming sessions. Right now, let's go ahead and focus more on this particular feature, which is called as max underscore feature. Now, in this, I've already told you. See, based on frequency, right, we can pick up the top 10 features, top 20 features, top 30 features, right? And you know that whenever we try to solve any problem with respect to sentiment analysis and all, we obviously get some kind of vocabulary size. But when I see, right, how frequent those vocabularies basically present, right, and it is not necessarily that everyone will be available for 100 times or 200 times. There will be some of the words that will be just present for once and twice, and sometimes those words will not play a very important role. Okay, so what we basically do is that we can set some max features. Okay, I'll just give you one idea that how we can set a max features with respect to this. But other than that, ngram underscore range, we'll discuss it later on, not right now. But I really want to show you an example with respect to max underscore features. By default, other things we have already done it, so we don't have to really worry about it. Okay, and one by one we'll try to calculate it, and if you're not able to understand it, don't worry. Everything will be covered as we go step by step. So here you'll be seeing that max features. Let's say I'm saying that out of all these words, right, from the vocabulary, take the top 2500 words which are having the maximum frequency. Okay, so this is what I'm actually creating. I'm creating a bag of words which is saying that take the top 2500 words from this particular data set which is having the maximum number of frequency. So once I execute it, so this is my CV. Okay, now after this, all I will do is that I will just say cv.fit underscore transform, and I will apply it into my entire data set like corpus. Right, the corpus is basically having my entire data set, and I will try to convert this into an array, and let me save this in my x variable. Now if I probably go and see my x values, so here you'll be able to see that I'm getting so many different x values, and some or the other way you'll be able to find the ones and zeros. Now see, I've taken the max 2500 words, right, and because of that you'll be able to see this. So in short, if I probably see x.shape, I've taken that. Okay, take 2500 max number of features. So obviously the number of vocabulary size, the number of columns that I'm going to have is 2500. Let's say if I say take the max 100 features and I just try to do the transformation with respect to on the x itself. So if you remember this, I'm just going to execute this on the corpus. And now if I go and see, this will be my shape with the next 100 vocabulary size, right? And if I again go and see my x, so here also you'll be able to see somewhere ones will come and remaining all will be zero, ones will come and remaining all will be zero, ones will come remaining all will be zeros. There will be multiple ones wherever those specific word is present. Now you need to understand one more thing. Over here I'm getting 2. So this basically becomes that this is not binary bag of words. This is normal bag of words. Now how do I make sure that I also enable this binary bag of words? So for that you just go back to sklearn, and there will be a feature which is called as binary. Let's see where it is. Over here we are not able to find out. Okay, here it is, binary. Okay, so what I'm actually going to do, I'm going to just go over here along with this max feature. I'm just going to write a comma, and I'm going to write binary is equal to true. Right now, once I do this, right now you'll be able to see that you're having truths. Right after I apply this binary is equal to true, no, you'll not be able to find out any values that will be greater than 1, because even though it is greater than 1, it is always going to set it as 1. Okay, and once I execute it, now here you'll be able to see either I'll be getting ones or zeros. Okay, so all this specific thing has got updated. You'll have only ones and zeros. Now it is up to you which you want to basically use, and again it depends to problem statement whether you want to go with binary bag of words or not. Okay, so I'm just going to write it over here for binary bag of words enable binary is equal to true. Okay, so this is done. Very good. We are in the right state and we are able to convert this into this. And here I'm just going to execute it. Let me keep binary is equal to true. Otherwise, I don't want you all to miss this. So done. And this is what we are able to get. Now understand. the array shape, since I've taken the top max 100 features which are having the maximum frequency, the column size will be 100, right? And this 5572 is basically the length of the entire list. Okay, so here we have got a complete idea about how to basically convert this into bag of words. You can play with max features, you can play with binary, you can play with other things, but the most important thing is that you really need to understand what is ng_gram range, which I will show you in the next video. First, we'll understand the theoretical intuition behind it, and then we will try to also implement it. But right now, I feel that yes, we have done a bag of words easily. We have converted this word into entire vectors, which is a very, very good thing, very amazing thing, because now we know at least how to convert a text into the vectors. Now, what I can take all these arrays as my independent features and all this particular output like label, ham, and spam, and we'll try to solve the problems. Okay, so yes, this was it from my side. I hope you like this particular video. Please make sure that you keep on practicing with different data sets. But one assignment that I really want to give you over here is that please make sure that you try to do it with the help of lemmatization also. Instead of doing stemming, just try to do lemmatization, because you may get a better accuracy with respect to that also. Okay, so that will be an assignment. So yes, this was it from my side, and yes, I will see you all in the next video. Hello guys, we're going to continue our discussion with respect to natural language processing. In this video, we're going to discuss about a very important topic which is called as n-grams. Now, why n-grams is used, and it can also be used with bag of words and TF-IDF, but till now we have just discussed about bag of words. Let me take a very good example. Suppose I have two sentences, and this particular sentence is something like this: the food is good. Okay, food is good, and the food is not good. Okay. Now here you will be able to see that both these words are completely different. That is completely exactly opposite of each other, right? Both the sentences. This is my sentence 1, and this is my sentence 2. So I cannot say that these two sentences are same. Okay. Now what I will do is that and obviously over here, right? Let's consider that this is my vocabulary. The food is good. Okay. Food is good. Or let me just add this vocabulary. Food is not good. Okay, these are my vocabulary with respect to feature 1, feature 2, feature 3, feature 4. Because these are the possible vocabulary that I have. I'm not considering the, because the can be a stop word. I can also remove is. Let's remove is. Okay. So what are the possible vocabulary that is basically present? I'll basically having food. I'll be having this not keyword, because not keyword will distinguish, right, whether the sentence is positive or negative. So this is super important. So I may have this all possible options with respect to vocabulary. Now for the sentence 1, I may get a vector of something like this: 1, 0, 1, right? Because not is not present over here, so obviously it is going to be 0. For sentence 2, I will be getting something like 1, 1, 1, right? Understand that why the and is not present, because we have removed this with the help of stop words. Okay, we have removed this with the help of stop words. Not a problem. You may be thinking this not can also be there in the stop word. It can be, but we're not going to add it, because this word is basically distinguishing the entire sentence. Now you need to understand that with respect to these two vectors, you'll be seeing that these two vectors are almost similar. Only one change is there, like 0 and 1. In real world scenario, I will say that these two sentences are completely opposite of each other. But when I'm trying to convert this into vectors, it is just almost similar with only one change, right? And this is a bigger issue, right? Now what we'll do is that we'll try to solve this problem with the help of n-grams. Now see, this is super important, and you try to understand this. Now you know that these are my possible options. These are my possible options with respect to words, right? So I have my first word like food, not good, right? So this is my initial vocabulary. Now what I'll do is that I will make a combination of this. Let's say from the sentence 1, I'm going to make a combination of something like this: food good, right? So my next word that you'll be having is something called as food good. And let's say that I'm going to just perform bigram, not trigram also. Bigram basically means that I will have a combination of two words, right? So I'll be having food good. Then similarly over here you'll be able to see I will also be having something like this: food not. Right? So this is one combination. One more combination I have over here: food not. Okay. And then the next combination will be not good, right? So here I will be having my next word, which looks something like this: not good, right? Now see this. Now if this becomes a possible vectors, then we will be able to clearly distinguish much more better when compared to this. And here I have implemented bigram. Bigram basically means combination of two words. I can also take trigram. In trigram, I'll take the combination of three words like food, not good, right? So that will be one combination, like something like that. So let's understand with respect to bigram. Now how will the vectors get updated for sentence 1? Wherever there is a food, I will put it as 1. Not is not present, I'll put it as 0. Good is present, I'll put it as 1. Now wherever food good is present, I will put it as 1. Wherever food not is present, I'll put it as 0. So food not is not present over here, right? If food not is present over here, I'll put it as 1. But right now it is not present. Not good over here with respect to sentence 1 is also not present, so I will make it as 0. Now if I go with respect to sentence 2, okay, now see, the difference between the vectors will be very much there. Okay, so food is there, I'll put it as 1. Not is there, I'll put it as 1. Good is there, I'll put it as 1. Food good combination, you can see the continuous combination is not there. Let's say I'm going to put it as 0. Food not is there, obviously I'm going to put it as 1. And food not good is also there, I'm going to put it as 1. Now here you can see that if I try to compare these two vectors, now they are not exactly the same, and there is a huge difference, because I have one difference over here, two difference over here, three difference over here, four difference over here. Now my model will be able to clearly distinguish these two sentences because I've implemented something called as n-grams, right? Now if I probably consider trigrams, that basically means I'm going to make a combination of three words, right? So in sklearn, here in sklearn, you have a very important parameter which is called as n-grams. Okay, and you can make a combination of something like this. If I make a combination of 1, 1, that basically means I'm just going to implement unigram. Unigram basically means only one word vocabulary. Okay, if I write the combination like 1, 2, then what it is going to do? It is going to consider something like unigram and bigram, like how I have explained you in this example. This is a combination of unigram and bigram. Okay, and if I probably consider like this 1, 3, then what I'm actually going to do? I'm going to get a combination of unigram, bigram, and trigram. So trigram basically means three words, right? All the possible combination with respect to this. And then suppose let's say if I'm writing 2, 3, then it is not going to take unigram. It is going to take the combination of bigram and trigram. And this is what I'm going to show you probably in the next video, but understand why we are specifically using n-grams over here, right? Super important topic. Since we are going to use the combination of all these words, it will give us a very good contextual information about the sentence. And wherever do you feel that the sentence is completely opposite, but still we are getting the similar kind of vectors, this can be very, very handy. So I hope you're able to understand about n-grams. And in the next video, we'll try to do some practical implementation with respect to this, which will be superbly important. Okay, so let's go ahead and I'll see you all in the next video. Hello guys, we're going to continue discussion with respect to natural language processing. In our previous video, we have already seen ng-grams intuition. Now we'll try to implement it with the help of NLTK. We're going to take the same problem statement what we have taken for the spam classification. So this is how we had actually created a bag of words, right? Where I took maximum features as 100. 100 was go, great, go out, what, okay, free, win, text, txt, say, already, I think. So here you can see these all are indexes of the columns, right? So if I probably say which is the first column that you'll be able to find, it is nothing but ask, right? Which is the second column, it is something like game, okay? Third column like that. So total you'll be able to see it'll be having the indexes from 1 to 100, right? Something like that. So these are my top 100 words, okay? So this is with respect to CV.vocabulary. If you're able to find it out, you'll be able to, if you're just executing this, you'll be able to do it. Now let's go back to this SQL and feature extraction. Now this is super important. Now I'm talking about this ngram underscore range, okay? Now see this. What will happen once I just copy and paste the same thing? So let's say I'm going to copy this and I'm going to paste it over here, okay? I'm just going to paste it over here. Now this is super important, okay? So I'm just going to execute this and I'm going to paste it over here. Here I'm just going to say ngram. Okay. Now you know that there is a parameter which is called as ngram range. Okay. Now once I do 1 comma 1, nothing is going to change. Now see this. Okay. Nothing is going to change, and I'm just going to do the same fit transform on the corpus. Okay. And I'm going to save it in a X. Okay. We need to do fit underscore transform. So once I execute this here, if I go and write cv.vocabulary, and now if I show you, it'll be the same words. See, so these are the 100 most frequent occurring words. And here I've given nggram underscore range as 1 comma 1. That basically means all my features will be 1. There will not be any combination of two words like bigram or trigram. Now see this, okay? What I will do is that I will change this to 1 comma 2. Now once I write 1 comma 2, now it is going to be the combination of unigram and bigram. Okay? Unigram and bigram. Now see this, okay? And I'm also going to increase the number of max features. Let's say I'm going to make it as 200. Okay? Now let me just go ahead and execute, and now let me see the vocabulary. Now vocabulary over here you can see all these words are there, single words are there. Now as you go ahead, right, there will be two words. See over here, please call. Okay? So here you'll be able to see please call, and you won't be able to see the other words because that is not the maximum occurring words. Let's say I want to increase this number. Let's say I'm going to basically write it as 500. Now the number of words will keep on increasing. So yeah, here you can see that let know is in the 228 index of the column, right? Still you have how many? Please call is also there, which is present in the 325 index, and that index number is basically given based on the maximum number of occurring frequency, right? So more words are there, something called as customer service, right? And if I probably go and explore more, price guarantee, guarantee call, try contact. See, all these words are definitely there. There's obviously some spelling mistakes, but it's fine. So over here, LT decim GT, something is there. Now you see, good morn, right? So morning, something like that. Good night, right? So this is basically the combination of this. Now what I can also do is that if I really want to see the maximum occurring just a bigram kind of words, I can just write 2 comma 2. That basically means I'm ignoring unigram. So now here you'll be seeing that free entry, claim call, claim, free call, chance win. Every combination of the possible words are basically there along with the column index. Now I hope you're able to get an idea what is the basic difference between unigram, bigram, trigram, right? So suppose if you also want trigram with respect to this one, I can basically write 1 comma 3. Now let me do one thing. I'll also take a combination of first 3 comma 3. Let's see and let's execute this. Now here you can see call, claim, code. So this is the 6th index. That basically means this kind of message are occurring more and this is basically in the column 6th index, right? Like LTGT, sorry, call later, please call custom service, right? All these things are there. Now you can see this is the combination of 3 words, right? Now if I want to use the combination of 2 and 3, I can basically use 2 and 3, bigram and trigram. So here you can see call customer service, then you can see let know, then you can basically see claim call. So you can basically make the combination of various unigram, bigram, and trigram. Usually, if you're not getting a better accuracy, first of all, start with 1 comma 1. Okay, I'll tell you the simple phenomenon. Just try with 1 comma 1. With respect to 1 comma 1, you'll be getting a vocabulary word which is the most frequent words, right? Let's say with respect to this, you're not getting a good accuracy. Then what you can do? You can increase 1 comma 2 and go ahead and execute it, right? Suppose let's say it is not increasing. Then what you can do? Try 1 comma 3. Now, if even 1 comma 3 is not working, you can play with this max feature also. This is called a hyperparameter. You can play with different max features. If that combination is also not working, use the combination of bigram and trigram, and this will definitely give you a better answer, right? So definitely, my suggestion would be that try to check each and every parameters of this and how we can basically use it. Ngram underscore range plays a very important role, and this was with respect to the practical. I've already shown you that how you can play with this and how you can actually use it, right? So at the end of the day, after you do this, now you'll be able to see that once I make this combination, right, and this will basically be my vector of x. So here, if I probably go ahead and execute, so this is how my vector of x is there. You'll also be having ones and zeros since binary and true, and all the remaining things are actually there. So I hope you got an idea about how to implement ngram. Yes, this was it. In the next video, we'll try to see with respect to TF-IDF intuition, and we'll also try to solve it with the help of NLTK. So yes, this was it. I will see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to natural language processing. In our previous video, we have already seen what is ngrams. Now what we are going to do is that we are going to see one more efficient way of converting a words into vectors, and we specifically say it as TF-IDF. Now what exactly TF-IDF is? It is nothing but term frequency and inverse document frequency. So we'll try to understand how with the help of TF-IDF, we will be converting all these particular sentences into vectors. Okay, and I've taken the same example what we specifically did with bag of words like good boy, and this is after lowering all the character cases, along with that after performing or after removing the stop words. So I have sentence 1 as good boy, sentence 2 as good girl, sentence 3 as boy, girl, good. Okay, and this is the same thing like from same materials. If you will be able to see, I've done the same thing. I've taken the same thing over here. Okay, now there are two components in TF-IDF. One is term frequency and the other one is something called as inverse document frequency. So whenever I talk about term frequency definition or the formula, how we calculate it, it is given by number of repetition of words in sentence divided by number of words in sentence. Okay, I'll try to show you completely taking this as an example how we can calculate term frequency. And over here, inverse document frequency formula is very simple. We basically calculate it by inverse document frequency is nothing but log to the base number of sentences divided by number of sentences containing the word. Now this is super important, and probably don't get confused with the formula right now. I will try to explain you each and everything. Okay, so let's go step by step and let's see how we can calculate the term frequency. Now first thing that I'm going to make sure that what I calculate is nothing but I will be using this term frequency. Now with respect to this term frequency, you know that how many vocabulary of words are there. Okay, so first of all, I will just try to show you in a different way by creating a table. So I have S1 sentence, I have S2 sentence, and I have S3 sentence. Okay, and then with respect to my vocabulary of words, I have something like good. Okay, then I have boy, and then I have girl. And already we know that only 3 words are basically present in the vocabulary. I'm trying to show you with a simple example so that you'll be able to understand how TF-IDF will work. Okay. Now the first thing, let's go back to the definition. Term frequency is nothing but number of repetition of words in a sentence divided by number of words in a sentence. So suppose if I take S1, and with respect to S1, if I really want to find out the term frequency of this particular word that is good, how do I calculate? I just need to see how many number of times this particular word is repeated in the sentence. So here you know that it is repeated just 1 time, and then I will be dividing by number of words in that specific sentence. So it will become 1 by 2 because I have 2 words. Now let's go to the next word, that is boy. So boy is also present how many number of times? 1, and this will be divided by 2. Okay. I'll tell you why we are doing this, because when we understand the advantages and disadvantages, you'll get a clear idea about why TF-IDF will perform better than compared to bag of words. Okay. Then I have the word girl. So girl, I know that over here it is not present, right? In the sentence one, so it will be 0 by 2, so which is nothing but 0. Okay. Similarly, with respect to S2, here you'll be able to see how many times good is present, only one time, and the total number of words is 2, so 1 by 2. Boy is present 0 times, so it will be 0 by 2, which will be nothing but 0. And girl is basically present over here one time, so again I'm going to write 1 by 2. Now let's go with respect to the sentence 3. So sentence 3, how many times good is present? One time, and the total number of words now is 3, right? And then if I go next to see the boy word, how many times boy is present? Only one time, so this will also be 1 by 3, and girl will also be present 1 by 3, because the total number of words are 3. Okay, so this is how simple we are able to calculate the term frequency. Okay, now let's go ahead and let's try to find out the inverse document frequency. So I'm just going to write over here as IDF. Now with respect to IDF also, we will be creating two fields, very simple fields. And remember, this will basically be my IDF, and this is with respect to my words over here. So my words are nothing but good, boy. Let me write it down in a better way so that it should look in the same order. So here will be my good, here will be my boy, and here the next word is something like girl. Now in order to calculate the inverse document frequency, it is very much simple now. All I have to apply this log base E, right? How many number of sentences are there with respect to good, right? With respect to good, suppose if I really want to calculate the inverse document frequency of good, okay? So here what I'm writing, I'll write log base E multiplied by number of sentences. How many sentences are there? There are 3 sentences, so 3 divided by number of sentences containing the word. So good is present in all these 3 sentences, 1, 2, 3, right? So I will basically be writing log to the base 3 divided by 3, okay? And if I basically calculate this, if you try to calculate it, it is nothing but I will be getting as 0, okay? And you can basically do with the calculator. Boy over here, again log to the base E, number of sentences are 3, and how many times boy is present? How many times boy is present in? How many sentences boy is basically present? It is present 1, 2, right? Sentence 1 and sentence 3. So I will be writing log base E multiplied by 3 by 2. Similarly, girl will also be present same number of time. If you probably see how many sentences girl is basically present. Okay, so I have independently calculated term frequency and I've independently calculated inverse document frequency. This is perfect, right? Now, whenever we say TF-IDF, in short, what I'm actually doing, I'm multiplying this two. Okay, term frequency and inverse document frequency. I'm taking the combination of this two. Now let me go ahead and write it down in a better way still, in the way that we specifically want, and finally how our vectors will look like. So this is my vocabulary: good, boy, girl, and this is the final TF-IDF. Okay, so final TF-IDF based on this calculation, and this will differ based on data set to data set. Okay, so first of all, with respect to sentence 1, whenever I see the combination of TF-IDF with respect to good, all I have to do is that multiply 1 by 2 with this 0. Okay, so I'm going to multiply this with this. So in sentence 1, so see, this is the sentence 1, right? This entire thing is the sentence 1, right? So this is my sentence 1. Okay, so I will be taking this combination and I'll multiply with this, right? So sentence 1, good, 1 by 2 multiplied by 0, it is nothing but 0. With respect to boy, 1 by 2 multiplied by log base E, 1 by 2 multiplied by log base E, 3 by 2 will be the value that I'll be getting in sentence 1. And with respect to girl, 0 multiplied by this, it will be 0. Now let's go to the sentence 2. In sentence 2, I will go ahead and look for this now. Again, 1 by 2 multiplied by 0, again, good will be 0. And this boy is nothing but 0 by 0. So this 0 multiplied by 0 is nothing but 0. And here I have 1 by 2 multiplied by log base E, 3 by 2. I will tell you the exact thing, what we really need to know, why we are doing this specific thing. Everything will make sense. And it will make sense, and I'll make you definitely understand all these things. Okay. So coming to the next one with respect to sentence 3. In sentence 3, I will do this multiplication with this, right? So 1 by 3 multiplied by 0, again it will be 0. 1 by 3 multiplied by log base E, 3 by 2. And 1 by 3 multiplied by log base E, 3 by 2. Perfect. So we have got all this calculation, and this is how my vectors will look like. So here you'll be seeing that for sentence 1, we converted this entire sentence into vectors, which looks like this, right? So this is my sentence 1 vector, this is my sentence 2 vector, and this is my sentence 3 vector. And obviously I'll be having an output with respect to any kind of classification that I want to do. And then I will train my model by passing my sentence 1. So in short, if you see good boy is basically converted into a vector which will look like this. Okay, this entire sentence 1 is getting converted into a vector 0, this, and this 0, right? So again, you can calculate this with the help of calculator, but this is what is the way that we have actually done. We have converted all our sentences into vectors, and in TF-IDF, this is the phenomenon that is used in converting the words into vectors. Now you may be thinking, Krish, what is so special about this? We have got some values, okay, that is fine. And that is what I'm going to talk about in my next video, about the advantages and disadvantages of TF-IDF. At the end of the day, the best one is nothing but word to vec, but I really need to show you this also, because majority of the use cases also you can basically solve with this technique, that is TF-IDF technique. Okay, so yes, this was it for this particular video. I hope you like it. Again, you can take different sentences and just try to apply this and try to see whether you're able to find out TF-IDF or not. So yes, I will see you all in the next video where I'll be discussing about the advantages and disadvantages. Thank you. Hello guys, so we are going to continue the discussion with respect to TF-IDF, and already I've shown you how we can, what is the formula of TF-IDF, that is term frequency, and IDF, that is inverse document frequency, and I've also shown you an example over here, right? So till here, that is everything is fine. Now let's talk about the most important thing about advantages and disadvantages, and why this is probably better than bag of words. Okay, so first of all, the basic advantage that we have, again, this is quite intuitive. The implementation is also quite intuitive. Coming to the second advantage, okay, like bag of words, here also our inputs are basically fixed size, and this is based on the vocab size, right? And this advantage is also present with respect to bag of words, that is also there. But the third advantage that I'm actually going to talk about, see, in bag of words also we had fixed size, right? But this third advantage is a major advantage. Now let's talk about the third advantage, okay? So the third advantage is that the word importance is getting captured. I'll explain you what exactly this is. Word importance is getting captured. Super important point, and probably they may also ask you this specific thing in interviews. Now, if I probably go and see my entire paragraph, let's say this is my paragraph, good boy, good girl, boy, girl, good, right? I'm getting a TF-IDF of this number, right? And over here, I've also written this with the help of bag of words. In bag of words, I used to get either ones or zeros. Wherever that word is present, that is coming as one, otherwise it is zero if it is not present in the sentence. But how the word importance is getting captured? Over here, equal importance is given to both the word, like good and boy, right? Because it is present in the sentences. But here it does not work like that. Here, considering the entire paragraph, what it is happening is that we are focusing on two things: term frequency and inverse document frequency. If a word is present in all the sentences, it should be given less importance. Understand this, okay? If a word is present in all the sentences in that paragraph, it should be given less importance. Why? Because all the sentences having that specific word, so it is not playing that amazing or important role. Word importance needs to be captured for every sentence. That is what we specifically want. Now over here you can see that boy is there, right? Over here girl is there. Now boy and girl are getting repeated in one or two sentences, not in every sentences. So if it is not repeated in every sentences, we need to value this particular word in every sentences as such. So if I probably take an example of good, good is present in all these three sentences. So if we calculate TF-IDF, here you'll be seeing that all zeros we are getting over here. Major issue, right? So not an issue, but it's a good thing. We are ignoring the good word because it is present in all the sentence. Now if I consider with respect to boy, so sentence one, boy will play a very important role now, right? So with respect to boy, here you'll be seeing that I'm getting some values, right? I'm getting some values. Now in the second sentence, obviously boy was not there, so it became 0. But if I consider girl in the second sentence, so here you'll be seeing that I'm getting some value. That basically means in this particular sentence, the girl word is super important, and the context is based on that specific word that we are having a value of TF-IDF, right? So in short, what is happening is that word importance is getting captured. And in the third sentence, it is talking about both boy and girl. So you'll be seeing that both this boy and girl has some values. So in short, we are capturing some word importance over here based on the context, right? Super important point. And by this, our machine learning model will be able to understand that, okay, something specific we are basically talking about, and that way the mathematical models will be able to find out what kind of predictions it actually wants. And through this, the accuracy increases. Now let's talk about the disadvantages. Obviously, in this particular case, also you have a lot number of zeros. So sparsity still exists. Okay, sparsity still exists over here. And again, we will try to see how we can solve sparsity using word to vec. The second thing is that what we specifically discuss about is something called as OV, out of vocabulary. Now here also, if I probably add any more words over here with respect to the test data, that is going to get ignored because over here also all my features is basically made based on our training vocabulary size, right? So this is basically the advantages and disadvantages with respect to TF-IDF. But definitely just by seeing the advantages and disadvantages, we can definitely know that TF-IDF performs better than bag of words, right? Now in the next video, we'll try to see some practical implementation with the help of NLTK and Python. And again, guys, you really need to practice this considering different data sets. We will try to provide you more assignments as possible so that you can practice these things also. So yes, this was it from my side. I will see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to TF-IDF, and now we are going to basically implement it with the help of Python, and we'll try to see that how easily we can implement TF-IDF with respect to all the concepts that we have learned in our previous video. I'm going to take the same example with respect to pd.read_csv with respect to the dataset that we specifically have over here, spam collection, right? So this is the dataset that we specifically have. So I am just going to rename this over here, just a second. Spam classify, yeah. So this is my dataset, like how we did it for the bag of words and all the things. And again, this is the normal cleaning process that we specifically did. I think all these things are repeated, right? Port stemmer and all and all. And here also you'll be able to see that we are basically cleaning the data, lowering it, splitting it, and applying stop words and then stemming it. Okay. So just to make some little bit changes, what I'll do instead of doing stemming, right, I'll do lemmatization. So already I've shown you how to perform lemmatization, and for that we import wordlet lemmatizer, right? So I'm just going to go over here, copy and paste it over here, and instead of using port stemmer, I'm just going to use wordnet lemmatizer just to give you an added flavor. So I will write word lemmatize and I'll execute this. Okay, and then instead of writing ps.stem, I will write word lemmatize dot lemmatize. Okay, so I think this is almost repeated. I've done it again and again. Now I think you'll be able to understand. Now this will probably take some time based on the size of the data set we have. And again, yeah, obviously it is going to take time, so we'll just wait. But let me repeat what I did. Instead of doing stemming, I'm actually doing wordlet lemmatizer, right? And this is also one of the things that you should always try different variety of things, right? So finally it is done, and this is my corpus. Now with respect to the corpus, you'll probably be able to get correct words over here, right? And these are all my sentences, input sentences, and which I will probably be using to further create TF-IDF. Now to create TF-IDF, I've already opened this TF-IDF vectorizer. It is again present in sklearn. It is again a technique. Whatever things I explained you with respect to TF-IDF, similar, all the things that will be done. But it is almost like bag of words. All the features are like bag of words. Here also you have lowercase, you have tokenizer, you have analyzer, and all these things. And you also have ngram, right? So you can also perform ngrams over here. Now let me go ahead and let me try to implement and show you how you can implement TF-IDF vectorizer. So I will say from sklearn dot so feature extraction dot text import TF-IDF vectorizer. Okay, so I'm going to basically use this, and let me make my mic a little bit straight. Yeah, so over here this is done. Now all I have to do is that initialize TF-IDF vectorizer, provide after initializing it, right, like how we did it for bag of words. In the bag of words, if you see in our previous statement, we imported this and then we initialized with max features this. So what I'm going to do, I'm just going to initialize this with the same thing. Okay, and over here binary will not be required because binary is not at all required, because binary will not be working with respect to that, like how we used to work in bag of words, right? So that's it. See, same thing, I've done it over here. Now what I'll do, I will just say TF-IDF as my variable, and then let's say I'm going to take the top 100 most occurring words, right? So after this I will write TF-IDF dot fit underscore transform on my corpus, right? Like how we did it in the bag of words, right? Fit underscore transform on corpus, and then I'll convert this into an array, right? So to array, and I will store this in my variable x. So once I do it, now you'll be able to see x over here, and for that I'm also importing this numpy so that I can see all my values. Again, not a big issue because just I'm trying to display all the arrays clearly over here, right? So if I probably go and click on x, so now you'll be able to see I'm getting decimal values like 0.434, 0.461, 0.554. Similarly, you'll be able to see these are nothing but word importance of the word that is given in a specific sentence. So you'll be seeing different values like 0.365, 0.384. Now here you're not getting ones and zeros, so definitely some importance to the word is definitely given over here. Okay, so this is what simply so easily you can actually do with the help of TF-IDF vectorizer. Now what I will do along with this, I will try to again go ahead and show you in ngrams also. You can also create words. And let's say here I'm just writing n gram range. Let's say I want to go ahead and drive it 2 words. Okay, and once I execute it, this is entirely executed. But before that, let me show you the vocabulary. Okay, so sorry, TF-IDF dot vocab. So if I probably go and see the vocab, so these are all the words that has been selected as the features. I give 2, you can also give 1, 2, and based on that you'll be getting the top 100 most frequent occurring combination of words with respect to 2, 2, right? Same thing, no changes, nothing as such. So that is why I like this, because you don't have to do anything. You're just trying to understand which is the better one, what advantage it basically has, right? Now finally, if I probably go and see the x value with respect to this, here also you'll be able to see some of the other updates, which is not probably if you explore it some of the other way, you'll be able to see it. See over here 0.688, 0.726. So all these combinations are already available. 0.588, 0.56. So this is one sentence vector. This is another sentence vector, and the size will be 100. Why? Because your vocab size is basically 100. You've taken the top 100 occurring words that are there with respect to frequency. So yes, this was about the TF-IDF practicals. In the next step, all you have to do is that take these vectors, apply with any machine learning algorithm, and you'll be able to get the output. But before that, you really need to do train, test, split, and all in all. Anyhow, I'll be showing you some project implementations also, and we'll also be doing some end-to-end projects, right? So yes, this was it. I hope you have understood this. I will see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to natural language processing for machine learning. In this video, we are going to discuss about word embeddings. And this was probably the topic that I should have covered long back, but I'm deliberately keeping this particular topic at this point of time. Why? Because we have discussed so many topics wherein we focused on converting word into vectors. So now you'll be getting a very clear idea about what exactly word embeddings is. And here I've given you a Wikipedia definition. So this is a very simple Wikipedia definition. I've taken it from Wikipedia. So the entire credit goes to Wikipedia over here. So here you can see the definition that in natural language processing, word embedding is a term used for representation of the words, right? For text analysis, typically in the form of real valued vectors that encodes the meaning of the word such that the word are closer in the vector space are expected to be similar in the meaning. So let's say that I have two words, king and queen, okay? Or forget about king and queen. Let's say that I have two words and the two word is like happy and excited, right? Let's say I have this two specific word. Now, when I have this two specific word, with the help of word embedding techniques, what we do is that we convert this particular word into vectors. And let's say if I try to plot this vectors in a two-dimensional graph, okay? I mean, if I really want to convert this into two-dimensional graph, we have techniques like PCA or other techniques, which is an unsupervised technique to do dimensionality reduction. So once I probably plot this, let's say happy and excited are coming near to each other. Based on this particular vectors, it basically indicates both are similar word. Okay, let's say that I have one more word like angry. Now in this case, with the help of word embeddings, if I'm trying to convert this into vectors, the tentative thing is that obviously happy is the opposite to angry. So angry will be somewhere here if I probably try to plot this particular vectors over here. Why? Why it is coming so far? Because it is an opposite word. So the distance between this word will be quite high, whereas the distance between this particular word will be quite less. So this indicates that both the words are similar, whereas both words are opposite to each other, right? And this is all possible because of efficient conversion of the word into vectors, right? And how we are doing this again with the help of word embeddings. But the techniques we have learned till now is something like one-hot encoded we have learned, about bag of words we have learned, TF-IDF we have learned, and all these techniques are a part of word embeddings. So if I properly clearly show you the division, in the first step, if I have the word embedding techniques, so let me just again go ahead and write it. Word embedding techniques are specifically of two types. So this is my first type and this is my second type. The first type is based on count or frequency. Count or frequency. And the second type is based on deep learning trained models. Please hear to this very properly because this deep learning trained models will give you very good accuracies. Okay. Now in count or frequency, we have learned about three different types. One is one-hot encoded. Second one is something called as bag of words. And the third one is something called as TF-IDF. Right. So all these techniques we have learned, right? And we know the advantages and disadvantages. But here we're focusing more on count or frequency, right? But the major one, which is having a better accuracy, which is actually, and all these techniques at the end of the day is also converting words into vectors, or it is converting sentence into vectors, right? Sentence into vectors. But we have seen a lot of advantages and disadvantages. Maximum number of disadvantages are there with respect to all these techniques. And all disadvantages are getting solved by this deep learning trained model. And the trained model is nothing but, which is basically called as word-to-vec. It's not like we cannot create it from scratch. We can definitely create it from scratch. But again, you require a huge amount of data. And what we are going to do in that, first of all, we are going to understand in the upcoming videos what is exactly word-to-vec and how it is basically converting a word into vectors and how it is solving all the disadvantage things that were there in this particular technique. Everything we are going to discuss. But just understand that what is word-to-vec? It is a word embedding technique which will efficiently convert a word into a vectors, which will be making sure that both this property it is expected to have similar in meaning whenever it is converting into a vector space. Along with that, it will also give you a very good representation of the words. Right? Sparsity will not be there and all. There are many points which I'm going to discuss in the upcoming videos with respect to word-to-vec. Now, word-to-vec are of two types. One is because the entire deep learning architecture is built on two different types. One is we basically say CBOW. CBOW. CBOW is nothing but continuous bag of words. Super important. Continuous bag of words. And we are also going to see that how the models get trained. But for this, you really need to have a prerequisite knowledge of how an ANN works. What is loss function? What is optimizers and all. Right? The second technique is something called as skipgram. Skipgram. Again, this is a different technique. And again, it is a part of word-to-vec itself. It is a different type of word-to-vec. At the end of the day, we can either use CBOW or skipgram to get an efficient conversion of word to vectors. Right? And this is what we're going to see. We're also going to see some pre-trained models of word-to-vec, probably created by Google, and it is somewhere around 1.5 GB big model size. We'll try to download it, we'll try to see it, we'll try to execute it. But in the upcoming videos, what we're going to see is that how word-to-vec, word embedding works, right? And how it is making sure that all these disadvantages that are present in these techniques is getting removed, right? So this is what we're going to discuss. But I hope you got an idea. At the end of the day, whatever techniques we have discussed till now in converting word into vectors, it falls under word embeddings, right? So yes, this was it from my side. I will see you all in the next video. And in the next video, I'm going to discuss about word-to-vec. Thank you. Hello guys, so we're going to continue the discussion with respect to natural language processing. In this video, we are going to cover word-to-vec. We have already seen what exactly word-to-vec is. It is a deep learning trained model. And again, it is a kind of a word embedding techniques wherein focus is to convert word into vectors, making sure that the meaning of different words are actually maintained. Like if there are similar words, we'll be getting vectors that are very near to each other. We'll probably find out the difference. And we'll also be able to see that which all words are completely opposite based on these vectors. Okay, so let's discuss about word-to-vec. And I will give you an idea about like what exactly is word-to-vec and how the words is getting converted into vectors. In the upcoming videos, I'll try to show you that how word-to-vec models are basically prepared with respect to architecture in the case of deep learning models. And for that, you really need to have knowledge about ANN models, right? If you really need to understand that how we can train word-to-vec from scratch. Okay, and yeah, let's go ahead and with the definition and let's see that what a problem it actually fixes. So over here, word-to-vec is a technique for natural language processing published in 2013, and it was published by Google, an amazing company. Already you know that they've done some tons of work with respect to NLP. They're doing a lot of research. The word-to-vec algorithm uses a neural network model. We'll be discussing about this, how we'll be using it, how it uses a neural network to learn word association. Please make sure that you understand these words. To learn word association from a large corpus of text. Once trained, such a model can detect synonym words or suggest additional words for partial sentence. So it will be able to detect synonyms. It will be able to detect opposite words and many more things. As the name implies, word-to-vec represents each distinct word with a particular list of number called as vectors. So at the end of the day, we are converting a word into vectors, but this vector will have many things. It will be able to detect synonym words, or it will also be able to suggest additional words for partial sentence. Okay. Now let's understand what exactly this is. Now see guys, in bag of words, TF-IDF, we have already seen, right? Based on the vocabulary size, we'll either get ones or zeros, and in short, we're getting a sparse matrix. In TF-IDF also, we may get decimals like 0.2, 5.6, then again zeros are there. In word-to-vec, it will be a little bit different. Now let me talk about how it will be different. Let's consider that I have a vocabulary, okay, and I have a vocabulary let's say I have my vocabulary. So these are basically this many number of unique words I have in my corpus. Okay, unique words I have in my corpus. Corpus basically means paragraph. Okay, now let's say the vocabulary words that I specifically have, like something like boy, girl. Okay, and then we have something like king, queen, and if I probably talk about some more words like apple and mango. Let's say in my vocabulary I have this many words. Okay, now one very important word I'm going to put up over here, which is called as feature representation. Feature representation. Please listen to me very, very carefully. A very important topic. Now, each and every word that are present in the vocabulary will be converted into a feature representation. Now, what this exactly means? This basically means that we are going to convert this all words into a vectors based on some features. Now, what all features can it be, right? Let me give you a very good example about it. But understand that when we are training a very big word-to-vec model, at that time you'll not be getting a clear idea about all the features. But here, just to make this intuition, to make you understand the intuition, let's discuss about this feature representation. So in the left-hand side, what will happen is that let's say that I will be having a lot of features like this. So I may be having a feature called as gender. I may be having a feature called as royal. I may be having a feature called as age. I may be having a feature called as food. Like this, I will be having a lot of features. And let's say that the total number of features, are basically 300 dimensions. That basically means I will be having one more nth feature over here. And the size of this entire features, like if I probably count all of this will be 300 dimensions. Let's consider 300 dimension basically means I will be having this 300 features. Now with respect to all this vocabulary, we are going to represent this word in the form of vector considering this feature representation. So this is my entire feature. Okay, what I'm actually going to do, I'm going to take up all these words that are present in the vocabulary. Based on this particular features, we are going to assign one numerical value. Okay, and understand one thing, this numerical value will be assigned based on the relation of these two words, that is the vocabulary and the feature representation that we have. Here I have given you as an example, but when we are training a very large word-to-vec model, we will not be able to see these features entirely, right? If I take an example of Google, they have come up with this amazing word-to-vec model, which is basically trained in 3 billion words, I guess 3 billion words, which is coming from the news feed, right? And that practical example also try to show you. And at the end of the day, you'll be able to see that each and every word is basically represented by 300 dimension of feature representation. That basically means every word will be having a 300 dimension vectors. Okay. Now this is super important. What kind of values that I can have over here, right? What kind of values I can have over here? Now let's say with respect to boy, which is present in the vocabulary, okay, and its relationship with respect to gender. Let's say that I'm having -1 over here. Let's just consider, okay, -1 over here. Now with respect to girl and gender, the value can be +1 because it is the opposite of boy, right? Opposite with respect to gender. If I say boy is the opposite of boy is nothing but girl, so -1 and 1. This kind of vectors can come. Now here you can see with respect to the next word. Over here we have boy, we have royal. We obviously know we cannot say, right? We don't have a sentence that he's a royal boy. He can be a royal prince or he can be a royal king, right? So there is no proper relationship. So in this particular case, there will be a value like 0.01. I'm just giving you as an example, right? Similarly, we will also be having with respect to boy and age. Let's say that there is not much relation, so I'm just going to put it as 0.03. Okay, very near to 0. Now similarly, I can have all these values over here, and these all values comes through proper trained models like word-to-vec, which is trained by deep learning techniques like ANN. Okay, and I'll show you in the next video how those models are basically trained. But just understand, over here, each and every vocabulary that we are seeing is represented based on this feature representation. So that basically means for boy, I will be having this vector. So for boy, you can see over here, I will be having this specific vector. Okay, so this all vectors will be here. Okay. Now similarly with respect to girl, now you can see with respect to gender, if boy is having -1, then this will be +1, right? Because it is completely opposite. With respect to royal, again no relationship, so it will be 0.02. Let's say here I'm going to put 0.02 because age with respect to this also no specific relationship, right? So similarly I'll be having other values like this. Now see, with respect to king, I may have gender like there's a relationship with respect to gender and king, so -0.92 will be there. With respect to queen, it can be +0.90. So here you can see opposite, right? Opposite over here, right? And similarly I can have other vectors like over here royal and king are related, right? So I can have 0.95. Okay, and over here you can see also royal and queen can also be a royal, right? So over here probably the value can be 0.96, 0.97, very much nearby each other, right? Now understand, because of these vectors, similar words will be very, very close to each other. Because if I try to subtract it, I'll just give you an idea about it. So right now with respect to age also, obviously there will be some relationship between age and king because we say that old king, right, with respect to age. So suppose let's say here I'm having 0.75, here I'm having 0.68, and like this I will be having multiple vectors like this, right? And we can clearly see, right, over here it is. Now see, with respect to apple, obviously it will have no relationship with respect to gender, so I can probably write 0.5 or 0.01 something, right? With respect to mango also it cannot be, so I'll write just 0.23. I'm just saying that okay, we basically can have some values over here. If it is not having a relation, it will be very much near to 0, like 0.05. Okay, I'm just putting some values, but once we train all these models, right, we will be getting this value. Here I'm giving a crux idea about like how each and every vectors may look like. Okay, now over here with respect to apple and royal, also I'll not be having much relationship. So let's say I'm putting -0.202, this will be +0.02. With respect to age and apple, this may have a very good relationship, right? Because let's say if the apple is kept for 10 days outside, it may rotten up, right? It may not have a nutritional value. So this with respect to age, it may have a direct relationship. Mango also may have a direct relationship. So we are going to have this vectors pretty much similar. With respect to food, yes, apple belongs to a food item, right? So this will probably have a good value. It may be 0.91. This is also 0.92, right? And similarly, I'll be having different vectors, right? So here, what we have done is that each and every vocabulary word is represented based on this feature representation, right? And here, the feature representation will not only be 300 dimensions. It can be 100 dimension, it can be different dimensions, right? But here I'm just showing an example with respect to Google. And what will be the features that will also not be exactly no. But just consider that I'm just giving an intuitive example that yes, based on some relationship with respect to the word, you're able to get the specific vectors. Now there are a lot of advantages with respect to this. Why I'm saying you? Because suppose let's say if I do a calculation which is like king minus man plus queen. If I do this calculation, and this is a famous calculation, this is also written in Google research paper. If I probably do this calculation, the output that I'm going to get is something called as human. Okay, I will definitely get it as human. Why? Over here, human is not there. It's okay. So let me just remove it. Suppose if I say king minus boy plus queen, then the output that I'm going to get, see, king is this vector, right? I'm subtracting with boy, and then I'm adding it up queen. At the end of the day, you'll be seeing that the girl will be much more related to boy, so I'm going to get the output as girl. Yeah, I'm just doing a vector calculation, and this is what kind of relations we'll be able to get it. This is an amazing thing. We are getting this kind of relation just by seeing these vectors, which has been provided by word-to-vec. Again, I'm not going to do the calculation here. I've just randomly stuffed some values. But in the real word-to-vec use case, you'll be seeing that if you do this kind of calculation, you're going to get girl. And this I will show you practically also as we go ahead. Once we use this Google word-to-vec, which is basically trained on 3 billion words, which is quite amazing, right? So let me give you another example. Let's say here, what I'm doing instead of using 300 dimension, I'll represent every word by 2 dimension. Let's say I have 0.95, 0.96. Man is represented by something like 0.95, 0.98. Let's represent like this. Okay, I'm just giving some values. Okay, some meaningful values so that you'll get an idea about it. Let's say queen is given as 0.96. Let's say because this is the opposite of this, right? And again, this can be the similar keyword, similar vocabulary. And with respect to women, let's say that I'm having something like 0.94 or 0.196, let's say. Then what I do is that if we do the calculation of king minus man plus queen, I'm going to get the woman, right, as the output. Now, what does vectors represent? That also you really need to understand. It's super, super important. And that is where I'm going to discuss about something called as cosine similarity. Okay? Cosine similarity. Super important topic with respect to understanding these things, because if you understand these things and all. Now see, over here, king is given by two vectors, right? 0.95, 0.96. So obviously I can basically construct this into a two dimension. Let's say that I'm getting king over here. Okay? And in order to make you understand, let's say queen is over here. Okay, or queen can come over anyway. Let's say man is over here. Right? Man is over here. If I probably say king with respect to gender, right? This two is going to be the most nearest one when compared to queen, right? So how do I calculate the distance between this vector and this vector, which is provided in this form? All I do is that I try to probably calculate the distance like this. Okay? I try to find out the angle. And for this, to find out the distance between two vectors, we use a distance formula which says it is nothing but 1 minus cosine similarity. Now, what is cosine similarity? This is super important to understand. Cosine similarity, I can basically say that cosine similarity is nothing but the angle between these two vectors. Let's say the angle between these two vectors, let's say I'm just taking as an example, is 45 degrees. Let's consider. Then this is nothing but cos 45. Cos 45 is nothing but 1 by root 2. And probably I think this is approximately equal to 0.7071. I've done the calculation. If it's wrong, just let me know. Okay? But over here, then the distance between these two vectors will be nothing but 1 minus 0.7071. Now, if I'm calculating the distance, it is 0.29, let's say. So if I'm getting this 0.29 distance, right, I will say that, okay, almost this particular word are similar. Let's say if I have two more vectors, if I have two different vectors, one of the vector is basically over here, one of the vector is over here. Then the angle between the two is nothing but 90 degree. In the case of 90 degree, my distance will be nothing but 1 minus cos theta. Cos theta is nothing but cos 90. Cos 90 is nothing but 0. 1 minus 0 is 1. So I can definitely say this vector and this vector are completely different because the distance between them is 1. If the distance is nearer to 0, I will say that they are almost similar vectors. Now in this case it is 0.29. I can say that, okay, somewhat similar, right? Let's say if I have one more vector which is in this point only, then I can say that these two vectors are almost same because the angle between them is cos 0. Cos 0 is nothing but 1 minus 1, which is nothing but 0, right? Because over here, the angle between these 2 points is nothing but 0, right? There is no angle at all, right? So if there is no angle, then I will be able to find out the distance. In this case, my distance will be nothing but 1 minus cos 0. 1 minus cos 0 is nothing but 1 minus 1, which is nothing but 0. Now, if the distance is coming as 0, that basically means these two are same word, right? Now, so this is super important because recommendation also happens in this way itself. Now, in recommendation, let's say I have a movie which is like Avengers. Let's say Avengers is over here. Where do you think Iron Man will come? Iron Man will come again near this or near this at this particular point only, right? Iron Man will be coming, and it will be based on different feature representation, right? Whether it is a comic movie, whether it is an action movie. So action, comic, right, or comedy, these all are feature representation. Try to understand this. And movie name is basically my vector, my vocabulary. It can be Avengers, it can be this one, right? So I hope you're getting an idea about how word2vec is basically working. At the end of the day, we are basically creating a feature representation of every word, okay? And we are able to find it out. So yes, this was about word2vec. Now what we are going to do is that you need to understand that how this feature representation is created and how this vectors is basically created. How this vector, because here I have randomly written boy to gender is -1, boy to girl to gender is +1, because I said that, okay, this may be the opposite one. Now you get an idea that how in an deep learning neural network, basically a simple neural network, how this entire word2vec is trained. And that is what I'm going to discuss in my next video. Then I'm going to also show you the practical implementation. So I hope you're able to understand this with respect to this, a very good, amazing model developed by Google, a very good architecture for with respect to this, and we'll try to solve that in the upcoming video. And I'll give you a clear idea about it, okay? Just the prerequisite is that you really need to know about ANN, loss function optimizers and all. So yes, this was it. I will see you all in the next video. Thank you. Hello guys, so we're going to continue the discussion with respect to word2vec. Already we know word2vec are basically of two types. One is CBOP, which we have already seen previously, continuous bag of words, and SkipGram. In this video, what we're going to do is that we're going to understand that how word2vec model is basically created, what is the deep learning model that we are specifically saying, how the inputs and outputs are there, and how the model is basically trained. One important thing is that you really need to have a prerequisite knowledge about ANN, loss function, and optimizers. So if you do not have this, I would suggest first of all, please make sure that you have some knowledge about this, right, before you understand this. Now with respect to word2vec, one more important thing is that in word2vec we also have a pre-trained models, right? Now if I talk about a pre-trained model like Google, right, Google has a pre-trained model with respect to word2vec, which is trained on 3 billion words, and we can also train a model from scratch. Okay, and again, the reason why I'm taking this because you really need to understand that how the feature representation is basically getting created. Okay, now let me go ahead and let me say is that let me take a simple corpus and let's say that first of all we'll start with CBOP. Okay, so we're going to discuss about CBOP, which is nothing but continuous bag of words, and how this model is basically created. It is a type of word2vec, right? Continuous bag of words. Now to solve any problem, I will definitely have a data set. So let's say that this is my corpus, and remember corpus because all these models, like word2vec is trained on a huge data set. Like this particular pre-trained model from Google is basically trained on 3 billion words. So let's say I have a corpus or a statement or a data set or a paragraph. It can be anything. And for just making you understand, I'm just going to take a simple paragraph. I'm going to say that, okay, iNeuron is iNeuron company is related to data science. Let's say I have this particular corpus. Now, remember like this, in a use case, you'll be having a bigger corpus. It can have millions of words, right? But let's say that I'm taking just a simple corpus over here, just a single liner. Now we're going to understand that how a CBOP word2vec is basically created and how a model is basically trained with the help of deep learning. Now, first thing is that whenever we have a corpus, we really need to know what is our input data and what is our output data, because word2vec altogether is a supervised machine learning, right? So first of all, what we do is that we select a window size. And I'll talk about this window size and why it is super important. Let's say that I'm going to select a window size of 5. Now this window size is super important to basically create your input data and output data. Okay, super important. Like what should be your input data and what should be your output data so that you can train a model, right? Now this window size 5 indicates that how many words I need to select initially. So let's say I'm selecting 5 words. So here is my 5 words. Now from this particular 5 words, I will take the center word. Now understand how I will take up this window size 5 words and convert into input and output data. So let's say this is my input data and this is my output data. Okay. Now the central element that I've actually taken over here is right. Now in the input, I will be having iNeuron company. and then on the right hand side I have related, and I have two. Okay. Now why you may be thinking that I'm taking the forward and the backward? Because understand, if I'm taking this as a central word, and this will basically be my output word. Okay, this is basically my output word. Now it should be knowing that what all words are in the forward context and what all words are in the backward context. So that is the reason we are creating in this particular way, so that this is output should be knowing about its forward word and its backward word, just to get some idea about the context of that specific sentence. Now this is the first step. Now when I took the window size as 5, the initial 5 words, I divide my data set into input and output. Perfect. Now the next step is that I will go ahead and I'll move this window by one step and take the next 5 words. So the next 5 words over here is nothing but, so here this is my sentence 1, so sorry, input 1, and now this will become my input 2, and here I will be having company. Okay, and again from all these 5 words, which is my center word, so this is basically my center word, related, right? So related. So here I'll write company is 2 and data. So this is my second input, and over here the output will basically be related, right? Then similarly I will go to the next step and I will push this windows to one step more. Okay, so here now I'll be having my third sentence with respect to my input and output, and the third sentence again, which is the central word, so this will basically be my central word. So here you have 2, okay, and here I'm going to have is related, okay, and then the right hand side data and science. Now you may be thinking, English, should we only take the window size as 5? No, you can take any value. You can take any value. And why this window size is playing an important role, I'll just say in some time. You can take up any value, but don't take an even number. Take an odd number so that I will be getting the central element which I'm taking as an output will have the correct number of words in the forward context and in the backward context. Okay. So is related data science is there, right? Now, which is the central word over here? 2, right? So I'm just going to write it as 2. Now this became my input and output. Now what I'm actually going to do is that I'm going to train my model with this. Very simple, right? I'm going to train my model with this. Now how the training will basically happen. Now one very important thing that you need to understand. Over here you'll be seeing iNeuron company related to all these inputs and outputs. So I cannot probably send this text directly. I need to convert this into some vectors initially to send it in as an input to the neural network also. So for this, what I'm actually going to do, first of all, you know that how many number of words I have, how many number of words I have in the vocabulary. I have iNeuron, I have company, I have is related to data science, right? So they are on 1, 2, 3, 4, 5, 6, 7, right? 7 words are there. Now if I probably use one hot encoding technique. Now see this. Okay, this is super important. In one hot encoding technique, if I probably consider iNeuron, let's consider the first sentence. Over here I have iNeuron, and then I have company, then I have related, and then I have 2, right? So for all these words, how I'll be giving the one hot encoding representation, wherever there will be iNeuron, I'm just going to make it as 1. Remaining all will be zeros. So there will be around 1, 2, 3, 4, 5, 6 zeros. Similarly, when company is there, I'll make this as 1 and remaining all will be zeros, right? Similarly, related is in the fourth word. So I'm going to make it as 0, 0, 1, 0, 0, 0, and then 2 is present after this. So I'm basically going to write it as 0, 1, 0, 0, right? So this is pretty much clear till here, right? So here you can see that I've basically done this a simple one hot encoded format. That basically means if I really want to pass iNeuron, I need to give this as my vector. This is what is the understanding. And this vector is basically given by 7 dimensions. So 7 vectors I'm giving it over here, right? 1, 0, 0, 0, 0. If I'm sending company as my next word, then this should be the vector it should go, right? Then if I'm sending related, this should be the vector I should go. So similarly, all these particular words will be converted into this particular vector using one hot encoding. Now let's go to the next step, which is super important. Okay, super important. What does CBOW basically mean? Continuous bag of words. Okay, this is nothing but this is a fully connected neural network. Now you'll be able to understand how these models are created. Fully connected neural network. Okay. Now in this fully connected neural network, you'll be able to see one very important thing. One is, first of all, just understand how many number of inputs should I be giving, right? Like how many words I will be giving as my input, right? Since my window size is same, window size is 5, all my inputs are fixed. I hope that is very much clear, right? Now in this particular problem statement, you'll be seeing I'm giving 4 words in every sentence. So my input is basically fixed. Now, iNeuron, when I give my word iNeuron, let's say in the first case I give my sentence 1, and this is my sentence 1. When I give iNeuron is represented by 7 vectors over here. It is represented by this vector. Then company is basically represented by this vector. So if I probably see in fully connected layer, my first input layer will basically be nothing but, so here you'll be able to see, this will be my input. Okay. And this is super important. See this. So this will be my input, my first input word. Okay. And understand I'm creating this circle as my inputs. Okay, I'm just creating this circle as my input. So if you see 1, 2, 3, 4, 5, 6, 7. 7 inputs I'm giving it, right? Now when I give this 7 inputs, then similarly how many words will be going? 4 words will be going, right? So 1 word, 2 word. So this is basically my input layer. So this layer is nothing but my input layer in a fully connected layer. A simple ANN, if I probably consider an example of ANN. So here also how many inputs I'll be having? 1, 2, 3, 4, 5, 6, 7, right? And this is my first word, second word, third word, fourth word. So I will be having 4 different words over here that will be going. And each word will be having a dimension of 7 vectors. 1, 2, 3, 4, 5, 6, 7, right? I'm not giving this value. Don't consider that these all are zeros, okay? I'm just saying that these are my input layer, input circles, okay? That is how we create it in ANN, right? And then probably I have my last one. So this is my input, right? I'm basically designing the neural network, how it will look like when we're training the word to way. So these are my four words. Understand, in the first case, I'm going to pass iNeuron over here. So let's say I'm going to pass over here iNeuron. This will be my input over here. This is represented, iNeuron will be represented by 1, 0, 0, 0, 0, 0, right? And similarly, if I go to the second word, that is like company, then it will be represented by another word like this, right? It will be represented by a different vector like 0, 1, 0, 0, 0, 0, 0, right? 7, it will be 1, 2, 3, 4, 5, 6, 7, right? Now similarly, other words will be represented like this, okay? So this becomes my input layer, okay? And every input is basically given by a vector of 7 dimensions. So because I'm representing every word based on the vocabulary size using one hot encoding. Now this becomes my input layer. Now let's go to the middle layer, that is called as the hidden layer. Now in this hidden layer, this is super important. Just pause the video and guess what will be the size. You know that our window size is how much? Our window size is basically 5, right? So I'm just going to make this as my window size. Okay. So this is my window size. Now in my window size, if you remember, how many we are having in our window size? Our window size is nothing but 5. So I'll be having 1, 2, 3, 4, 5. Right? Window size is basically 5. So in my hidden layer, I'll be having this 5 vectors. Okay. So just understand that with respect to this 5, our window size will be set over here. Okay. Now with respect to the output, in output, how many values I have? I just have one value. And each word, I just have one word in the output, right? And each word is represented by a vector of 7. Because if I'm also considering this is using one hot encoding, I'm going to get this vectors of this dimension that is 7. Right? So what I will be doing in output, I will basically be having another output layer like this, which will again be having 7 different outputs. 1, 2, 3, 4, 5, 6, 7. Okay. Now this is how my fully connected neural network will look like. Now you need to understand one thing. Over here, each and every node will be connected to the other node, right? Like this. Like this it will be connected. Like how an ANN will work. It will be connected like this only, right? Similarly, right? Now, similarly, this all will be connected to this also. So in short, I can basically make a very simple connection like this, which will look like this itself. And this will be entirely connected to this, right? Understand all these lines will have some initialized weights, and we need to train these weights. And this is what it happens in ANN, right? Similarly, this will be connected to this. This will be connected to this. This will be connected to this, right? And finally, this will also be connected to this, right? So everything is basically getting connected. And from the hidden layer, this is my hidden layer 1, HL1, and this is my output layer. Right? Now from this hidden layer, it will basically get connected over here, and this will get connected over here. Okay. Now understand one very, very important thing. Okay. This is super, super important. Fine. We are connecting it with the help of loss function. We'll also do forward and backward propagation. Now let's say we'll consider let's pass this particular word ineuron company related to. So I passed ineuron company, and here also you'll be able to see I'm passing related to. Very simple. Okay. Let me just zoom out a bit. Okay. Now once I pass all these things, what happens over here? With respect to the 7 output, I already know what is my real output is, right? I'll be getting some values over here. Okay. I'll be getting some values. Okay. But the real output is what? If I consider is my third word. So is my real output. So this will basically be represented in this vector format. That is 0, 0, 1, 0, 0, 0, 0. Right. But after training, while we are training the model with different weights, this is my true output. This is my y. I may also get different y hat, right? I may get some values like 0.25, I may get some values like 0.33, then like the 0, 1, 0, 0, 0, something like this. Then what we do, we basically calculate the loss function, and based on this loss, we need to reduce this. We do the backward propagation, right? Backward propagation, and we do it unless and until the difference between y and y hat are minimal. Okay, and this process is continuous. Very simple. But now you really need to understand one very important thing. Very, very important thing. Now, since this is giving me a specific output, okay, this is basically giving me a specific output. When I say my middle layer is basically window size of 5. Window size of 5. That basically means over here in the Word2Vec, when I said I will be getting a 300 dimensions over here, when I'm using Google Word2Vec, this is all because of this window size. Okay, that basically means if my window size is 5, I'm going to get the output as 5 for every word. That basically means when a word is getting converted into a vector, I'm going to get a size of 5 vectors, and this will basically be my final output. Now I hope you're able to understand. Again, let me repeat it. The reason I have actually selected window size is equal to 5 because I want to probably provide a feature representation with a vector size of 5. Okay, that basically means every word will be converted into a 5 vector. Now, when I took an example of Google, which was getting converted into 300 dimension, that basically means my window size is 300. And more the bigger window size, the better the model can basically perform. Okay, so in this case, you'll be able to see that over here my window size is 5. That basically means if I see from starting, right, my metrics for every word will be 7 cross 5. That many number of weights will be there. And here also I'll be having 7 cross 5 weights. Here also I'll be having 7 cross 5 weights because I'm giving 7 different vectors. Here also I'm having 7 cross 5. But in this case, I'll basically be having 5 cross 7. Now, what does 5 cross 7 basically mean? When this loss gets reduced, then my final vector will look something like this. This all will get connected to this. This all will get connected to this. Let's say it is getting connected to this one. It is getting connected to this one. It is getting connected to this one. So once we have this particular connection, let's say our first word over here is, what is our first word? If you probably see, what is our first word with respect to this particular vectors with vocabulary? You'll be seeing ineuron, right? This is my vocabulary. The first word that is basically getting represented over here is ineuron, right? So ineuron will have an output dimension of 5 vectors because I'm getting this 5 vectors over here joined to this. So this 5 vectors will be like 0.92, it can be 0.94. Based on the training, it can be 0.25, it can be 0.36, and it can be 0.45. And this is based on some feature representation. So I hope you're able to understand. And this is how ineuron will be represented. The second word that we have in the vocabulary, that is company, right? This will again get connected to this company. This will also get connected. This will also get connected. This will also get connected. This will also get. And this entire word will be the vector for the company itself. For the company, we may have a different vector, but again, the size will be 5 dimension because our window size is 5. And this training of forward and the backward propagation, when the loss is minimal, then only we'll be able to get the vectors. And that vector is basically taken and it will be represented in the format of the feature representation for each and every word. So I hope you are able to understand like how Word2Vec actually works with respect to CBOB, right? That's continuous bag of words. If you don't know about ANN, then it will be quite difficult, but again, understand the loss function, it'll keep on reducing. And finally, whatever vectors you're getting at the last, that will be combined and that will be taken as the first word, then second word, and third word like that. Okay. So yes, this was it about CBOB. In the next video, I'll be talking about skipgram, right? And then we'll talk about the advantages and disadvantages of this particular Word2Vec. So yes, I will see you all in the next video. This was it. Thank you. Bye-bye. Hello guys, so we're going to continue the discussion with respect to natural language processing. In this video, we're going to discuss about the second architecture, that is skipgram. Now, already I've actually shown you how the CBOB actually works, continuous bag of words, and I've also showed you that how the neural network gets trained, right? Now, what is the difference between CBOB and skipgram? What is the difference between the architecture? It's very simple, guys. Right now, just focus. I'm going to take the same data set over here. Let's say the ineuron company is related to data science. I've written over here, right? And with respect to this, you can see that I've created my input and output. Now, if I am using skipgram, then the thing that is going to change is that everything will be same. Let's say that I have taken the window size as this. So if I probably go ahead and show you, now what will happen is that before, the input was this specific test and the output was this specific test. Now, with the help of skipgram, over here, initially, let's say that if this was input, now this is going to become the input, and this will basically be the output, right? And this is with respect to window size is equal to 5, right? Window size is equal to 5. All the steps will be same. Only what we are doing is that we're changing the input and we're changing the output. Before, the input was this all text and the output was this. Now, what will happen is that entirely when we are creating this neural network, now in the input, let's say that I have this is word, related word, to word, right? So in the input, I'm going to basically have input layer with 7 vectors that will be going. Why 7? Because if we probably see this, our vectors, how many number of vocabulary, what is the vocabulary size? 1, 2, 3, 4, 5, 6, 7, right? So initially in the input layer, I'll be giving input, which will be basically having 7 vectors, 7 dimension vectors. And then in the middle, I will basically be having my window size vectors. So window size is nothing but 5, 1, 2, 3, 4, 5. Just understand this, these are just nodes, okay? And in the output, you can see that I'm having 4 words, right? So everything that is present with respect to this, right? Similarly, this will get constructed over here at this point of time. So over here in the output layer, you'll be able to see that I'll be having 1 word, 2 word, 3 word, and the 4th word. So this is what is the kind of output we will be getting. And again, here it is very much simple because every one will be like 7 dimension over here again, right? So I hope you're able to understand. We just change the direction with respect to this, right? So this will be my input layer. So here you can see that we will basically be having a 7 cross 5 matrix with respect to the weights, because weights initially be randomly and initialized, right? And then we need to train this, right? And then we will be having with respect to this all, I'll be connecting here to here, here to here, and this will basically be a 5 cross 7 matrix with respect to weights, and then this will be 5 cross 7. Similarly, over here you'll be seeing that this will be 5 cross 7, and below one will also be a 5 cross 7. But in with respect to that, you can see that initially when I give the input is will be the is vectors will be going over here, and as you know that is the third word, so this will be going like this, right? So 0 0 1 0 0 0 0. So this is the vectors that will be going over here, and again since my window size is 5, over here you'll be able to see other vectors that will get initialized. Randomly, this all will be connected with weights, so 7 cross 5 weight matrix will be created, and with respect to this, how forward propagation will happen. And obviously, you know that if you probably know ANN, right, what all things happens in between the hidden layer. The input weights is getting multiplied by the weights itself, and then a bias is added and an activation function is applied on top of it. In the output layer, we basically apply a softmax function. Softmax function, so that we compute it with y and y hat. Y hat is the predicted one, y is the real data. In this particular case, this is my y. Sorry, this is my y. Right? In the first case, y is I neuron. So I neuron, whatever things will be there, whatever vectors will be there, here you'll be initializing it. Right? So here I basically apply a softmax function. Let's say with respect to I neuron, my y is nothing but 1 0 0 0 0 0 0 0 7 zeros, and then y hat will be computed since we apply a softmax over here. Right? So y hat will be something, right? Some values over here, and then what we do, we calculate our loss function, and we make sure that we keep on doing the forward and the backward propagation unless and until all the loss function decreases. Right? The loss value decreases, and finally you'll be seeing that whatever is connected, right? This particular word will be shown in the form of 5 vectors. This word will be shown in the form of 5 vectors once the loss is completely minimized. So same process. You should definitely know how the ANN actually works, how the optimizers actually work, and this was just a brief idea about scriptgram. Right? Now, how can we improve this? Or the basic question is that when should we apply CBOW? CBOW. So the question is, when should we apply CBOW or skipgram? Right? The simple thing is that according to the research, right, whenever you have a small data set, small corpus, we can definitely go with something like CBOW, that is continuous bag of word. If you have a huge data set, you should definitely go with skipgram, and that is proven in many research papers. I'm just giving you the direct observation out of it so that you'll be able to do this. Now, let's say if you want to increase CBOW or skipgram, how can you basically do it? One thing is that you should increase your training data set. Increase the training data. That basically means the more the training data, the better the accuracy, right? Increase the training data. The second thing is that you can also increase the window size, which in turn leads to increase of dimensions, increase of vector dimension. This is super important. Okay, so here I'm saying how to improve CBOW or skipgram. So this is what you can basically do. Increase the window size. Okay, this is super important. Increase the window size. I'm again going to take this separately or forget it out. So over here again, let me write this. We have to increase. We can also increase the window size. Instead of having 5, I can make this as 100. You know, so obviously with the increase in the window size, increase the window size. If you are increasing the window size, that basically means the vector dimension is also increasing, right? The vector dimension is also increasing. So when we keep on increasing and try it, you'll be able to see that we'll be getting better performance. So this is also you can basically use. You can increase it. Now when we see in the next example, right, we'll be using a pre-trained model with respect to Google. So Google word2vec, right? Now this is basically trained in 3 billion words. I guess it is 3 billion words. 3 billion words. And it is going to give me a feature representation of 300 vectors. Sorry, 300 dimensions. That basically means, suppose if I have a word cricket, okay, since cricket is always there in the news, this 3 billion word is from the Google News, right? And Google is a very big company, guys. But then this amount of data is very much easy. So what they're going to do is that if we give a word called as cricket, then it is going to basically convert this into a 300 dimension vectors. Okay, vectors. This is super important. 300 dimension vectors. Okay. I'm just going to write it as 300 dimension vectors. And this all example I will try to show you when we use this. What we'll do is that in the upcoming session we'll try to use a pre-trained model also, and we'll try to also make sure that we train a new data set from scratch with the help of word2vec. And that we are going to basically do with a GenSim library. Okay. So yes, this we will be doing in the next video. So I hope you have understood both the architecture. One is CBOW and one is the skipgram. Only the thing that you really need to know is that you need to have the knowledge of ANN or a fully connected layer neural network. If you know that, it'll be very easy to understand. So yes, this was it from my side. I will see you all in the next video where we discuss about how to implement word2vec. Okay. So yes, I'll see you all in the next video. Hello guys, so we're going to continue the discussion with respect to word2vec. In this video, we're going to discuss about the advantages of word2vec. Now, already from our previous techniques, like bag of words, TF, IDF, we have already seen that what were the main problems. See, initially, before we used to get a sparse matrix, right? Sparse matrix basically means we used to get a lot of zeros and ones or decimals or zeros. This kind of matrix we used to get, right? And obviously, what is the problem with sparse matrix? It leads to overfitting. But now, with the help of word2vec, you are actually being able to get a dense matrix, right? So now you'll be able to get a dense matrix, and this is only possible because of word2vec. That basically means you will not have many zeros or ones. You know, so this was the first amazing advantage with respect to word2vec. And again, if you have a dense matrix, again, machine learning models will be able to train in a better way, right? Coming to the second point, right? Because we have already seen with respect to every word, we are getting a separate dimension of vectors, and we're also able to find out the similar vectors also. Now, the second thing is that based on the similar vectors, before semantic information was not getting captured. Now, semantic information is getting captured, right? Info is getting captured. Now you will be able to find out the similar words with the vectors itself, comparing the vectors itself. So semantic info is getting captured now, right? Before, with the help of techniques like bag of words or TF, IDF, there was some amount of semantic information getting captured, but not much. That basically means if you really want to find out a word, let's say there's a word like honest, right? And you want to find out a similar word, or you want to find out how similar this specific word is. So that you will be able to do with the help of word2vec. Now, honest and good, I think it is almost a similar word. We'll also be able to find out the cosine similarity with respect to this. And that is what I will be probably showing you as we go ahead, you know, by seeing the practicals of word2vec by using pre-trained models, and again from scratch also we'll try to see it. So coming to the third one over here, now you don't have to actually worry about vectors becoming bigger, because before with the help of bag of words and TF, IDF, we are completely dependent on the vocabulary size, right? Vocabulary size. But now we are not dependent on the vocabulary size. So over here you'll be having a fixed set of dimensions. Now if I probably take an example of Google pre-trained word2vec, right? Google Word2Vec, pre-trained Word2Vec, there you'll be able to see that we'll be having only 300 dimensions, and it has been trained in huge data, huge data. So obviously, this again solves a very big issue. Before, again, we used to get a very, like, if the vocabulary size is huge, that many number of vectors we used to get. Now, no, fixed set of dimensions with respect to vectors, we are able to get it. Okay, so this is also a very important thing. Coming to the next one, which is called as out of vocabulary. Now, out of vocabulary, there is hardly any scenario that you will be able to see that some words may be outside the dictionary or outside the corpus itself. With respect to out of vocabulary is also solved. Why? Because now we are capturing all this information like semantic info and all, right? We also making sure that because we represent every word with some feature representation, right? So that is also out of vocabulary is also solved with respect to this. So these are some of the advantages of Word2Vec, and again, right, it will definitely perform well when compared to the bag of words for TF-IDF model. But yes, this is a good good way. Basically, we'll think of. We'll also show you that how we can actually solve a text classification with the help of Word2Vec and all as we go ahead, right? So this was in short the advantages of Word2Vec. In our next topic, I'm just going to show. I'll try to show you one more very important topic which is called as average Word2Vec. Super important topic because if you really want to solve any text classification problem statement, we really need to also use average Word2Vec, and that is what we are going to see in the next video. So yes, this was it from my side. I'll see you on the next video. Hello guys, so in this video we are going to basically see the Word2Vec practical implementation. I really want to show you some Google pre-trained models and basically give you an idea like how Word2Vec creates a vector, right? So for this tutorial I'm going to use a library which is called as Gensim. So let's go ahead and let's install this particular library. So you just need to write pip install Gensim. So here you can see that requirement is already satisfied, and what I'm actually going to do is that I'm going to import Gensim, and from Gensim.model I'm going to import Word2Vec and keyed vectors, okay? And I'll talk about this why these two libraries are specifically required. Now one very important thing for this, as I said that to show you the practical implementation of Word2Vec, here I'm going to take a Google pre-trained model. In the upcoming video I will try to show you a different model which can be trained from scratch, but here I'm going to show you a Google Word2Vec pre-trained model, and what this particular model is all about. So I'm basically taking a Word2Vec Google News 300, okay, and this is basically a pre-trained vector trained on Google News dataset about 100 billion words. The model contains 300 dimensional vectors for 3 million words and phrases, right? These phrases were obtained using a sample data driven approach and distributed representation of this and all the research paper and everything is basically given over here, okay? So this same model we are going to use, and we're going to see that how it can easily create vectors whenever we give any kind of words. So in Gensim, you have something called as API, right? So there is a library called as API. So you just need to write import gensim.downloader as API, and you just need to write api.load and basically the model name, right? So the model name is nothing but Word2Vec Google News -300, okay? Now once you do this, all you have to do is that when you provide any word inside this WV variable, which is nothing but this is an instance of the specific model, it will try to give you the vector. I'm not going to execute this line of code because I've already done it, because the model size is 1662.8 MB, right? So it will probably take some time for you all to download. So I have already downloaded this so that I can record the video directly. You can just go ahead and download it. Now let me go ahead and see that how the king vector look like, okay? So this is basically the king vectors, how the word is basically converted into vectors, and the dimensions that you'll be seeing, right? How many vectors are there? As said from here, right? We have 300 dimensions. So this is what we're getting. This entire vectors you'll be able to see will be having 300 dimensions. So if I probably use this vector underscore king dot shape, right? So if I execute this here, you'll be able to see 300 dimensions, right? So with respect to this, you use any kind of word, you will be able to get some kind of vectors. Now let me give you some of the example. Okay, suppose I make over here, and for this particular vector, what all things I use this WV variable, which is a Word2Vec object, right? All I have to do, I have to give this and give any word of your choice. Let's say I want to give cricket, right? So if I give probably cricket, you'll be able to see that the vector is automatically generated. So here is again the vector which you are basically getting with respect to this particular shape, that is 300 dimension. Now this WV variable, right, which is a word vector, it also has some of the functions. You can actually use something called as most underscore similar. Now let's say that I've given this most underscore similar. I'm saying that from if I'm giving this cricket word, right, which is the most similar word present in this entire corpus, right, and I'm actually going to use the same Word2Vec object, and I'm going to find out all the words. So if I execute this here, you'll be able to see the most similar with respect to cricket. It will first of all try to convert into a vector, and then it will probably check whether that vector is being able to see any similar kind of words or not. So these are all the words that is similar to cricket in that specific corpus. So you have cricketing, it is having like 0.83 similarity, 0.83% similarity. Then cricketers 81% similarity. Then you have test cricket. Here you can see 80% similarity. 20 cricket, right? You have 80% similarity. Then you have cricket. Then you have cricketer. All these things, they are showing some kind of similarities with respect to this Google News feed, right? Now similarly, if I really want to find out which is the most similar word with respect to happy, you'll also be able to see I'll be having words like glad, pleased, ecstatic, overjoyed, thrilled, satisfied, proud, delighted, and understand that these all are similar words when I compare to happy, right? So it is also being able to say that okay, these are the similar words when compared to the happy word, and they're also being able to show with respect to how much distance. And I've already shown you how this distance is basically calculated, right? So we have a concept of cosine similarity and all. Similarly, I can also provide two words, and I can basically say that okay, how much these two words are basically similar. So if I probably execute this, here you'll be able to see WV.similarity. I'm getting hockey and sports are somewhere around 53% similar, right? Now this is very interesting. Okay, I'm going to take the vector of king, and I'm going to subtract with the vector of man, and I'm going to add the vector of woman. Now let's see what will be the kind of output vectors that I'll be getting. Okay, so once I do this, in short, what I'm doing, I'm subtracting king minus man plus woman. Obviously, the answer should be queen, but I really want to prove you through the vectors itself whether we are able to get the queen or not. So here I'm going to execute this. I got my vector. So this is my entire vector. So this is my entire vector, and again this vector is of 300 dimensions. Okay, so this is my entire vector. Now what I'm going to do, I'm going to use WV dot most underscore similar, and I'm just going to pass this entire vector over here. So once I execute this, here you'll be able to see that. See, king is the first. Obviously, king should be the most similar vector, but here I'm getting queen, monarch, princess, crown prince, king, sultan, queen resort. But here you can see that the most similar word after king is queen. So the kind of vector we are getting after doing all this particular subtraction matches more towards the vector with respect to queen, right? And this is what we are able to get with the help of Word2Vec. Try to use this, guys. This is an amazing model altogether. You'll be able to see that you can actually use this model itself. You can actually use Word2Vec Google News 300, which will be able to solve many problems of yours. And this is just a brief idea about a pre-trained model. How a Word2Vec pre-trained model looks like. You can also take your own text and train it from scratch. But again, there's a different process for altogether. And this entire thing I've executed in Google Colab because the model size is quite huge. Okay. So in the upcoming videos, what I'm actually going to do, I'm also going to show you a Word2Vec technique by using Gensim where you can train the model from scratch. Okay. So yes, this was it for this particular video. I will see you all in the next video. Thank you. Hello guys, so in this video I'm going to talk about NLP and deep learning. Till now, if I talk about machine learning with respect to NLP, we have discussed about various topics, and all these topics were involved wherein we were specifically working with text data, right? And with respect to this particular text data, if we really wanted to convert this into some vectors, which is some numerical representation, right? Numerical representation, we used various techniques. The first technique, if you remember, in NLP machine learning, we discussed about one-hot encoding, right? Then we went up with bag of words. Then the third topic that we discussed was with respect to TF, IDF, right? Coming to the fourth one, we discussed about word to vec. Along with this, we also saw about average word to vec. And we saw a lot of practical application. We took a specific data set and we tried to solve problems like sentiment analysis, and text classification, right? We did this kind of task, text classification in practicals, okay? Now, when we move one step ahead, that is nothing but NLP in deep learning. Now, as you all know, this text data are nothing but these are sequential data. And if I just give you a brief information about ANN, we learned about artificial neural network. And this artificial neural network, let me just go ahead and write it down again. This artificial neural network was used to solve various problem statements, specifically supervised problem statements like classification and regression, right? It was used to solve classification and regression. Now, when we use this classification or regression, here you can consider that I had some kind of data, and this data was nothing but it was a tabular data. What do I mean by tabular data? So this was nothing but it was a kind of tabular data. Now, when I say tabular data, let's consider an example. Suppose I have a house price prediction data set. Okay. In this specific data set, you will be seeing that I may have some features like what is my house size, what is my number of rooms in the house, and what is the price of the house. So when we have this kind of tabular data, okay, I'll be having a lot of key points over here. I will be considering this as my output variable, my dependent variable, and then I can probably go ahead and solve a regression problem statement for this because price is a continuous value. If my output feature is a categorical value, then I can probably solve it with the help of classification. Over here, all these features that you will be seeing, right? If I probably change the order of this particular feature, let's say, and for this, right, if I really want to solve with the help of artificial neural network, since I have two inputs over here, I may go ahead and create this kind of ANN, right? So let's say this is my input layer where I will be giving my two features. Let's consider this is my F1, this is my F2, and this is my Y, right? So here I will be giving my F1 feature, I'll give my F2 feature, and then along with this, I may have some hidden layers. Let's say this is my first hidden layer, and as discussed, all this input feature will be connected to this particular hidden layer over here, and over here, right? And let's say this is my output feature, and this will also get connected, right? And finally, I get my Y hat. So in the ANN, what we do is that we give this feature F1 and F2, and then we initialize some weights. Let's say this is W1, W2, W3, W4, W5, W6 weights. And here also we have W7, W8, W9, right? So based on these particular weights, we do forward propagation, okay? And then we do backward propagation. Now in the forward propagation, what we do, we basically take the input, multiply the weights, and then along with this, we also add a bias. So let's say this is B1, this is B2, and this is B3. And then we apply an activation function. And similarly, we do all the steps in all the nodes. And finally, we get the Y hat. Then we calculate our loss. Loss is nothing but y minus y hat. Let's consider this as an example, y of I minus y of I hat. And then based on this particular loss, our main aim is to reduce this loss. So in order to reduce this loss, we need to change all these weights, and that usually happens in the back propagation. And that is how we basically solve this problem. Now, one very important point in ANN is that if I interchange this feature, let's say that if I change the order of this feature, let's say that if I initially I had this F1, F2, and Y, let's say my first feature was house price, and the second feature was number of room. Even though I make this feature as F2, F1, then also we will be able to train this particular model with the help of ANN. Now, one very important information about tabular data is that here, tabular data, you have features, you have some values, like how we have our data in our CSV format and all. And the second thing is that over here, your sequence of data does not matter. Okay, so this is very much important point. Your sequence of data does not matter. That basically means you can change the sequence, right, while training it. You can keep F2 first, F1 first. Let's say if you have F3 feature, I can keep F3 first. Because at a time, this entire row will be sent for training, right? So here we are giving out F1 and F2. So this will be for my first row. Then for my second row, right? Based on the batch size, we will be giving this entire data and doing the forward and the backward propagation. Now this is fine, right? And this is with respect to ANN. Now if I consider the second example that we have seen already in our session, that is nothing but it is about CNN. CNN basically means convolutional neural network. Okay? And here with respect to convolutional neural network, you use this for, so basically over here your data will be in the form of images. It can be in the form of images, it can be in the form of video frames, right? And here, most of the tasks that you specifically do, right? Some of the examples are like image classification, right? You have image classification. Let's say you want to do object detection. So you use some higher variants of CNN, like RCNN, you have YOLO, all these kind of algorithms you have, right? So this is kind of task you'll be able to do with the help of CNN, okay? Now this is fine, and this is also fine over here. Now let's talk about the third thing, and that is where we are going to come up with. That is nothing but NLP and deep learning. The third thing that we will be specifically talking about is for a data that is of sequential type. Sequential type. Or I can also say this is nothing but this is my sequential data. Now, what exactly is sequential data? Some of the examples that I will be considering over here. Let's say this is one of the examples that I will say. I have a data set which involves some kind of text, okay? And or let me just take one example over here. I'll just go ahead and write it down. So let's take this example, text generation. Now, text generation is a kind of application where I will be having some kind of input, right? Let's say if I say, hey, how are, or I say, this is a apple juice, right? Now, juice, I'm not giving the word, right? So what my model should be able to do is that it should be able to generate this specific word. It can say, hey, it is an apple juice, or it is an apple pudding, something, right? So it should be able to generate this particular output. Now, in this kind of scenario, the data that you specifically have is a sequential data. The sequence is very much important to understand context of this sentence, right? So this kind of data is basically called as sequential data. Let's take one more example. The second example that I will be probably taking is nothing but your chatbot conversation. Now, in your chatbot conversation, what you do is that you basically have a Q&A chatbot, right? Now, in Q&A chatbot, let's say if a user is asking any question, and based on this question, the chatbot should be able to give an answer. So here, both on this question and answer, the sequence of information is very much important. The sequence of text is very much important. And based on the question, since the chatbot is answering, the context of the question is also very much important. Okay, so that is where you can consider this as a chatbot conversation. Is another one example where our data set will be a sequential data itself, right? Because see, what is a sequential data? I'll just give you a basic definition. Okay, sequential data. A sequential data is something like this. If I take one example, I go ahead and say, hey, the food is good, right? Now, when I see this data, right, here, the sequence of this data is very much important because based on the sequence, the sentence is making some meaningful meaning over here, right? If I change the order, if I just go ahead and say, hey, good, the food is. If I go ahead and write this kind of conversation, if I probably see the sentence over here, right? Over here, based on the sequence of these words, the meaning may change, right? The meaning may change, right? So this is just one example of sequential data where ordering of this word is very much important because it makes sense of the entire sentence itself, okay? So if I probably consider one more example with respect to the sequential data, one more application, let's go ahead and see. This is nothing but, this is called as language translation. Language translation. Now see, in language translation, what do we exactly do? Let's say I have a text in English. I want to convert this into French. Okay. I want to convert this into French. And I hope everybody is in Google Translation. As soon as I keep on writing the word in English, automatically you'll be able to see that it'll be able to generate the sentence in French. So over here also sequence of information is very much necessary. Okay. One more example. I'll be giving you tons of examples now. This is nothing but auto suggestion. I hope everybody has been using LinkedIn, has been using Gmail, right? Over there, whenever you're writing a mail, whenever you're writing a message, you will be able to get auto suggestion with respect to the sentences, with respect to the mistakes that you do. Okay. So this is also one very good example. The fifth kind of example that I'm actually going to take, let's consider my sales data. Now, what is so amazing about this sales data? Your sales data is based on date time, right? So if I go ahead and plot this entire data, let's say this is my date and this is my sales, right? So I may have this kind of graph, right? It may be increasing or it may be decreasing, right? So this is basically my sales data, right? And over here also, this is a sequence of information, right? Why I'm saying you, because one of the use cases that you'll be seeing is something called as sales forecasting. And probably we can solve this particular use case by just taking the previous timestamp and we need to predict the future date, what will be the sales, right? So that kind of forecasting can also be done, okay? So in short, I've given you so many different examples to just make you understand about sequential data. Now, in order to work with a neural network, and in order to work with this kind of sequential data and probably use a neural network, we cannot directly use, okay, here I'll write, can we use ANN to solve this problem? Okay, can we use ANN to solve this problem, right? This is what I'm going to discuss in my next video. But I hope in this particular video, you have understood, right? Since we're discussing about NLP in machine learning, okay, sorry, NLP in deep learning, I had to give you a brief idea about what does exactly ANN do, CNN do, and then we discussed about sequential data. Now my next question is that, can we use ANN to solve this problem which has sequential data? And this is what I am going to probably discuss about in my next video. While we are discussing this, I'll also give you a brief idea, like what all things we really need to learn in NLP in deep learning, okay? So just to give you an idea, what all things to learn over here. So NLP in deep learning involves a lot of amazing topics, right? A lot of amazing topics. And this will turn lead to right now, generative AI is in trend, right? Generative AI is in trend, LLMs are in trend, right? Multimodals are in trend, right? If you really want to learn this, right, this is the prerequisite. You really need to know each and every architecture with respect to all the neural networks that we specifically use for NLP techniques in deep learning, okay? So first topic that we will be learning in NLP in deep learning is nothing but it will be about simple RNN, right? After learning simple RNN, we will be seeing what is LSTM and GRU RNN, okay? So this will be my next RNN that we'll be discussing. Then after this, you will be seeing that we'll also be learning about bidirectional RNN. Then once we complete this, the next step will be that we will go ahead one step more, and then we will be discussing about something called as encoders and decoders, right? Encoder and decoder. And finally, after doing this, we'll be seeing about what is self-attention. And then we'll also be seeing transformers, right? Now, after we see all these things, right now, most of the variants of LLM models that you will currently see in the generative AI field is specifically of different types of transformers, right? And that is where you'll get a brief idea about how to work in generative AI, right? Specifically with the help of LLM models, like you know about OpenAI LLM models, right? So we'll be discussing this step by step. We'll be understanding the architecture, we'll be solving some problem statements, and we'll be learning this, okay? So this was a brief idea about NLP in deep learning. And trust me, guys, these are like a prerequisite to probably enter into the generative AI field and work with LLM models. Even in interviews, they still focus on all these kind of questions. So we will be solving step by step. Each and everything we'll be discussing. We'll be understanding theoretical intuition, and we'll also be understanding the practical implementation. So yes, now in our next video, we'll try to answer this question: can we use ANN to solve this problem statement with sequential data, right? So yes, this was it for my side. I'll see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to NLP in deep learning. In my previous video, I was asking you a question: can we use ANN to solve this problem with respect to sequential data, right? Now, when I said that, I know you may have got confused, like what kind of problem statement we are solving. So let us go ahead and let us see the problem statement, okay? So let's consider that I have a data set, and this is my data set over here. And with respect to this particular data set, let's say I have something called as text, and this is my output, okay? The problem statement that we are solving is something called as sentiment analysis, okay? Sentiment analysis. Let's say one of the data set is like, the sentence is something like this: the food is good, okay? And let's say here I have one. The next statement that I have, or next sentence in my data set I'm writing, the food is bad, and here I have 0. 1 basically means good, 0 basically means bad, okay? And then third one that I have is nothing but the food is not good. I have 0 over here. Let's say that in my training data set, I have this all sentence, okay? Now, how do I solve this with the help of ANN? Yes, can we solve it with the help of artificial neural network, right? So let's consider that over here. First of all, we will go ahead and see. And again, first step in this is that regarding your text pre-processing, if I really want to solve it with the help of ANN. So in a text pre-processing, what we do is that we have to convert our text into vectors. And we have seen a lot of various ways, like bag of word, one-hot encoding, TF, IDF, and all, right? So let's consider that I take this particular data set, okay, and I will first of all go ahead and design my neural network also, okay, ANN, that is artificial neural network. But before that, let's see that how many unique words I have in this. Let's say I have one unique word, 2, 3, 4, 5, and 6, okay. I have 6 unique words, okay, and in this I will not consider is because I consider this as a stop word, okay. So I'm not just going to consider is. So over here the number of unique words is 1, 2, 3, 4, 5. I'll also not consider the because this is a stop word, okay. So let me just go ahead and use this all remaining words. 1, 2, 3, 4, okay. So 4 words I have. So that basically means my vocabulary size. Vocabulary in this particular case is 4. Vocabulary size, okay. Now in this vocabulary size I have 4. That basically means my entire corpus, word corpus is nothing but 4, okay. So as you all know, if I want to convert sentence by sentence from text to vectors, so you have something like bag of words, right? In bag of words, what we actually do, right? We basically try to convert every sentence into a vector, right? How do we convert it? Let's say over here I have all these words, so I'll take this food, good, right? So I'll say food, good, bad, and not, okay? Bad and not. And with respect to sentence 1, what we do is that wherever food is present, right, in this particular sentence, I will make that as 1 and remaining all as 0. So food and good, where it is present, that will be 1, 1 and remaining all will be 0. So here for sentence 1, if I convert this into vectors, it will be 1, 1, 0, 0. Okay. Then in the sentence 2, you'll be able to see over here the food is there, bad is there. So this will basically become 1, remaining all will become 0, and this will become 1, and this will be 0. Okay. I'm just using the technique of bag of words to convert text into vectors. Similarly, the third one is saying that the food is not good, right? So food is not good with respect to sentence 3. So I have this one, not is there, and good is there. So this 3 will basically be having 1. So this is just a simple way of converting a word into vectors, right? And here you can see that I have some fixed vector size, right? I have this fixed vector size. So this is one way, okay? Now, one very important information that we can see from this particular sentences and the text that we have converted that into vectors, okay? One is like when I probably create my artificial neural network, okay? Here you'll be able to see these are my inputs that I have to give to my neural network, right? These are my inputs that I give to my neural network. And since these all are text data, these all are text data. Text data basically means the sequence information is important. Sequence information is important. Again, I'm stressing on this. But here, do you think this all words are in sequence? No, food is coming first based on the frequency. Food is over here, maximum number of time food is present, right? So food is basically written first, then good you have, then bad you have, then not you have. So these words are exactly not in sequence, right? And when we use this particular technique and when we try to train it with the artificial neural network, first of all, we are losing that sequence over here. When we lose the sequence, that basically means the meaning of the sentence is lost. Meaning of the sentence is lost because the context information is lost, right? So that is the reason why I say the sequential information is super important, and we are not able to manage this. This is the major one problem. Here, if I go ahead and even use TF-IDF, right? In TF-IDF, I may do the calculation and I may get different values, right? Even in word2vec, if I use word2vec, I may be able to fix this into some dimensions, right? Just by considering every word will be converted into one dimensions, right? The dimension size may be 300, it may be different sizes. But at the end of the day, we are losing some sequence information, right? Over here. Now, very much important thing. If I'm training my neural network, right? Let's say this is my ANN. Let's say over here, I can see that the maximum number of words are 4. So I will give my input sizes 1, 2, 3, 4, right? I go ahead and create my neural network. Let's say in my neural network hidden layer, I have 3 neurons. And finally, since I have just one output, this basically is connected. This input layer is connected to all the hidden neurons. This is basically connected to this particular output layer, right? And this is also connected to every hidden neurons. This is also connected to every hidden neurons, right? So this here you can see that, hey, fine, this is how my artificial neural network looks like. The first problem we have already discussed, that sequence information is getting lost. Okay, now second problem. Here, with respect to the text, right, the food is good. Yeah, I will be sending all this information. Like let's say my first sentence is basically 1, 1, 0, 0. So I'll be sending my 1, 1, 0, 0 over here, right? This is what is the entire information that I'll be sending over here, right? While training. This will be my input, okay? Just a second. So this will be my input that is basically getting sent, okay? And here you can see this is my input layer, and this is my hidden layer 1, and this is my output layer. And finally, I get my y hat. Now, what is one problem over here that you see? In case of whenever we work with text data, it is always a good idea that whenever I have sequence of information, let's say over here, I go ahead and write the food is good. To solve any use cases, we have to give one word at a time. So let's say during timestamp 1, I just give this the word, then forward propagation should happen and backward propagation should happen. Then in my second timestamp, the next word is food. I have to give that. In my third timestamp, the next word is. Then in the next timestamp, my next word is good. So it is always a good idea that whenever you have sequential data, you really need to give based on a specific timestamp, not all at once. Now in this particular scenario, I'm giving this entire sentence one, all the words all at once as my input. So here also input is going, here also input is going, here also input is going, here also input is going. And by this, the sequence information will also not be maintained, right? And that is the reason the neural network will not be able to efficiently train themselves, right? In case of sequence of data, sequential data, it is always a good idea that we pass one word at a time to our neural network, right? And this is a major problem, right? Because just by using ANN, what we are doing, we are just directly giving all the information, then we do forward propagation, then we do backward propagation. And why I'm saying you should not give all the words at all at once? Because let's say that if I want to solve a problem of language translation, now in the case of language translation, I have to give one word by one, right? If you know about Google Translation, right? If you have used Google Translation, then let's say I want to convert from Hindi to English, or let's say English to French. As soon as I give one word, right? Let's say I say the, then it should automatically give you that French the word, right? Then if I keep on adding words, then it should similarly go ahead and translate in that way. So it is always necessary that you provide this information in a sequential way based on the timestamp, not all at once. So this is one more major problem, and that is the reason we cannot just directly use ANN. Two important information. First of all, it is not able to maintain the entire sequence. And the second thing is that it is giving all the words to the neural network all at once for a specific sentence. Okay, and that is where we will be using a new kind of neural network, which was proposed by researcher. That is nothing but a simple RNN. So simple RNN will basically be used, and if you don't know the full form of RNN, it is nothing but recurrent neural network. So we will be using recurrent neural network to solve this problem. So here, in the case of neural network, our data will be sequential. Now, just to give you a brief idea, how does a recurrent neural network look like? Okay. So first of all, I will go ahead and take ANN. So in the case of ANN, I will be having an input. So let's say this is my input, and this will get as an output. Okay. So this is my hidden layer. This is my hidden layer. Okay. Now with respect to this, I'm giving my input. Over here, some processing will happen in the hidden layer, and finally I get the output. If I want to expand this, let's say in my input layer, I have two inputs. Let's say this is my two inputs. Let's say in my hidden layer, this is my three neurons in my hidden layer, and finally I have my output layer. So I can also represent this in this way. So this will be connected over here to all the neurons. This will be connected to all the neurons over here, right? And finally this will be connected to my output layer. Okay, so this is my output layer, and this is my input layer. This is my input layer. So here, this representation that I've actually shown is nothing but this only. I have my input, I have my output, and in middle, I have this hidden layers with hidden neurons. That is how an ANN looks like. Okay. Now, in the case of RNN, how it is different from ANN and why it is suitable for, you can just consider for a sequential data. Because if I go ahead and see the neural network now, the neural network looks something like this. So initially, I will be having my input layer, then I have my hidden layer, and then I have my output layer. This is perfectly fine. But along with this, we also have a feedback loop. Okay. Now, what does this feedback loop basically say? Is that whatever output I am getting from my hidden layer neurons, it will be sent to that particular neuron and to all the other neurons in that hidden layer. Okay. So if I go ahead and expand this, now see the magic. Okay. Now if I go ahead and expand this, this will look something like this. Let's say I have two inputs, then I have three neurons in my hidden layer, and finally I have one output, right? Because to solve this problem also, I'll be requiring this neural network itself to solve this kind of data set problem, right? Because here I have this output as 1, 0, 0. Okay. So here you'll be able to see that I will be having one final output over here. Okay. Let's say we go ahead and connect this. Okay. We go ahead and connect this. Now this is important, okay? Because I'm expanding it. Okay. So this is very simple. Expanding from input till the hidden layer is very simple, and connecting hidden to the output also is very simple. This is nothing but this is my ANN only. Okay. This is my ANN only. Now see the magic. Okay. Now see the magic. I will just go ahead and connect this. I will just go ahead and connect this. Okay, so let's connect this. So this is my input 1, input 2. This is my hidden layer. Now, obviously, ANN is looking similar like RNN. Now, we have to think about this feedback loop. Now, this feedback loop will be like this hidden layer will be sending its output back to its node. Okay, not only that, this hidden layer will also send the feedback to this particular node. Along with this hidden layer will also send the feedback to this particular node. Okay, that is what it is saying, sending the information, sending the output back to itself, right? To all the hidden layer it will be sending. Okay, similarly, you'll be able to see that the second hidden layer, the second neuron in the hidden layer, will also sending in the loop, and it will also send to this hidden layer, to this hidden neuron, along with this to this hidden neuron. So you're just passing the information to each and every hidden neuron. And finally, here also you have in this neuron, here you have the self loop, feedback loop, and then this information will also be sent to this, and it will also be sent to this. So in short, whatever output we are getting after we probably take the inputs along with the weights that are initialized, then we add a bias, then we add an activation function. Whatever output is basically coming, we also share it with all the other hidden layers. Okay, all the other hidden neurons in the hidden layer. Okay, and with respect to this particular neural network, all the inputs that is passed. Let's say this is my input. The food is good. The food is good. Here we will be doing some kind of numbering based on sentence. Okay, sentence and words. Let's say this is my first sentence. So I will go ahead and note this as x11. X11 basically means first sentence and first word. Then you have x12, first sentence and second word. Then you have the first sentence and third word, and first sentence and fourth word. In the case of RNN, we pass an input at each timestamp. That basically means at t is equal to 1, we will be passing the input as x11. So here you'll be seeing at t is equal to 1, we will be passing x11. Then as t is equal to 2, we will be passing x12. That basically means when x11 is basically passed, okay, whichever information it has with respect to the word that we are having, right? When it is passed, right, it goes to all these hidden neurons, it does the calculation, and whatever output is there, it will be shared with all the other hidden neurons that are present in the hidden layer. Then in the t2 step, what we do is that we basically go ahead and write we go and pass this next word, that is food. Okay, so here we initially pass then food will be basically passed, all the operation will take place. Then t3 is equal to 3, x13 will be passed, t is equal to 4, x1 will be passed, right? That is how each and every words are passed from a specific sentence based on timestamp. In ANN, we used to pass each and everything at the initial stage while doing the forward propagation, but in case of RNN, we just pass one word at a time. Okay, now in my next video, here I've just shown you the basic example of just to make you understand the difference between ANN and RNN. Okay, and if I want to probably expand this, this will also look something like this. Okay, I'll just give you one more brief unfolding technique that we specifically use. It looks something like this. So this is my neuron. Okay, this is my hidden layer. So now, what happens in RNN? We create a self loop. Okay, sorry. So this is nothing but this is a self loop. Okay, here also we part some information. Okay, now if we unfold this with respect to timestamp, understand this is my hidden layer. Okay, so here I will just go ahead and write like this. So this will be my input, this will be my output, and then I have this, and then this output will go to the next timestamp. Okay. Then again you have this and you have this. So that basically means during timestamp t is equal to 1, here I'm going to pass my x11 word of my sentence 1. See, my sentence 1 is something like this and my output is 0 or 1, right? Let's say this is 1. So what I will do in my t is equal to 1, I'll be passing x11, and then at t is equal to 2, I will be passing x12. At t is equal to 3, I will again be passing x13. Okay, at t is equal to 3, and finally at t is equal to 4, I will be passing my last word. So based on the number of timestamps, you'll be seeing that each and every word will be passed. Okay, now what operation is going to happen, that we'll discuss, right? But here you can see that whatever output is coming, it is also being shared with all the hidden neuron. But at t is equal to 2, I will be sending my second word, and it will also have the first word context, right? The entire RNN will have the first word context also, and that is how the previous context information will also be retained by the RNN, right? Please observe this, right? At t is equal to 1, I'm passing x11, right? So when we pass the first word, all this propagation will happen. Let's consider that I'm just going to pass one neuron, so this will be only one input, okay, not two, one input. So once I do this, everything will be happening. Once the input will be multiplied by all the weights over here, then bias will be added. We'll talk about how the forward propagation will happen. But once I get this particular output, it needs to be shared with all the other neurons. So it has been shared with all the neurons over here, right? All this information, all this output is basically shared with this particular neuron. Now this neuron, based on the timestamp, and this neuron is the same hidden neuron, right? Based on the timestamp t is equal to 2, has the previous information of the first word that is the, right? Now in t is equal to timestamp 2, I'm getting the second word, food. So it has the previous context, it has the current context, and again, this operation will take place. What kind of operation? I'll talk more about it as we go ahead. But this is just a brief idea to talk about how a simple RNN architecture looks like and how it is different from ANN. Okay. So in my next video, I will break down this entire diagram again, okay, and show you like how detailedly it will be looking like. And along with that, we'll discuss about this architecture more in a better way. This is an important architecture, so I will be taking more couple of classes to make you explain each and everything. Okay. So yes, this was it from my side. I will see you in the next video, and we'll continue the discussion with respect to the architecture of RNN. Thank you. Hello guys, so we are going to continue the discussion with respect to simple RNN architecture, and in this video we are going to discuss about forward propagation in simple RNN, right? Already in our previous video we just saw about the entire architecture, how does a basic RNN looks like. I hope you have understood this and what is this unfolding technique, okay? Now let's take this example. The foot is good, so we will try to solve this problem with the help of simple RNN. We'll understand how does the forward propagation actually happens with the help of RNN itself. So let's consider that here I have all these words, and with respect to this particular words, first of all I'm just going to go ahead and find out how many unique words are there, okay? So let's say the number of unique words are the, food, okay, good, and I'll say bad, and I can also say not, okay? So total number of words are 1, 2, 3, 4, 5, okay? Now let's consider, initially I need to convert this words into vectors, okay? Now there are multiple ways to convert it. We can also use word to vec, we can use multiple techniques, okay? But I'll just use the most basic one, which is called as one hot encoding, okay? So we will go ahead and use this one hot encoding. Now one hot encoding, what it does is that it converts each word into vectors, okay? So let's say if I have this the word, okay? Since I have 5 words, so whenever the is available, that will become 0, and remaining all will become 0. Right? So this basically becomes my first word. Okay. Wherever the is available, so that actually becomes 1 because the number of unique words are 5. 1, 2, 3, 4, 5. Right? So wherever the is present, so that actually becomes 1, remaining all will become 0. Okay. Similarly, if I go ahead and consider with respect to food, wherever food is present, that will become 1, remaining all will become 0. Okay. So this actually is my another vector for the food word, for the word food. For my next word that I have over here is let's say good, because I'm not going to consider is because it is a stop word. So wherever there is good in the word, this third one will become 0, and then remaining all will be zeros itself. Sorry, third one will become 1 as a vector, and remaining all will be zeros. Right? And finally, you have this bad. Bad basically means let's say this is my fourth word, so this will become 1, and remaining all will become 0. And finally, when you have not, this will be 1, and this will become 0. So this exactly is the entire vector for my sentence 1. Okay. So for my sentence 1, this is how my vector looks like. Now, I need to train this entire sequential data with my neural network, that is RNN, and probably make sure that how to do the prediction. We'll probably see how to do this, how to train this particular neural network for this particular classification problem. That is nothing but text classification. Okay. So now we will go ahead and consider our RNN. Right. Now in this case, as you have seen, the generic architecture of RNN is nothing but it will be something like this. So I will be having my input. This will be my hidden layer. This will be my output. Okay. So input, output. Along with this, I will be having a feedback loop. Okay. And this feedback loop is nothing but it will be sent to each and every hidden neurons in that particular hidden layer, all the information, all the output. Okay. So here, first of all, you need to understand how many inputs I need to give, right? Because at a time, I will be giving one word, right, to my neural network for the training purpose. And every word is represented by these 5 vectors. So here, I'm just going to consider this 1, 2, 3, 4, 5. So this will be my 5 inputs that I will be giving to my RNN neural network, okay? Now in my hidden layer, let's consider that I'm just going to use 3 neurons, okay? So here, I will be considering 1 neuron, 2 neuron, and 3 neuron, okay? And timestamp is equal to 1. I will be passing this word, which is nothing but x11, x12, x13. Okay, so I'll be passing this all words, right? 1, 2, 3, like that, right? All the words will be passed. So here you can see for the first word, this will be passed over here as x11. And I know what is the vector? It is nothing but 1, 0, 0, 0, 0. Okay, this is the vectors that I'm going to pass through these inputs. So this basically becomes my input layer. Okay, now this will basically get connected to all the hidden neurons, right? Over here, then you have here, then you have here. So this will basically get connected to all the hidden neurons. Okay, perfect, right? Now, this is my hidden layer, as you all know, this is my hidden layer 1. But with respect to an RNN, we need to have a self loop, right? What does this self loop basically mean? That whatever is the output, I will be passing it to itself and all the other hidden neurons. So let's consider that. I will now go ahead and use timestamp t2, and here I'm going to pass my another word that is nothing but x12. Okay. Now in this case, when my x12 is passed, 3, 4, 5, right? X12 is the word that is food. And here I have my another neuron that is with 1, 2, and 3, right? Sorry, 1, 2, 3. I will just go ahead and use the same hidden neuron over here. 1, 2, and 3, right? This needs to pass over here, right? And when I'm passing this information at t is equal to 2, as you all know, this information that we have computed at t is equal to 1. So here we'll take this input, multiply by all the weights, and whatever output I get, it will be returned back with the help of self feedback loop itself. Okay. This in short is what is basically happening is that this input will probably go over here. Sorry, this output from this will go to the next timestamp node. Then this will also go over here, and this will also go over here, right? So this is 1, right? And this is what is basically happening, right? At t is equal to 1, like when we use the self loop, right, or feedback loop, what we are basically doing, whatever output is actually coming up, we are sending it to its all the hidden neurons, and that is what is basically happening at timestamp is equal to 2, right? And similarly, you'll be able to see that again. We will go ahead and pass this information to this. We'll go ahead and pass this information to this, and we'll also go ahead and pass this information to this, whatever output I'm actually getting. And finally, you'll also be seeing that this will also get passed to my third node, and this will also get passed. The output will also get passed over here. The output will also get passed over here, and here also you'll be able to see it will get passed over here. So that basically means that timestamp t is equal to 2. This hidden neurons will also have the context of this word, that is the. Over here, this word is nothing but food, right? So when this food is basically passed in the neural network, in the timestamp is equal to 2, this context, this neural network, this hidden layer will also have the context of the previous word. And similarly, at t is equal to 3, same thing is going to happen, right? This output will be passed to the next hidden layer, right? And here I'm just going to give my inputs, my next word. And similarly, when the sentence ends, this neuron, this entire RNN is basically going to have the context of all the previous words from timestamp is equal to t is equal to 1, right? Now, this is basic funda. I know the diagram looks quite messy over here, but you can just understand in this way that after calculating whatever over here, whatever operation is specifically happening with respect to the forward propagation. In forward propagation, what do? We take this inputs, we multiply by the weights, and then we add a bias to this hidden neuron, and whatever output is basically coming, we are passing it to itself and the other hidden neurons at timestamp is equal to 2, so that they get the context information, right? And that is how we go ahead and do our forward propagation, right? Now, this is how you can easily do each and every step. So in a generic way, if you also want to probably go ahead and write it, it is very much simple. So I can go ahead and say, hey, let's see, this is my 5 inputs that I'm passing. This is my hidden layer, okay? This is my hidden layer with any number of neurons. Okay, so right now in this case, I've used how many? 3 neurons, right? And finally, this is my output. So this will get passed, this will get passed, this will get passed to everyone, right? Similarly, this will get passed to everyone, this will get passed to everyone, okay? All the hidden neurons. And finally, we get the output over here. It will get connected to this, it will get connected to this, it will get connected to this, but there will be an additional feedback loop that we will be using. And finally, we get our output, right? So input 1, input 2, input 3, input 4, input 5. This is based on the one hot encoding, whatever I'm actually getting with respect to the words that I have. right? Over here, whatever vectors I basically get, that I will be passing it over here, right? So if I want to probably see how many weight metrics will be there, how many weights, how many bias will be there, here you can see that I have 5 inputs, and here I have 3 hidden neurons in the hidden layer, right? So this basically becomes 5 cross 3. So let's go ahead and calculate how many weights will be there. So here it will become 5 cross 3, that is nothing but 15 weights, right? Then over here you'll be able to see that since I'm passing 1 cross 5 and the weights will be 5 cross 3, right? 1 cross 5, 1 cross 5 and 5 cross 3. 1 cross 5 why? Because one input with 1 row with 5 inputs. When we do the dot operation between them, right? Weights multiplied by the bias. Then in short we're going to get 1 dot 3, 1 cross 3. So for every neuron over here I'll get 1 cross 3, here also I'll get 1 cross 3, here also I'll get 1 cross 3. So this in total for this entire hidden layer will be 3 cross 3. So 3 cross 3 is nothing but 9 weights. Okay, and then finally you'll be also able to see that this will be my 3 cross 1, which will be nothing but 3 weights, because here also we initialize weights, right? So total number of weights that you'll be able to see 15 plus 9, 24, 24 plus 3, right? 3 weights, 27. But here we are also going to use bias. So here I'll be getting 3 bias, and here I'll be getting 1 bias. So 27 plus 4 will be 31. So 31 number of total trainable parameters will be there. Trainable parameters will be there. Okay. So this is how it specifically happens with respect to the forward propagation. Okay. But again, we need to understand in forward propagation what all operation specifically happens. Okay. So I'm going to take this entire example for the forward propagation. I'll copy this. I'll paste it over here. Okay. Now, in order to understand forward propagation with time, so here I'm going to go ahead and write forward propagation. Forward propagation with time. So now let's go ahead and discuss about the forward propagation. Okay. Let's say that I have my input over here. That is nothing but, so let's say my data set is present over here. The data set is nothing but, I will go ahead and write the food is good. Okay. So as I said, and finally my output that sees over here is 1. Let's consider it. Okay. So let's say this is my x11, x12, x13, and x14. Okay. At timestamp t is equal to 1, I will be giving x11. This x11 will be in the form of vectors. Right? Let's say that I've converted by one hot encoding and I got 5 characters over here and I'm sending this to x11. Okay. Now this, initially we need to convert this word into vectors first of all. Okay. Now when this passes through the hidden layer, so this is my hidden layer. Here some weights will be initialized. Okay. So here my first weights will be initialized. Then this input will be multiplied by the weights. Okay. Here a bias will be added. So at every node there will be bias. Here also bias will be there. Bias and bias. Okay. Based on the number of hidden neurons. So once we use this x1 along with this weights, I will be specifically getting my output 1 over here, O1. Okay. Now this O1, when it is getting transferred back to the to its particular hidden nodes, right? Then here also this weights will be assigned in this. So let's consider this weight as W dash. Okay. Then again at timestamp is equal to 2. So we'll first of all discuss about this particular operation, what exactly happens. So if I go ahead and see or calculate with respect to forward propagation, please focus on this. Okay. Forward propagation. So with respect to forward propagation, here you'll be able to see my O1 will be nothing but it will be a function basically means an activation function, because in every hidden neuron we also apply an activation function. Okay. A function of, here we'll go ahead and multiply x11 multiplied by W, okay, this W, and then we will go ahead and add a bias. Okay, it can be B1, it can be anything. I'll just go ahead and write B1. Okay, this F is nothing but it is an activation function. So F is nothing but over here as an activation function. So this is with respect to timestamp t is equal to 1. Okay, now t is equal to 2. What will happen at t is equal to 2? I'll be sending my next word, that is x12, and here I'll be having my words weights W dash, W, and here we will go ahead and compute our O2. Now while we are computing O2, this O1 will also get multiplied by the weights W dash, because here also we are having some different weights. So next time, if I really want to go ahead and calculate my O2, so again here we'll be using a function F, and here I'll go ahead and write x12 multiplied by W. Okay, x12 multiplied by W. Let me write it in white color. So here I'll be using a function. Okay, so first thing first, over here you'll be able to see x12, which is my vector, will be multiplied by W, plus I have to also use O1 multiplied by W dash, right? So O1 multiplied by W dash. Now along with this, I also need to add bias. So here I will go ahead and add bias, that is B1, right? And then we go ahead and apply the activation function, right? This is very much simple. Then again, if I want to go ahead and compute my O3, now O3 will be nothing but over here, right? This will be my O3, right? Now in order to calculate O3, again I have W over here, and this will be my W dash, this will be also my W dash, right? This weights will not get updated during forward propagation. All these weights will be getting updated with respect to time during backward propagation. I'm just showing you in forward propagation what all operation is going to specifically happen, right? So here you'll be able to see that if I go ahead and show you with respect to O3, now O3 is nothing but my function of. So O3 when I'm sending, O3 is nothing but I want to calculate this. So I have to use x13 multiplied by W. So let me quickly go ahead and write x13 multiplied by W plus on the left hand side you have O2 multiplied by W dash. O2 multiplied by W dash plus another bias, right? And that is how you basically get O3, right? And finally, when you get O4, again by doing the same operation, O4, since this is a classification problem, right? It is a binary classification problem. Then here we are going to use, so let's say that here I go ahead and probably calculate my O4. This will forward, we will use this output. If it is a binary classification problem, we will go ahead and apply something called as softmax. Softmax is basically, not softmax, sorry. We will go ahead and apply sigmoid, okay? So sigmoid activation function for a binary classification over here. So this will basically give my binary output. Okay, 0 and 1. If I have multiclass, then instead of using sigmoid, I may go ahead and use softmax. Softmax activation function. And finally, I get my y hat. Here, I may get my y hat, right? Once I get my y hat, then what will happen? Whatever will be my y hat, we will go ahead and compute the loss, and we will try to reduce this loss by doing backpropagation. So backpropagation, I'll be discussing how it happens in my next video, but forward propagation, you saw this. This is how the entire operation will happen with respect to each and every word, right? In a specific sentence. And that is how the forward propagation with time actually happens. And this function is a kind of activation function. For every word, we will go ahead and use, we go ahead and multiply each and everything as we go ahead till the end of the sentence. Okay. So I hope you got an idea about forward propagation. That is how it actually happens. But here also you got an idea with respect to weights, how many bias will specifically be there. Initially, this inputs will be 1 cross 5, then 5 cross 3 weights are basically getting applied. When we do dot operation, I'm going to get 1 cross 3. So 1 cross 3 will be with respect to every node. There are 3 nodes, so it will be 3 cross 3, total 9 weights. Since it is getting passed to each and every each and every hidden node. So that is the reason I'm basically using 3 weights. And here you'll be, sorry, 3 cross 3 it will become, right? And then finally here you can see again another 3 cross 1 is there. And when we try to multiply this, again 3 cross 1, I'll be getting 3 weights, and here will be 1 bias. And this is how the forward propagation basically happens. So in short, here it took so much time, because if you understand this architecture, right? Trust me, it will be very much easy to understand all the upcoming architectures like LSTM or GRU and all, right? But here I hope you got an idea. I broke down completely to make you understand about RNN, right? So yes, this was it from my side. I hope you like this particular video. I will see you all in the next video where we'll be discussing about backward propagation. Thank you. Hello guys, so we are going to continue the discussion with respect to RNN, and in this video we are going to talk about RNN backpropagation with time. Already in our previous video we have seen how the forward propagation with time happens in RNN, in a simple RNN. We have also seen about the basic architecture of a simple RNN. Now with respect to this particular forward propagation, once we go at the end, once we calculate the loss function, our main aim is to reduce this particular loss function. Now in order to reduce this particular loss function, we have to do a backpropagation, and we have to update all these weights that are available over here, right? So in this video we'll be understanding how the backpropagation will happen and how the weights will get updated in a simple RNN. Now before I go ahead, what I will do is that I will again quickly revise our forward propagation. So let's say this is the basic architecture of a simple RNN, and here you know that we use a self-feedback loop. And here also we pass some kind of input. So here also some weights will be involved. Okay. But when we unfold this with respect to time, okay, and let's consider I'm going to take my sentence 1. It has this x11, x12, x13. Let's say that my sentence 1 has this 3 words, and this is my output. It can be 1 and 0. Okay. Similarly, my sentence 2 may have another one like x21, x22, x23, right? And let's say this is the output 0. And similarly, my sentence 3 may have something called x31, x32, x33. Okay. I'm just considering 3 words at a time. Okay, you can have any number of words, that is up to you. And this word may also vary, because at the end of the day, we'll be converting these words into some kind of vectors by using one-hot encoding, by using word to vec. It is up to us. Okay, and we'll be passing every input one at a time based on the timestamp. But if I really want to give this generic format, so here I can go ahead and write something like this. I'll make this sentence 1 as generic. I'll say, hey, this will be xi of 1, then this will be xi of 2, and this will be xi of 3. Okay, so here I is nothing but it will be the sentence number. Okay, sentence number. Perfect. So I'm just giving some basic information over here. Now let's do one thing. Let's unfold this entire RNN, simple RNN, with respect to time. Now, you know, with respect to time, when my t is equal to 1, I will be passing my first input, right? So I will be going and passing my first word. So let me just go ahead and define this. And this will basically be my first word. Okay. So at t is equal to 1, I am going to pass x of I1. Okay. Now, initially, I will also pass some kind of weights over here. Let's say this is my hidden weights. By default, some weights will be getting assigned. And initially, I'll not put this. Okay. Let this be empty for now. Okay. I will just go ahead and unfold this entire network over here. So we are just going to unfold it. Now, once we give an input at a time step t1, t is equal to 1, here some weights will get assigned. So let me just go ahead and write this as w of I. Okay. Now, you know that what will happen in forward propagation, we multiply with the specific weights, then we add a bias, and after this, we get an output. So this will be my output, right? And this output will be nothing but O1. Let's consider O1. So this will be my O1 output. Now, you know that my output, I need to send it back to this particular RNN, right? To this particular hidden layer and all the other hidden neurons in that layer. So this will be sent to my neuron, hidden neuron. Okay. The same output will also be sent to my hidden neuron. But at time step t is equal to 2, I will be passing my next input. So here it will be writing, right, xi2. Okay. That basically means we are just passing the second input with t is equal to 2. Again, the same weights will get initialized over here. Along with this, we will go ahead and initialize one more weight over here, w of h. Okay. So this is nothing but this is the hidden neurons weight, right? If you remember, over here in this hidden neurons, I told you, right, we are also going to assign dissolved weights, right? Dissolved weights will be also getting assigned, right? And the next step will be that we will multiply with this, and we'll add O1 with WH. And finally, when we combine both of them, you'll be able to see that we will be getting our next output, that is nothing but O2. Now, with respect to this particular O2, again, I will go ahead and use my, the weights will get assigned in this. And here I'm actually going to get my next input. Again, at t is equal to 3, I'm going to pass x of I3. Okay. And finally, I will get my output, which is called as O4. Okay. Now, with respect to this particular output of O4, okay, again, I will go ahead and pass this to my sigmoid if it is a binary classification, right? And finally, I get my output over here, which is my y hat. Okay, so this is how I had also written it over here earlier when you saw this entire steps. Let me just show you once again. So here, right, we were getting this O4, we send it to the sigmoid, and finally, if it is a binary output, we use sigmoid. Otherwise, we use softmax. If it is a multi-class classification, we specifically use something called as softmax. And here also, you know that with respect to this O4, I will also assign some weights with respect to this. So let's say here also we go ahead and use w of h. Okay, now. And here, there will be a weight of I that will get initialized over here. Now, with respect to the forward propagation, so quickly, let me just go ahead and write. So here is my forward propagation. And forward propagation, what happens? Okay, one more important thing is that, guys, initially I did not pass any input, right? Because when we are starting this, we will also initialize some kind of input weights. And here, when I'm initializing some kind of input weights, obviously, I will also initialize some WH over here. Okay, this will be my WH. Along with that, you'll be seeing that since every layer has some kind of output, here also we need to make some kind of output, right? We need to probably initialize some kind of output. So here, I will be getting my O0. This O0 can be initialized as zeros, you know, it can be initialized any values as such, right? But randomly it can also be initialized. So here we can also initialize at zeros, or here also randomly any values can be initialized based on some initialization factor, right? The initial output. And again, here also you'll be having this hidden weight. Okay. Now, in forward propagation, what happens is that whenever we go with the forward propagation, the first thing that we need to compute is O1, right? So O1 needs to be computed over here. Now, in order to compute O1, what I will do is that I will just go ahead and in every hidden neuron, I apply some kind of activation function. So let's go ahead and apply this activation function F. Let's say the activation function in this particular case is tan h, right? So I will go ahead and multiply x of I1 multiplied by W of I plus, then you can see O0 is also there. This O0 is nothing but it is zeros only, right? I'll be just considering that we have initialized all the values 0. So 0 multiplied by this hidden weight will be 0 only. So that entire thing, right, it will be 0 because we need to sum this up. Then we have a bias. Let's consider a bias over here. In every hidden neuron, we will be having a bias, right? So let's consider this as a bias. Okay. Now this is my first operation with respect to this thing, right? And one more important thing over here is that I will just go ahead and write this also so that you will not get confused. So I'll say, hey, my O0 multiplied by WH plus bias, okay, B1. And then we basically go ahead and apply an activation function. Okay. Now coming to my next output, O2. Okay. Now this is how the forward propagation will happen. Now in forward propagation of O2, my next word is basically sent. So this will nothing be, but it will be a function of x of I2 multiplied by W of I plus, now O1 and WH is also there. So I'll go ahead and multiply O1 multiplied by WH plus, there will again be a bias over here. Let's consider this bias as B, and here I'm going to use another activation function. This is how we go ahead and calculate O2. Right? Now similarly, when I go ahead and send my third word, that is to calculate O3, it will be nothing but X13 multiplied by W of I plus O2 multiplied by W of H plus B. Bias, right? O2 multiplied by W of H. W of H is nothing but my hidden weights. Okay, so everything looks perfectly fine over here. Now finally, when we get our output, right, we send this output to a sigmoid activation function, and then only we'll be able to get my y hat. So in order to get the y hat, let's say the sigmoid activation function I'm going to apply over there, it will be nothing but O3 multiplied by. So here you can see O3, O3. Oh, sorry, I did not write. I wrote O4 over here. So it should be O3. This is my output, O3 multiplied by W of H, right? And then we send it to the sigmoid to get my output, right? So here what we're doing, we're just going to multiply O3 with W of H. So once I probably do all these things over here, see O3, W of H, instead of writing W of H, here I'll not use hidden weights because this will be my output weights. So let me just go ahead and write W of 0, okay? So this will basically be my W of 0. Perfect, right? So this is how the forward propagation usually happens. And finally, when we pass it to sigmoid or softmax, I'm going to get my y hat, okay? O3 multiplied by W of 0. So here we are specifically going to apply W of 0 because this is my output weights, right? And finally, this is my output node where I'm getting my output, okay? Now this is fine. This is perfectly till here. Everything, I think we have discussed this in our previous video also. Now the time comes is that after we calculate y hat, now once we calculate y hat, what will happen? We will take y minus y hat and we will calculate the loss, right? There will be some loss value. Now our main aim is to reduce this loss. And how will we be able to reduce this loss? Only when we update all the weights. Now what are the weights that are available over here? As I probably see, there are three weights that will be involved over here. One is W of I, the next one is W of H, and W of H, W of I, and one more weight is W of 0. Okay, so these three weights needs to keep on getting updated during the back propagation. Right? This is the most important thing, that if we really need to update W of I, W of H, and W of 0, right, I need to probably update this weights itself and probably do the backward propagation and then continuously do the forward and the backward propagation in similar way. And we'll be doing unless and until this, till when? Till our entire convergence will happen in this gradient descent. We'll reach this global minima. Or when my loss will be really less. This is equivalent to when my loss will be really, little bit less, right? Now, let me just go ahead and quickly show you with respect to the back propagation. How does back propagation actually happen? So I will just go ahead and create one more cell over here. Okay, so this is my forward propagation. Now, in the backward propagation with respect to time. Backward propagation with time. Now, see, at the end, over here, when we do the forward propagation, we finally go ahead and calculate our loss, right? So this is our loss. So we go ahead and calculate our loss, okay? Now, once we calculate this loss, okay, please focus on this, okay? Once we calculate this loss, the first output, so first weight that we need to update is WO. Now, in order to update W, and as I said, we have to update, which all weights? We have to update W of I, W of H, and W of O, okay? We need to update these three weights. Now, in the backward propagation, the first weight will get updated based on your timestamp. So let's say timestamp is equal to 3, the first weight that is coming is W4. So in order to update W4, how do I do it? So here, I will be using a weight updation formula. And I hope everybody remembers this. What is the weight updation formula? It is nothing but, you will be able to see that weight of new is equal to weight of old minus some learning rate, derivative of loss with respect to derivative of W old. Okay. Now, this formula, I hope you are very much familiar because we have also discussed this in ANN. But out of it, this is the most important one. Okay. Because of this here, when we are doing this, this is basically my derivative. And why we are doing it? Because we need to calculate the slope of gradient descent. We need to go ahead and calculate this. Slope of gradient descent. Okay. Now, my question is that, our question is that, how do we solve this? Now, see, first is derivative of loss with respect to derivative of W old. So, first weight, that is WO. So, first thing that we really need to calculate over here is that derivative of loss with respect to derivative of W old. This is what I really need to calculate, right? If I calculate this, then only, see, this weight is nothing but derivative of loss with respect to derivative of WO, right? And if I talk with respect to the weight updation formula, this will be nothing but derivative of O is equal to derivative of O old, or I'll write like this, derivative of O new, W of O new is equal to W of O old minus learning rate, derivative of loss with respect to derivative of W O old. Okay, so this will be old. So this is my entire weight updation formula for WO, right? But here I need to calculate this. This is fine. I'll be getting the old value. Now, in order to get the new value, I have the learning rate. Learning rate will be a small value. So let's consider learning rate will be something like 0.001. Okay, but I need to compute this. So in order to compute this derivative of loss with respect to derivative of WO old, how do I probably write this entire, or how do I find this? Okay, now it is important for you all to understand is that here WO is directly dependent on y hat, and y hat is also dependent on loss, because at the end of the day we are calculating the loss. So here you can see there is a direct relationship. The loss is dependent on y hat and y hat is dependent on W, right? So if I want to probably expand this equation based on chain rule, so this based on chain rule of derivative, if you remember this, we have already discussed. So based on chain rule of derivative, you'll be able to see that I'll be having derivative of loss with respect to derivative of WO old. Instead of writing WO old, I know loss is dependent on y hat. So I'll go ahead and write derivative of loss with respect to derivative of y hat. And similarly, I'll go ahead and say derivative of y hat is dependent on, now I can go ahead and write derivative of y hat is dependent on what? WO old, right? Now, once we do this, we will be able to get this value. And this is nothing but this is a chain rule of derivative, right? And through this, you'll be able to see that we will be able to calculate, or we'll be able to update the weights of WO new. Okay, this is perfect. So our first main thing is that how do we update W0? That has been very much clear. Okay, because there are three types of weight. One is W0, one is W of H, and one is W of I. So here, with respect to timestamp, here you can see that I have updated my W0. Now coming to the second important case, we need to update W of H, and this is nothing but this is my hidden weights, right? Hidden layer weights. Now, these weights are important because this weight is used in all timestamps. right? T is equal to 1, T is equal to 2, T is equal to 3, T is equal to 4. So we have used this in each and every timestamp. Now how do we do that? Okay, so here you can see. Now what we are going to basically do while updating this is that it's very much simple. Okay, and first of all, let me just go ahead and write the weight updation formula here. So I'll say, hey, W of H new is equal to W of H old minus learning rate, derivative of loss with respect to derivative of WH old. So this is the formula, the weight updation formula. And out of this formula, the main thing that I have to compute is nothing but derivative of loss with respect to derivative of WH old. Okay, this we need to compute. So in order to compute this, how do I write now? Derivative of loss with respect to derivative of WH old. How do I compute it? I have to make sure that how many timestamps are there in my entire RNN? T is equal to 1, 2, 3. So I have to make sure that I have to find this based on my timestamp T is equal to 1, 2, and 3. Now how do I do it? Okay, first of all, let's in the back propagation, my first timestamp is 3. Now I need to update which weight over here. I need to update this W of H, right? I need to specifically update my W of H weights. Okay. Okay, perfect. So let's go ahead and do that. Okay, and here you can see there is W of H and there is W of I. Okay, so I will just try to show you how we'll update this W of H. So W of O, we saw it how we can update it. Now let's go ahead and see with respect to W of H. Now this hidden weight, you know that this is dependent on O3. See, just try to always make a rule like this is dependent on O3. O3 is dependent on Y hat, and Y hat is further dependent on loss. Okay, so here you can clearly see this. First of all, loss. Like if I go from this particular, because I'm searching with respect to time is equal to 3, right? And time is equal to 3, I have WH over here. Now first of all, this is dependent on O3. O3 is further dependent on Y hat, right? And Y hat is further dependent on loss, right? So there is a kind of dependency, right? And vice versa also I can say, right? I'll not say, okay, WH is dependent on O3 and all. I'll say O3 is dependent on WH. Or you can also think in this way. Let me reframe it, okay? So I have my loss. Loss is dependent on Y hat is dependent on O3, and O3 is dependent on WH. Now in order to update this, I have to follow this chain, okay? I have to follow this chain, okay? So let me just go ahead and write it and how it will look like. So first of all, I'll go ahead and write derivative of loss. Let me go ahead and write this. So here I'll go ahead and write derivative of loss with respect to derivative of Y hat, because this is the first dependency. Then derivative of Y hat will be dependent on what? Derivative of O. Let me just see this weight. Okay, W4. Okay, so derivative of W4, or instead of writing derivative of W4, I know this will be dependent on derivative of O3, because O3 is the output over here, right? O3 is the output. Then similarly, this O3 will be further dependent on derivative of O2, right? Now I know that in timestamp T is equal to 3, I have to first of all update this weight. So what I will do, instead of writing O2, I will go ahead and write derivative of derivative of WH. WH. Okay. Now this is very much important because when T is equal to 3, I'm doing the back propagation and I'm finding out this particular derivative of this value in this way. Okay. Now I will take this as 1. Okay, one entire thing, and we'll update this. We'll calculate it. Okay. Now we will go ahead and write plus. Why? Because at timestamp T is equal to 2, I still have W of H over here. Okay. Now what kind of rule we will follow, or what kind of chain we'll follow? So here you can see loss is dependent on Y hat. Y hat is dependent on O3. O3 is now dependent on O2, and O2 is now dependent on WH. Now in order to update this W of H, please see this. Okay. In order to update this W of H, I have to follow this chain rule. Okay. So here what I will go ahead and write again. Derivative. So I will start from here. Okay. I will go ahead and write at timestamp T is equal to 2. How I will update this? First of all, I will go ahead and write derivative of L with respect to derivative of Y hat. Then I will multiply derivative of Y hat. Derivative of Y hat with respect to derivative of O3. Then I have derivative of O3 with respect to derivative of O2, because there is also a dependency over there. And then with respect to derivative of O2, I will be calculating the derivative of WH. So this will be my, for timestamp T is equal to 2, how I will go ahead and calculate my W of H, right? This is how, based on the chain rule, it will happen. Again, let me repeat it. Loss is dependent on Y hat is dependent on O3 is dependent on O2 is dependent on WH. And that is how I've actually calculated my derivative. Now comes to the next point. And the next point is nothing but with timestamp T is equal to 1. Now how do I calculate it? So here, what I'm actually going to do, I'm going to probably create this chain. Now I need to update this particular value, that is W of H. Right? Now how do I calculate it? Now you can see there'll be a dependency. Now from here I'll say O2 is dependent on O1, O1 is dependent on WH. Right? So first we'll say loss is dependent on Y hat is dependent on O3 is dependent on O2 is dependent on O1, and finally O1 is dependent on WH. And that is how this chain rule will be working. Okay. Now if I really want to write this again, so it will be nothing but here I'm going to write derivative of loss with respect to derivative of Y hat multiplied by derivative of Y hat multiplied by derivative of O3 based on the chain rule, derivative of O3 divided by derivative of O2. Then again I will go ahead and calculate derivative of O2 divided by derivative of O1. I think it is O1, right? O1. Then O1 is derivative of then O1 is dependent on W of H. Derivative of W of H. So here I have my next one. And once we add up all these particular values that we are going to get, that is when we are going to get this entire value. And we'll go ahead and update it. And our WH new will be the value with respect to this old minus learning rate multiplied by this, whatever value we specifically get. And that is how, in one back propagation, all the hidden weights gets updated. Okay, this is perfect, right? So I hope you are able to get how to update WH, which is my hidden layer weight based on timestamp. Now coming to the third and the very most important thing, that is W of I. Okay, so third is nothing but updating weights W of I. Now let's go ahead and discuss about this. So guys, now we are going to probably see how we can update weights W of I again based on timestamp. Okay, because at T is equal to 3, I'm sending one word. At T is equal to 2, I'm sending one word. And at T is equal to 1, I'm sending one word. So we are just talking about this weights, right? So this weights we also have to update in the back propagation. So let's go ahead and see step by step. Okay. Now first of all, for this, what kind of chain rule I'll go ahead and apply. So here you can see that first I have loss. Loss is dependent on Y hat. Y hat is dependent on O3. O3 is dependent on W of I, right? So again for this, the weight updation formula will look something like this. So here I will go ahead and write W of I new is equal to W of I old minus learning rate of derivative of loss with respect to derivative of W of I old. Okay. Now as you know, we have to go ahead and compute this. Okay. And this will be with respect to time. Now quickly, derivative of loss with respect to derivative of W I old is equal to, I know first of all loss, this derivative of loss. So this will be with respect to timestamp T is equal to 3. Okay, we have to do the back propagation. So here you can see derivative of loss with respect to derivative of W. Here you know that loss is dependent on Y hat. Okay, then I have Y hat, which is in turn dependent on. So Y hat is dependent on what? Y hat is dependent on O3. So I'll just go ahead and compute O3. Then O3 is dependent on W of I, right? And when I say W of I, this is nothing but W of I old. Okay, so this is with respect to my timestamp t is equal to 3. Okay, similarly, we'll go ahead and write plus. Now let's go with respect to timestamp 2. Now with respect to timestamp 2, you know that how we are going to go. Y is dependent on y hat is dependent on O3, O3 is dependent on O2, O2 is dependent on W of I, right? So we will go in this rule. So first of all, I will say, hey, let's go this. So this you have one dependency lost with this, then O3 from O3 to O2, and O2 to this W of I. Okay, so we'll go ahead and write this. So quickly, let's go ahead and do this. So here I'll be writing derivative of loss with respect to derivative of y hat multiplied by derivative of y hat multiplied by derivative of O3. Then you have derivative of O3 divided by derivative of O2, and finally you have derivative of O2 divided by derivative of W of I old. So here is my total thing, right? So O3 to O2. See, I'll see O3 to O2, O2 to W of I. So O2 to W of I, right? And finally, you'll also be seeing that we will go ahead and write my final and this is for t is equal to 2. Now let's go ahead and write it for t is equal to 1. T is equal to 1 is very simple. Derivative of W of y hat multiplied by derivative of y hat with respect to O3, derivative of O3 with respect to derivative of O2, then O2 to O1, and finally O1 to W of I old. Once we calculate this all values, you'll be able to see that I'll be getting this entire value over here, and this will be replaced over here, right? And finally, we update W of I weights in the back propagation. And this usually happens in one back propagation with respect to time. So finally, when we are using this weight updation formula, what exactly is happening, right? And I hope everybody knows about gradient descent, okay? Our main aim is to probably come to this global minima, right? And there are different weights. One is W of H, there is W of I, and there is something called as W of O, right? My main aim is that whenever this conversion basically happens, we have to probably come towards this global minima, right? If you're coming towards this global minima, that basically means our loss will be very much near to 0, or our loss will keep on decreasing, right? And this is what we had already discussed in ANN regarding gradient descent. So I hope you like this particular video. This was it from my side. Here in this video, we have discussed about RNN, simple RNN, we have discussed about forward propagation, we have discussed about backward propagation with all the equations and all, right? So yes, this was it from my side. I will see you in the next video. Thank you. Hello, so we are going to continue the discussion with respect to RNN. Already we have seen about forward propagation in RNN, we have seen about backward propagation in RNN. Now we're going to understand what are some of the problems with RNN, okay? And because of this, the next neural network after RNN, which we are specifically going to discuss about is LSTM RNN and GRU RNN, right? Why we require this variance of RNN when we already have a simple RNN, okay? So we'll be discussing about that. And in the upcoming videos, we will be discussing about LSTM RNN and GRU RNN. So let me just go back and probably revise some of the concepts with respect to RNN. So here is what my RNN looks like, right? A simple RNN. I have a feedback loop. And then when we unfold this, you will be able to see that I will be getting something like this. And this will basically be the output will go to my hidden layer again with respect to the specific neuron. This is my input. This is my input. And again, it will go like this. And I'll keep on going to the next stage till we get the last word with respect to the timestamp, right? And once we get this, what happens? Once we get the output here, we are just going to apply a sigmoid or softmax activation function. Let's say soft or sigmoid. And finally, we will be getting a y hat. And later on, we go ahead and calculate our loss, y minus y hat. And our main aim is to reduce this loss. So what we do, we basically do the back propagation. And if I just talk about over here, I will be having W of I. Here, I will be having W of H. Okay, this will also be W of H. And here, I will be having one input, which will be like initialized to 0 initially. And similarly, this will also be W of H. Here, I will be getting W of I, W of I, W of H. Similarly, W of I. And here, finally, we get W of 0. And with respect to this particular output, here you'll be seeing that I'll be having O1, O2, O3, like this up to ON, right? So we discussed about this entire process and we have discussed about forward and backward propagation. Now let's understand what is the problem with RNN, okay? And I hope in ANN, when we were discussing, we discussed about a very important topic, which is called as vanishing gradient problem. Vanishing gradient problem, okay? So let's go ahead and discuss about this again. And here also, in our simple RNN, we may face this problem. Now the thing is that you really need to understand how do we face this particular problem, okay? Now let's consider in my data set, I have some text, I have some output, okay? Till now, we just saw smaller sentences. Let's say I have 4 words like the food is good, right? So my output will be 1. The food is bad. So the output is 0, okay? When we're using this all kind of words, right? Or this all kind of text or sentences, this sentences was small. This sentences was specifically small, right? And instead of taking this particular use case, let's consider one more use case, which is called as text generation, okay? Let's say some of the example with respect to text generation. I'll go ahead and write, hey, I'll take a very simple example. I like to play dash, okay? So here, I need to probably go ahead and predict my next word. It can be cricket, it can be football, it can be anything, right? And over here, this word will be predicted based on the context or based on the previous words that we have, right? For this particular sentence, if I have this sentence as 1, over here you can see this word may be actually dependent on this word, or it can be on this word, or it can be on this word, or it can be on this word, right? If I consider and if I try to train my neural network, right? Here you can basically consider that this has a kind of short-term dependencies. Now, when I say short-term dependency, what does this basically mean, right? Let's understand this with a very simple example right now. Here I have specifically written that I like to play. I need to predict the next word. Now this word may be dependent on this word, or this word, or this word, or this word. Okay. So here you can see based on the length of this entire sentence, right? Based on this length of this entire sentence, there are hardly 4 words, right? So I have a dependency within this shorter sentence. Okay, but let's say I will go ahead and write a new sentence. Let's say I'll write, hey, my name is Krish, and I like sports like cricket, volleyball. Okay, and I like, let's say I'll go ahead and also like to make and this will be dash over here. I need to predict this particular word. Now this word can be videos, I like to make FUD, it can be different words. Now here, in order to determine this specific output, now the dependency is on this word, right? It may be on this word, it may be on this, or it may also be on other words. But here you can see this sentence is long, is really long, right? Now when this kind of sentence is long, just imagine if I am passing through my RNN. So how many timestamps I will be requiring? I'll be requiring t is equal to 1, I may require t is equal to 3, 4, like this. If I keep on counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So at t16, I will be sending this word for my forward propagation. Okay. Now similarly, this is just a smaller, this is still, I'll say a sentence with a good length, but let's say if I have a sentence which may have 100 words, So at t is equal to 100, I will be sending my last word for the forward and the backward propagation, right, to calculate the loss. Now what will happen as the sentence keeps on getting longer and longer, right? The final output that I really want to get, right? This may be dependent on some words that may have started earlier, right? That may have come up in time stamp t is equal to 4, 3, 2. And this dependency cannot be captured by simple RNN. Okay, so let me just go ahead and write it down. Why it cannot be captured? I will be explaining about it, right? The long-term dependency cannot be captured by RNN. And hence, RNN cannot provide a better accuracy in this kind of use cases where it has this kind of dependency. It has this kind of dependency. Now you may be thinking, Krish, whatever things you are actually explaining over here, it hardly makes sense. Please try to give some example. Obviously, I'm not going to stop over here, right? Now let's take one example. Let's say I'm going to use this entire neural network again. Okay, I will just go ahead and copy this. I will go ahead and copy this. And let's paste it over here. Okay, let's go ahead and do this. Okay, let's say for the first instance, I give my xi1, xi2, xi3. Okay, so in one of the sentences, I just had 4 words, right? Or I just had 3 words. And after that, I got my output. I passed this to my sigmoid. So if I really want to show you with respect to, let's say, in one of the sentences, I just had 3 words. So my unfolding will basically happen like this. So at t is equal to 1, I will be giving my x11. As t is equal to 2, I'll be giving x12, then my x13. And finally, when I get my output, this will be passed. This will be my output. Here, instead of writing hidden, I will be writing something like this. I will be sending it to my, let's consider this as sigmoid, okay? So I'll be sending it to my sigmoid. Let me just draw this properly, okay? So here, I'll be sending it to my sigmoid to perform the, to capture or to calculate the y hat, okay? So this is pretty much easy, and here I will be saying that this will be my W0, okay? Now in this case, when I try to find out the weights, right, I need to update weights over here as W of H, W of I, and W of 0. Now in order to calculate this weights, again, the generic formula is nothing but W new is equal to W old minus learning rate of derivative of loss with respect to derivative of W old, right? And out of this, what is the main thing that I really need to calculate is this particular value, right? This. And this value needs to get calculated for, first of all, I'll go ahead and write W of 0, right? This loss with respect to 0. Here, I will go ahead and calculate my loss, y minus y hat, okay? Now when I calculate derivative of loss with respect to derivative of W0, so here you'll be able to see the equation will be very much simple. So I will go ahead and write derivative of loss with respect to derivative of y hat, derivative of y hat with respect to derivative of WH. Okay. So for this, the calculation will be very much easier. But now let's go ahead and consider one of the examples. Let's say I want to update this hidden weight. Okay, this WH. Okay. So let's go ahead and update this hidden weight. Okay. I'll take this example. So for this, I will go ahead and write derivative of L with respect to derivative of H old. Now you know that my loss which is getting calculated is dependent on, in this particular case, it is dependent on O3. O3 is dependent on O2, and O2 is finally dependent on WH. Okay. So here what I'll write simply like derivative of loss with respect to derivative of y hat. Sorry, loss is dependent on y hat is dependent on y hat is probably dependent on O3. Okay. So now I will go ahead and write derivative of y hat with respect to derivative of O3. Okay. And this is simple chain rule that we have actually discussed. Derivative of O3. Okay. Then we'll go and write derivative of O3 to O2. Then we'll go and write derivative of O2 to derivative of WH old. Now remember one thing. Here we are calculating with timestamp is equal to t is equal to 1, right? If I really want to calculate all the derivatives, I need to keep on adding. For t is equal to 2, I need to add. So I can go ahead and take this entire value. Okay. So at t is equal to 2, I can go ahead and add that. So at t is equal to 2, let's say I want to go ahead and do this. So I will be having a different derivative, or I'll be having this different separate chain rule over here. I'll be able to get it. Then at t is equal to 3, I'll be able to get it a different chain rule. Okay. But I just want to focus over here right now in this, right? Now here when you're seeing this is a specific chain rule that I have. Okay. And here you can see that with respect to t is equal to 1, when my total number of words was just 3, when t is equal to 1, I was able to get this big chain rule of derivatives. Okay? Now if I go ahead and consider if my length of one of the sentence is having 50 words. Now in the case of 50 words, now just imagine what will happen to this particular W of, like if I go ahead and try to calculate the derivative of loss with respect to derivative of W hidden. Please focus on this, okay? If my length of the word is 50 words, so at t is equal to 1, how my equation will look? So I will go ahead and write like this. So at t is equal to 50. Oh, sorry, at t is equal to, like total number of timestamps will be 50. And I want to find out derivative of loss with respect to derivative of W old with respect to t is equal to 1, right? Now this same equation will come, right? And here what it will become? See, now my derivative of loss will be dependent on derivative of y hat. Next step will be that derivative of y hat will be dependent on what? Derivative of O, whether it will be 3 or whether it will be 50. So now I'll go ahead and write 50 because I'm going to go ahead with till t is equal to 50. So my last step over here will basically be O50, the output 50 that we'll be calculating, right? Then similarly, we will go ahead and calculate derivative of O50 with respect to derivative of O49. Similarly, we'll go ahead and write derivative of O49 with respect to derivative of O48. And similarly, like this, we'll keep on going till what step we'll be going? Till we get this one, right? Till we get derivative of O2 with respect to derivative of WH old, right? So at t is equal to 1, this will be my first step. Right, at t is equal to 1, this will be the value that I really need to compute. Then again at t is equal to 2, I'll keep on writing it. Right, and again over there, hardly from 49 it will start. From 49 it will start and it will end till here. Then for t is equal to 3, it will start from 48 and then it will end till here. Right, same thing will basically be happening along with this. Right, now let's focus on these important things. Right, let's focus on these values. Okay, let's focus on these values. These are very important values. And we'll take this up. Okay, let's consider one of the equation like, out of all this, I will go ahead and take one more over here. Derivative of O3 with respect to derivative of O2 plus, multiplied by this last one. Okay. So what I'm saying is that if I keep on doing this, right, if I keep on going this, like this will continue till this particular value, right? And before this value, I also have something like derivative of O3 divided by derivative of O2. Now let's go ahead and calculate this, okay? We will just go ahead and calculate it. Now derivative of O3, what is O3 over here? O3 is nothing but, it is very much simple. We basically take this W of H. See, let's go ahead and see what exactly is O3, okay? O3 is nothing but derivative of, let's say I'm going to apply a sigmoid activation function on this node, okay? Let's consider this. For O3, I'm just considering, okay? Just taking an example. So O3 is nothing but, first of all, I'll just go ahead and write about O3, okay? What is O3 over here? O3 is nothing but, it is, how we are getting this particular output, it is very much simple. First of all, I will go ahead and multiply x of I3 multiplied by W of I, right? So let me just go ahead and write it down over here. X of I3 multiplied by W of I plus, okay, plus we are multiplying with W of H multiplied by O2, right? So here I'll go ahead and say O2 multiplied by W of H, right? So this is my derivative of this O3 value, okay, divided by derivative of O2, divided by derivative of O2. Now once we perform this derivative, since we are doing it with respect to O2, this will become 1, okay? This will become 1, so I will be getting this WH, and this will be considered as a constant. But before this, you'll be able to see that when I am applying derivative over here, on top of it, I also have to perform a sigmoid activation function. On this node, I have to perform, on top of it, I also need to perform sigmoid activation function because there will be a sigmoid activation function over here. Along with this, you'll also be seeing that I will also have one bias parameter. So this will be plus bias. Okay. Now this will how the equation look like. So I'm saying here derivative of sigmoid of this x of I 3 multiplied by W of I plus O2 multiplied by W of H plus 1 plus B. Okay. And this is entirely my O3. Right. This is what I have replaced O3 by. Right. So O3 over here means what? O3 is nothing but it is sigmoid of xi3 multiplied by W of I plus O2 multiplied by W of H plus B. Right. Now if I go ahead and find out the derivative, how it will work? Derivative, if you know, I will get this is sigma dash, I will write because this is the derivative. Now further going ahead, you'll be able to see that it's like if you use the derivative for this entire thing, okay? If you probably use this entirely, this particular derivative, this will be nothing but here you can specifically write 1 multiplied by W of H, okay? 1 multiplied by W of H because this will be a constant, this will be a constant, this will become 0, this will become 0, okay? So I have something called as 1 multiplied by W of H, that's it, okay? So here is what I'm actually going to get, okay? So this is nothing but derivative of sigmoid, and here I'm just going to get 1 multiplied by W of H. Now this will be nothing but whenever we try to find out the derivative of sigmoid. So I have actually explained this in my activation function. So derivative of sigmoid ranges between 0 to 0.25. The output of the sigmoid ranges between 0 to 1, but whenever I try to find out a derivative, it will be ranging between 0 to 0.25. So this value that you are going to get is nothing but 0 to 0.25. In between this values you'll be getting. Now here you can see that you observe one thing, right? One of the values that I calculated in this multiplication, which was this one, okay, this one, was ranging between 0 to 0.25, okay? Now as we go ahead, right? Now this is a decimal. Let's say that we went and calculated here, we got a decimal as 0.015, okay? I just calculated it randomly. Now let's say for this I got 0.02, right? For this I got 0.25, right? For this I got not for this. For one of the internal one I got 0.01. Now when I keep on doing this multiplication, you'll be seeing that after some point this will become a very small value and it will be approximately equal to 0. Now when this is approximately equal to 0, that basically means what? At t is equal to 1, where I had this first word that I'm actually giving, it is not participating much to update the weight value, right? So what is happening over here? The t is equal to 1, the word is not participating to update the weights value. Do you agree or not? Just see this. Why it is not participating? Because this entire operation will be approximately equal to 0 because we are just multiplying with these numbers, right? These numbers. And as you know that if you keep on multiplying with decimal numbers, you'll be seeing that, hey, we'll be getting a value which will be approximately equal to 0. It will become smaller value, a very, very small value. Now, since this entire value is becoming 0, you'll be able to see that when I will try to add this number, or when I'll try to add this with my next timestamp, it is not probably going to impact the weights, right? It is not going to change this specific value, right? You will be seeing, so what is basically happening over here? Here, in short, it is saying that the word that you initially gave in our simple RNN, when compared to the last word, this word is not playing a good or amazing impact in the simple RNN to probably predict the outcome or the output, right? It is very much simple over here, right? Whichever will be the nearest value with respect to the timestamp, that may create a bigger impact. The reason is very much simple. Why? Because when you perform the operation will be very smaller. So here, when I am trying to calculate, let's calculate for O3, right? Just for this last timestamp. If I'm calculating, I'm trying to find out O3. Loss is dependent on y hat is dependent on O3, right? Or loss is dependent on y hat is dependent on WO, and WO is further dependent on W5. If I want to update this, the chain rule will become very smaller. But in this case, the chain rule is big. Now, when the chain rule is big, right? Big basically means the chain is very big over here, right? Over here you can see that whichever is our first word, that will not play a very bigger impact to finally predict the last output, right? And that is what we will be seeing because here we have a long-term dependency. Long-term dependency, why? Because in this case I took 50 words. This was my first word. This was my first word that I passed with respect to timestamp. And if I'm updating this weight, it's hardly 0 and it is not creating any impact for my final weight, right? So this is the major problem. And whenever we face this kind of problem, right? This is basically called as vanishing gradient problem. Okay, vanishing gradient problem, right? So this is very much important. Let's consider at t is equal to 50, what is going to happen? Okay, so at t is equal to 50, you'll be seeing if I go ahead and calculate my derivative of loss with respect to derivative of WH old. Now first, I know my derivative of loss will be dependent on derivative of y hat. Then I have derivative of y hat. It will be dependent on what? If I really want to just play with the last WH50, right? So this will basically be dependent on derivative of y hat will be dependent on my final output. My final output will be O50, and derivative of O50 will be dependent on derivative of WH old. Right? This is what is going to happen at t is equal to 50. Now here you can see this is the right. So this is basically t is equal to 50, right? This is what I'm actually going to add at t is equal to 50, right? So this here you can see my chain rule is very small, and here I may be getting some value because the chain rule is small. I don't have to probably do so much of calculation, so much of multiplication like when we did it for t is equal to 1. So similarly, I'll go ahead and add with t is equal to 449. Then we'll have t is equal to 50. And we'll keep on adding it till t is equal to 1. Finally, we'll be having t is equal to 1. Here you could see that almost my value was approximately equal to 0, right? And as we keep on going towards this timestamp, which is the last timestamp, you'll be seeing that these words will play a very important role while predicting the next output. right? So here you'll be able to see that these all values will never be equal to 0, right? It will have some values because this will be creating an impact on this, and this nearest words with respect to the timestamp will be responsible in updating the weights. But some of the weights that are present in t is equal to 1, t is equal to 2, these all values will be approximately equal to 0. And that is what vanishing gradient says. And this is the problem in simple RNN. It is just focusing on, it is just having a dependency in this entire chain rule. It is having a dependency on the nearest word, not on the farthest word that is available in that entire sentence, right? And this is a major problem. Now, how do we solve this problem? See, instead, I told here we are using sigmoid. The derivative of sigmoid is 0 to 0.25. We can also change this to tanh activation function. But again, in tanh, you'll be getting a derivative between 0 to 1. But as the chain rule keeps on increasing, the multiplication will keep on happening, and you'll get a smaller value. Okay. So, in order to solve this, you can use other activation functions like ReLU, okay, or leaky ReLU. So this here it makes sure that the derivative is always near to 1. Okay. The other case is that researcher came up with an amazing one more network which is called as LSTM RNN. Okay. Now this LSTM RNN solves this problem of long short-term memory, and that is why it is called as long short-term memory RNN. Okay. Not only this, you'll also be seeing along with this, we'll discuss about GRU RNN. Okay, GRU RNN. So both this RNN will solve the problems with respect to a simple RNN, and that is what we are going to discuss about in the upcoming videos. But I hope you got an idea, right? If I have a long-term dependency with respect to the sentences, then your simple RNN will not be working well. Right? That is the major problem, and I've also explained to you why. Because at times you got to 50 steps, you could see my chain rule was so big, and when we did just one of the derivative problem statement, when we try to solve it, here you could see that hey, I'm getting this particular value with respect to weight, so this will be nothing but this will be weight. Over here we are multiplying with this specific weight, but we are multiplying a smaller value. Okay, smaller value. So I hope you were able to understand this particular video. This was about the problems of RNN. Yes, I'll see you all in the next video where we'll be discussing about LSTM RNN and GRU RNN. Thank you. Hello guys, so we are going to continue the discussion with respect to artificial neural network. Now in this video and in the upcoming series of video, we are going to develop an end-to-end project using deep learning where we are specifically going to train artificial neural network. Here, one of the two most important libraries that we are going to use is Keras and TensorFlow. Okay, so TensorFlow is over here and Keras is over here. Now, if you don't know about TensorFlow, this is an open source library specifically used to create end-to-end deep learning projects, and it has some amazing features. And you will be able to implement various kind of neural networks from ANN to RNN to LSTM RNN to GRU to transformer. Each and everything you'll be able to implement from this. Now, many people may be thinking, Krish, is it a good idea to probably create all these specific models and train all these neural networks completely from scratch? I would suggest guys right now, since all these libraries are open source, right? Like you have TensorFlow, you have PyTorch, and I would always suggest you be an expertise of one of this. You need not learn both the libraries, because at the end of the day, when we start learning generative AI, or when you will be learning generative AI, there all the LLM models, all the generative AI models that we will be specifically using in the backend, we will be able to convert or change the libraries from PyTorch to TensorFlow at any point of time. So again, my suggestion would be learn any one of the specific libraries and learn how to build end-to-end projects. That is very much important. So in this course, we will be focusing more on TensorFlow, and we will try to create end-to-end projects with the help of machine learning, deep learning, like ANN. We will try to see how we can train. And again, along with TensorFlow, we'll also be using this Keras API. Now, Keras is just like a wrapper on top of TensorFlow. So in TensorFlow, we will be able to create sequential neural network. We'll be able to create RNN. We'll be able to create ANN. We'll be able to create LSTM RNN. So when we are creating all these things, we really need to write a lot of code if we are only using TensorFlow. But if you go ahead and use Keras, which is again integrated into TensorFlow, this actually provides APIs. And this API is so good that you will be able to call each and everything. You'll be able to create your entire neural network just with less lines of code. Okay, but don't worry, I will be talking about it. So here you can see Keras also works with JAX, TensorFlow, and PyTorch. Right now in this course, we'll focus more on TensorFlow itself. Okay, so what is the problem statement that we are going to discuss? Okay, so here I have a data set. Okay, so this data set is basically called as churn modeling.csv. And as you all know, we use ANN to solve if you have a tabular data, we have some classification or regression problem statement, we will be able to solve with the help of ANN. So here you'll be able to see I have this churn modeling.csv file. And here my output is something called as exited. Exited basically means this data is from a bank. Based on some information, the data is basically given that whether the person is going to leave the bank or not. Okay. And over here, these are the past data from this particular bank, which shows that this information was there and the person left the bank. When these informations are there, the person did not leave the bank. Okay. There are some features like credit score, geography, gender, age, tenure, balance, number of products, has credit card, is active member, estimated salary. And then here you specifically have whether the person has exited or not. Okay. So what we'll do is that we'll try to solve this simple binary classification problem again with the help of ANN. Here you'll be seeing that whatever things we have learned in ANN, right? Like how a neural network is basically created, how forward propagation actually happens, backward propagation actually happens, how to calculate loss function, how to use optimizers, that everything will be explained when we are creating this particular project. And this project will be completely end-to-end. We'll also focus on the deployment. We'll try to create pickle files. I'll tell you why pickle files will be required over here, each and everything. Okay. So this is the entire problem statement. Again, our main aim is that based on some features, we need to predict whether the person is going to leave the bank or not. Okay. So just to give you an idea what exactly we are going to do in this particular project. First of all, we'll go and focus on classification. So here we have this particular data set. Now we will take this entire data set. Okay. We'll take this entire data set. We'll perform some of the basic feature engineering. Okay. Basic feature engineering. Now what all basic feature engineering we will do? We will convert, let's say, categorical variables into numerical. Okay, we'll convert this categorical variables into numerical. We'll be doing some processing. We'll use some standardization process, right? All these things we will specifically. So this is the first step, some type of basic engineering where we will be transforming the entire data. After we do this, we will be getting our good data itself that will be available with us. Then we will try to create an ANN. So if I just consider as an example with respect to ANN, let's say in this particular feature you have 11 features, okay, 11 independent features. So this will basically be my input layer, okay, with 11 nodes like this. I've just written dot. Then we will go ahead and create our hidden layer. Okay, let's say this is my hidden layer that I'm actually going to create. One more hidden layer I can create over here. Okay, it's up to us how many hidden layers you will be creating and all. And then finally, you know that this is basically giving you output as one, right? So here I will be having output as one, and finally we will go ahead and basically create this entire ANN. And as you all know, this will be interconnected, right? This will be interconnected. So I think you can go ahead and do the connection. I'm just doing one part of the connection. And this is finally going to go ahead with the output layer. Okay. Here I will also show you how you can apply dropout. Okay, dropout basically means some of the nodes I will disable it while doing the forward propagation and backward propagation. Like some of the weights we will not be updating. Okay, why do we do that? So that our model does not overfit. Okay, so it does not overfit. Then after training this particular model, we will see the concept of, so this is forward propagation, we'll go ahead and calculate the loss, we'll use some kind of optimizers, right? Everything we'll try to write this particular code with the help of Keras, TensorFlow. Keras TensorFlow. Okay. Now once the model is trained, then the next step will be that how do I take this model and convert into some file format. Let's say I will be using some pickle file format or .h5 file format. Okay, we'll talk about this file format, what exactly it is. Because if we really want to do the deployment, we really need to convert this particular neural network. We need to save their weights. We need to convert them into pickle format file or h5 format file so that we can reuse this and deploy it in any environment that we want. After doing all these things, we will go ahead and further we will use Streamlit to create our web app. Okay, and from this web app, we will integrate all our models. Okay, we'll integrate all our models and we'll deploy this in the Streamlit cloud. So all these things are basically going to happen. Okay. So this is the overall things that we are specifically going to do in this particular project. It will be step by step, and how this neural network is basically created, how optimize the loss function, how dropout will be done. Everything I will be discussing about it as we go ahead. Okay. So first thing first, what I will do, I will go to my folder over here, and I will just go ahead and open my VS Code. Now, as soon as I open my VS Code, this is my VS Code over here. Okay. So here you can see my file is there. Now, quickly, as you all know, the first step, because I'm going to do this in my local, and if you have a little bit powerful machine, like let's say i5, i7 processor, you will be able to run this entire code in a faster way. Again. Obviously, when we see more complex projects in the future, we will not be using local machine. Instead, we will go ahead with Google Colab. Okay, but right now, I think the data set that we have, I've also tried it to run in my local machine. Everything will be running. So I'll just give you a brief idea like how you can do that deep learning project setup in your local machine also. Okay, so first of all, I will go ahead and open my terminal. Quickly, let's go ahead and open my command prompt. Okay, here I'm just going to use this conda, and I'll say, hey, conda create -p venv environment, and let's say I take Python double equal to 3.11. Okay, and I'll say yes. So this entire environment I'm actually creating, and here once this environment gets created, I'm going to just create my requirement.txt file, requirements.txt file. Understand now there are different versions of TensorFlow that have earlier come, but I'm just going to do with the recent one. The reason is very simple, because now you have Keras integrated within TensorFlow. Before, Keras was a separate library and TensorFlow was a separate library. Now Keras as an API has been integrated inside TensorFlow. So let us go ahead and write the first library that we are specifically going to use. Okay, and again, as I said, we are going to use the recent TensorFlow version. So I will just go ahead and write TensorFlow. Let's say that I will go ahead and use 2.1.50. Okay, and I think this is the recent one that we are specifically going to use. And if any update comes, let's say you don't want to use this, just remove this particular version and just remove it in this way. Whichever will be the recent one, that will get updated. But right now, since I have implemented this project with 2.1.50, you'll be able to see that it will work absolutely fine. Along with this, what I'm actually going to do, I'm going to use pandas, I'm going to use NumPy. Along with this, I will also use scikit-learn, because I'm going to use some of the feature engineering libraries or data transformation libraries that are available from scikit-learn, like standard scalar. You also have, we'll convert that into a pickle file also. Then we'll also go ahead and use this tensor board. I'll talk about this tensor board, what exactly it is and all as we go ahead. Then we have this matplotlib for some plotting, and finally we'll also go ahead and use this Streamlit library. So all these libraries we are going to specifically use it. Now let me quickly go ahead and activate my venv environment. So I'll go ahead and write conda activate venv. Okay, and now from here I'll go ahead and write pip install -r requirement.txt. So now you can see that my installation of this entire libraries will happen. It will take some time because TensorFlow is also a big file, and it will download based on internet speed. By default, I'm just going to use TensorFlow not with GPU, instead with CPU. As I said that if we are solving a larger problem statement, CPU sometimes will not be sufficient. Okay, and based on that, we'll try to further do this discussion. Okay, so let this installation take place. Now in the next video, we will start implementing our problem statement, and we'll take this particular dataset, we'll read this dataset, and we'll see step by step what all transformation techniques we're going to use and how we're going to create the ANN with the help of TensorFlow. So yes, I will see you all in the next video. Thank you. So guys, we're going to continue the discussion with respect to this particular project. You can see over here all the libraries has been installed. Okay, and I even did not get any kind of error. Okay, now I've also activated this specific environment in my terminal. So let me just hide my terminal right now, because I will not be requiring. What I will do along with this one last thing, I also need to do the installation. That is nothing but IPy-kernel. So since the first experiment that I'm actually going to do, I'm going to do in my Jupyter notebook, and for that I require this IPy-kernel library so that I'll be able to attach a kernel and execute my Jupyter notebook file. So here I'm actually going to write pip install IPy-kernel. Okay, so once I execute this, you'll be able to see that the installation will take place. Okay, so once this IPy-kernel has been executed, then I'm going to probably start my coding. And first thing that I will do is that I will read this entire CSV file. And let me do also one more thing. Let me just go ahead and create my experiments.ipynv file. Okay, so I'm going to use this ipynv file, and in this my entire experiment will happen. Okay, so right now here you can see my IPy-kernel library is basically getting installed. That is going to take some amount of time. Now it is done. Now I will quickly hide this terminal. Okay, let me just go ahead and select my kernel first of all. Like here I've selected my kernel with Python 3.11. Okay, now I will just go ahead and make some more code cells. Now let's start this entire coding. Okay, so first of all, what I'm actually going to do is that I'm going to import pandas. So let me just go ahead and import pandas as PD. Along with this, I will go ahead and import from sklearn.model selection, because I also have to do the train test split, right? So for that, I'll be using this model selection import train test split. I hope you know this from the machine learning, which we have actually used. Then along with this, I'll also go ahead and import from sklearn.preprocessing. So here I will just go ahead and write pre-processing, and then I'm going to import two important libraries. One is standard scalar, and the other one that I'm actually going to use is something called as label encoder. Okay, so these two libraries I'm actually going to use. Along with this, I'm going to go ahead and import pickle file. Okay, pickle is specifically for pickling, because when we are using this standard scalar and label encoder, it is important that we go ahead and pickle this file so that we can reuse it when we are doing the deployment. So here are some of the libraries that we have already done the installation, and we are just going to import it. Okay, so these are some of the basic libraries. Now let us go ahead and load the dataset. Okay, so for this, I will say data is equal to pd.read_csv, and here I'm going to basically call churn_modeling.csv file. Now over here you'll be able to see, I'll just go ahead and display data.head. Okay, so these are all my values or all my features that are available over here. I've already told you in my previous problem statement what we are going to do. We're going to take this credit score, geography, gender, age, tenure, balance, number of product, has credit card, is active member, and estimated salary as my independent feature. And I'm going to predict whether the person is going to exit the bank or not. Okay, and this is the past data from the bank which shows which person has exited or not. So this is just the top 5 records. Now the first important thing is that this first 3 features are not that important, right? You have row numbers, you have customer ID, you have surname. This definitely will not play a very important role. So first of all, what we'll do, we will go ahead and pre-process the data. Okay, what we are going to do here, we are just going to drop irrelevant features. Okay, which we can directly see it. Okay, so here I'll use this data variable, and from this I'll say, hey, go ahead and drop which all features we need to drop. Okay, so drop is a function over here. We really need to drop this row number, so I'll copy and paste it over here. Then we have something called as customer ID. Okay, then we have something called as surname. Okay, and we're going to drop all these things with access equal to 1. Access equal to 1 basically means column wise. Okay, so once we do this particular drop, we will be able to get the data value. So here is my data value. Now here you can see my features are starting from credit score, geography, gender, age, balance, and all these values are there. Okay, perfect. So this is good enough. We have done this. Now here you can actually see we have a column called as geography over here, right? So geography is there. Okay, and then we also have this gender. We have this these two features we specifically have, geography and gender. Now geography and gender is specifically in this particular case you can say it is a categorical variable. Okay, now in the case of categorical variable, what I can actually do is that I can apply some kind of encoding for this categorical variable. Okay, and that is what I'm actually going to do. Now let's go ahead and encode one categorical variable. Now in this, I will say, hey, let's take first of all gender. I'll say label underscore encoder underscore gender is equal to label encoder. Okay, I'm going to just use this, and I'm going to say, hey, df of gender, or I'll say data of gender, because we have used this particular feature, data of gender, and I'll just use this label encoder underscore gender dot fit. And along with fit, we will also be using transform. And we have already discussed this, why we use fit underscore transform. And here I'm going to take this particular data. I'm going to basically apply this on my gender itself, right? So now let's go ahead and see the data, and let's see with respect to this particular gender. So here you can see, okay, I'm getting an error, the spelling mistake. I'll go ahead and write this one. Okay. So once I do this, so my gender will have two main features, right? One is male and female. So that male and female with the help of label encoder has got converted to zeros and ones. Okay. We have also seen this in machine learning. Okay. So this is one of the encoding techniques with respect to the categorical variable. Okay. I hope you are able to understand this. So guys, over here in the gender, we saw that our values are male and female, and so that is the reason we use label encoder and we change it to zeros and ones. But what about this geography column? In the geography column, you basically have 2 to 3 features, right? 2 to 3 categories, like France, Spain, and Japan, Germany, right? So all these country names are specifically there. So here, if we apply, just imagine that if we go ahead and apply, the label encoder. So let me just go ahead and open my Epic Pen so that I will explain you over here why I'm specifically focused on this particular geography column, right? So let's say if I just go ahead and convert this into a categorical column, so here you'll be able to see I will be able to get France as 0, Spain as 1, and Germany as 2. And when these types of numbers are specifically coming up, then there is a problem, because when we assign a value of Germany to 2, at the end of the day, ANN is all about numerical calculations. Since the label of Germany is 2, it will just consider that Germany is greater than Spain or Spain is greater than France, right? So this should not happen. So for this particular case, what we will do is that we will not directly convert this with the help of label encoder, but instead what we'll do, we'll go ahead and write some code and we'll use one hot encoding. Okay. Now one hot encoding will just actually give us some values with respect to zeros and ones. Okay. So now I will just go ahead and write one hot encode geography column. Okay. So here I'm just going to write geography column over here. Now quickly, let's first of all go ahead and import the one hot encoder. So I will say from sklearn.preprocessing, I'm going to just import one hot encoder. Let me just see this particular. I'm seeing the documentation sidewise, so it'll be helpful for me to also check it out directly instead of wasting time. Okay, and writing each and everything. Okay, so here what I'm actually going to do, I'm going to specifically use one hot encoder. Now quickly, I will just go ahead and use this one hot encoder. I will initialize this. And this time there's a parameter which is called as sparse, right? So I will just make this feature sparse is equal to false. I will let you know why we are basically using this. And once you see the encoded values, then you'll be able to understand. I'll create a variable called as one hot underscore encoder underscore geo. Okay, so this will basically be my values over here. Okay, now quickly the next step that we are going to specifically use is nothing but geo underscore encoded value, and I'll say, hey, let's apply this one hot encoder underscore geo dot fit underscore one hot underscore geo dot fit underscore transform on which column? Basically on my geographic column, right? So here I'm going to give my geography column, right? Now once this is done, you'll be able to see that. Let's go ahead and see how I'm actually going to get this geo underscore encoder. And let's execute this. So here it says got an unexpected argument sparse is equal to false. Okay, let me just remove it for now onwards. Okay, let's execute this. So here I'm actually able to get a sparse row matrix. Okay, I think in one hot encoder I have something called a sparse. Sparse is equal to false. Let's see. Got an unexpected argument called a sparse. I think in the recent version the sparse is not present. Let me just go ahead and use directly this one. Okay, now once I get this geo encoder over here, right? What I will do is that if I use this geo encoder, okay, or if I also go ahead and see what all features specifically we have, if I try to convert this into a NumPy array, I will be able to see all the values. So first of all, what I will do, I'll just go ahead and write one hot underscore encoder underscore geo dot get underscore features underscore names underscore out, right? So if I go ahead and see this parameter, okay, sorry, out, and here I'm just going to give my function, and inside this I'm just going to give my column geography. So if I go ahead and execute it, it says get underscore features. Okay, it should be feature. Sorry. Get underscore feature underscore names underscore out. Okay. So here you'll be able to see with respect to the geography, I have this 3 features that is getting converted into a one hot encoder, right? So with respect to this, if I try to convert, I'll use this particular features and I will be using this sparse matrix that I've actually got in the form of data frame. Now in order to get that in the form of data frame, what I will do, I'll just go ahead and write geo underscore encoder or geo underscore encoder. Here I will use this particular value and I will convert this entire into pd.data frame. So I'll just go ahead and write pd.data frame, and here what I'll say, this is my data, geo underscore encoder. Along with that, if I really want to assign the columns to this, it will be nothing but this entire values, because from this I'm actually able to get the columns. Okay. So this is my data frame, and this is what I'm actually getting as my encoded underscore df. Okay, so let me just go ahead and execute this. So once I execute this, and if I go ahead and see my geo underscore encoded underscore df, I'm getting an error. The reason is shape of value is 1000, so So guys, here you can see that I'm actually getting this particular error. It shape of value that is passed is 10,000, 1, and it is specifically implying that it needs 10,000, 3, because here we're giving 3 columns, right? Now, why this specific problem is happening? See, if I go ahead and print this geoencoder, it shows compressed sparse row matrix of D type, right? Now, if I probably convert this geoencoder to underscore array, okay, and if I execute it, 2 underscore array, sorry, it should be 2 array. So here you'll be able to see that I'm able to convert this into a sparse value, right? And that is the reason, before I was just giving this. Instead of giving this, I will just go ahead and give this, okay? So here you'll be able to see that if I go ahead and give it now, and if I go ahead and see this encoded underscore df, so here you can see that I'm actually able to get this geography France, geography Germany, and Spain. Wherever France is, that value will be 1, and remaining all will be 0. Wherever Germany is, that will be 1, like over here, and wherever Spain is, that will be 1, okay? So this is how you fix this particular problem. Again, I'm not going to probably delete any of this or remove any part of this particular video, because I want everyone to see the errors that we specifically face, because once you see the error, you probably become much more confident in solving that particular error, right? So let's go ahead and combine all the columns now. So here I will just go ahead and combine all the columns with the one hot encoded columns with the original data, okay? With the original data. So here what I'm actually now going to do is that quickly, and this is really important because without this, trust me, because the new part of the code, right, what we did with respect to transformation, we really need to update that. So I will just go ahead and update it, and I will write data is equal to pd.concatenation, and here first of all I have to concatenate the new geo encoded d underscore df without this particular data, right? So first of all, I will just go ahead and do the data dot drop. So I will go ahead and write data dot drop, and here I'm going to use my column, which is called as geography, because I don't require it anytime now, and here I'm going to just use it as x is equal to 1, okay? So once this is dropped, the next thing is that I will just go ahead and concatenate with my geo underscore encoded underscore df, and this time I'm just going to give my x is equal to 1, right? So now if I go ahead and see my data dot head, you'll be seeing that, okay, gender has become 0, 1, and along with this there'll be 3 more features like geography, France, Germany, and Spain that has got concatenated, okay? So this is how we have actually converted our categorical features into numerical features, and we have basically used 2 important type of encoding techniques. One is label encoder, and the other one is one hot encoder. So I hope you are able to understand this entire thing, and see, everything I'm trying to do step by step, we'll do it very much in a slower way so that you get all the points, you understand things, and you go in. All these are like all machine learning kind of feature engineering only we did. Something new will not apply over here. Everything is same like how we have actually performed, right? Now let's quickly go ahead and see. One is what I have used label encoding. One I have used one hot encoder, right? So I have to probably go ahead and save all these particular files, right, in the form of pickle file, because the same one hot encoding and same label encoding I'm actually going to use in the later stages, right? So label encoder gender, I will try to go ahead and save it, and then one hot encoder with respect to the geo, I'm going to save it. Okay, so let's go ahead and save this particular file in the pickle, so that in our end-to-end project we have to probably use this. So I'll just go ahead and write save the encoders and scalar. Okay, so I'll say hey with open. I'll open a pickle file. I'll say label underscore encoder. Okay, label underscore encoder underscore geo. Okay, label underscore encoder underscore gender. First of all, we'll go ahead and save this pickle file. And for this, I've already imported my pickle file. I'll go ahead and open this in my write byte mode, because this is a deserialized or serialized file itself. So we will be writing in the form of bytes. And this as file I've created a temporary variable. I'll just go ahead and write pickle.dump, and I will dump this entire label encoder gender inside this particular file. Okay. Similarly, you'll also be seeing that I will go ahead and open. With open, one more pickle file, I'll just go ahead and create it. That is nothing but one hot encoder underscore geo dot pickle file. And this will also get open in my write byte mode, okay, WB mode. And here I can see as file, okay. And this also, we will go ahead and dump it. So I'll say pickle dot dump. And here also I'm going to use my one hot encoder underscore geo. And finally, I'm just going to convert this into my file, okay. So let's go ahead and open it. So I'll say with open, okay. This 2 file right now, I'll save it. So once I save it, you can see this is my pickle file that has got created. So till here, the basic transformation that I have actually done, right, that all has been completed. And we have almost done this kind of transformation, and we have saved it. Okay. Now let's do one thing. Okay. So you have done the transformation. Now let's quickly divide our data, divide the data set into independent and dependent features. Now you know that my data.head, if I just go ahead and execute it, right? So this is data.head. Here, exit is my column, which I will be keeping as my dependent feature, and remaining all this particular column I will keep it in my independent features, right? So quickly, let's go ahead and do that. So I will just try to go ahead and divide my data set into independent and dependent features. So I'll say data.drop, and here I will go ahead and write exited, comma x is equal to 1, okay, y is equal to data, and here I will just go ahead and say exited, right? So this will basically be my dependent, y will be my dependent, x will be my independent feature. Then we will split the data in training and testing sets. Okay. Now let me just go ahead and write xtrain, comma xtest, comma ytrain, comma ytest quickly, and then this is very much common because we are using it from machine learning. X, comma y. Let's go ahead and use some test size. So test size will be 0.2, and some random underscore state will be 42. So here we have also, we need to do one more thing, guys. We'll scale down these features. Okay, scale these features, and the scaling of this, all the features also we will be specifically doing. Okay, now scaling, we will use the standard scalar. Okay, and once we'll go ahead and initialize it. Here I'm just going to write xtrain is equal to scalar dot fit transform on my the entire xtrain data, and for my xtest underscore data, x underscore test data, I'm just going to use scalar dot transform, and here I'm just going to go ahead and write x underscore test. So this transformation is specifically required. I will quickly go ahead and execute it. So okay, x comma y. Okay, perfect. So let's go ahead and execute this. So here you'll be able to see this will be my xtrain data, which will be the it will be basically scaling is getting applied with the help of static scalar, and similarly I have my xtest. So once this is done, we'll also go ahead and save this scalar file with the help of in the form of a pickle format. Okay, we will be requiring all this pickle format. So with open, I will say hey, go ahead and use my scalar dot pickle, and it will be in the write byte mode. Okay, write byte mode. Now once we're using this write byte mode, I will just go ahead and create my context over here as file, and we'll go ahead and dump this scalar comma 5. Okay, whatever scalar value is there. So let's go ahead and execute it. So here you have each and everything. Here you have label encoder pickle, you have one hot encoder pickle, you have scalar pickle. Just perfect. So in short, in this video, what I've done is that I've just cleaned some data set. I've applied all type of feature engineering that I want to do. Okay, I have divided this into dependent and independent features. What all main feature engineering methods that we have applied is nothing but we have applied both our stand scalar, we have applied, we have converted categorical features into numerical features using label encoder, one hot encoder, everything we have specifically done. So now my data is specifically ready. Okay, this is my data. Now on this particular data, I'm going to just go ahead and train my artificial neural network, and that is what I'm actually going to show you in the next video. So I hope you like this particular video. I will see you in the next video. Thank you. So guys, now we are going to continue the discussion with respect to this particular project. Now, already in our previous video, we have actually created 3 pickle files. One is the scalar pickle file, label encoder, gender pickle file, and one hot encoder for geography pickle file. Right? Now we'll go ahead and train an artificial neural network, and that is what we are going to see. How we are going to train this and all. We'll be discussing about that. Okay. So first of all, we will go ahead and import TensorFlow. Okay, since we are going to just use TensorFlow as TF. Okay, so TF is an alias which we will be specifically using. Now, before I go ahead, let me just give you a brief idea like how does a neural network basically get created with the help of TensorFlow Keras. Okay, so as I said, with respect to ANN, right? In ANN, you have an input layer, then you have a hidden layer. You can have multiple layers like hidden layer, like you can have HL1, HL2, any number of hidden layers, right? But just to give you a basic idea, basic ANN looks like it'll be having one input layer, it can have one hidden layer, two hidden layers, and finally it has an output layer. Okay. When we probably take this entire neural network, like a specific ANN, let's say in this input I have like this, hidden layer I have some 3 nodes, one more hidden layer I have 2 nodes, and finally I have one output, right? This neural network, here we are going to perform the forward propagation and backward propagation. So in TensorFlow, we basically call it as a sequential model. Okay, what do we call ANN as? It is nothing but it is a sequential model, right? And this sequential model here, you'll be able to see that we will be doing forward propagation, we'll be doing backward propagation, and all these nodes will be interconnected, right? This input will be interconnected to this, then this will be interconnected to this, and similarly this will be interconnected to this will be interconnected to this, right? And this will also be interconnected, and finally you'll be interconnected to the output. So this is my input, this is my hidden layer 1, this is my hidden layer 2. All these interconnected lines that you have are nothing but these are weights, W1, W2, W3, like W4, W5, W6, like this, right? Now, in order to give you a brief idea, since I have, let's consider this, right? I have 2 inputs, I have three nodes, hidden nodes in this hidden layer, right? So here the number of weights that will be, it will be nothing but 2 cross 3 weights, right? And 2 cross 3 is nothing but 6 weights. Why 2 cross 3? That's very simple. 2 inputs, and it is getting connected to 3 weights, 3 hidden neurons in the hidden layer, right? Along with this, here also you'll be having a bias, B1, you'll be adding bias B2 and B3. So along with the 6 weights, there are 3 bias in this first hidden layer, okay? In the second hidden layer, again, here you have 3 hidden neurons. This is getting connected to 2 hidden neurons. So over here, you'll be able to see that the weight matrix will be 3 cross 2, right? So again, you will be having one more additional 6 weights, right? And here also, bias will be added. So this will be my B4, this will be my B5. So here, 6 weights and 2 bias will be there, okay? So this is with respect to the hidden layer 1. Hidden layer 2, and this is with respect to hidden layer 1. And finally, you have this output layer. Here also, your weights will be connected. So here, some weights will be there. So here also, how many weights will be there? 2 cross 1, which is 2 weights, right? And here also one bias will get added, so one bias. And after this, you can probably apply a sigmoid activation function if it is a classification. If it is a multi-class classification, you can apply softmax, right? So total number of parameters that you see, right? If I say how many trainable parameters are there in this neural network, it's very simple. You'll just say, hey, 6 plus 3, this is 9, then 9 plus 6, 15, 15 plus 2, 17, 17 plus 2, 19, 19 plus 1, 20. So with the help of 20 trainable parameters, we will be doing the forward propagation and backward propagation. Now similarly, this input is basically defined by the number of inputs that we have in our CSV file or in our dataset, right? In our dataset, how many inputs we have? In dataset, how many inputs we have? If you have 2, so it'll be 2. If you have 3, it'll be 3 nodes, right? If you have 4, 11, 10, any number of nodes. So in this way only, we will be going and created our ANN, which is a sequential network. Sequential network basically means it will be interconnected, right? Now there is also one more important part. If we really want to just create this hidden neurons, so in Keras there is a library which is called as dense. Okay, there's a class which is called as dense. Okay, so let me again repeat what are the key parameters that we will be specifically using. First, when we start creating our ANN, we have to initialize a sequential network. Okay, sequential network. The second thing is that whenever we need to create a hidden neuron, right? Hidden neuron. I'm not talking about hidden layer. If we need to create a hidden neuron, we will specifically using dense. Okay, so if I say, hey, dense, I want 64 nodes. So in that particular hidden layer, I will be having 64 hidden neurons. Okay, something like this. So we will be using dense. Okay, along with this, you know that in every node we apply an activation function, right? So here we'll also be using activation function. Activation function can be sigmoid, it can be tanh, right? It can be ReLU, it can be leaky ReLU, right? It can be any number of others, right? But always it's a good idea that in the hidden layer you try to use ReLU. In the output layer you can use sigmoid or softmax, which I've actually discussed about it. Now this is my third important parameter. The fourth parameter that we will be using is something called as optimizer. Now this optimizer can be any kind of optimizers that we have. I'll show you how you can initialize this particular optimizer also. Optimizer is useful in backpropagation because these are responsible in updating the weights. Okay, updating the weights. Very important. Okay, and the fifth one that we are specifically going to use is nothing but our loss function. And our main aim is that what loss function we'll be using, and based on this loss function, we'll be having a gradient descent and all. We'll try to reduce this. Okay, and the sixth and the final thing is something called as metrics. Usually in a classification problem, your metrics is like accuracy. In a regression problem, you have MSE, mean squared error, mean absolute error, and all are there. Okay, so all these things we'll try to implement. And my training information also, what I will do, my entire training information, I will store the logs in some folder. Okay, so that I will be able to use TensorBoard. And the main aim of the TensorBoard library is to display these logs in a way that we will be able to understand. Some visualization graphs will be used in order to display it. Okay. So these are the steps that we are going to first of all focus. We are going to just go ahead and create a sequential neural network. Whenever we really want to create any hidden neurons, this hidden neuron, or even in the input, I will be specifically using dense. Okay. So all these things we are going to go ahead and discuss. So let me quickly open this now. I will go back to my code. Okay. And here you will be able to see that I will just go ahead and import TensorFlow. Okay, so I'm going to import TensorFlow HDF. I told you I'm going to use sequential model. So how do I import it? So I'll go ahead and say, hey, from TensorFlow dot keras dot models, we are going to import this sequential model. Sequential, okay, from TensorFlow dot keras dot model. Okay, similarly, I will go ahead and write from TensorFlow dot keras dot, as I said you, whenever I need to create a node, it is nothing but using dense. Okay, dense will be that library that we'll be using, and this entire thing will be present inside layers. Okay, so I'm just going to import dense. So this is one more library. Along with this, I will be showing you one very important property we'll discuss about, which is called as TensorFlow.keras.callbacks. Okay, and we're just going to import something called as early stopping. We'll discuss about this early stopping, what exactly it is. Okay, and finally we have this tensor board. Okay, now tensor board, we have implemented this, and finally I'm also going to import date type because I'm going to use this date type also. So I have executed or imported all these libraries which we are going to use. One is sequential, one is dense, one is early stopping, and one is tensor board. Okay, now let's go ahead and build our model. Build our ANN model. Okay. Now to build the ANN model, what all things we are specifically going to do? As I said, I'm going to create first of all a sequential model. So I will go ahead and initialize, and let me just go ahead and initialize sequential. Okay. Now inside the sequential, it is important. Please try to understand this. Okay. Inside the sequential, I'm going to use some layers, dense layers and all. Okay. So here, if I go back to my diagram, okay, let's go back to my diagram over here. First of all, let's go ahead and understand how many number of inputs that I have. Okay. So first, this is my entire sequential model. Okay. This is my entire sequential model. Now inside the sequential model, how many inputs I need to probably consider? So if I go ahead and see my X train dot shape, and from this, if I just try to find out how many columns are there, that will actually help us to decide how many inputs will be there, right? How many inputs will be there? So I have to probably use this entire inputs, okay, over here. And let's say that I will be using the sequential, and I'll say, hey, initially I take this 11 inputs, and then I will go ahead and create my dense. I'll use this dense library and create my hidden layer. Let's say that I'm going to use 64 nodes, any number of nodes in this hidden layer, right? And when I'm creating this dense, I will also give my input shape, like how many elements are coming from this input data. So let's say from this, I'm getting this X train dot shape of 1. If I go ahead and write like this, it says that what is the input that is probably coming from my X train data. That input will get corrected over here. Okay. So we are initializing our input over here along with the dense layer. So this is what we are going to first of all do. Okay. So quickly I'll go back over here and now see, focus on this. Okay. I need to give my input and my hidden layer 1 first. I'll use this dense. Let's say in my hidden layer 1, I'm going to say, hey, we are just going to use 64 neurons. I'm just considering, hey, let's go ahead and use 64 neurons. Now in all these neurons, I also need to apply an activation function. So I will go ahead and apply an activation function. Okay. Now once I apply the activation function, I will just go ahead and apply ReLU activation function. Okay. It is up to you, whatever activation functions that you really want to apply. Now, to this hidden layer, what will be the input that will be coming? So here you will be having this particular parameter which is called as input underscore shape. And this is only for the first hidden layer that you really need to write because it is getting connected to some inputs over there, right? In the second hidden layer now, we don't need to write this input underscore shape, but always for the first hidden layer, we need to write this. So my input underscore shape will be nothing but it will, I can just go ahead and write something like this, right? So it will be X underscore train dot shape, because this shape of 1, if I probably consider, it is just going to take that particular value and it is going to consider that many number of inputs are there. So if I just go ahead and execute this over here, what is my X underscore train dot shape of 1? Okay, I'll be okay. Tuple. So here it says okay. I have to use this. I have to use this index. Okay, so shape of 1. Okay, so here you can see that there are 12 elements. Okay, in my X underscore train dot shape of 1. Right now, if I'm giving input underscore shape of this value comma blank, if I just give comma blank like this in a tuple, so I'm just saying that hey, it is a single dimension and it has 12 inputs. Okay, and that is how I'm also giving over here as my input shape. Clear? Very simple. Now this is my first hidden layer. So I'll write down the comment over here, first hidden layer, and it is connected with input layer. Okay, connected with input layer. This is perfect. Okay. Now in my second layer, again, let's go ahead and use the dense. I will use 32 neurons over here, and I have to just go ahead and apply my activation function. Now after I apply my activation function, I don't even have to give any input shape over here because now we know since we have used sequential, it knows that it will be connected. Right, all these layers will be specifically connected. Okay. Now finally, you'll also be see that I'll go ahead and apply one dense 1. Okay, and then I will say hey, go ahead and apply another activation function. And the reason I'm saying that another activation function, this is my hidden layer 2. HL2, okay, and here you'll be able to see that this is nothing but this is my output layer. Output layer, how many outputs I need to find out? Only one, right? It's a binary output, right? So I'll say, hey, let's go ahead and use this sigmoid over here. Okay, so once I execute this, so this actually becomes my entire model. Okay, my entire model over here. Okay, so if I go ahead and execute this, this is my entire model. Very simple, I guess, right? Now, just imagine how many parameters will be there. So what I've actually done over here, let me just go ahead and talk about it. Okay, so here I created an input layer. So this is my input layer. This input layer has inputs of 12 inputs, right? 12 inputs, 12 comma some. Let's consider 12. Then I have a hidden layer. This hidden layer is basically having 64 hidden neurons, right? 64 hidden neurons. Then I have one more hidden layer, which has 32 hidden neurons. And finally, this is my output layer, which is having one output, right? One neuron. And this all will be interconnected. And this is what we have actually created, right? And now we have to probably do the forward and the backward propagation. Now, let me just go back to the code. Now, let's go ahead and write model.summary. And with the help of model.summary, you'll be able to see that I'll be able to see how many total number of parameters are there. So they are around 2, 9, 4, 5 parameters. Okay. So here you can probably see in my dense, initially you have the 64, then you have this 32, then you have this 1. Okay. Parameters, this is nothing but it is a combination of all the weights and bias. And that is the reason the total number of parameters will be 2, 9, 4, 5. Okay. So this is the entire model, and I'm actually going to do the forward and backward propagation with respect to this. Now, in order to do the forward and backward propagation, we need to compile this model. So let me just go ahead and write compile the model. Okay. Now, with respect to the compile the model, I'll just go ahead and write model.compile. And here, I'm just going to use some parameters. One is optimizer. Okay. Right now, let's keep it blank. I will initialize some optimizer over here. Then you have loss. And this loss, I'm just going to use binary cross entropy. If it's a multi-classification, you can use sparse cross entropy. Okay, so there is different values. With respect to multi-classification, you'll be seeing a parameter which is called as sparse cross entropy. Again, you can go ahead and check with respect to Keras API. And here we will also go ahead and use one metrics parameter, and this will be nothing but it will be accuracy. It is given in the form of list because you can add multiple values also. Now, quickly, one more thing that I really want to show, that over here, is this the only way to probably put any values, or can I probably go ahead and use some other way of applying optimizers and all? Okay, so let me just show you one more way. Okay, so here I'll say OPT optimizer is nothing but TensorFlow dot. Okay, there's a function which is called as optimizers. TensorFlow optimizers. Okay, sorry, TensorFlow dot Keras. Okay, dot Keras dot optimizer. Okay, and here we have something called as Adam optimizer. I think so it should be working fine. And let's use my learning underscore rate is equal to 0.01. Okay. Okay, TensorFlow is not defined, so that is the reason we could not see it. Okay. Okay. So now what we have actually done is that, see, over here, when we go ahead and give one optimizer, let's say that I want to go ahead and give one optimizer over here, and the optimizer name is Adam. Okay. This is the keyword that we can specifically use. Again, in Keras API documentation, if you go and see, I'm actually applying Adam over here. Okay. But this Adam has a fixed learning rate. Okay. Over here it has a learning rate, but you need to provide your own learning rate. So what you can do, you can just import TensorFlow, and you can write, hey, TensorFlow.keras.optimizer Adam, and not only Adam. See, there are a lot of other optimizers also. Let me just show you. So here I'll just go ahead and write optimizers dot Adam. So instead of using Adam, you have added delta, added factor, added grad, Adam W, Adam max. I think most of them I have already discussed. We have discussed Adam, we have discussed added delta, all these things, right? Added grad also we have discussed, right? So let's consider right now, we'll just go ahead and use Adam. And here there will be a parameter which is called as a learning rate, which we can actually define. Okay. So here I've actually defined 0.01. Similarly, what you can do is that you can also go ahead and write TensorFlow dot Keras, and you can also set your loss, okay, losses, and dot different losses will be also there, I guess. Let's see. See, over here you have binary cross entropy, then you have categorical cross entropy. You can use all the specific losses if you want. Let's say if I want to directly use binary cross entropy, I can also use this, okay? And I can store this in one variable, like one loss, and I can use this particular loss over here. Like, see, if I use this op, I'll be using this over here, copy and paste it, right? So I'm showing you both the ways how you can actually do it. Directly, you can also use this particular keyword, or you can also go ahead and initialize this. Okay, so if I go ahead and initialize this, so I will be able to see that, hey, this is my loss, which looks like, right? But both this way, so what I'll do, I'll take this optimizer, I'll put it over here, and similarly, I'll use this particular loss, and we'll go ahead and do the compilation, okay? Now, when we are doing the compilation, this is the compiling the model over here. So, okay, there's an error. Metric, please, okay, let's see what it says. Including this metric. Metrics. It should be something like metrics. Okay, so this is the keyword that is used. So again, this kind of error will come. I'm making sure that I don't delete any of the error. Okay. Now the next thing what I will do, I will go ahead and set up the TensorBoard because we have still not started the training, right? We have still not started the training, and training will be set up, as soon as I probably start. Once the training gets completed, we will also be able to capture that logs and we'll be able to visualize that log. So that is the reason we set up this TensorBoard. So I will create a directory which is called as log underscore directory, and here I will say, hey, make this folder. Okay. So first of all, log/fit. I will probably make this folder over here. Okay. And I'll say, hey, go ahead and make this and use some date type. Use some datetime format so that you'll be able to see this, and then I will go ahead and write datetime. Okay, dot now. Okay, I'm using this datetime, and let me use some time format. So I will go ahead and write str of time, and I will just use this particular time format to capture my logs. Okay, so let me just copy and paste it over here. Okay, so this is my time format that I'm actually going to use. Okay, it will basically go ahead and create this entire directory in short. Okay, now quickly let's do one more thing over here is that I'm also going to okay, for right now let me just go ahead and create this logs directory, and it is going to make sure that whenever we train our model, it will go ahead and it will store all the logs over here. Okay. Perfect. Till here, I think everybody is good enough. Now, let me do one more thing. Let me just go ahead and create my TensorFlow callback. Okay, so I'm going to probably create this particular variable. And what is the main name of this? We will just go ahead and say, hey, use this TensorBoard, what we are trying to import. Now, this TensorBoard, we need to import it. Okay, so in order to import it, I will be importing two libraries. Since I'm going to import two important things, one is import TensorFlow.Keras.callsback. Okay, I'll be talking about what is the importance of this callback just in some time. So I'll go ahead and write, hey, import early stopping. Along with this, I'm just going to import TensorBoard. I will talk about both early stopping and TensorBoard. But right now, just understand that TensorBoard is just to visualize all your logs that you have while training your entire model. Okay, you can also do it manually with the help of Matplotlib, but I feel TensorBoard will be a good one. Okay, so here I've initialized TensorBoard. I'm saying, hey, let's give this as my log directory over here. Log directory is equal to, I'm just going to give my log directory, whichever log directory I've actually created. The next thing that I will be using is some histogram frequency as well to just see that some of the histogram diagrams is also created from here. Okay, so once this is done, I'll go ahead and execute it. Invalid syntax. Okay, from I have to use over here as from. Okay, so perfect. This works absolutely fine. Okay, now we will also go ahead and set up something called as early stopping. Now, why exactly is this early stopping? See guys, when we are training a neural network, we can train it for any number of epochs. Okay, we can train it for multiple epochs, 100 epochs. We can create different batch size and we can do forward and backward propagation. But it may happen in such a way that even we run for 5 to 6 epochs continuously. There, let's say I'm trying to run it for 100 epochs. Okay, well, if we see such a scenario where in 20 epochs only my model has trained at this best level, and after that it is just varying by 1 or 2%, right? Then it is not necessary that you need to probably train that particular model for 100 epochs, right? Whenever we train our model, we have to probably continuously monitor our loss value. If that loss value is decreasing, then it is fine. We can train it continuously. But let's say that after a certain number of epochs, that particular loss value is not decreasing. So what do we do at that point in time? We don't need to probably run the entire 100 epochs. Since what we can do, we can say, hey, go ahead and apply this early stopping, where go ahead and see only the loss value. If it is not decreasing, let's say for the 5 epochs itself, then you can stop the training there itself. So that is the reason why we use early stopping. So here I'm just going to create my early stopping callback. Okay, so this is just like a callback that we use. And here we will go ahead and write early stopping. We will go ahead and monitor one very important parameter while we are training, right, which is called as validation loss, val underscore loss. I will talk about what all keys is also getting created. Okay, like you'll be able to see multiple keys. You'll have validation loss, you'll have training loss and all. But right now I'm just going to monitor this validation loss. And let's say I'm saying, hey, be patient for at least 5 epochs, okay, before taking that particular decision. If till the 5 epochs you see there is no improvement, then you can stop it over there. Okay, and then one more parameter that I'm actually going to say, hey, restore the best weights. So when you are going through the forward and the backward propagation, at which epoch you find out the best weight, you can probably consider that and you can reload it when you stop the early stopping. Okay, so I'm just going to use all these parameters and do the early stopping. stopping, right? Very important. So this will be my early stopping that I'll use. Now finally, now this is the stage of training the model. Okay, I've created my step by step what I've actually done. I have created my entire model. I've said, hey, which optimizers I'm going to use, which loss I'm going to use, and I've assigned that entire optimizer and loss to my model along with my metrics. Okay, then I'm saying, hey, go ahead and set up a tensor board. You have to probably create all the logs while training. So this is the logs. And from this particular logs only, we'll try to visualize some of the data. Now, here I've created TensorFlow callback, and here I've actually created early stopping callback. And I've told you what is the importance of early stopping callback. Now for training the model, I will just go ahead and say, hey, history is equal to nothing but model.fit. Okay. And here I'm going to give my xtrain, comma ytrain. Okay. Comma. Along with this, I'm also going to give my validation underscore data. Validation underscore data will be the combination of xtest, comma ytest. Understand this ytest data will be used for comparison with respect to the accuracy. Then I'm going to say, hey, run it for 100 epochs. Let's say I'm saying go ahead and run it for 100 epochs. And finally, I'm also going to apply my callbacks. So this callbacks is nothing but two callbacks I'm going to apply. One is TensorFlow callback, and the other one is specifically my other callback, which I'm going to use, which is nothing but early stopping callback. Okay. So this two callback I'm going to basically see, and then after we train this entire model, we will load our entire tensor board that I will show you how it is basically done. But over here you'll be able to see my logs file will start getting created. Okay. So let's quickly go ahead and execute this, and I hope everything should work fine. So I'll just go ahead and hit execution. Now here you can see my epochs has started. Right. Initially I'm getting the accuracy over here, validation accuracy is over here, and you can see. I told it to run it for 100 epochs, but this has just stopped at 7. Okay, let me do one thing. Let me increase this patience level to 10. Okay, I'm saying, hey, try to just see till 10 epochs. Now let's go ahead and execute it. So here you can see accuracy is 85, validation this one. I think we are getting the best validation loss still here. Okay, it will wait for a 10. Now in the 16, 17th epoch it has stopped, right? And this is all the values that I get. I get my loss. So till 87% I'm able to get it. Validation loss I'm able to get this much. Validation accuracy I'm able to get 0.85, right? So these are all the information that you will be seeing over here that we are able to get it, right? Which is amazing. And here you can see that I'm able to train the neural network quickly as possible, right? Let's do one thing. Let's save this entire model file. So I'll say, hey, go ahead and save this model.save. And I'm going to probably create one H5 file. So H5 file will be compatible with Keras, so that is the reason I'm actually creating it. So here you can also see model.h5 file. Okay. Let's do one thing. Let's load tensor board extension. Okay. So let's load this. So for loading, I will just go ahead and write load underscore extension, and here I'm just going to use tensor board. Now this extension also we need to install in our so here you can see line magic function load underscore extension not found. I think the spelling is wrong over here. I just need to write like this. So here you can see I have launched my tensor board session. It looks something like this. Then what I will do, I will just go ahead and say, hey, take this tensor board, my magic function, okay, and along with this use this log directory, and inside that log directory I have my logs/fit folder. Okay, so this is how you load this entire tensor board. Now if you see inside this logs, this is nothing but it has your entire information with respect to training and with respect to validation. Okay, and it is just going to load this, and it is going to show us in this visualized format. Let's see this. Okay, so here you will be able to see it. I think it is getting loaded. Let's see whether it is getting loaded or not. So quickly, I think it should get loaded. Yes. So it says, hey, so it says, hey, no dashboards are active for the current data. The problem may be, let's go ahead and launch this. Sorry, let's go. Okay, see what you have to do is that. Let me click it over here. Click over here, right? Launch tensor board session. Okay. Now in this tensor board session, just click and launch. Over here, you'll be able to see use current working directory or select another folder. I'll go ahead and select another folder. And let me just go ahead and click this. And let me just go ahead and cite this particular folder. And let's go ahead and select this train folder. Okay. I'll say, hey, just go ahead and load this train folder. Let's see whether it will load or not. I think it is not able to find out this log fit directory, which is already there. Okay, that is the problem. See. Okay, I got it now. Okay, so the problem is what, right? It is trying to find out this log/fit folder, but this is the folder name that I'm actually getting. So let me just go ahead and write log fit folder. Okay, let's see. I think it should replace the name, or I can just give that particular folder name over here. Even though if I execute it here, you'll be able to see that I'll not be able to get it because this is getting renamed. Okay, so let me quickly rename this. So I'll say, hey, reveal in the file explorer. Inside this logs folder, this is the folder name, and here is my events. That is the information that is coming up. Okay, so quickly let me do one thing. Let me rename it from here. That would be a little bit faster. I think it will not allow because the file may be getting used somewhere. Okay, so let me do one thing. Let me quickly rename this. Instead of rename, right, I will just go ahead and take this name entirely. Okay, and now I will go back over here and say instead of fit, you just go ahead and use this entire name. Okay, so now I think it should be able to load it because I've given the correct loading directory. See, I'm not going to edit all these things. Whatever error that I'm actually facing, I will be showing you so that you will be able to execute it. Okay, that is my main name. Okay, I don't know why we have to probably execute 2 times. Oh, it was getting loaded. Now here you can see beautiful. You're getting all these diagrams. See. So here, based on epoch accuracy, let's go ahead and see this. Let's say I will just uncheck it, and here I will just go ahead and write epoch accuracy. Now with respect to this epoch accuracy, you'll be able to see. Let me do one thing. Let me just uncheck this. Okay, so this is my epoch accuracy, this is my epoch loss. Okay, now see, with respect to this epoch loss, you'll be able to see my loss is decreasing. This is good, right? If I close this over here also, you'll be able to see, let's go ahead and use this. In epoch accuracy, you'll be able to see this graph. See, it is increasing from 0.855 to 0.8655. So this is good. It is going in this direction, right? And you can see what relative step, what value, what accuracy you have actually got. Every information is basically getting stored over here. You can also change this value with respect to smoothing, and here you'll be able to see how the accuracy changes, right? See, these are some of the parameters. This is also something very important, the dense underscore 3, right? This it just looks like a, see, if you have seen this histogram, it just looks like a gradient descent in opposite manner, right? This is the maximum top pick, and this is the minimum loss we are able to get, right? Which looks like this over here. So here also you can probably observe each and every this. But the main thing is epoch accuracy and epoch loss, which you are able to see over here. Not only that, let's do one thing. Let's instead of taking train, let's go ahead and see validation. Now in validation, you have this epoch accuracy. So here again, there's some up and down, but at least you are able to get it to 0.855. Then you also have this epoch loss, epoch accuracy versus iteration, epoch loss versus iteration. So please go ahead and check this out entirely. I've already shown you how to do it. First of all, you need to set this entire logs. Whatever folder name you're probably getting, you have to probably use that. Okay. but still need to think why that folder came in that way. Okay, I was using this plus, right, some date sign over here, and automatically with the help of date sign you could see that instead of writing like this, right, I could have written something like this. I'll keep this code like this. Okay, it'll be slash, and inside that any date format will be created. Okay, perfect. Till here I think everything looks good, but always make sure that if I am using this folder wise over here, let me just show you again. Please make this change. So I'm saying, hey, inside the fit folder, you have to probably create every time date timestamp, and then you have to probably go ahead and create your logs. So in this case, you don't even have to use this, right? You'll be able to get it. Perfect. So this was about this one. We have also saved the pickle file. We have done almost each and everything, and this is how ANN neural network is basically created. Let me just show you how do we load the pickle file, because we need to do the prediction, right? So how do we load the pickle file? That is very much important to show, because at the end of the day, when we create a end-to-end Streamlit project, so we definitely require all the pickle files. So in order to load the pickle files, so first of all, what I have to do, because see, here I now have the pickle files, I have all my model trained, I have to make sure that I load that particular pickle file and I do the prediction, right? That is what I have to actually do. If I don't do that, then it will not work out, right? So let me quickly go ahead and import all the libraries again. So let's say that I'm doing it in my new file, okay? Or let's consider a new file. So here I'll say prediction.ipynb, okay? Here, the first thing first, I'll go ahead and import this. Select the kernel, okay? So here you'll be able to see that I'm going to execute this, okay? Now we are going to load all the train model, right? So how many train model we have? So load the ANN train model, then scalar pickle file, and one hot encoding pickle file also, right? One hot encoding. So we'll load this. So I'll go ahead and write model is equal to load underscore model. So here is what we have imported. See, from TensorFlow models, import load underscore model. So here I'm going to write load underscore model, and here I'm going to take my model.h5 file. Okay. When I probably go ahead and use this, here you'll be able to see I will also go ahead and load the encoders and scalar. Now in order to load this, I'll go ahead and use with open. Quickly, let's go ahead and write label underscore encoder underscore geo dot pickle file. So this will be my pickle file. We'll be reading this time in the read byte mode as file. Because picking is nothing but it is a deserialized format, right? We can serialize it, we can deserialize it. So here I'm going to basically go ahead and use this label underscore geo is nothing but pickle dot load this specific file. Okay. So here is what I get this particular pickle file over here. Okay. And similarly, I will go ahead and do the same thing for the gender and for the scalar. Okay. So here I have my gender and for my scalar. Now let's take some input data. So I will take some input data. So this I will go ahead and execute it. Label encoder underscore geo. What is the name that I've given? Label encoder underscore gender. Oh, sorry, it should be gender, not geo. Okay. Oh no, this pickle file should be my geo pickle file is what? One hot encoder geo, right? Not label encoder. So here I'll go ahead and write one hot. Let me rename this and let me copy this entire pickle file. Okay. So here I'm just going to go ahead and write one underscore hot encoder underscore geo dot pickle file. Now let me go ahead and execute it. Now it works absolutely fine, right? Now I'm going to take some example input data, because based on this input data, I'm going to do the prediction. So here I've written credit score is equal to 600, geography, France, male, gender, male, age 40, tenure 30, this, there. Now when I'm giving this particular data, the first thing that I need to think is that how do I convert this particular value into numerical and this particular value into numerical, right? So and then after that, take all the numerical value and convert that into standard, scale down that particular value using standard scalar. That is the reason we have stored this in the form of pickle file. Okay. Now let's quickly go ahead and do this. First of all, I would like to see. Just think over it, okay? You just try to think like how do we probably go ahead and apply one hot encoding in this, okay? Now you really need to think, guys. You cannot just think over it, okay? I'll give you 5 minutes. Just pause the video. But what task you really need to do, okay? This is my new input data I'm actually getting. And now with respect to this new input data, you need to think how can I probably take this particular data and perform or convert categorical features into numerical features. That is what you really need to think first of all. The second thing is how do you apply standard scaling, right? And then how do you do the prediction with respect to the model, okay? That is what we are going to probably see. Okay, so first of all, pause the video and do it. Till then, I will start copying and pasting the code over here. The reason is very simple because I've already told you all these things. Okay, so here one hot. So let me just go ahead and write this label encoder geo. So I'll take this label encoder geo dot transform. Okay, and here you'll be able to see that I am getting some values over here, right? Key value pairs, right? Key value pairs over here. Now, when I get this key value pairs, I need to take out the information of this particular geography. So what I will do, I will say, hey, label underscore geo underscore encoder geo dot transform, and here I'm just going to use my input underscore data. Okay, I think it is input underscore data of geography column. Okay, and then this geography is basically my key. So let me just go ahead and copy and paste it over here with respect to this. So I will be able to get my key. Okay, and then finally I get it. I convert this into an array. Okay. Now once you do this, again I'll be using this label underscore geo, okay, dot get feature names out of geography, and this is what in my geo encoded that I'm actually giving. Okay, so if you see, this is for my new data that I'm actually able to get this, right? So here it says reshape 1,1. Okay, let's see this. Okay, here I'll just go ahead and use this as like this, then it should work. Okay, expected 2D array got one D array instead. Okay, so array of France I've given over here. I'm using this transform. Okay, this is okay. I have to use one more brackets, because that is the reason how we got it. Right now it should work. So here you can see geography underscore France, geography underscore Germany, geography underscore Spain. Guys, you may be thinking, how did I get to know that I have to use double brackets? See over here, if you go ahead and see with respect to the transformation that we did with the help of one hot encoding, right? So here when we use this one hot encoding, here you can see that let's see where it is. Okay, here you can see I'm actually giving this one hot encoding over here, and I'm giving a list of features, right? List of features. And similarly, I also have to give a list of features over here. That is the reason this is one of my features over here, and I'm giving it as a list of features, right? So that is the reason I'm able to get it. Okay. So once I do this, then I will go ahead and combine this entire data, this data, with my input data. So I'll say input data dot reset index drop is equal to true, because if I do the reset index, I'm actually going to get that default index value, row index value. And I'm saying drop is equal to true, and then I'm adding this geo underscore encoded underscore df. Okay. So if I go ahead and see my input data now, input data. See, so guys, here you can actually see that I'm getting this particular error. Dictionary object has no attribute reset index because I just made one simple mistake after this particular code. See, the input data right now is in the form of key value pairs, right? I need to convert this into a data frame. So in order to convert this into a data frame, we will go ahead and write pd.data frame. Let me quickly go ahead and use this input underscore data. Okay, and once I get this, this will basically be my input underscore df. And let's go ahead and execute this. So here is my input underscore df, and this is what is my entire row, right? Now this row only I have to pass it over there, right? Now for this particular row, what I really need to do, first of all, I need to do the concatenation, right? So this is my input underscore df, and I after converting this into my data frame, I should probably concatenate my geography column, right? So I'll do that concatenation right now. Okay, I've actually changed all the values with respect to the geography column over here, right? So it is basically into two array. We have actually done this, and I've actually got this geo underscore encoded underscore df. Now let's quickly encode my categorical variables. Okay. Now I will say, hey, let's take this input underscore df and let's convert first of all this gender, because gender also needs to be replaced with some label encoded value. So I'm just going to use this label encoder, label encoder underscore gender. And I'll say, hey, go ahead and do this transform operation on my input underscore df, on which column? On the gender column. So this basically becomes my input underscore df. So if you go ahead and see my input underscore df now, the gender column will either have zeros or ones. So right now it is one, right? So this particular value may be a male before, now it has basically got one. Okay? So this is perfect till here. We are able to get it. Okay. I've already done the one hot encoding for geography column. So I have this geo underscore encoded underscore df. Now what I will do is that I will quickly go ahead and do the concatenation. Now finally, let's do the concatenation with one hot encoded data, and along with this we also need to add the no need to add the gender data because it was already done the changes in input underscore df. Now what we'll do is that whatever encoding we have done for the geography column, right, we need to append all those columns inside this, and we need to drop this column. So here I will just go ahead and quickly write input underscore df is equal to pd.concatenation. Let's concatenate our input underscore df. And from this, I'm just going to drop my geography column. Same thing, what we have actually done over there, right? So geography column, and this drop will be done with respect to axis equal to 1. And here, I'm just going to go ahead and write geo underscore encoded underscore df, right? So geo underscore encoded underscore df is nothing but this particular value, which has this one hot encoding of this particular feature. Okay, that is what we are basically going to do over here. And I have to also make sure that I put with axis equal to 1, otherwise it will become row-wise concatenation instead column-wise concatenation. Now, if I go ahead and write input underscore df, you'll be able to see that gender has got converted from male to 1, and here you'll be also able to see that my 3 features have got added on geography, France, Germany, and Spain. Okay. Now one more transformation is left. That is nothing but scaling the data. Scaling the input data. Now, in order to do the scaling part, so I will be using scalar dot transform, and here let's go ahead and write input underscore df. Okay, so this will basically be my input underscore scaled. Done. Okay. Now, if you go ahead and see this input underscore scaled, I will basically get all the data in the form of array, and all these values has basically got scaled. Okay. Now, finally, we need to just predict and see whether the person is going to leave the bank or not. So I'll go ahead and write prediction. In order to do the prediction, I'll just go ahead and write model.predict. Here, give all the values over here like input underscore scaled. Okay. Get my prediction. So I will just go ahead and print my prediction quickly. So here you can see that I'm getting this particular value 0.02976 so and so, right? I can just go ahead and get my prediction probability also. So if I just go ahead and write like this, prediction of 0 of 0, I'll be able to see that I'm okay right now. Let's see this. I'll just go ahead and write prediction score probability. So here you'll be able to see 0.297, it is there. I'll go ahead and say this particular condition, if the prediction probability is greater than 0.5, the customer is likely to churn, otherwise the customer is not likely to churn. Okay, because this is the binary output, and I'm just going to keep the binary output with respect to 0.5, but here I'm actually getting 0.029, so the customer is not likely to churn. So in this video entirely, right, how to do the specific prediction, I'm actually done it. Again, first of all, we have loaded all the pickle files. Then whenever we get any input data, first of all, we converted that into a data frame. Then we did a one-hot encoding of geography. Then we did label encoding for gender. Then we combined all those things. Then we created our entire data frame. Then we did the scaling, right? Again, we used the transform feature. Then we did the prediction. Then finally we got the probability. And then we finally checked whether the person is likely to churn or not, right? So yes, this was it. Now in my next video, what I'm actually going to do is that I'm going to deploy this entire content with the help of Streamlit in the Streamlit platform itself, right? So I will see you all in the next video. Thank you. So guys, till here now we have seen each and everything. We have trained our entire ANN, artificial neural network. We got the loss. The loss was also very less. We saw the loss in our tensor board. Visualized the entire diagram. We saw various parameters. Then we went ahead and did the prediction. We saved all the pickle file. We loaded all the pickle file, and we could also see the prediction was also happening. Everything we did it. Now it's time that we create one app.py file, and this is what I'm going to specifically use as my Streamlit web app. I'm going to probably create an end-to-end web app where I will be able to give the inputs and do the prediction from there. So let's go ahead, and here is my app.py. So first of all, I need to import all the libraries that I really require. So one is Streamlit, as NumPy, TensorFlow, scale.preprocessing. I'm going to use standard scalar, label encoder, one-hot encoder. So whatever things we specifically did in the prediction.ipy and file, we'll be doing it. Okay. So the first step is loading the train model. So I'll go ahead and write here.keras.models .load underscore model, and I will be giving my model.hy file name. Then what we will do is that we will go ahead and load all our encoder, scalar, one-hot encoder, all the files itself. So here you have one-hot encoder geo.pickle file. Then I'm encoding this. So here you can see one-hot encoder underscore geo.pickle. I am loading this in the read byte mode. Then I have this pickle.load. Then I'm also loading this scalar, right? So all this pickle is specifically getting loaded, right? Now let's quickly start with the Streamlit app. So here I'm going to use Streamlit app because I don't have to worry about HTML and all. So that is the reason I'm using this. So I'll go ahead and write st.title. Let me go ahead and write customer churn prediction. Okay. So customer churn prediction I'm going to use over here. Customer churn prediction. So this will basically be my title of the Streamlit app. Now, see, you know that how many types of inputs you're specifically giving. You're giving geography, gender, age, balance, credit score, estimated salary, tenure, number of products, has credit card, or number of products already mentioned, right? Is active member. So these are some of the features. So based on these features, I need to provide my input from the Streamlit webpage. So for this, we will go ahead and create all these inputs. So for geography, I'll be using a dropdown, which will be specifically using all the categories. So categories of 0, whichever is the categories of 0, by default it will get loaded over here. It can be 0, 1, 2, or any name that we're going to give over here. Then you have this st.select box, whatever values or with respect to classes that I have, I'm actually able to get it over here. Then you'll also be able to see st.slider. I'm using a slider for age. I'm using a input for balance, credit score, ST underscore number, credit score, estimated salaries again, number underscore input. Then for tenure again, I'm using a ST dot slider between 0 to 10. I'm also using a slider for number of products, and similarly has credit card and is active number. Okay, so this is what is the input data I will be giving from my user input. Then I will prepare this input data by taking it in some kind of dictionary, right? So we will go ahead and prepare this dictionary. So here I have my credit score. I'll take this data. Gender, I'm going to use this labeling, go to gender and use transform, and probably get the 0th value. Then age is here, tenure is here, balance is here, number is here, and each and everything, all the information are specifically here. Okay. Now one more information that is missing is basically our one hot encoder, which is my geography column. So for geography, I will try to encode it in a different way, like how I did it in my prediction.ipynb file. So I will just go ahead and encode this geography. So here is my geo encoded. I'll take this geography value, which is from here, right? This geography value. I will take this in the form of list. I'll convert this into an array by using one hot encoder dot underscore geo dot transform. Then I'm converting back into a data frame by taking the feature names over here, right? So this is what I'm actually specifically getting for all my values. Now I will combine this one hot encoded with my input data. Right, so for that again, we'll go ahead and pd.concat. I'm saying input data reset index top is equal to true. Then take the geo underscore coded encoded underscore df with access equal to 1. Same thing. What we did in the prediction.ipynb file, right? Nothing is different. Then we're going to take this entire data and we're going to scale it also. Okay, so here I'm going to probably go ahead and scale it. Okay, then let's go ahead and do the churn. And with respect to the churn, I will just go ahead and write like this: if prediction churn, whatever prediction probability I'll get, I will just go ahead and compare and say, hey, if this is greater than 0.5, I'll go ahead and write it in my Streamlit app. Otherwise, I'll go ahead over here and say that hey, it is not likely to churn. Okay. So yes, this was it. I think everything was discussed already in the prediction.ipynb file. So let me quickly go ahead and run it. Okay. So now this is the first time in order to run a Streamlit file, I'll just go ahead and write Streamlit run app.py. Okay, Streamlit. Okay, Streamlit. So once I execute it, I will just say allow access and let's load it. So my file is getting loaded. Let's see, I should not be getting any error. Now, right now here you can see the customer is not likely to churn. It's coming up over here. Let me print this particular value also over here, right? What probability we are getting. So I'll say, hey, go ahead and just print this. So tell here what I will do. I will just go ahead. Once I get the probability, right, I'm just going to go ahead and print it over here. So now let's go ahead and see. And let's reload it. Okay. So here you can see churn probability is 0, 0. So if I keep on increasing age, is this increasing? See, churn probability is increasing. Now you can add up any values. You want to select Germany, go ahead and select it, add any balance like 10,000, go ahead and add it. Here you can see churn probability. Automatically the calculation will happen. If I go ahead and add one credit card, one active member, so see, this value is also decreasing. So on the runway, it is probably predicting, my model is entirely predicting it, right? Now, this was a very simple end-to-end project where I've used customer churn prediction. And what you can do is I can select different values and do the prediction. Automatically this will do the prediction. Now quickly, I will go ahead and open my GitHub. Okay. And with respect to GitHub, I have to probably go ahead and see the deployment, right? So what I'm actually going to do is that first of all, I'll go ahead and check in the code. You know how to do the checking with respect to the code. You can also use Git in it, but this project, I will just try to quickly upload it in my GitHub repository. So I'll just go ahead and create my GitHub repository. Let's say I'll go ahead and write ANN classification, okay, churn. And here, I will just go ahead and create this, add a README file, general public license, go ahead and create a repository, okay? So once this is created, now in my next step, what I'll do, I will go ahead and upload all the code over here. And then we will go ahead and see how we'll be doing the deployment this into a Streamlit app, okay? Streamlit Cloud. That is what we're going to see in the next video. So I hope you like this particular video. I'll see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to this ANN end-to-end project. Now in this video, we are going to see how we are going to deploy this entire project in the Streamlit app. So Streamlit is a faster way to build and share data apps. I've already taken a module regarding Streamlit, which you'll be able to find out in this course. So let's go ahead and first of all sign in over here. Once I sign in, I'll be getting this share.streamlit.io. And here you can probably go ahead and create your own app, right? But before that, I will go ahead and upload all my code in my GitHub, right? So here, let me do one thing. Let me go over here. Let me reveal in the file explorer. Okay, so this is the file. I will quickly go ahead and deploy some of the files, right? So I will take this, okay, this, all the pickle file along with the requirement.txt. So you can even commit it directly from the GitHub using the command line, but I'll just directly copy and paste it over here. And I hope everybody knows that how to do it, right? Because already GitHub session is already spoken about it, right? We have discussed about it, right? So I'm uploading all these files quickly. And here I also have my requirement.txt. So let's go ahead and put this requirement.txt over here. Okay. So yes, this commit, we will be doing it. Okay, I have to just go ahead and reload it. Just a second. Okay. So here you can see processing your files and all the files is over here. You have your README file, app.py, pickle file, everything. Now let me go over here. So here you can see that you have your share.streamlit.io. Now Streamlit allows you to probably create your free apps just by integrating with the GitHub. So I will just go ahead and click on create app. It is asking, do you already have an app? So I'll say yes, I have an app. It is in GitHub repository. So I will just go and search for this GitHub URL and I'll paste it over here. Okay. Once I paste it, so the branch is main. Let me just go ahead and say main file path. It should be app.py. And this is the URL that is basically creating. Okay. So step by step, you're doing it. Okay. ANN classification churn this particular .streamlit.app. So I will go ahead and deploy it. So there is also something called an advanced token. If please provide environment variable and other secret key to your app using TOML file format, the information is encrypted and served securely during your runtime. Learn more secrets in JSON. If you have any secret key, you can probably mention it over here and save it. Okay. That also we will be seeing as we go ahead. Okay. How to probably use some secret keys. Now I'll go ahead and click on deploy. Once I do the deployment, automatically see requirement.txt, all the files is there. This will actually do the deployment to all the installation that is required and to create the entire environment over here. And my entire platform will be ready just in another 30 seconds to 45 seconds. And then we are good to go to probably check out our application. So let's wait for some time. The reason why we really need to wait for some time is that because it will be doing the pip install requirement.txt, all those things. I'll also show you an example how to probably do it with the environment variables. But right now, let's focus on this and let's see how quickly we'll be able to do it. Okay. So it shows your app is in the oven, so it is getting warm. In short, your entire server is getting warm. So we'll wait for some time till this installation takes place, and our platform is once ready. And this is the URL which you can also use it and you can also access it. So I think now my app is ready, and here you can see it's running, stop, share, everything is probably displayed over here. I think it should be displayed in short over here. So let's see. Yes, perfect. This is my entire app, and right now it is in the cloud of Streamlit. Now, if I go ahead and select any value that I want, it should be able to directly compute things, right? Directly, just by selecting values, it should be able to compute. And this entire thing is working with the help of ANN. Okay, you can select any of the values, and then you'll be able to get the answer. And this is with respect to just a runtime, right? So I hope you like this particular video. This was it, and this was one amazing end-to-end project using ANN. I'll see you all in the next video. Have a great day. Thank you. Take care. Bye bye. So now let's go ahead and probably implement this regression problem statement. So what I will do, I will go ahead and write over here. And inside this folder only I will be creating this because we are going to follow the same steps. So I'll go ahead and write I regression, IPY and B. I'll say churn regression or I'll say salary regression. Okay. So this will be my file. I will go ahead and quickly select my kernel. Okay. Now, first of all, what are the steps that we will do? So initially we will go ahead and import all the necessary modules that is required, like train, test, plate, standard scalar, label encoder, one hot encoder, and pickle. Okay. So we'll go with the first step over here. Then after this, we will be reading our CSV file. So I'll go ahead and write read underscore CSV. And let me just go ahead and write this as churn modeling, churn underscore modeling .csv file. Okay. Now, if I go ahead and write data.head, I will be able to get my input over here, and this is my entire data set, right? As I said, estimated salary will be my output feature, and remaining all will be my independent feature. Okay, and that is the reason the output feature is a continuous value over here, so we are considering this as a regression problem statement. Now, after this, the next state that what I will do is that I will delete this row, number, customer ID, and surname. Whatever things we did in the classification problem, almost the same way we have to probably do this. Okay, so I've executed this. Then we will go ahead and convert this gender from female male to zeros and ones because this here I'm going to use my label encoder. So for that, I will go ahead and create my variable label encoder gender. I will initialize to label encoder, and then I will go ahead and write data of gender is equal to label encoder dot fit underscore transform. Okay. Similarly, I will go ahead and do it for the geography column also, where I'm going to use one hot encoder. Again, I'll use fit underscore transform. I'll convert this into arrays. I will get all my values. Then convert this into my data frame along with my features. Okay. So if you go ahead and see your geo underscore encoded underscore ds, you'll be able to see, hey, I'm getting these three features. Okay. Then we are going to combine this one hot encoded columns with my original data. Step by step, we're going to do this. So finally, you'll be able to see data.head, and we're also dropping the geography column. Now I don't have my geography column, and if you probably go ahead and see, my these three columns have got added. Perfect. Now we are going to split our data into features, into our independent features and target feature, right? Dependent features. So I'm dropping estimated salary from this, and all the remaining features will go in x-axis, and my estimated salary will go in the y-axis. Okay. So this is done. A bit of processing. Now I will save all the pickle file specifically for transformation, like label encoder.pickle. Then you have one hot encoder.pickle. Then one more pickle that we are going to probably create is scalar.pickle. But the scalar.pickle we will specifically use only when we try to do the train test split. So let's go ahead and do the train test split also. So here I will take this code quickly. I'll just copy and paste it so that I don't have to waste more time on this writing the entire thing because we're doing the same thing. If I was doing something else, then I could have probably done that. Okay. So here I'll go back to my salary regression. Quickly, I will go ahead and write code. Now quickly I'll paste it over here. Okay, train test split. And now I will go ahead and apply my standard scalar. Scale this feature. Quickly, salary. Okay. And here I will go ahead and do this. And this is done. Right. Okay, I'm getting an error to not convert string to me. Why? Because let's see my x value. Okay, gender is still male and female. Why? Because data of gender it is. Okay, fine. Data of gender. So if I replace this, what is my data over here? If you see the data, or let me execute this once again. I think I missed something. So I'll quickly execute this. I'll remove this tree. I'll see this. Now let's go ahead and check my data. So my data is basically having zeros and ones. I think I missed one line of code in executing it. Then I'll do the concatenation, and finally I will do the concatenation. This is got executed. I have gender 0 and 1, x1, y. I get it, and I'm doing the train test split. And now it should do the scaling. Okay, so I missed one code, so that is the reason that was the issue. Now we'll go ahead and save all the pickle files. Scalar.pickle file, one hot encoder geo, and label encoder gender file. Okay. Now it's the time to train our ANN with regression problem statement, right? How to train our ANN. Over here, that is what we are basically going to discuss. And this is the important thing. The remaining thing are almost same. I do not have to make any changes. Okay. Now let's go ahead and quickly do this. So first of all, again, I will import TensorFlow as Keras. Okay. And then we are importing sequential and dense. So first of all, we'll go ahead and import this. So once this is imported, we are good to go and work with sequential and dense. And we are good to work with our entire neural network. Okay. So here we are executing this. Then quickly, let's go ahead and do this. Okay. So we will go ahead and build our model. Again, to build our model, we will use the same technique. Like first of all, I will say, hey, go ahead and take this exchange.shape of 1 as input here. This will be my input layer. Then we are going to apply an activation function. The first hidden layer will have 64 neurons. The second hidden layer will be having 32 neurons, and the activation function will be value. And the dense will basically have 1. Okay. Now when we are using 1, here we are not applying any activation function. When we don't apply any activation function, the default activation function that will be applied is called as linear activation function. Now linear activation function is specifically for regression. That basically means I'm not doing anything. Instead, I'm getting whatever output I'm getting, I'm using that. Okay. Now after this, we will go ahead and compile this model. Okay. So we will go ahead and write compile the model. Now for compiling the model, I'll go ahead and write compile model.compile. And here, first of all, I'll go ahead and write my optimizer. Let's say the optimizer is Adam for this case. You can also go ahead and initialize it from TensorFlow.keras, but I'm directly writing the keyword. Then my loss. Now this is what is the main thing that actually changes in regression. In loss, we will basically use mean absolute error. Okay. You can also use mean squared error, but here we are just going to use mean absolute error. It's up to you. And here the metrics that we are specifically going to use is nothing but it will be ME. Okay. Again, you can see the Keras documentation. What all loss will specifically be happening over here. So if I go ahead and open Google, right, and if I just search for Keras loss functions. Okay. So if I just go ahead and click on this, so it shows so many different classification problems. You have binary cross entropy, binary focus cross entropy, categorical cross entropy. Then you have binary cross entropy functions. All these things, right? For regression, you have mean squared class. See, this is what I've used, right? Means absolute error, right? Function. You can also use mean squared error, right? And already I've spoken about this even in machine learning. If you know machine learning, I think there all these things will be probably covered up. So you need to have that basic knowledge with respect to all using this kind of loss function. Okay. So now what I will do, I will use the matrix as ME, and then finally let's go ahead and display the summary. So I'll just go ahead and write model.summary. And when I display the model.summary, then here you can see this is my input. This is my input. So the total number of weights and bias are nothing but 2945. These are the trainable parameters that we have, right? Then I have dense 1, dense 2, and finally my output is over here. Okay. Now let's go ahead and train this particular model. Again, for training this model, I will go ahead and set my logs. Okay. So here are some of the logs. I'll say this is my regression logs. I'm using early stopping and TensorBoard, as you all know. So we are going to use both of them so that this folder will get, it'll just try to, whatever logs is basically coming during the training, it'll be coming over here. Then we are going to set it to early stopping also. So in the case of early stopping, I will be using validation loss. Like whenever we are training our neural network, you'll be getting training accuracy. You'll having training loss, then you'll also have validation accuracy and validation loss. But I really need to monitor the validation loss. And I'll keep the patient's value to 10. That basically means I'm going to see it for 10 epochs. Okay. And finally, we'll go ahead and train the model. Now in order to train the model, I need to use this callbacks. So early stopping and TensorBoard callback. I'm giving extend my train. My epochs will be 100 and all, everything is there. Right. So let's go ahead and train this. And let's see how much will be the answer that I'll be getting. So epoch 1, here you can see ME. These all values are there. Validation loss here also values are coming, right? And these are keep on decreasing. Unless and until it keeps on decreasing, this epochs will be going on, right? So the validation loss also you'll be able to see that it is decreasing. Okay. See, validation ME, validation loss. Unless and until it is not decreasing, right? If it is maintained in a similar manner, hardly there is not much difference, then it will stop. So here you can see in epoch 47 it has stopped because till here the loss was going down, but after this it was almost similar, right? So now my model is almost trained. Again, this is I'm actually doing it in my local machine. Again, I have a powerful CPU, so I'll be able to do it very much fast. Now let's go ahead and evaluate the model. Okay. Now before that, let me just go ahead and load my load extension tensor board. Okay. So I'll just go ahead and execute it. Then I will say, hey, go ahead and take this tensor board, and my directory will be regression logs slash. Let's see this particular folder. So here you have regression logs slash fit. Okay. So slash fit will be my. So once I execute it, here you'll be able to see that we'll be able to load the tensor board. Now in this tensor board, all the information regarding how the training has happened and all. So I'm getting some error. So this should be directory, I guess. Let's see over here. Okay. Again, you don't need to by heart it. You can see the documentation, and you should be able to see this. Okay. You may be thinking that you don't know all these things. I'm not. I'll definitely not by heart it. So you should also not do that. Okay. So this should be the log directory. And here should be my folder. Okay. Now I think it should get executed. Now we are launching the tensor board. Now this is good enough. It will take all the events from inside this and it will display it to you. Okay. And let's see, it is taking some time to load it. Quickly let it get loaded. I think for the first time I have to execute 2 times, but it does not happen in Google Colab. In Google Colab, in the first instance only, you'll be able to run it. Okay. So this is really, really good. So here I have got my entire information, which is amazing in the tensor board. Now see this entire things, right? Now if I go ahead and see with respect to regression, epoch versus loss. Wow, this graph looks amazing. See, it is going down completely, right? So loss is coming down. If you see mean absolute error, this is also coming down. I think this is an amazing graph. And this looks good. That basically means your epoch is going down. That the model is really performing well. Then here you have evaluation loss versus iteration. Iteration by iteration, how much it is basically getting reduced. Then you also have ME versus iteration. This also you can actually check it out, right? If you just want to see the validation, validation has this epic loss and all. So sorry, epoch loss and all. So here you have your ME. You can probably zoom in and zoom out, and based on this you can check. You can also do something like this and check it out, right? So all this information from the logs you're able to see it. Okay. Now let's do one thing. So if you see ME and all, we will also try to evaluate this model for our test data. So let's go ahead and evaluate model on the test data. We're just going to check the accuracy, how good it is. So I will just go ahead and compute my test underscore loss and test underscore EME. ME, mean absolute error. I'm just going to write model dot evaluate x underscore test, y underscore test. Perfect. So now I'll just go ahead and print, and I'll use a string, and I'll say, hey, this is my test MAE, which is nothing but it'll be test underscore ME. So here you can see 5016, and more near to 0 if it is going on, we can probably say that our model is pretty trained in an amazing way. Okay, and this is done. And what you can also do is that along with this, I can also go ahead and save my regression.py file. So I'll say, hey, go ahead and save this as my regression model .h5 file. Okay. So once I do this entire model will get saved, and I have my regression model.h5 file, right? So almost we've done each and everything, right? Now, if you want to deploy this, you have all the h5 files, you have all the training that has been done. Now you can also go ahead and deploy it. So for deployment purpose, what I'm doing is that I'll give you the entire code. Again, with the help of Streamlit, you can deploy it. Let me just go ahead and create a file over here. Let me say Streamlit underscore regression.py. Okay. So I'll give you the code over here so that you can go ahead and do the deployment, and it's very simple. It's almost like this only. So here you can see all the things, and estimated salary, you can basically go ahead and compute it. Okay. So we are loading it. We are creating some user input box. We are converting this into a data frame. We are doing the encoding. Then we are predicting the salary. Okay. You can do this entire thing. Okay. Let me see one more model, regression underscore model.h5 file. Okay, perfect. So I hope you understood this particular video. Again, it's more about how much you practice and how easy it was probably to train the entire ANN, that is artificial neural network, for classification for regression. Now, one of the most common questions that has been asked is how do you decide how many hidden layers or hidden neurons you need to take? We need to discuss about that also because that is something very important. So in this case, it is very, very much difficult to just say that, hey, you probably need to just use this many number of hidden layers or this many number of hidden neurons. That is not possible. So what we do is that we basically apply a lot of hyperparameter tuning, like with respect to the number of hidden layers and with respect to the number of hidden neurons. And that is what I will be showing you in the next video, like how you can also come to a conclusion. And I'll show you one type of hyperparameter tuning, how we can specifically do. So yes, this was it from my side. I hope you like this particular video. I'll see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to ANN. Now finally, we are going to discuss about a very important problem statement or question that comes in everybody's mind whenever you are implementing any application with deep learning neural networks. That is determining the optimal number of hidden layers and neurons for an artificial neural network. Okay. Now this can be really challenging and it often requires experimentation. However, there are some guidelines and methods that you can help in making an informed decision, right? So here are some pointers in order to probably come to a conclusion that how many optimal number of hidden layers and neurons you should probably use for an ANN. So the first point over here, it says that please go ahead and start simple. Begin with a simple architecture and gradually increase complexity if needed. Okay. The second thing is that you can also perform grid search or random search. I hope everybody knows about this hyperparameter tuning. Using grid search or random search to try different architectures. So you can make different architectures, and with the help of grid search or random search you can actually do it. Then you also have cross validation. Use cross validation to evaluate the performance of different architecture, like how we used to do in machine learning. And here is one more approach which is called as heuristics and rules of thumb. Some heuristics and empirical rules can provide starting points, such as the number of neurons in the hidden layer should be between the size of the input layer and the size of the output layer, right? Between that particular size, that many number of hidden neurons can be there in the hidden layer. Okay. And the common practice is to start with 1 2 hidden layers. So obviously there are so many statements that I've discussed about, but we will try one approach where we'll also perform hyperparameter tuning. The hyperparameter tuning will be done in such a way that I will take various number of neurons, various number of hidden layers, and then we will try each and every architecture and try to see that which is the best model, which is probably coming out of it. Okay. So first of all, what I am actually going to do for this, I'll be using one very important library which is called as Keras. Okay. So here, instead of TensorFlow, I'll also use one more library which is called as Keras, because in this Keras there is one very important module which is called as Keras classifier. Okay. And that actually helps you to perform this entire hyperparameter tuning, just to find out which is the best model. So I'll quickly go ahead and install this library. Okay. So I'll go ahead and write pip install -r requirement dot, oops, that is 5 it went ahead, So requirement dot txt. So let me just go ahead and do this, and I hope I should be able to get the installation of Keras. Let's see. Right now it is not giving me anything, but let's go ahead and import things. So here I will be importing some very important libraries. One is GridSearch CV. See, one more additional library that we are going to use is GridSearch CV. Standard scalar, label encoder, one hot encoder is done. We're also going to import pipeline. Then we are going ahead with Keras Classify, which is present in keras.wrapper.scikit-learn. Along with that, we are going to import TensorFlow, TensorFlow Keras model for sequential, dense, and early stopping. Okay, so this is almost same. Nothing changes over here. But I think I'll be getting an error over here. Let's see if the installation is not taken place. Okay, so here you can see module not found, no module keras.wrapper. So let me go ahead and see in the Keras whether we have this wrappers or not. Okay, I don't know. We need to probably check it out. Okay, pip install -r requirement.txt. Okay, keras.wrapper. So let me just go ahead in Google and search for it. So pip install keras.wrappers or scikit-learn. So for this here, you have this particular module. Okay, so I will go ahead and use this module. So always remember, whenever you find this kind of errors, please make sure that you have a good sense wherein you will be able to find out which library we are talking about. So let's see SkyKeras. I think if this is the library that we are searching for, I think it should work. Okay, but if it does not work, then again we'll look for a solution. But we'll look for a solution together. Okay, so here you can see it has been successfully installed. Now I think it should work. Okay, let me restart the kernel. Okay, so let me see. I think we should not be getting an error now. Okay, we are still getting an error. So let's search for this itself, right? Let's search for this. So here, what I will do, I will go ahead and open my browser. I'll search for no modules keras.wrapper. Okay. So here it says this works for me. Another approach you can try. Okay, it comes with TensorFlow 2.12. Okay. From SkyPy. Okay, I can also use this. Let's see. I've also installed this, right? Instead of using this, I will use this. But I think now this should work. Okay. So I've used SkyKeras and there I've actually done this installation. Okay. Now this is done. Now the next thing will be that I will go ahead and quickly import our pandas, use pandas and read our CSV file. And here I'm actually going to write my John_modeling.csv. Here you'll be seeing how I specifically experiment with things. Okay. So here I'm actually going to get my data. Okay. Then you know what all things you really need to do. Okay. So I will just try to copy and paste it over here. And I hope I don't have to make you understand. We're going to apply label encoder, one hot encoder. Then this is my entire data frame. Then we're concatenating. We are getting the independent features. And after this, we're also going to do the train test split. Okay. Because this is not that important because this all things we have repeated again and again. Okay. And then finally we are dumping all the pickle file or we are saving all the pickle file. So quickly I will copy and paste it over here. Let me go ahead and write import pickle because I will also be requiring import pickle. Okay. Done. So let's go ahead and execute this. Now here you'll be able to see my pickle file will get created. So this has got executed. Now we are going to create a function. Now see, here is where I will write my coding completely from scratch. So define a function to create a model. Okay. And try different parameters. Try different parameters. Okay. And here we are specifically going to use Keras Classify. Okay. So I will go ahead and write definition create underscore model. Okay. Here, what I'm actually going to do is that by default, I will be providing two parameters whenever we create a model. One is how many number of neurons are required. Let's say by default I'm giving 32 neurons if I'm not passing any value, and how many layers I want with respect to the hidden layer. By default, I'll give one hidden layer. Okay, so I'll create this function and I'll say, hey, go ahead and create my model is equal to sequential model. Okay, and then what I can do on top of this particular model, I can go ahead and add one dense layer. So I'll say, hey, go ahead and add a dense layer, and dense layer by default will be this entire neurons. Okay, and along with this, I'll say, hey, go ahead and apply my activation function, which is nothing but relu. Then here you'll be able to see that I'm also going to use my input underscore shape is equal to x underscore train dot shape. Please observe very carefully what I'm actually doing over here. Okay, so this is my input shape. So in the first layer, I'm basically adding this, right? Now I need to probably check, do I need to add more layers or not? Okay, if I give 2 to 3 layers, then we should also add it, right? So based on this parameter, I'll write a generic code, right? I'll say, hey, if I'm giving 2 to 3 layers, if I'm giving 3 layers also, along with this first layer hidden layer will be there. Okay, and here you'll also be seeing that at least this will be there with respect to the number of neurons that we have. Okay, then a generic representation, I'll say, hey, for dash in range of layers -1, because I have to probably create that many number of hidden layers now. Remaining hidden layers is layer -1. I'll go ahead and write, hey, go ahead and add model.add and use the dense, and here use the neurons. The neurons will be same what I've actually passed over there, and the activation function will be nothing but it will be relu. Okay, so this is just my for loop. We will be keep on adding this particular layers. Finally, our output layer, I'll go ahead and write model.add. Here we are going to use my dense, and here I'll use 1 comma activation is nothing but it will be my sigmoid. Okay, so I'm basically going to add this, and finally I'll go ahead and write model.compile, and let me just go ahead and use my optimizer, which is nothing but Adam. Okay, loss, since it is a binary loss, so I'll go ahead and use binary underscore cross entropy, and finally you'll also be seeing that I'll be able to add matrix, and the matrix is nothing but it will be accuracy. Okay. And finally, I return the model. This is what we are doing inside this function. Okay. So whenever I usually call this particular function, I'm just going to give this parameters, neurons and layers, and based on that, I need to add how many number of hidden layers and all. First layer is added by default. We have also added output layer by default. We have also added which optimizer and loss we are specifically going to use. Okay. Now we will go ahead and create a Keras classifier. Okay. So I'll go ahead and write, hey, model is equal to Keras classifier. Let's go ahead and call this function. Now this Keras classifier is responsible in creating the entire neural network. ANN. So I'll say, hey, go ahead and call this create model function. I will say, hey, go ahead and pass epochs as 50. I'll say, let's pass the batch size is equal to 10. And here I'm specifically going to use verbose is equal to 0. Some information with respect to this. Now this is fine with respect to my model. My model is a Keras classifier, which is going to probably call this function and create an entire model. And then you need to run the model needs to be run for 50 epochs, batch size is 10, and all the information. Now is very much important thing. So here I will go ahead and define my grid search parameters in the key value pair. So this will be neurons, like neurons, which how many neurons I want to play with every layer. It can be 16, 32, 64, 128 layers. I'll go ahead with 1, 2, 3. If you want to add more, you can go ahead. And I'll keep on playing with each and every parameter over here. So let's go ahead and let's remove the batch size because I just want to play with one batch size that is 10. Okay, so that I don't have to probably play with more things. And my training will also happen fast. This is just to show you. And epochs I'll play with 1500, right? Now grid search CV is going to probably take this entire model it is going to take this entire param grid and it is just going to perform this cross validation that we get. And once we write grid.fit, I'm probably going to get the best number of parameters. So I'll probably, after the fit operation happens, we can just go ahead and print it. I can write grid underscore result dot best underscore score and best underscore parameter. Parameter will be like how many neurons, layers, or epochs I need to probably take this. Okay. So here our training will start and grids to see what it does. Every combination it will probably take. It will go ahead and see what loss is there and whichever has the highest accuracy will take that particular parameter. So let's go ahead and execute this. So it is going to take time. That fast it is not going to happen, all these things, because here now the combination is many, right? Okay, I did not. Okay, I had to probably print it. At least we'll not be able to see it. Okay, over here. So that is the reason it is just showing all these things. Okay, I'm getting some error. So guys, the error that we got, right? So what I will be doing is that along with this parameters, I will also be adding this layers is equal to 1 and neurons is equal to 32, because in this create model, I'm actually passing this particular values, right? Neurons 32 and layer 1, right? So that parameters also I'll be passing in my keras classifier. Along with this, I also saw one more issue that is with respect to, let me just go ahead and have a look where it is regarding binary cross entropy. So how many time I have basically written this, okay? So I think now it should work fine. Let's run this. And finally, I'll also run this, okay? Now, the entire fitting will specifically happen, and here you can see 3 folds for each of 16 candidates, totally 48 fits that is basically going to happen. And now the training has already started. I think once the epoch starts with respect to this, we should be able to see more information. But just by using this verbose is equal to 1, we'll be able to see some information otherwise. And right now, when I wrote this n underscore jobs is equal to -1, right, it is probably going to use all the cores out there, okay, of my system. But again, if you're trying to do this in your local, and if your local is not a good system, then it may take some amount of time, okay. Otherwise, please go ahead and do it in Google Colab. Google Colab is any point of time you will have some kind of GPUs that will be available. So what we'll do, we'll wait for some time, and then we will continue the discussion. So here you can see, oh, perfect, the epoch has started and it's running like anything. See, quickly. This is the power of a powerful workstation, right? I have a powerful workstation. I have GPUs. I have all these things done as a setup over here, and this is mainly to show you like how things work over here. So here you can see accuracy is there, loss is there, and finally the best accuracy that you got is nothing but 85% using epochs 100 layer 1 and neuron 16. So it is saying that hey, just go ahead and use one hidden layer and go ahead and use 16 neurons and just try to do it and try to find it, right? So when you use this, now you can go ahead and create your own custom your entire ANN with this many number of layers, and by this you'll be able to find out the best parameter. So I hope you were able to understand this. Once you get this information, then constructing an ANN becomes very much easy, right? So this is what we have actually discussed about determining the optimal number of hidden layers and neurons for an artificial neural network. Again, you can try out with different parameters that we can use keras classify with respect to this. So yes, this was it from my side. I will see you all in the next video. Thank you. Hello guys, we are going to continue discussion with respect to simple RNN. Now in this particular video, we are going to develop an end-to-end deep learning project using simple RNN. For this, the dataset that I'm actually going to take is something called as IMDb dataset, and this is nothing but it is a movie reviews dataset. Now our main task is that in our dataset you'll be able to see that we'll be having some text and some output labels. Text will be specifically the reviews, and your output label will be having something like positive or negative. Okay. So with the help of simple RNN, what we are basically going to do is that we are going to train this model, and we are going to see that how we can do this specific prediction. And we'll not stop here. We'll also do this entire deployment in the cloud. And for this, I'm also going to perform some trainings in my local machine. Okay. Now, for all those who do not have a powerful machine, you can also go ahead and execute this in Google Colab. Okay. Google Colab. You can go to the Google Colab and you can probably create your model. Okay. Basically train the model, because in Google Colab they even provide you GPUs. Okay. Free GPUs. Free GPUs. And it's not like I'm just taking a very small data set. It will be good number of data. Like over here, 50,000 records will be specifically there. Now, before I go ahead and probably create this end-to-end deep learning project, understand what we are going to do in this deep learning project. Okay. So I have my, first of all, I just draw the architecture. I have my input data. So this is my data set, the reviews data set. We will take this data. We will perform some feature engineering, and we also say it as feature transformation. After we do this, we need to keep ready for this particular data so that it will be ingested in the simple RNN for training the entire neural networks, right? So after this, we will go ahead and build our simple RNN. So we will probably take a simple RNN architecture, we'll feed this data, we'll train it completely. Once we train it, here we are going to get our model file, which I will be storing it in the form of .h5 file. Okay? .h5 file is nothing but a kind of format, like how in machine learning we use pickle files. Similarly, in deep learning we use, if you're using keras, you can actually convert that into a .h5 file. Okay? Then after this, we will go ahead and create a Streamlit web app, and then we will further do the deployment. Okay, we'll further do the deployment. Perfect. Now this is the entire fundamental things that we are specifically going to do in this particular project. Okay. Now the best thing over here is that how do we go ahead and implementing this? Okay. Over here, dataset, feature engineering, Streamlit web app, and deployment. This we obviously have seen even in ANN. The major thing will be training the simple RNN. Now this simple RNN will definitely have two important components. Okay. I will be talking more about it. One is something called as embedding layer. We also need to use embedding layer over here. Now, what is this embedding layer? We will just talk about in some time. And along with this, we will also use a simple RNN for training our neural network. So both of them we really need to use. Okay. Now let me just talk more about this embedding layer. What does this exactly mean? As you know, if I just take the simple RNN, okay, you know what is the architecture of simple RNN. So this is my simple RNN over here. And if we just make sure that we unfold this with respect to time, it will look something like this, right? This we have already discussed in our theoretical session. Like this, and it will go on till my last layer. And finally, I'll have my output, and this will probably go to my sigmoid or softmax, and then we get y hat. Okay, so this is the process that we specifically use. But along with this, let's consider any of my text. Let's say in my data set I have a text, and this is my output. Let's say in this text I have some inputs like x11, x12, x13, x14, and then I have my output over here. It can be 0 or 1. Let's say it is 0. Okay. Similarly, my next sentence will be x21, x22, x23, x24, and this will be 1. And whenever we are doing the forward and the backward propagation with respect to every sentence, we give words by words. Right? Initially we give x11, then in t is equal to 2 we give x12, then x13, then x14. Okay. Now this x11, x12, x13, these are words, right? And we really need to convert these words into vectors. Okay, so here you'll be seeing that we also have to convert these words into vectors with respect to some dimensions, which I will be passing it over here, right? Now, already we have discussed about this architecture. One thing that I never discussed about specifically in deep learning, how these words are converted into vectors. Okay, and here is what your embedding layer comes into picture. Embedding layer. We have another embedding layer like this. Let's consider it like this. Okay, and this embedding layer is responsible in converting your words into vectors. This embedding layer uses something called as word embeddings. I hope you have some idea about word-to-vec. Word-to-vec is a kind of a word embedding techniques which we can also specifically use in the embedding layer. Now, in the next video, before we start this entire project, we really need to understand about embedding layer, and that is what we are going to discuss. First of all, we will go ahead and discuss about how does embedding layer work, and then we will try to understand the mathematical intuition. Okay, we'll just try to understand the intuition. Along with this, we will also do some practical implementation, because unless and until we don't know this, right, it will be very difficult to understand the project. So both of this, I will try to cover it up, okay, for you all. So this was just an introduction video about this end-to-end project. Now in our next video, we will talk about word embeddings, embedding layer, and feature representation. What exactly is this feature representation? Okay, so let's go ahead and discuss this in the next video. Thank you. So feature dimension, let's say I'm using over here as 300. So there is a word-to-vec technique from Google, there is also a library called as Glove, right? This has specifically 300 dimensions, okay? Then these two are the important parameters, and you have to remember this, because in the next video, what I'm actually going to do is that I'm going to show you a practical implementation, how word embedding will work, word embedding layer will work. And this is what we are going to discuss in the next video. And here, I'll just take some examples and then convert that into vectors before I convert that into vectors with the help of word embedding layer. Okay. Then after that, we will start our end-to-end project. Okay. So yes, this was it from my side. I hope you like this particular video, but I hope you got an idea with respect to word embedding or what exactly is embedding layer or feature representation. I will see you all in the next video. Thank you. So guys, now we are going to continue the discussion with respect to word embedding. Now in this video, we are going to see a practical implementation that how we can use word embedding and convert your word into vectors. Again, before I go ahead, please remember this vocabulary size and feature dimensions, because we are also going to use the same thing in our code. Okay. So let's quickly go ahead and open my file. So here is my entire, you can see in ANN classification, I created a folder over here. Similarly, in simple RNN, I will go ahead and create one of my file, which is called as embedding.ipynb. Okay. Now in this embedding, I will first of all go ahead and select our kernel quickly and start our code over here, right? So here you'll be able to see that first. Let me make some code cells, and this is where I'm going to write my code. Okay. Now here also we're going to use this current TensorFlow, so that is the reason in the same VNV environment we are going to work. Okay. So here I will go ahead and write from TensorFlow dot keras dot preprocessing dot text. First of all, what I'm actually going to do is that I'm going to perform one hot representation for a specific word. Okay, so that is the reason I will go ahead and import one hot. Okay, so this one hot representation I've already shown you in my previous video how do we specifically do it. Now to try some of the sentences, here are my list of sentences that I'm actually going to use. Okay, so I'll go ahead and execute this particular code with respect to one hot, and these are my sentences: the glass of milk, the glass of juice, the cup of tea. I'm a good boy. I'm a good developer. Understand the meaning of words. Your videos are good. Okay, so these are my set of questions that I'm going to specifically use. So if you go ahead and execute this, now if I go ahead and probably see my sentences, here are all my sentences. Let's say as I said you that we need to define the vocabulary size, and we're going to use this word and probably convert this into vectors. Each and every word you'll be able to see that I'll be able to convert into vectors. Okay. So here my vocabulary size that I'm actually going to consider, it's 10,000. Okay, let's consider 10,000 that I'm actually going to do. Now the first thing that we're going to discuss about is one hot representation for every word. Okay. So I will just go ahead and write for word in sentence. Okay. So first of all, I will just go ahead and write. Let's say for words in sentences, because when I'm running through each and every sentence, I'll get each and every sentence itself. So I'm writing words, okay. And for every words that or every sentence that I get, okay, in this specific sentence itself, I will pass it to one underscore hot. And here I'm just going to give two parameters. Okay, please focus on this. I'm going to give two parameters. The first parameter will be my words, what sentence I'm specifically giving, and the second parameter here we're going to focus on the vocabulary size. And this I will try to create as a list representation or list comprehension. Sorry, right? And this will basically give my one hot representation. Now once I write this code, let's go ahead and execute it. Okay. I will just go ahead and execute it. So here you can see vocabulary size is not defined because, okay, I did not execute this code. Okay, now it should get executed. Now if I go ahead and execute it, now see, this is very amazing. Okay, if you remember what were my sentences, if I go ahead and write my sentence, here you can see my first sentence is the glass of milk. The second sentence is the glass of juice. Third sentence is the cup of tea. Here you have, I'm a good boy. Now this glass of milk has got converted into this vectors in my 10,000 vocabulary size. Okay, 10,000 vocabulary size. That basically means this the is given by the index 6186, right? Glass is given by the index 6775. Off is basically given by the index 637, right? And milk is basically given by 4895. What does this basically mean? If I expand this off into a vector of dimension, in the 638 index, I will get 1, remaining everything will be 0. Similarly for this particular word, similarly for this particular word. This is what it is basically saying. It is just giving an idea, right? For every word which index, it is just going to be 1. Okay. Now here also you can actually see, this is one hot representation I'm specifically using, but we need to use this in our embedding layer. So we are not going to use that entire vectors where only 1 is present and remaining all are zeros. We will try to convert all our words based on this index. So every word that you'll be seeing in the sentence is representing one index. Okay. Now once we do this, okay. Now see, observe one thing. I have written the glass of milk and also I have written the glass of juice. Okay. Now, when we write the glass of milk and the glass of juice, okay, it is very much important to see. You'll be able to see all these words are same, all these vectors are same. Only this particular vector is basically changed, right? Because over here I have milk and then I have juice. So that is the reason. Let's say vector, but the index has got changed, right? Now, this is a very important thing that I really want you all to explain, okay? So please focus over here. Now, in word embedding, if you probably see based on these vectors, okay, based on these vectors, if I take all these vectors, okay, and if I start plotting this, let's say I apply a PCA. PCA basically means principal component analysis, and I convert this 300 dimensions into 2 dimensions. Let's say that I go ahead and do a dimensionality reduction. Okay, and if I then plot all these vectors, you'll be seeing. Let's say if I have man over here. Okay, human will be somewhere here again. Okay, king will be somewhere here. Queen will be somewhere here. So here you can actually see the vectors like man and king, because they are almost similar kind of vectors. It'll be near to each other. Woman and queen, they're similar kind of vectors. It'll be very close to each other. Similarly, if I go ahead and see with respect to fruits like apple and mango, these all are fruits, right? If you go ahead and see, both these vectors will be very much nearby, right? So this is very much important. That is what it actually mentions. Whenever you have this particular vector, you will be able to find out which vector is near to which one, right? And here only your very important algorithm gets applied, which is called as cosine similarity. One of the amazing use cases that we will be seeing is something called as recommendation system, right? Recommendation system uses this based on this particular vector. If I'm watching an action movie, I should be recommended another action movie, okay? And that is what we are specifically doing. Now I told you there are some problems with respect to one-hot representation, so I'll not directly use that. Instead, I will convert all my words into this particular indexes, okay? And now I will take all these words sentence by sentence and I'll pass it to my embedding layer, and then we will try to convert this into a word embedding representation. So let's go ahead and write this word embedding representation. Very much important, okay? So quickly, let's go ahead and do this. Now in word embedding representation, as I said, right, how we use dense layer. Similarly, there will be one more addition layer, which is called as embedding. So for that, we will go ahead and import for TensorFlow dot keras dot layers. I'm just going to import embedding, okay? Then we have from TensorFlow dot keras dot preprocessing dot okay, let me just go ahead and from TensorFlow dot keras. I'm also going to import one very important library, which is called as dot sequence, and we are going to import pad underscore sequence. I'll talk about it, why this is really important, okay? Pad underscore sequence, okay? I will talk about it, just wait. But I have imported the embedding layer over here. Along with this, we know that we are going to create a sequential model. So for this, I'll go ahead and write from TensorFlow dot keras dot models import sequential. Now I'm going to use these three important libraries. So I'm actually getting one error saying that, hey, from TensorFlow.keras.processing. So now here you can see, guys, we are getting an error which is called as no module name TensorFlow.keras.preprocessing. Now previously, this preprocessing.sequence was present inside this TensorFlow.keras.processing. But now after seeing the documentation, it has changed. Okay. So I will go ahead and write from TensorFlow.keras. Okay. From TensorFlow.keras.utils. Okay. And here we are just going to go ahead and import my pad sequences. Okay. So we'll just comment this out. It was before in this, but again, whenever you see this kind of error, always refer to the documentation page. Okay. So now I'll go ahead and execute it. This has got executed perfectly. The next step that I'm actually going to probably do is that we will also go ahead and import one important library called as NumPy as NP. Okay. Now, first of all, we'll understand what this pad sequences basically mean. Now see, observe each and every sentence. Every sentence is of different number of words. Let's say, okay, first sentence is having 4 words, second sentence is having 4 words. This is also 4 words, but here you have 5 words. Here you have 5 words, and here also you have 5 words. And some of the sentences also have 6 words, 7 words, right? One very important thing is that we need to make all the sentences of equal size. Okay. Otherwise, we'll not be able to train it in our RNN, because at the end of the day, all the words that will be probably going, it will be going for a fixed number of timestamp based on the sentence size. Okay. So that is the reason what we do is that we import this pad sequences, and what we are going to do with this pad sequence, we will go ahead and set up one maximum sentence length. So here, let me just go ahead and write. Right now, based on our data set, I will just go ahead and set this sentence length to 8. Okay. Because I know maximum number of words are 5. So considering this, all the words, all the sentences in this should have a maximum of 8 words. Okay. So I'm just keeping it. You can also keep it to 10. Okay. Now I will go ahead and say, use this embedded docs or create my new docs where I apply all this pad sequence, because if I want to make this sentence of 8 words, I need to add 3 zeros more, right? So pad sequences does that only. You can add 3 zeros before, or you can add 3 zeros after. So in order to make all the sentences equal. So for this sentence also, I'll say if 4 words are missing, so I'll go ahead and add either 4 zeros in the forward or 4 zeros in the backward. So that will actually become 8 sentences. Similarly, here also I'll try to make it as 8, sorry, not 8 sentences, 8 words. Similarly, I'll also try to make this as 8 words. Similarly, I'll try to see over here what is the length, 5 words. So 3 more zeros if I add it, you'll be able to see that, okay, it will become 8 words. So that is what pad sequences basically do. Okay. So I will go ahead and use this, and I'll use the one hot representation that I've used. I'll say, hey, go ahead and apply padding. And inside this padding, I'll say, hey, go ahead and do pre-padding. Pre-padding basically means if I want to make the sentence of the same length, I will, how many words are basically remaining out there, that many number of zeros will get added forward, right? And the third parameter that we really need to give is something called as max length. So inside this max length, I'll just go ahead and give my sentence length. Okay. And now let me just go ahead and print my embedded docs. Now this will be lovely, because now you'll be able to see that all my sentences are of equal words. There are 2 ways. One is post, one is pre. So if I do post, I will be getting the zeros at last. If I go ahead and write pre, I will be getting zeros at the first. Okay. So right now I will just go ahead and use this pre. Okay. So I've used my vocabulary size. I've converted all my words into a representation wherein I'm using pad sequences along with that pre, right? And I've converted all the things based on my maximum sentence length. Okay. Now is very much important. Now we will talk about feature representation. Okay, feature representation. Now in this feature representation, I'll say, hey, use the dimension 10. That basically means I want 10 features with respect to the dimensions, right? In the word embedding. Okay. Over there I showed you in my theoretical intuition, I showed you the maximum example of 300 dimension. But here we're going to use this 10 dimension. Okay. I'll go ahead and execute this. Now let's go ahead and create this model. That is embedding layer. So I will go ahead and write model is equal to sequential first of all, and then we will go ahead and add model.add one embedding layer. How do I add my embedding layer? I'll just say embedding. Now inside this embedding layer, there are some parameters that we need to give. One is my vocabulary size. Second is my dimension, how many dimension I want, and third is nothing but my input underscore length, which is equal to your sentence underscore length. This is just to give you the maximum length. Okay. And this is my model with respect to the embedding layer. Now, along with this, I will go ahead and say, hey, I'm going to probably train with this entire. See, I'm showing how you can also train your entire embedding layer, right? So I'll say, hey, model.compile. I'll use the optimizer, which is called as Adam. Along with this, I will go ahead and use my loss function, which is nothing but MSE. Okay, done. Now, if I go ahead and execute this, okay, so this is what it has got executed. Now I'll go ahead and see my model summary. So this is my embedding model, right? I have this many number of parameters, this many number of params are there because my vocabulary size is 10,000. Okay, and then you have this 8, 10. Okay, so this is perfect. Now this is my model. Now I will just go ahead and use this model. I'm not trained it. See, I've used this embedding layer. So embedding already is a class over here. Now, if I pass any words, right, you'll be able to see that how it will be converting into vectors. Now, what I will do, I will take this embedding layer. I will go ahead and write model.predict, and let's go ahead and give my embedded docs, all the embedded docs. And this is what is very amazing. Every word will be represented by how many number of dimensions? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, 10 dimensions, right? And if I just get the first sentence, okay, so my first sentence, what is my first sentence if I probably see over here, right? So let's go ahead and write it this way. Then you'll be able to understand. I'll go ahead and write embedded docs of 0. So this is my first sentence, okay? Now I will just go ahead and predict for the first sentence what my embedding layer will basically be giving me as a vector representation. Obviously, it needs to be 10 dimension. So embedded docs of 0. Okay, 0 of 0. Perfect. Okay, 0 of 0 is not working because this I'm getting is an array. Then this is my first sentence. So what you can see over here, this entire sentence has got converted to this. Okay. Then my second sentence, where only the last word is changing, has got converted to this. So that basically means this 0 is got converted to this 0 is got converted to this 0 is converted to this particular vector, this 0 is converted into this vector, this index is converted into this vector. So here you can actually see all these vectors, right? And that is how your entire embedding layer works. Okay, please see this. We don't even have to train anything. I've used the embedding layer internally. I think so. It is using word2vec. Here it takes vocabulary size input, then it takes the dimension, then it takes the input length. Now this is something really important because in my next video, I'm going to start our end-to-end project, and I'm going to take a very much bigger data set, and this embedding layer will be a part of that simple RNN, right? But I hope you got an idea with respect to working with embedding layer. So yes, this was it. And you can proceed further and you can go ahead and practice with different text. You can go ahead and write more text over here. And because these all steps will follow over there, you can add any number of sentences, you can verify, right? So yes, this was it. I will see you all in the next video. Thank you. Hello guys, so we are going to continue our discussion with respect to our end-to-end deep learning project using simple RNN. So already in my previous video, I've already shown you how to actually use embedding layer. Now let's go ahead step by step and see like what kind of deep learning project we are implementing with the help of simple RNN. And as I've already told you, I'm going to use the IMDb dataset and we are just going to do the text classification using simple RNN. So let's go ahead and first of all, I will quickly use the same environment. You will be able to see that over here I have my simple RNN folder with ANN classification, what requirement.txt was there, what virtual environment was there. We're going to use that same thing. Okay, so here is my ANN classification folder, here is my simple RNN, and similarly I'll keep on creating all the other projects as we go ahead, like LSTM RNN or GRU or any other further variants of RNN we are going to see. Everything will be creating folder wise. Okay, so first of all, I will go ahead and select my kernel. Okay, here I'm going to import numpy as np. Okay, np. Let's execute this and see it's working fine. Then along with this, we are also going to import TensorFlow as TF. Here also we're going to use TensorFlow and Keras. Then, as you all know, this IMDb dataset is available inside the TensorFlow. For that, you can actually load that particular dataset directly from there. So let's go ahead and import that also. So if I go ahead and write from TensorFlow.keras.datasets, I'm going to import IMDb. Okay. Then I'm going to basically write from TensorFlow.keras.preprocessing. As I said that I can also use this preprocessing. Okay, preprocessing import sequence. Okay, so I'm going to import the sequence. I'll talk about it, why we'll be using the sequence and all, but you can just imagine that this is a kind of a pre-processing technique that we really need to use. And then from TensorFlow.keras.models, I'm going to specifically import sequential. Sequential is must for any type of neural network that we're going to use. And then from TensorFlow.keras.layers, I'm going to import embedding. Along with the embedding, I'm going to use simple RNN. Okay. And then we'll also use another layer which is called as dense. Now, usually with the help of ANN, we usually use this dense layer, right, where we create the hidden layers, where we create the hidden nodes. With the help of simple RNN, we'll be creating the RNN nodes, right? And this embedding is basically for your embedding layer. So let's go ahead and import this. So this has got successfully imported. Now I'm just going to go ahead and import my IMDb, which I've actually done it over here. Now let's load the IMDb dataset. So here you'll be able to see I will be loading the IMDb dataset. So first of all, I'll just go ahead and use my max features. This max feature is just like your vocabulary size, right? So here I'll go ahead and first of all write my vocabulary size. I'm basically initializing my vocabulary size. Perfect. Then I will just go ahead and create my x_train, comma y_train values. Okay, I will talk about this particular dataset in depth. Okay, what kind of dataset is given, everything I'll be talking about. Then along with this, I will go ahead and write x_text, comma y_test. And if you go ahead and write this IMDb dot load data, okay, and I'll say based on how many number of words, what is my vocabulary size, right? So that is nothing my max features. So once I give this, I will be able to print the shape of my training and test data. Okay, so here I will just go ahead and execute it. So I'll say, hey, go ahead and print the x_test shape just to make you understand how many records we are actually playing up with, right? So here you'll be able to see that it will be downloading this entire dataset, and the training data shape is 25,000 records. Okay, so this will get downloaded in your local, and it will be staying in their cache memory itself. Then here you have your testing data, which is again 25,000 records. Okay, similarly for this particular sentence, you have these labels, right? It can be positive or negative. Now let's do one thing. Let's go ahead and explore this kind of sample reviews, what is there inside it, and what kind of labels is specifically present. Okay, so we will just go ahead and inspect sample review and its label. Okay, so here I'm going to write sample review is equal to x_train of 0. Okay, so if I'm taking x_train of 0, let's see first of all what is there in my x_train and what is there in my x_test. Okay, so in x_train you'll be able to see x_train of 0. In my first sentence I have this kind of words, and you remember this kind of words, when do we get it? I have already shown you with respect to the embedding layer, right? So if you go ahead and open this, here also you could see in every sentence I was getting this kind of words, right? So in short, this is nothing but it is a one-hot representation of every word, right? When I say one-hot representation, here you are able to see the index, right? So this is one sentence, okay, and as you know my vocabulary size is 10,000, so based on that you'll be seeing different index, and each index represents one word. Okay, so this is what you can actually get it. Okay, so I'm going to take this as a sample review. Okay, and let's see y of train of 0, y_train of 0. This will basically be 0 or 1. Okay, so here you can see it is 1. Okay, it can be 0 or it can be 1. 1 basically means says that it is a positive sentiment, 0 basically means it says a negative sentiment. Okay, so I will also go ahead and take my sample_label. Okay, and then I will go ahead and write y_train of 0. Now you might be thinking, Krish, how did we get this direct vectors, right? How do we get this indexes directly? This data set is put up in that way, but I will decode this and I'll try to show you what exactly is the real sentence also. Okay, now let's go ahead and print this. So I will go ahead and print. Okay, I'll say, hey, this is my sample review as integers. Okay, and here I'm going to specifically use this as my sample review. Okay, I'm just printing it. Similarly, I'll go ahead and print my sample label. Okay, so once I print both of them, you can see this is my sample review as integers. This is my entire sentence, and it is like very big, right? So that many number of sentence length is quite big, I guess. Okay, and the sample label is 1. Now let's do one thing. Okay, let's mapping of word index back to words, we need to do this. Okay, we will try to convert this just for our understanding. Okay, how do I do that? Okay, that we will try to see. So here I'm going to basically use word underscore index is equal to, I'll say, hey, go and use this IMDb, and I'll say, hey, get all the word index. How many word index are there? You just get it. Okay. So once I execute this, I will be able to see my word index. So this will basically be my word index. For this particular word, you'll be seeing this is the index. For this word, it is this index. For Nunari, this is this index. For Javani, all these words, I'm actually seeing the indexes. Okay. Now what I will do? Now, as you know, this word index is an dictionary, right? It is obviously a dictionary. What I will do, I will try to reverse. See, I can also reverse this word index. Okay, I can basically write first of all index information, and then I can go ahead and write this particular value. Okay. So for this, I will just go ahead and write this code. Please focus on this. And this is where dictionary comprehension will also come into picture. So here what I'm saying, for key comma value in word underscore index dot items. Okay. And then I'm saying, hey, write like this, value colon key for key, value colon key. Right. So value. So this is basically just getting reversed. Okay. So now, in order to see the reverse word index, I can also go ahead and print it if you want. So I will go ahead and print it, and this also will be able to see it. See. Let's see, where did it go? Okay. I will just try to print in this way. Just a second. Instead of using print, I will just use this. Let me comment this out. So this is how it is reversed. Okay. Now, what we are going to do is that we are going to probably from this particular keys, or from this particular keys, I'm trying to get all my reviews. Like let's say I'll consider this particular sample review. I'll get all my words. So 1 is over here. So for 1, what will be the word we'll try to see. Then I have 14 over here. Then for 14, what is the word I'll try to see. Okay. So when I check the documentation with respect to the TensorFlow, this was the code that is used. Okay. So here I'm saying reverse underscore word underscore get index. Okay. Over here, it is saying dot get I minus 3 comma question mark for I in sample review. See what it is doing. First of all, I'm going through each and every words in that sample review. Then it is taking this particular I. Right. So here you can see for I in sample underscore review. So first index I got, whatever index. Then over here I'm writing I minus 3. Okay, I minus 3. We're trying to get that specific index value. If you're not getting that index value, it will be just replaced by question mark. Okay. Now if I go ahead and see this decoded review, you'll be able to see this. See, initially I got question mark. It was 1. 1 minus 3 is minus 2. So when we are trying to search for minus 2 index, I'm not getting any value, so it is replaced by question mark. Then it shows this frame was just brilliant. So and so all the information is over here. This frame was just brilliant. Casting, location, scenery, story, direction, everyone really suited that part. They played, and you could just imagine being the Robert, and all this information is specifically there. So this is nothing but this is my decoded review, right? So initially this was my entire sample review, and we had completely decoded it over here. And this is just one sentence along with the text. Okay. So this is just to give you an idea from where this exactly sentence is coming. But for our sake, this step is already done. We are able to get this particular 100 representation index. We'll directly go ahead and use it. Just for your understanding, I've actually given over here. Okay. Perfect. So this was one of the basic information. What we did is that we loaded the data, we did all the things and all. Okay. Now let me just go ahead and use this from text from TensorFlow. If you remember, we have also imported something called a sequence, right, in pre-processing. Now, why the sequence will be very much necessary? Because here we are going to do the padding sequence. Padding sequence has been done by in embedding. Also, I showed you right how to do the padding sequence. We can use this padding underscore sequences, right? We can use pre and post. I'll also show you one example with respect to the sequences. Let's say the maximum length of my sentence, I'm just going to take it as 500. Okay, that can be the maximum text probably that I can have in my sentences. Now I'll go ahead and write x underscore train is equal to sequence dot pad underscore sequence, and here I'm going to basically write x underscore train comma max length is nothing but it is equal to this max length. So that's it's just like we are trying to apply pre-padding, right? By using this pad sequence. Similarly for x test, I can go ahead and write something like this. Okay, sequence dot this. This will basically be my x test. Okay, and let's say this is my x test. Okay, and here also I can go ahead and write my max underscore length. Okay, let's go ahead and display my x train now. So x train max underscore length max. Okay, here my feature is max underscore length. Okay, again I'm getting an error. Max underscore length. Okay. This should be, okay, I made one mistake. This parameter is max length. Okay. So once it is got executed, here you can see by default it is done that pre-padding. Okay. Pre-padding. Before zeros are basically coming up. So if I go ahead and see x train of 0, x underscore train of 0, here is what I'm actually able to get. See, initially all I'm getting is zeros, and then I am specifically getting all these values at the end. So pre-padding technique is basically applied. So this step is also done. Okay. Now, in the next step, we will go ahead and design our simple RNN. We will train our simple RNN. And this is what we are basically going to see in the next video. Till here, we have kept all the transformation technique that is required, and we are ready to probably use this entire inputs for training our simple RNN. So yes, I will see you all in the next video. Thank you. Hello guys, now we are going to create our simple RNN neural network, and then we will go ahead with training this entire training data, and then we'll be seeing that how we can also apply early stopping in this, and yes, there'll be a lot many things that we are going to do right now. So let's go ahead, and now first of all, in order to create our simple RNN, we will go ahead and create model equals to sequential model. So this is the first thing that I will be creating. As you know that in my sequential model, the first thing that I'm actually going to add is something called as embedding layer. So in order to add, I'll just go ahead and write model.add, and here I'm going to call my embedding layer. Inside this embedding layer, I have to give my vocabulary size, which is initialized in this max underscore features, and you know that I also have to use some feature dimension for my feature representation in the embedding layer. Let's consider that I'm going to use 128 features. For our dimension, right? Like how in the embedding we used some dimension over here, right? We represented 10, but since we have a very big data set, I'll just go ahead and represent it to 128. You can probably put different numbers also. It is up to you. Okay. Then finally, I'll also go ahead and give my input underscore length. Okay, and this will be nothing but my max length. Okay, max length, which I have already created. This is nothing but the length of the sentence. So this is nothing but it is our embedding layer, and this is responsible for taking all the words, converting that particular word into a vector of this dimensions. Okay, that is mentioned over here. Then we will go ahead and add a simple RNN. So for that, I will just go ahead and use simple RNN. This is also present in the layer section, and then inside the simple RNN, let's say I'm going to use 128 neurons. So this is the number that I have come up with. You can select any other numbers, and I've also shown you in ANN how you can go ahead and find out the optimal numbers, right? And here I'm going to use the activation function like relu. Okay. Finally, we'll go ahead and add a dense layer because I need to have only one output, and my activation function will be over here as sigmoid. Okay. So these are all the things that is available over here. Then we will go ahead and execute it. Once we execute it, you will be able to see my model summary. See, if I have a multi-class classification in the output layer, that many number of nodes, how many number of outputs you specifically want to have, and the activation function can be changed to softmax. That's it. Only that is the change that you really need to do. Now, if I go ahead and see the model summary, so this is how the model summary looks like, and these are the total number of parameters. Okay. Now quickly we will go ahead and create an instance of early stopping callback. right? Let's go ahead and do this. So first of all, I need to import from TensorFlow dot keras dot callbacks import early stopping. Okay, then I'm going to initialize this early stopping and I'm going to monitor. So I'll just go ahead and use this early stopping. I'm going to monitor my validation loss. So I'll go ahead and write val underscore loss. And here I'm going to use my patience. Let's say the patience, I'm going to use it for 5 epochs. And I'm going to say, hey, whenever you find the best validation loss or best accuracy one, you can restore the weights from there. So for that, I'll just go ahead and restore best weights to 2. So this is done. And this I will initialize it to my variable, which is called as early stopping. So let's go ahead and execute this. I'll go ahead and write early stopping. And this is my values. Okay. Now, finally, train the model with early stopping. Okay, so here I'm just going to go ahead and write model.fit. And inside this, let's go ahead and write my x underscore train, y underscore train, and then I'm going to use an epochs of 10. And finally, you'll be able to see that my batch size, the batch size that I'm actually going to use over here is 32, let's say. And finally, I have my validation underscore split. Let's say I'll say use 20% of that in the validation underscore split. And finally, I have my callbacks. And this callbacks, I can assign it to my early stopping. Okay, so whichever we have initialized. And all these things, we will keep it in history, the model history itself, and then we will go ahead and execute it. So here you can see some error. You must compile. Okay, I forgot to compile things over here. The reason is very simple. Okay, after this model.summary, I will just go ahead and compile it. The reason of compiling is that because I need to assign what is the optimizer function that I need to use. So I will just go ahead and write my optimizer is equal to Adam. Okay, and my loss, since loss over here is the loss that I'm actually going to use is for binary classification. So I will just go ahead and write binary underscore cross entropy. Okay, and you can go ahead and see the Keras APIs. If it's for multi-class classification, this will basically become sparse categorical cross entropy. And metrics, I'm just going to use my accuracy. Done. Now I'll go ahead and use my early stopping. And finally, let's go ahead and train it. Now this is obviously going to take some amount of time if you do not have a powerful machine. So I would suggest please go ahead and do it in Google Colab. I'm doing this in my local because I definitely have a very powerful workstation. I have NVIDIA RTX GPUs, so that is the reason I will be able to train it with a good speed because I have over here 25,000 records, right? So we will wait and we will wait till all the epochs gets completed, and then once this training is done, we will save the specific model and we'll see whether the accuracy is increasing or not. So here you can see loss is increasing, accuracy is also increasing. So I think after we complete this, we'll be able to get a good accuracy. And after that, we will go ahead and create a Streamlit web app. And then we'll try to see that how the prediction is basically done, as an end-to-end project. So right now epoch 2 is going on. It will take some time. So let's see. Let's wait for some time till this happens. Okay, I'll see you in some time. So finally, guys, you can see the training has got completed. It took somewhere around 8 minutes and 8.8 seconds. Okay, and these are the number of epochs. I was able to get a maximum accuracy. The training accuracy was somewhere around 94%, and the validation accuracy was that is 81%. If I probably go ahead and do another 10 more epochs, I feel that still the accuracy will keep on increasing. Okay, but I just wanted to show you till 10 epochs so that it won't take more time for the training. But initially, what I thought, so over here, please focus on this, right? So loss and accuracy. Initially, loss was shown as a very high value. I got worried. Okay, and then accuracy increased. Then you can see loss also increased. I think this is a kind of a glitch that has actually happened because after this, you'll be able to see the loss was in decimals in itself, and this was also getting decreased. Okay, but if you see with respect to validation loss, here there was no glitches as such. So from 0.59, we came back to 0.50, which is good enough. Okay, and we are able to achieve the validation accuracy of 81%, which is good enough. Now what I'm actually going to do is that I'm just going to go ahead and save this entire file. Now, in order to save this, I will just go ahead and say, hey, model dot or whatever models we specifically have, we can just go ahead and save it into the H5 file, right? So here I'll just go ahead and save my model file. Okay, I'll give you an assignment. You can also keep all these logs in your log folder and use TensorWord to probably display how we did it in the ANN. Okay, so here I'm just going to write model.save. Let me just go ahead and write simple underscore RNN underscore imdb dot h5 file. Okay, so once I execute it, so this particular file may have got saved over here. Okay, now quickly let's do one thing. Let's also create one prediction.ipynb file. The reason is very simple because I also need to create a Streamlit app right later on. So how to probably load this entire model, we'll be discussing about that. Now this will be very simple. First of all, I will go ahead and import all this particular libraries. So let's go ahead and import this datasets, reprocessing all these things. Now from this particular IMDb datasets, let's get all the word index. Okay, load the word index, and we also have this reverse word index. Okay, this also I've already explained you. Then we will go ahead and load our h5 file. Okay, model.h5 file. If you go ahead and see the model.summary. Okay, model.summary, you'll be able to see it. One more thing that I forgot to show you, right? That is how do you probably see model.summary? If you write, you'll be able to see the model summary. If I also want to probably get the weights, and I hope I've never shown you this, so here you can actually see all the configuration. If you want to probably go ahead and see get all the weights, so here are all the weights that is used with respect to the parameter. So this is also very handy. Sometimes we don't even save the file. That file, what we do is that we save the architecture, we save the weights, and then we try to combine it. Okay, so that we also can do. But right now, let's focus on this h5 file. Later on, when I get an opportunity, I will also show you that. Okay. Then we require two helper function. One is for decoding review. Okay, and one is for pre-process input. Now in pre-process input, what we do, we basically do the padding, right? Sequence.pad sequences. And here the max length is 500. I hope in simple RNN, what was the max length that we took, right? I guess it was somewhere around 500. So, yeah, I'm sure 500 only. Okay. So here this two will be my utility function. Okay, one is for decoding review and one is for pre-process text. Whenever the user input gives an user input, we have to probably take that particular word. We have to encode that entire review. We have to pad that review, and finally we get that padded review. Then only we'll be able to pass it right to our model. Now this is very important. We will go ahead and create our prediction function. Okay, prediction function. Now in this prediction function, you know that we have loaded the model, right? So I will just go ahead and write definition predict underscore sentiment. And here I'm just going to see the review. Inside this review, what I will go ahead and do is that, first of all, whenever I get the review, I have to probably pass through this pre-process underscore text, right? And I will give the review over here, right? Once I call this function, what is going to happen? All the padding is basically going to get applied. First of all, I'm going to get the encoded format for that particular review, and then we are going to pad all the sequence, pre-padding. So I'm going to probably get the zeros and ones that I want. Then I will go ahead and save this particular variable called as preprocessed underscore input over here. Okay. Then once we get this, I'm going to use model.predict and I'm going to pass my preprocessed input over here. Right. Once I pass this over here, I will be able to make my prediction. So once I'm able to make the prediction, I will quickly go ahead and write one very important condition. So I'll say, hey, I'll create a variable sentiment. I'll say, hey, positive if prediction of 0, 0 is greater than 0.5, else negative. Okay. And then we're going to return both sentiment and prediction, whatever values we are actually able to get. So this will basically be my function, which is called as predict sentiment. Okay. Now let's go ahead and see with respect to some examples. So this is my next step. Here I'm taking a review. The movie was fantastic, the acting was great, and the plot was thrilling. Okay. So this is my review. Okay. Now see this. As soon as I go ahead and pass my predict sentiment and I pass my example review over here, I'll be getting two values. One is my sentiment, comma prediction, right? Or I can just go ahead and write my score. Okay, sentiment and score. Now I will go ahead and make sure that print with the F string, and here you'll be able to see this. Okay, so I've got my example review, sentiment, prediction, score. If I go ahead and execute it, here you can see the movie was fantastic, acting was great, sentiment is positive, the prediction score is 0.811. So this prediction of 0, 0 when we are using, in short, we are getting the score, right? And this is greater than 0.5, so that is the reason we are getting positive. So in this video, we have saved the RNN file, we have loaded it over here. We got a very good accuracy with respect to simple RNN, right? And we're also able to make the prediction. Now the same thing, we'll try to create a Streamlit app, and then we'll create our entire web app, and finally we'll also go ahead and deploy our Streamlit web app in the Streamlit cloud. That I will be showing you in the next video. Thank you. So guys, now we are going to continue the discussion with respect to our end-to-end project. Already we have trained our simple RNN, we have saved the H5 file, we are also able to do the prediction. Now let's go ahead and create our Streamlit app. So here I'm going to basically go ahead and write main.py, and inside this main.py, I am going to write my code. Now with respect to prediction.ipy, it's almost similar like this, like there will be a decode review, there will be a pre-processed text. So we need to probably go ahead and combine each and everything. Okay. I need to also load my model itself, right? So let's go ahead and do it. So first of all, I will go ahead and import my model libraries. So let me do one thing. Let me quickly import all the libraries that I have. So here we are going to import all these libraries like IMDb sequence load model. Then I'm going to load the word index specifically for the IMDb because I need to convert that based on our decode review. So basically all the reviews need to be converted into vectors. So that is the reason we require index, and that we will be specifically getting from this particular word index, right? Along with these two helper functions that I have actually shown you. We can also create this in another file and call this particular file, but let me just go ahead and put it over here so that it will be easy for you to refer. So here I have my decoded reviews, here I have my pre-processed text. Now finally, this is important. We will go ahead and create our step 3 will be creating our prediction function, right? Now inside this prediction function, I've already shown you what we basically do. So if you go over here down, this is the prediction function, right? Predict sentiment. So I'm just going to copy this same thing, okay? Model.predict positive. If this is, then we are going to return this. So the same thing will also be pasted over here, right? So this basically becomes my predict sentiment, right? Now let's do quickly one very important thing in this is that when we are probably using our Streamlit, so Streamlit app needs to be providing some input boxes, some buttons and all, right? So we can go ahead and do that, all the things over here, right? So quickly, I'll keep this predict sentiment and let's see whether we'll be requiring it or not. So I will go ahead and design my Streamlit app. Okay. So first of all, I'll go ahead and write st.title. So quickly, first of all, I'll also import Streamlit as st. Okay. Then I will just go ahead and give my title and some information over here. So I'll give a text which says IMDb movie review sentiment analysis. Enter the movie review to classify it as positive or negative. Right. So this is there. Then we will go ahead and create a user input by again using Streamlit. So for that we use st.text area and this will be my movie review. Then what I'm actually going to do is that I'm going to probably go ahead and create one button. Okay. And if I click this button, this classification should basically happen. Now when I'm giving this user input, first of all, once we click this particular button, it should be passed to our preprocess underscore text function, and here I will just give my user input. Through this, we will be getting our preprocess underscore input value, right? So this is how we will be getting this preprocess underscore input value. Then here, the next step will be that I will go ahead and make my prediction. Now this prediction, I'm going to basically use prediction is equal to model.predict, and here I'm going to use my processed underscore input. Okay, so this processed underscore input, I'll just keep a spelling which looks like this. Okay. Then once we get the specific input, then I'm just going to go ahead and calculate my sentiments, and sentiments will be nothing but here we're going to use this positive or negative, right? If this is greater than 0.5, that's negative, I'll say. Then we will display the result in my Streamlit itself. So we will go ahead and write st.write, else st.write, right? So here let me do one thing, okay? So here this else should be here, and here I will go ahead and write. So here I'll say if I go ahead and click the classify button, so I should basically do the prediction of this processed input. I should be getting a sentiment. I will probably display the sentiment in prediction. Else if I don't click it, it'll just give me a message saying that please enter a movie review. Okay. So this is done over here, and you can probably also display how the sample review should look like, right? Sample reviews also we need to probably display. So that is the reason we are using this decode review and preprocessed text over here. So let me do one thing. Let me just go ahead and run this. And I think we have almost done each and everything, right? If you want, you can also display your sample review below. You can just write st.write, hey, this should be a sample review. That is one way. But here, in short, let us revise what all things we did. We imported all the libraries. So here is my word index that I'm actually able to get. I'm reloading my H5 file. So let me just rename this H5 file like this. And then here is my helper function of decode review. Here is my with respect to preprocess input. So this function is basically just giving you the vectors with padded sequence, right? Not indexes with padded sequence. Then this is your prediction function. I have not even used this prediction function. I can also use it over here, but I have written it. So let me just remove this over here. Okay, I don't require it. Then we are importing Streamlit. Then we have created a text area. We have created a button. If you click the button, it should probably predict it and give you the sentiments. So finally, guys, now we're going to run this and see that whether everything is working fine or not. So I'll just go ahead and open my terminal. Please make sure to go to the simple RNN folder. Then only you'll be able to execute it because as you know, I've also created simple RNN. Similarly, when LSTM will be working, we'll create another folder. And we will be working in the similar way. Okay. So now here, what I'm actually going to do is that I'm just going to go ahead and write Streamlit run main.py file. Okay. So here is my URL that has been loaded. Okay, let's do one thing. I've already created in my prediction.ipy and be some text and all we have used, right? I'll copy that same text. This movie was fantastic and so thrilling. Okay, and then we will try to use this. Let's see. So quickly here I'm going to copy and paste it. This movie was fantastic. The acting was great. And the plot was thrilling. So once I classify it, you'll be able to see, wow, this looks good, right? My sentiment is positive. Prediction is 0.811. Let's go ahead and write something. The movie was scary. I did not like it. but the critics is good, right? We'll just go ahead and classify it. So sentiment it shows positive because it does not care about my feeling what exactly it is, but the prediction score that I'm able to get is 0.85, which is good enough, right? Now the next step is that you can go to the Streamlit Cloud, okay, and do the deployment. I've already shown you how to probably do the deployment. So this will be one assignment for you. Go ahead and upload all the files in your GitHub, and from here you can just go ahead and deploy in the Streamlit Cloud. Again, I'm going to keep this as an assignment, guys, but I'll not be uploading that specific video. So I hope you like this entire session wherein we discussed about so many things. We discussed about how to probably create or work with RNN. Again, completely end-to-end projects from embeddings to training a simple RNN to creating this H5 file. Everything we basically did, right? So yes, this was it from my side. I hope you like this particular video. I'll see you in the next video. Thank you. Take care. Bye. Hello guys, so we are going to continue the discussion with respect to NLP and deep learning. And in this video, we are going to see about a new variant of RNN, which is called as LSTM. LSTM is nothing but long short-term memory RNN, okay? Now, already in our previous video, we have discussed about RNN, and we also understood that RNN is not able to solve long-term dependencies, right? And that is where we got to know about something called as vanishing gradient problem, right? We got to know about this. Now, in vanishing gradient problem, whenever we had a long chain rule, at that point of time, what was happening? Whenever we are trying to find out the derivative of one output with respect to the other output, at that point of time, I was getting smaller values. So whenever we had a very bigger chain rule with respect to time, the value was approximately equal to 0. Okay. So that all things we discussed in our previous video. Now, again, I will go ahead and revise some important questions. So first of all, I will say again, I'll talk about the problems of RNN in this video. Okay. Then we will discuss about why LSTM RNN instead of directly using RNN. So this is the second topic that I will discuss about. Third thing, we will just how LSTM RNN is solving the problem, right? So here, two important topics we'll be talking about. One is what is this long-term memory, and then we'll also be talking about the short-term memory, right? Short-term memory. Along with this, then in the coming videos, we will be seeing the LSTM architecture, and finally we'll see the working of LSTM. Okay. Fifth will be working of LSTM with examples. Now, everything we'll be discussing, but before I go ahead, I really want to quickly give an amazing shout out to this amazing blog, which is called as Scholar's blog. Again, this blog, if you probably go ahead and see who's the author over here, he's an amazing author, right? His name is Jay. Okay, and definitely do check out this particular blog again. Because from here, I will be taking most of the diagrams, because here all the diagrams are given much more in an amazing way to make you understand, right, about LSTM. Again, a quick shout out to this amazing blog. The credit goes to this. I'm giving the proper credit, and I will be referring to this particular blog. So let's go ahead and let's start our session with respect to LSTM RNN. So guys, now let's go ahead and discuss about the basic problems with RNN. And already I have discussed this in our previous video, but here I will try to give you some more examples. Okay. So let's say that I am planning to predict the next word in a sentence. Okay. Next word in a sentence. So this is my task that I really want to do. Okay. Now with respect to this particular task, let's say one of the examples that I have actually taken, let's say my sentence is something like the color of the sky is dash. Okay. So I have to predict this particular word. Now you know that in order to predict this word, let's say the answer is blue. Okay. I'll just go ahead and write the answer is blue over here. So the color of the sky is blue. Now when we need to predict this particular word, you know that we don't need further context, based on the previous word, right? So based on this particular word, since as we know that, right? Obviously the color of the sky is blue, right? So this word is mostly proportionate to this, has a dependency to this particular word. And obviously to get the output, we don't require any further context. Any further context, that basically means there's no dependency on other word over here, right? Since we are talking about the color of the sky is blue, you can see that the sentence is also very small. And when in terms of dependency, let's say there are two words there that are dependent to probably find out the output. One is sky and one is color. The gap between this particular word is also not that long, right? So obviously with the help of RNN, we will be able to solve this problem, and it will even not face anything like vanishing gradient problem. So vanishing gradient problem will not be there, right? But if I take one more example, let's say I will go ahead and write something like this. I grew up in India, and let's say there's some more text over here. And then finally I say I speak fluent Hindi. Okay. Now here you can actually see, obviously just by seeing this, right? And let's say this is what I really want to find out. This is what I really want to find out. I want to find out this specific word. So this is the word blank that I really want to find out, the next word. Now just by seeing this, you can see, okay, fine. If I probably go ahead with this entire sentence, obviously a word that should come over here should be a name of a language. Let's consider it should be a name of a language, right? But which language, right? There are different languages that actually exist throughout the world, right? So obviously it requires some more further context. Now in this case, the context that it requires may be the name of the country, right? And as I said that this sentence, I grew up in India, this probably came at the first, and then we had a lot of sentence, and then finally we ended with I speak fluent, whatever language over here it is, right? So obviously this word is dependent on this particular context, right? And obviously you can also see that there is a long-term dependency, because there is a huge gap. There's a huge gap between the output that I want to find and the word which has its further context. So there is a huge gap over here. So in this particular scenario, so here you could see that if I just take this as an example, okay, so I will just go ahead and probably take this as an example over here, and I will write it over here. The reason is very simple, because this is the architecture that we are looking at, and similarly over here. Okay, let's go ahead and probably do this. Right? So here the problem was very simple, that whenever I was trying to perform a task, okay, whenever I was trying to perform a task over here with respect to this, so just imagine that I want to find out this particular output, and there is a dependency on this particular word to probably find out the output, right? So here the gap is less. So when the gap is less, so the dependency, and it may also not be probably requiring any further context. It is just directly dependent on this word or this word, right? And it is being able to find out the output. But if I have something like this kind of scenario where there is a huge gap between the output and the further context word that is required, right? Like in this scenario, let's say I want to predict this, I want to predict this, right? But this is completely dependent on the first initial word. And here you can basically see that there is a huge gap. when there is a huge gap, I can basically say, hey, there is a long-term dependency. And obviously, RNN cannot solve this, right? RNN cannot solve this long-term dependency. And it's very simple. Why? Because it faces this problem, which is called as vanishing gradient problem. In vanishing gradient problem, what it does? It basically says, hey, whichever is the nearest word to this, like let's say this word is nearest, this can really change the weights and it will be much more responsible in finding the next word, right? But if we see the words that came earlier at t is equal to 1, at t is equal to 2, this word, because of the huge gap that is present over here, right? The huge gap is between the relevant information, right? The output that we really need to find out, and with respect to the further context. Further context basically means it is having some kind of dependency on this particular word. So there is a huge gap, right? So this kind of scenario, what happens? Vanishing gradient problem is basically faced, and there the updation of the weights will not happen, because whenever we try to find out the derivative loss with respect to derivative words at this particular timestamp, right, the weight will be, there will be some value, but at this particular timestamp it will be approximately equal to 0, right? Why? Because the derivative of a activation function that we are specifically using is between 0 to 0.25. Let's say in the case of sigmoid, in the case of tan h, it is 0 to 1, right? And whenever we use this in derivative, chain rule of derivative, right, it will be a big rule. It will be a big chain, right? At that point of time, that value will be approximately equal to 0. That we discussed in our previous video, right? So I hope you understood this. And this problem that I would definitely like to say is something called as long-term dependency. This is the problem that is basically faced with RNN. And I was taking one example. If this is a smaller sentence, and let's say this particular word is just dependent on, the nearest word, the gap is not that much, it will not require any further context, right? So I hope you got an idea what was the problem with RNN. And obviously in our previous video, we have discussed about the vanishing gradient problem, mathematical intuition. Now let's go ahead and see how LSTM RNN solves this problem, okay? So before I go ahead, this on the left-hand side is a basic representation of RNN, okay? Now, here you'll be able to see that, okay, this is with respect to t is equal to t minus 1, this is t is equal to t. You just consider if I give some numbers, right? So let's say this is with respect to t is equal to 1, t is equal to 2, and t is equal to 3, right? We are passing some information. And over here you can see that the previous output from the timestamp is combined along with the input, right? Here there will be some weights that will be assigned. So if you really want to just see this, it will be looking something like this, right? This is the same thing that we discussed, right? So I have a neural network, RNN neural network, which looks like this, right? So I'll just take this as an example. So what exactly this is, right? So at timestamp t is equal to 1, I'm passing this information. Over here also we'll get some kind of information. Here there will be some weights that will be assigned. We've spoken about this. This will be my input weights, right? Here we are going to pass xi1. This will be xi2. This will be xi3. Again, I'll be having w5, and here it will be t is equal to 2, here it will be t is equal to 3. Okay? Now just imagine when we are passing this inputs along with the weights, I will be able to calculate my O1 over here. And this is nothing but this is my O1, right? I'm passing this information to my next timestamp, right? Over here. Now what will happen? This will be assigned with another hidden neuron weights, other hidden weights, okay? And this both are basically getting combined over here along with the weights. And then on top of it, you apply a tan activation function. And finally, we get an output. So this is my h of t, right? And I'm also getting an output over here, which is passed to the next state. And same representation is basically used, okay? Now, if I go ahead towards the LSTM RNN representation, see guys, nothing is different. So this is the same thing like what we discussed, because internally over here inside this hidden layer within each and every neuron, we basically apply tan activation function or sigmoid activation function, right? So here it is basically given as tan activation function. Okay. Now if I talk about LSTM RNN, so this is what is the generic representation. Okay. So don't get worried. Like it looks really complex when compared to this. I'll break this down each and everything as we go ahead. But just to give you a smaller idea, what exactly is done by LSTM RNN. Okay. So let's say this is my RNN. This is my RNN over here. Now with respect to this RNN, okay, when I'm passing this information, okay, see RNN usually has this short-term memory. Okay, it has this short-term memory. So since we know that whenever we work with RNN, how is the generic representation? It looks something like this, and there is a feedback loop. Okay, this feedback loop is specifically for short-term memory. Okay, short-term memory. Now with the help of LSTM RNN, what we are doing is that we are also adding a LSTM memory. Sorry, we are also adding long-term memory. Long-term memory along with the short-term memory. Now we know that in RNN, already short-term memory is there. That is this particular feedback loop, right? In RNN we know that, right? So this is this line that is specifically going to all the other hidden neurons. This is nothing but your short-term memory. But what about long-term memory? So over here, the long-term memory is added something like this. There will be a big line, and how this line will be like, this line will be like, I hope everybody has visited airport, right? So in airport, you'll be seeing something like a conveyance belt, right? Conveyance belt basically means where you specifically put luggages, right? Luggages. So there will be a continuously moving line, right? Whenever an airport arrives, people will start, the worker will start putting out the luggage over here. And when it reaches here, let's say there are some human beings, they'll take out the luggage from here, right? They'll take out the luggage from here. So this is with respect to all the human beings who are specifically using it. Similarly, in LSTM RNN, there will be this long-term memory. Long-term memory. And the main work of this particular memory is to just make sure, add what context is required and remove what context is not required. Okay. So in this particular case, let's say if I take this particular example, I grew up in India, I speak fluent this, right? So here you'll be able to see when we pass with respect to time, xi1, xi2, xi3, like this, when we go ahead and pass. As soon as we talk about India, right? Let's say the word over there is India, and we need to predict what is the language that I speak. Okay. So whenever till the context is, see this memory cell will make sure that it will maintain the context till whenever it is required. Whatever information is specifically required, it will store over here. If it is not required, it will be removed from there. Right. That is what is the main importance of memory cell. So that if I really want to predict this particular word, this India context will be saved in this long-term memory. Right. Even though the information is not there in short-term memory. See, in short-term memory, if I probably consider the same sentence, first of all, I will go ahead and give my word I, then grew, then up, right? In India. Now, once we went to India, over here some other sentence came. So the context switch has actually happened. So what will happen? We'll forget all this information, right? But I know that we are going to go ahead and probably this sentence is going to come, I speak fluent in so and so, right? So what memory cell is going to do, it is going to save this India word, or it is going to save this context in the memory cell, right? So finally, when it comes like I talk in whatever language it is, it will go ahead and check in the memory cell what all information is specifically there, right? And if that context is available, based on that, we will do the predictions, right? So this is just like a book of library, okay? And obviously, we as a human being, right? If I tell you, hey, let's say I am learning, I'm studying something, after some time I forget something. So what I do, if I want to probably refer that, I will remove the book from this particular shelf and I will try to go ahead and revise it, okay? And then whenever I do not require, I may forget it, right? I may just remove from my memory because it is not important. But when exam day comes, I really need to remember all these things. So this is also like my brain cells, which we also call it as memory cells, till what extent we can basically remember, right? And sometimes based on the further context, based on the exams, based on the test, I need to know like how much things I really need to remember, right? So that is the entire funda about LSTM. I've just given you an idea. So this is basically called as a memory cell. I will be discussing more about it because in the next upcoming videos, we will break down this entire architecture and we'll see how it is probably solving this long-term dependency, right? So I hope you understood this specific video. This was it from my side. So in this video, we have discussed about LSTM, what is the problem over here, why LSTM RNN, okay? And we have also seen the basic representation of both LSTM and RNN. Now in my next video, I'm going to talk about how RNN works. I give you an idea that, okay, we will be having a long-term memory separately, we'll be having a short-term memory. Whichever information I need to store for a longer period of time, I'll put that information in long-term memory. Whichever I do not require it, I'll remove it from the long-term memory, okay? And whenever I need to reuse it, I will go ahead and reuse it, okay? So yes, let's go ahead and discuss about this in the next video where we'll be talking more about how LSTM RNN works. Thank you. Hello guys, so we are going to continue the discussion with respect to LSTM RNN. Now let's go ahead and understand about the entire architecture initially, then we will break down this into topic by topic and try to understand that how does an LSTM RNN work, okay? So the basic architecture representation which we saw in the previous video was this one, okay? And here you could see that, okay, I have this x of t is nothing but it is the inputs which is passed with respect to time, like t is equal to 1 word is passed, t is equal to 2 other word is passed. If I probably expand this architecture, so we go to this particular next stage, the entire LSTM RNN has this 3 important gates, okay? One is the forget gate, okay? Now if you tell me which part is basically the forget gate, I will probably say from here to here. So if I divide this into 3 layers, let's say this is my first layer, okay? I'll not say layer, but first part, okay? So this entire part is all about forget gate. Then the next important gates that I have is something called as input gate and candidate memory, okay? So this is my second part. And the third part is basically output gate. So a single hidden neuron, right? A single hidden layer neurons with respect to our LSTM RNN has these 3 important gates. One is the forget gate, then you have input and candidate gate, candidate memory, and then you have this output gate, okay? Now let's go ahead and discuss more about this. So here, let's discuss about this entire parameters, okay? So here in the first instance, I'm giving my input over here, x of t, again with respect to timestamp I'll be giving. This ht of -1 is the hidden state of the previous hidden neuron, right? When I say previous hidden neuron, let's consider this as my neuron, right? So you know, with respect to neuron, in our case, right, a simple RNN provides one feedback loop, right? But in the case of LSTM RNN, we'll also have another feedback loop which will act as a long-term memory. This is basically a short-term memory, and this is nothing but this is a long-term memory. So long-term memory. So when I say ht-1, this is nothing but it is the hidden state with respect to short-term memory of the previous timestamp, okay? So here you can see I'm giving input x, then I'm giving ht of -1, that is nothing but the previous hidden state. Then these are both combined, then we pass it to the sigmoid activation function, and all these kind of operations will happen. Okay, we'll discuss one by one and what exactly it is. Okay. Now before this, with respect to every diagrams that we see, right, there's some notation that is specifically used over here. So let's consider this. Okay, this is basically a neural network. I will talk about, see, whenever you find out something like this, here sigmoid is there, here tan h is there, here sigmoid is there. This is basically called as a neural network layer. Okay, so this is specifically called as a neural network layer. What does the neural network layer basically mean? Nothing. Here you can just consider that it is one of my hidden neuron, hidden layer neuron, which has some neurons over here. And in all these neurons, we have applied a sigmoid activation function. So I have just applied a sigmoid activation function. And here we are giving the input. Okay. So if I probably consider this as an example, so here I'm taking the input x of t, and there's also one more input ht-1. We're giving both of them. First of all, we're combining this, and then we are giving it. Okay. So if I probably want to write this particular diagram in a better way, so I can say, hey, this is my ht-1, this is my x of t. I will take this input, I'll combine it together, and then I will send it to my hidden neuron. I'll send it to my hidden layer, which will specifically have this input nodes, this hidden nodes, and on top of that, I'm applying an activation function. This is what it looks like if I probably expand this. So over here, this entire thing, when we say we have this kind of notation, right? This is nothing but this notation. It is basically a neural network layer. We will discuss more about it as I keep on expanding, and once we go ahead and understand each and every gates, we'll be able to understand. Then the second one is that you'll be able to see this pink color operations. The pink color operations that you have over here. Let's take that particular color. I will try to find the pink color over here. Okay. So light pink, okay, dark purple, pink. Okay, let's go ahead and do this. So let's say there is one operation which is like this. This is nothing but this is called as a point-wise multiplication operation. And if I have this kind of operation, this is nothing but point-wise addition operation. Okay. And one more that you'll be able to see that something called as tan h. So this is nothing but point-wise tan h operation. Now what does this basically mean? Let's say if I have two vectors, my one vector is 1, 2, 3, and my another vector is 4, 5, 6. Let's consider that this is my x of t, or this is my ht of -1, or let's just consider this v1, v2 vectors. If I say point-wise multiplication, that basically means we are just going to take each and every number position-wise, and we are just going to multiply it. This is basically called as point-wise multiplication. So if I say point-wise multiplication, if I perform this, here I'm specifically going to get, let's say, if I probably say this, I'm basically going to get one vector, which will be a multiplication of 1 multiplied by 4, 2 multiplied by 5, and 6 multiplied by 3. Okay, so this is nothing but this is a 80. If I talk about point-wise addition, that basically means my output will be nothing but 4 plus 1, 5, 5 plus 2, 7, 6 plus 3, 9. And if I probably apply tan h as my point-wise operation, so here you'll be able to see, I will just go ahead and, we'll take one vector. Let's say for this particular vector, I'm applying tan h. So in short, we are doing tan h of 1, then we have tan h of 2, and then we will go ahead and calculate tan h of 3. So this is what we are specifically doing. And this is nothing but it is basically called as a point-wise operation. Okay. So I hope you got an idea with respect to point-wise operation. Any arrows that you'll be seeing over here, this is nothing but this is called as vector transfer. We're just transferring the vector. So let's say in this line, we're just transferring the vector from one state to the other state. Okay. Then similarly, you'll be able to see concatenate. Concatenate. What does concatenate mean? So let's take this as an example. Okay. So here you can see I have I have this scenario where ht minus 1 and x of t is there, and these are basically getting concatenated. Concatenated is like combining two vectors. Combining two vectors. It's not like adding two vectors, but I'm trying to combine. Let's say my ht minus 1 is represented by a 3-dimension vector, like this 1, 2, 3. And my x of t is a 3-dimension vector, 2, 3, 4. Now, if I say I'm combining, that basically means this is what in short is basically happening when I'm combining. In short, what I'm doing, I will just combine these 3 vectors like this. So this will be my ht minus 1. Okay. Along with this, I will go ahead and use my another vector, x of t. Right? And then I will send this as an input to any other neurons. Right? So this is what we are specifically doing. So when we say combining, we are combining them together, and then we are sending it to the hidden layer. Let's say this is my hidden layer. Okay, this is what we are trying to do. Okay, when we say combining two vectors, right, and that is nothing but concatenate. Okay, now similarly, copy basically means we can copy one vector to the other. Let's say there is one vector, then we can also make a duplicate copy of that. Duplicate copy. Okay, so these are some of the operations that we will be seeing with respect to the LSTM architecture. Okay, now let's go ahead and let's first of all discuss about some of the important points. Okay, now the first line that you'll be seeing on top of it, right, this line. This line is basically called as something called as memory cell. So here I will just go ahead and write this as memory cell. Now what does memory cell basically means? This is for my long-term memory. Whatever information I want, I will be saving inside this. Whatever information I don't want, I'll be removing from this. That is the main task of this memory cell. Okay. Till now, just get to know about this. CT minus 1 is nothing but the memory cell of the previous timestamp, and CT is nothing but after we are removing some context, and adding some context, After that, whatever state of this memory cell will be, it will be C of t for that particular timestamp. Okay. So I hope you are able to understand these basic things. Now it's time to understand how this forget gate works, how this input and candidate memory gate works, how this output gate works, and how the entire LSTM RNN works. We'll be discussing about that. Okay. So the first gate that we are going to discuss about is something called as forget gate. Okay. And this is what we are going to discuss in our next video. So we'll take this as an example, and here I will break down each and everything. How does that forget gate work? So in short, in our next video, we will be discussing about this stage, right? This stage, which is highlighted over here. And here also you should be able to see that I am giving this information. This should also be considered. Okay, this entire operation should be considered. This is my CT minus 1. Okay, as I said, HT minus 1 is the hidden state. So let me just go ahead and write some of the notation. HT minus 1 is the hidden state of previous timestamp. Let's say t is equal to 1, and right now we are working at t is equal to 2. X of t is nothing but word passed as input in the current timestamp. Okay, and here we are concatenating it. Okay, now let's go ahead and discuss about this forget gate in our next video. But till here, I think you've got a basic idea about the entire LSTM architecture and some of the important points which is basically mentioned in this diagram. So yes, this was it from my side. I'll see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to the LSTM, working of LSTM RNN neural network. Now in this video, we are going to discuss about the forget gate, which is the first and foremost important component in the LSTM RNN. Okay. Now, yes, we are going to discuss about this. We have already discussed in the previous video. We gave some example, what is the importance of this memory cell, then we understood what each and every operation is doing, right? Everything we discussed. Now let's go ahead and discuss about the forget gate. Now let's focus on this part. Okay. Let's focus on this part. So on the left hand side of this part. Now what is exactly happening over here, right? Let's consider that I am probably doing a functionality. I'm trying to solve a use case which has text, and we need to predict the next word. Okay. Let's say right now for every word that I have over here, right, let's say this is x11, this is x12, this is x13, x14, and this is my next word, which is nothing but my y word specifically. So this will be my y15. Okay, this will be my output. Now for every word, you know that we have to convert this into vectors, right? So let's consider that x11 or any word that we are going to use, we are just going to use it with the help of 3 or 4 vectors. Let's say I'm going to probably represent every word with 4 vectors. Let's say it will go like 0, 2, 4, 6. So this is my first word vector. The next word vector can be 4, 5, 1, 2. Okay, I'm just defining. Okay, and these are the vectors that I'm actually going to give with respect to timestamp. Okay. Now let's focus on this operation. Okay, let's focus on this operation. So guys, now let's take this first step, and I will show you like how in terms of neural network it will look like. Okay, so let's consider this x of t I've taken as 4 dimension. Now let's say that okay, it is every word we are just going to represent it with 3 dimension. Okay, so here is my 3 dimension. Every word that I'm representing is with respect to 3 dimension. I may use any technique, and that is what I'm going to pass in the LSTM RNN. Okay, now when we say x of t and ht minus 1, now when we say my x of t is represented, each and every word is represented by 3 dimension. So you will also be seeing that this will be my x of t. You'll also be seeing my ht minus 1, which is the hidden state of the previous neuron, right? This will also be a 3 dimension. Okay, this will also be 3 dimension. Why I'm saying it will be 3 dimension? Because later on when we do this entire calculation, right, I'm just saying that this is the previous state, right? I'll be getting 3 dimensions. We have to take 3 dimensions, and you'll be able to understand it. Why I'm saying this will be 3 dimensions. Can't it be 4 dimensions? Yes, it can be. See, I will just go ahead and write it over here. Let's consider. Okay, my ht minus 1 is also 3 dimension. Let's say 1, 2, 4. Okay, I can also have 4 dimension. I can also have 5 dimension. But if I have ht minus 1, which is the previous hidden state as 3 dimension, then what you see over here as a memory cell, this ct minus 1 will also be 3 dimension. And let's put some values. Okay. In order to clear the confusion, let's consider that I'm going to use my word with 4 dimension. Okay, 4 dimension. Every word I will just go ahead and use it 4 dimension. And let's say if in our previous state my ht minus 1 is 3 dimension, then my ct minus 1 will also be 3 dimension. Why I'm saying this? Because we'll do the calculation. Every calculation will be shown to you. Okay. Now let's take this xt and ht minus 1, and we are concatenating over here. What does concatenating basically mean? So I'll take this as this input. So this will be my input. Let's say input words that I'm giving. I know first of all I need to give ht minus 1, right? So this is my ht minus 1. Now in the case of ht minus 1, as I said, this is 3 dimension, right? So I'll be having 3 inputs that I will be giving over here, and then you have the next one that I'm passing xt. since we are concatenating it, I've already told you we have to combine this, right? So concatenating basically means I'm going to combine ht minus 1. Along with this, I'm also going to combine my xt. Now xt, I will just give this as 4 dimension. 1, 2, 3, 4. So this is for every word, right? So at t is equal to 2, let's say I'm passing this information. ht minus 1 basically means at h1, the previous hidden state, I'm getting these values. So this 3 dimension is specifically coming from ht minus 1, and this 4 dimension are basically coming from my x of my current word in this time stamp. Okay. When we concatenate like this, that basically means we are just combining it. Okay. We are just combining it. Perfect. Till here it is fine. Now this basically becomes my input. Okay. Now in the next layer, once I go ahead, there is a neural network. Now when I say this is a neural network, in short, what I'm actually going to do is that I will be having this kind of hidden layer, okay, where neurons will be there, hidden neurons will be there, okay. It can be 2 hidden neurons, it can be 3 hidden neurons, it is up to you. For right now, let's consider that I'm just going to use 3 hidden neurons, okay. So I'm just going to use this 3 hidden neurons, okay. So in this hidden layer, I'm having this 3 hidden neurons. And top of this hidden layer, what is basically getting applied? An activation function is getting applied, okay. An activation function is basically getting applied in every hidden neuron, and that is what it looks like, right? So I'm just applying an activation function on top of it, okay. And in all this neurons also we'll be having bias, okay. So till here it is very much simple. Now what I will do, I will just go ahead and combine every node which looks like this, okay. So here I'm just going to combine this, okay. I'll combine this to, let's say this is here, again you can combine each and every layer, it is up to you, okay. And you can complete this diagram. So this mostly becomes like a simple connected neurons, right? So this is my input, this is my hidden layer. Now once you apply the activation function, then what we are going to get, we're going to basically get f of t, okay. So in short, this part that you'll be able to see, which is called as forget get, I have changed into something like this, and this is the entire operation that is probably going to take place. Now let's understand how many weights is basically getting assigned. So here you'll be able to see how many inputs I'm giving, 1,7. That is 1 cross 7, right? So this will basically be 1 cross 7 because 1 row 7 inputs. And then with respect to this, since I have three neurons, hidden neurons in this hidden layer, so this is basically going to be 7 cross 3. Right, 7 cross 3 weights, right? This will be my 7 cross 3 weights. And once I perform this particular operation, if I do this entire dot operation, so it will be 1 cross 7, dot 7 cross 3, which will be nothing but here, this 2 will get combined, so I will finally have 1 cross 3. So that is the reason this f of t that you'll be seeing is that I will be getting a output dimension of 1 cross 3, right? 1 cross. This is what we are basically getting. Okay. Now you can understand why I basically took ct minus 1 as 3 dimension, ht minus 1 as 3 dimension. When this is 3 dimension, this has to be 3 dimension. And just by doing this calculation here, you can see that I'm able to get 3 dimensions, right? If this is 4 dimension, this also has to be 4 dimension because based on the calculation, it will happen in that way, right? So here my f of t, what I've done is that I've able to find out this output vector, which will be of 1 cross 3. Okay. Perfect. Till here, I think everybody has understood this forget get operation. Now going forward, you'll be able to see that there is a pointwise operation. So here, if I go ahead and take this forward, there is something a pointwise operation. Now this pointwise operation is along with a cell ct minus 1, which is with my memory cell. And ct minus 1 is the previous memory cell information that we are getting with respect to ct minus 1. Now once we do this point operation, what does this point operation basically mean? Whatever vector we are getting, we are doing a pointwise operation with the previous cell state. Now what does this mean? Let's consider this. From my previous cell state, I get this information ct minus 1. And let's say I have some values like 6, 8, 9. Okay. Now when we do this pointwise operation, pointwise multiplication operation, okay, and let's say my f of t that I have actually calculated is something like 0, 0, 0. Let's consider like this. Okay. So what we are doing, we're basically doing a pointwise operation with 0, 0, 0. Okay. Now what does 0, 0, 0 basically mean? 0, 0 basically means that whatever operation we are doing over here till finding this f of t, I'm saying that now let's concede that the complete sentence context has been changed. Now when the complete sentence context has been changed, and let's say I'm getting the value 0, 0, 0. This is the value that we are getting. What does this basically mean? Once we do the dot operation, here, the previous context, whatever was present, we are just making it entirely to 0. That basically means we are removing all the previous context. Now here you know that when we apply Sigmund activation function, it will give you an output between 0 to 1, right? It is going to give you an output between 0 to 1, right? And let's say I got all the outputs to 0. And if I'm getting outputs to 0, that basically means whatever operation we have done, right? And with respect to the new sentence, the complete context has been changed. So I have to remove all the context that is already remaining in the previous cell state. Okay. Now similarly, let's go ahead and consider that if my f of t is 1, let's say if my f of t is completely 1. Now if I do the dot operation, so this is my first scenario. Now this will be my second scenario. Let's say my ct minus 1 is nothing but 6, 8, 9. Now if I do this pointwise operation with 1, 1, 1, what I'm actually going to get? I'm going to get the same vector 6, 8, 9. So this actually means that I am not going to remove anything from here. From the ct minus 1 memory cell, I'm not going to remove anything because all the context is important for me. Okay. Now similarly, I may also give you another scenario. Let's say if I go ahead and say my ct minus 1 is 6, 8, 9. Now I'm going to do a dot operation with, the dot operation will be with, let's say 0.5, 1, 0.5. Now when I do this dot operation, what does this basically mean? So 6 divided by 0.5 is 1 by 2 is 0.3. 8 divided by 1 will be 8. 9 divided by 0.5 will be 4.5. Right? Sorry, 0.5 will be 4.5. Now here it says that from the memory cell, I'm removing some context from this vector and some context from this vector, but I'm not removing any context from this vector. Right? So in short, what we are doing by this operation is that we are adding some information or removing some information. Sorry, I'm not adding some information, but I'm removing some information out of it. Right? I'm not adding over here, but I'm removing. Right? Removing some kind of information. So that is the reason this is entirely called as forget get. So the conclusion with respect to forget get is that here, based on the context, this forget get will let go some information or will not let go some information. And that is what is all about forgetting information. It is making to forget some of the information based on the context, right? And this is how you basically understand about forget get, right? So I hope you were able to understand this entire LSTM architecture with respect to forget get. I broke this down completely and I also helped you to understand this. How does this neural network look like, okay? But with the help of forget get, what we are doing is that we may remove the complete, we may tell the memory cell to forget some of the information or to remember some of the information or forget some information. Something can be actually done. And this was the importance with respect to the forget gate. Now in my next video, we're going to basically go ahead and discuss about something called as input gate. Right? Now what exactly is this input gate? We'll get to know. But here I think we discussed till here, and this multiplication operation is just like you are forgetting some information, you are allowing based on the context, you are telling the memory cell to forget some of the information or let go some of the information by remembering it. Okay. So yes, this was it from my side. I will see you in the next video where I will be discussing about input gate. Thank you. Hello guys, so we are going to continue the discussion with respect to LSTM-RNN, and in this video we are going to discuss about input gate and candidate memory. Now, one thing that I missed out in the previous video is talking about this entire operation, right? When we are calculating f of t, what does this equation basically mean, right? I've explained to you each and everything with respect to working, but let's go ahead and write this equation. So first of all, you'll be able to see that I'm first of all combining this, concatenating x of t and ht minus 1, right? So this way we can go ahead and write like how it is written over here, ht minus 1 comma x of t. That basically means we are just combining all the inputs, right? Like how we combined over here. Then once we combine this, then you know that we are just going to have some kind of weights. So weights included over here is f of f, w of f. That is actually given over here. So we are just going to multiply with w of f as my weights, okay? And along with this, you'll also be seeing that in my neurons, right? I will also be adding a bias neural network. So here you'll be having plus b of f, right? And then finally you'll be able to see that I'm applying a sigmoid activation function, right? So this is how the entire operation has basically taken place, and this is how the notation looks like. Okay, I hope pretty much clear with respect to the explanation I have done. I think it should be very much easy to understand. Now let's go ahead and make you understand about the input gate and candidate memory, right? Now the input gate from this particular diagram is nothing but this specific gate where we are combining x of t, hidden state t minus 1, and we are passing it to this particular neural network. Okay. Now here when we are passing to this particular neural network, it is same thing like how we have actually done over here, right? How we have actually done over here, and instead of calculating ft, we are specifically getting let's consider over here as I of t. Okay, so this is nothing but I of t. Okay, so we know how I of t is basically getting calculated, but let's talk about this tanh. Right now, in this case of tanh, what will specifically happen? This I of t, let's say that I am actually getting some vectors. Okay, I of t, let's say I'm getting a 3 vectors like 2, 4, 6. Okay, now with respect to this I of t, over here you can see the operation is almost same, like how we did it for the forget gate. The similar operation will be over here, where I will be having all my inputs. Let's say 3, 4, 5, 6, 7. So this is my ht of my ht minus 1, and this is specifically my x of t. Okay, then the next layer I will just go ahead and pass it to my hidden layer, which will have this 3 neurons. Okay, and here we are also going to add, so there will be one bias that will be added over here. Now, apart from that, we apply a sigmoid activation function on top of it. Okay, I want to just go ahead and apply it. So here I'm going to apply a sigmoid activation function, and finally I get my output, which is nothing but I of t. Okay, I of t. Now let's go ahead and do the same thing for this candidate memory also. Now in candidate memory, what we do is that again the same way. First of all, we will take our ht minus 1. Let's say it is a 3 dimension. Then I have xt minus 1. Let's say this is xt. It is 4 dimension. We take this entire thing, and here this time we are using a hidden layer. Inside this hidden layer, let's consider that I'm using 3 hidden neuron. After this, I pass to an activation function which is called as tanh h. Okay, and here we add a bias. Okay, in short, we are just combining each and everything. So this will basically get combined to this, and you can further draw this diagram. I'll leave it up to you. Okay, let's say I am just drawing some of the diagrams so that you face this thing, right? Here also, and just connect all the other lines. Okay, here also you'll be able to see that I'm passing 1 cross 7. This will be 1 cross 7, and this will also be something like 7 cross 3. So the final one that I'm actually getting is 1 cross 3. After I apply a tanh h, so here also I'm basically going to get my C of t, which will again be a 3-dimension vector, because this is what I'm actually getting 1 cross 3. And let's say that I'm getting some values like 0, 1, 0. So again, 3-dimension vectors. Now you need to understand, whenever we take this input gate and along with this candidate memory, we have to combine this together, right? So whatever output I'm getting from IoT, IT and CT, we are performing another operation which is called as pointwise multiplication operation. Okay, we are performing this pointwise multiplication operation, which is basically mentioned over here, right? So this is my pointwise multiplication operation. Now with respect to the pointwise multiplication operation, why do we say this as input gate? This is called as an input gate because from here, based on the context again, so here I'm just going to write it down. Based on the context, if any new information needed to be added in the memory cell ct minus 1, then after this point operation the information will get added. So in short, forget gate, if you remember forget gate, the first gate, when we are trying to do the multiplication operation over here, pointwise multiplication, we are forgetting some information, and from this specific gate we are adding information, and that is where I get my final cell state, that is called as C of t. This is what we get as a final cell state, C of t. Okay, so this is more about a basic information of input and candidate memory. Again, to explain you, it's very much simple. When I do the pointwise operation, so here I'm saying, hey, there is some new information that I really want to probably add it up. I can add it up over here along with this particular information. In my forget gate, I know just by using this forget gate, I can remove some of the information, and that is the entire context of using input gate and candidate memory gate, right? So I hope you are able to understand this thing and you're able to make sense. Okay, so let's talk about these two operations. So first of all, you can see with respect to x of t ht minus 1 and with respect to sigmoid. So we are using this one, right? This is basically calculating I of t. Then you have we are combining for this we are using another weight w of I, and for this I'm using another weight w of ct. Okay, w of c. So for the tanh operation I'm specifically using w of c. So here you can see w of c with ht minus 1 with x, we're combining it, and then for that we're using another bias. So this is also another neural network, this is also another neural. So that is the reason I created this, right? This here, my weights that I have will be w of I. Here the weights that I have is nothing but w of c, and I'm combining them together, and finally I'm getting my c C of t. Okay, but once we do this dot operation of both of them, it's just like the the input and the candidate memory that I'm specifically having. With this operation, any new information that I want to add, right? You need to understand with respect to the candidate memory what important thing it is doing. Any new information based on the context that needed to be added, we will just try to do a pointwise operation over here, right? So let's say if CT has this important context in over here, right? So I may probably put some new information. I may go ahead and write 0 to 0, and when we do this dot operation, here you can actually see that this will become 0, this will become 8, and this will become 0. So new information is basically getting added in my CT minus 1 cell state along with the previous state, and we are adding it up. This is also very much important. We are adding it up. Okay. So let's do one thing. Let's discuss about both this, the combination of forget gate and input and candidate memory. So here we saw that with respect to this particular information that I had right over here, so So first of all, if I want to get to this final memory cell state, C of t, first of all, we'll multiply f of t multiplied by ct minus 1. So here we are removing or forgetting some information. If the context is switching. Otherwise, we'll just make the cell state pass in that way. Along with that, when we multiply I of t and c of t, that we are doing a pointwise operation. So this c of t is nothing but it is a what kind of cell it is? Basically, it is a candidate memory. It is nothing but it is a candidate memory. And the task of the candidate memory is to add new information, right? Add new information to this particular cell state. And here you can see pointwise operation. We're just adding it up. And finally, we get a new cell state that is c of t. Okay. So I hope you got an idea with respect to the input gate and candidate memory gate. So if I take a very good example, let's say I go ahead and write, I stay in India, okay, some sentence, and I speak dash. Okay, so if this kind of sentence I want to probably find out what is the next word. So all the words will be going line by line, right? But here you can see we will be saving this Indian context in the memory cell, right? When the context switches, we may be forgetting it, we may forget some other information, but for a longer term, we will be keeping this particular information over there to predict my next language. And obviously, just by seeing this context, my neural network will be able to predict, okay, I do speak Hindi or English, anything as such. But right now, this particular prediction is based on this context, that is which country I'm actually staying. Okay? So I hope you're able to understand it. I hope you're able to understand this entire equation. I hope you're able to understand the entire working, right? To simply give you, till now we have discussed about forget gate and we have discussed about input gate plus candidate memory. When we do a pointwise operation over here, candidate memory means we do the pointwise operation and then we do the addition operation with ct minus 1 to finally get c of t, which is my final cell state, memory cell state. So yes, this was it from my side. In this video, we have discussed about input and candidate memory along with explanation, along with mathematical intuition. This was it from my side. I will see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to LSTM-RNN. Now in this video, we are going to discuss about output gate. Now output gate is the third important module in this LSTM-RNN, specifically in architecture. And if I probably see with respect to this diagram, this is the part that is related to output gate over here. So we are going to discuss about the working of this. Okay. Already we discussed about forget gate. In forget gate, our main intention was to forget some information based on context from the memory cell. So all the operation that we are actually doing, it is actually leading to that specific thing. Now in the second one, which was specifically in my input gate, our main aim was to add information based on the context. Okay, add information based on the context. Now let's go ahead and discuss about the third output gate, that is the third component over here. Now there are two things. One is again the same operation which we have with respect to sigmoid. Here we are passing x of t, ht minus 1, and we are adding a bias. So here specifically we will be using b0 as our bias, and we finally do the sigmoid activation function. So if I consider this is nothing but it is my neural network, right? It is the hidden neural network. Perfect. Now after doing this specific operation, whatever information that I have, after I forget some of the information and then add some information from the input gate through this candidate memory, from that we will be passing one information that is called as ct. Now this ct that you'll be able to see, this is my memory cell, right? This is the information in my memory cell. Now this will continue on, right? And along with this, you should understand one thing, right? So see, let me just go ahead and discuss this. So this is my CT and this is my HT, okay? Whenever I talk about CT, this is my long-term memory. Long-term memory. And the output gate, what we do, we again do this tan h operation or tan h operation with respect to the output that we get from here. And we apply on each and every element, like point-wise operation is specifically done to this sigmoid output, right? That output that I have with respect to O of t. By doing this, what will happen is that whatever output is probably going to come from here, this will be retained in my h of t. H of t is nothing but my hidden state. And whenever I talk about hidden state, I'm actually talking about my short-term memory, right? Short-term memory. And this short-term memory will be related to the just the current context or one context before it, right? So this operation is specifically done to get the output. Once we get this particular output, we will be sending it, we'll be sending this h of t, which denotes our short-term memory, to my next timestamp, right? And similarly, with respect to the operation that we are doing here, the pointwise operation, from ct minus 1, I will be getting ct, right? So this will basically be my long-term memory, and this will be my short-term memory, which will be passed to my next layer, right? Next timestamp. And if I say this, this line also, probably I can just go ahead and connect this over here, right? This is the HT itself, right? I can use this also, I can use this also. So that is the entire operation with respect to output. Now, if I go ahead and see over here, you can see I'm using sigmoid of W of O. W of O is the weight that is assigned over here. Then I have HT minus 1, XT plus B0, and then I'm performing the sigmoid function. I'm getting the OT value. Then when I do pointwise operation with tan H over here, and C of T is nothing but, C of T is this specific value that I have. Then through this, I will be able to get the context that is available in the short-term memory. And then we continue this process, okay? Now, you can just imagine like this, right? Let's say this is my LSTM. This is my LSTM in T minus 1. Then in T is equal to 2. Sorry, I'll say 1, and T is equal to 2, I will be having another LSTM, and T is equal to 3. I will be basically providing this particular loop, right? So this will keep on going on, right? And finally, you'll be able to see that once I get the output, I may pass this to my sigmoid function based on the kind of output that I really want, y hat, right? And this operation will keep on going with two cells. As I said, one is the long-term memory cell, and one is the short-term memory cell. So here, this is my long-term cell, and this is my short-term, right, memory cell. And with respect to the information, what I really need to forget, I will be removing some of the information from here. I will be adding some of the information from here. Again, I may see both these things may happen over here, right? From one neural network, from one hidden layer, I may add some information. I may remove some of the information, right? Adding the information basically is done by the input and memory cell, and removing some of the information will be done by forget cell, right? Forget gate. Let's say cell, but forget gate. And adding some information will be specifically done by our input gate along with candidate memory. Right? So that is how the entire process will be going on. The forward and the backward propagation will keep on happening unless and until our loss keeps on getting reduced. Right? And that is how we make sure that we update all the weights. Now in this particular case, what are all the weights that we saw? One was W0, then here also we saw some more weights, W of I, and then you had W of C, right? So these three weights were specifically there, right? So all the three weights, W of I, W of C, and W of O. So let me just go ahead and do this and write down all the weights that we are updating, W of I, W of C, W of O. I is with respect to input, C is with respect to the memory cell, and O that you will be able to see is with respect to the output, which I'm actually getting back my hidden state over here, right? Sorry, not hidden state, but here when I'm putting it last on my, so this neural network that we are using over here, right? This will specifically be my level of 0. So we need to keep on updating this weight with the help of backpropagation. Backpropagation. But at the end of the day, you'll be able to see the memory cell is playing a very important role because it is keeping some of the information for a longer context. Whichever needs to be remembered, it will be remembered, right? And let's say if the context is switching and we really want to remove that, the entire training will be happening in this specific way, right? So I hope you're able to understand about the output gate LSTM RNN. Now, in my next video, I will be talking about one more variant of RNN, which is called as GRU RNN. Okay, so this is just another variant of LSTM, another variant. And here we will be understanding some important things with respect to this, what all things will be changing, right? This operation will be changing with respect to the GRU RNN. So yes, this was it from my side. I hope you like this particular video. I'll see you all in the next video. And I hope you're able to understand. But just to give a summary, you have this forward gate. Forward gate is responsible in removing some of the information from this particular memory cell. Input and candidate memory is responsible in adding some of the information. And finally, output gate is used to distinguish properly all the memory cell and the hidden state. Hidden state, which represents the short-term cell. Okay, short-term memory. Or I can also say short-term memory. Not write short-term cell, but instead I can basically go ahead and write short-term memory. So I hope you're able to understand it. I'll see you on the next video. Thank you. Hello guys, so in our previous video, we have already discussed about the architecture of LSTM RNN. Along with this, we saw three important gates. One is for gate. Then we saw about input gate, and this was with respect to along with the candidate memory. And finally, we saw about output gate. And we understood what forget gate was doing, input gate was doing, and output gate was doing, right? Now let's take one specific example and let's see that how this entire data is basically trained in an LSTM RNN. Okay, so here obviously I have an example. So this is my text paragraph and this is my output. Okay, let's say that based on this information, I need to find out whether this particular text, based on this particular text, the food is in the restaurant is good or bad. Okay, so I need to predict whether the food is good or bad in the restaurant. Okay, and these are some of the reviews that has come with for this particular restaurant. So here, let's read this text paragraph. It says, "Hey, I went to the restaurant and ordered burger." Okay, so in this paragraph, this is my first sentence. Then here you can see the burger looked tasty and crispy. Okay, but burger is not good for health. It has a lot of fats, cholesterol. But this burger was made with whey protein, and only vegetables were used, so it was good. Now see all this information here, it shows that it has a lot of fats and cholesterol. And here it is saying, hey, it is made up of whey protein and only vegetables. So it was good. And finally, my output is basically 1. So that basically means this burger is good, right? So this is my training data. So you can probably consider this as my training data. Okay. Now with respect to training data, how do we take this particular sentence and train it in our memory? What information needs to probably go to my memory cell or the long-term memory cell and the short-term memory cell? Okay. See, already we have discussed about this entire representation, right? With respect to the LSTM. Now I will just give you a simplistic representation. Now with respect to LSTM, you know that there are two important lines. There are two important lines. Okay, one is for the LSTM, right? So this is for the long-term memory, and there is also one more, which is specifically for the short-term memory. Okay, short-term memory. You know this. This short-term memory, how it is basically denoted by this is nothing but CT minus 1. This is nothing but CT minus 1. Let me just go ahead and write it down. CT minus 1, and this is the previous hidden state HT minus 1. Okay, here we give the input. Okay, x of t. As soon as we give the input, the first important I'll put a box over here to make you understand. Okay, so the first important gate is nothing but forget gate. Then the next important gate is my input and or candidate gate. Input and candidate gate. Input gate and candidate memory. Okay, and finally third that you have is something called as output gate. Right. So I'm not writing what operation is basically happening over here. Right. But I'll add this one. So here you have this pointwise multiplication. Here you have this pointwise addition. Okay. And considering this, I will just connect this. And finally, you'll be able to see that I will be getting back to my output gate and coming back over here. So this is my CT. Okay. Now, don't worry that I have missed some of the parts. If you really want to see the complete diagram, it looks something like this. But I've just combined this into some blocks, and here I've actually shown it. Okay. And this is nothing but this is my next state of HT. Now, the reason why I'm showing you this, right? Because I need to pass all these words with respect to time to this particular gate. Okay. So how does the training specifically happen? See, when I have this text paragraph, you know that every word over here, every word, the first step is that it needs to be converted into vectors. Okay. First step, we basically talk about it. And this layer, also we say it has embedding layer. That basically, whenever I take a word, first of all, I need to convert this into vectors, some vectors. Okay. Now, already we have discussed about word to vec. Okay. So in word to vec, what do we do? See, word to vec. If I probably consider an example of word to vec as a vector. Okay. In word to vec, let's consider that I'm converting this word into 3 dimensions. 3-dimension vector. 3-dimension vector. Now, since I have these words, let's say, see, word to vec, how does it work? I hope you may be seeing, you have already seen the previous videos of word to vec. So here what we do is that with respect to word to vec, we take one input. Let's say we have one word over here. And with respect to this particular word, if I want to probably convert this into a vector, okay, if I really want to convert this into a vector, then let's say one of the word is tasty. Okay. Now, in order to convert this word into a vector, so with the help of word to vec, what it does is that it takes some features, 1, 2, 3. Like we are just using 3 dimension, so it will try to find out the relationship of this word with this particular feature. Okay. Now, what feature it is, how it basically does it, I've already shown you how the entire word to vec basically training happens. Okay. But you can just consider, see, it's morely like a black box. This is completely a black box. You will not be able to understand or get to know what is basically happening internally. But it will just try to select 3 words, and based on this relation, it will assign some vectors. Right now, most of my text is related to food, it is related to good, bad, something like this, right? So I will just create 3 vectors, okay, over here. One will be finding the relationship with respect to good. then one will be finding the relationship with respect to bad, and one will be finding the relationship with respect to a healthy. Okay, so let's say I have selected this three, and based on this three, we will try to take each and every word and we'll try to find out one three dimension. Let's say as soon as I read the burger looks tasty. So here, when we say tasty, I will be getting a vector for good somewhere as 0.9. For bad, since it is not bad right now, so it will be 0.0. For healthy, still no information is given. So let's say that this is just 0.1. When we are saying tasty, it may be somewhat healthy. So as you all know, in LSTM RNN, what we do, we keep on giving every input over here, right? One input at a time. And let's say for tasty, this is my vectors that I'm specifically giving, right? This is the vector that I'm giving. And I'm considering, hey, it is 3 dimension. So similarly, for every word, what we do, we give this kind of dimension from here, right? But with respect to timestamp, first of all, we will go ahead and let's say I go ahead and says that I went to a restaurant and ordered burger. So every three dimensions will probably be going on over here. Now with the help of forget get, what will basically happen? We need to find out like what information needs to be passed through this memory cell, right? So here we have a memory cell. So here you can see I went to the restaurant and ordered burger. Okay, and ordered burger. So once I give this entire information, right now I know I don't want to skip anything from the previous memory because nothing new has come. But when I say the burger looked tasty and crispy, I know because this tasty and crispy is going to be used somewhere. So what I will do, when these words come from this input candidate gate, right? Input gate and candidate memory, we will try to add this information like tasty and crispy. We will add in the previous memory cell over here because this tasty and crispy will be getting used. Now when this tasty and crispy will be coming, right? You'll be seeing that once I add in this input or candidate gate, these all vectors will have more better values. Let's say over here it will be 0.9. Here bad, about bad it has not been told anything, but about healthy is not good for health. It is basically the next sentence is actually coming up, right? So right now if I say the burger look tasty and crispy, so it will be just 0.1 with respect to health. So this at this point of time, this information is going over here, and this will further get added to the memory because it's talking about tasty and crispy. Now when the next line goes, that is, but the burger is not good for health. So when this comes, since it is saying not good for health, right? Not good for health. Okay, fine. This information will probably go now. The vectors is going. Okay, but here you'll be able to see that after this particular operation, since we are talking about not good for health, right? Now my vectors will get changed to something like this. Now we are talking, see, good is already there, 0.8. Okay, let's say the good will reduce a little bit, but bad, if I talk about it, become 0.4 because bad is increasing. Okay, it's saying not good for health, right? Not good for health. So if I say not good for health, again this will become 0.0, right? So here bad value is also increasing, good value has decreased, right? If I say good value may have decreased to 0.7, 0.7. Okay, because here we're trying to find out the relationship of every word. So if I say health with good, bad, and healthy, right? If I try to find out this relation, so this value will keep on decreasing, right? Then it says it has a lot of fats and cholesterol. So for when we go to this sentence and then we pass the word, now what will happen? This good value will still keep on decreasing because we are saying it has a lot of fats and cholesterol. So this becomes bad. Bad value will increase. Now this healthy value will also like increase or decrease, right? Initially, let's say over here when we say it is not good for health, it is completely 0, right? And here we have said okay, it has a lot of fats and cholesterol, so it will be 0, right? Initially it can be 1. But this burger was made with whey protein and only vegetables. When this sentence comes, what will happen? This vectors will further change into something like, let's say now we are talking about more good things, right? So this will increase, the bad part will decrease, and the good and the healthy part may become 0.9 because we are saying that hey, it is made up of whey protein and only vegetables, right? So these vectors will keep on changing, and that is how word to vec work because we'll try to find out the relationship between this word to this particular features given by word to vec, okay? And then we will keep on giving that particular vectors. Now when this value changes, we now know what information we need to remove from the previous state and what new information needs to be added because see, this tasty and crispy is again going to come somewhere. So we are just going to add some information about tasty and crispy over here, okay? Let's say burger is not good for health, and later on we don't get anything about good for health or bad for health, something like that, right? Anything I will not be having reference of not good or not bad over here, right? So I will remove some of the information over there. So when see over here you'll be able to see that I'm reducing some value, I'm increasing some value, right? How this is actually happening? This is actually happening based on the sentence, and this is only why when we reduce something, that basically means we are removing something from the memory, maybe, or we are increasing something from the memory itself, right? So this is for your short term, this is for your long term, right? And this is how your entire forward propagation and the backward propagation will keep on happening with updation of the weights, okay? So I hope you're able to make sense like how each and every vector changes and how your forget get, input get, and output get will keep on working. With the help of forget get, we will just be doing one work, is that what information I need to let through this particular memory and what information I need to forget, make it forget. Okay. Now, as the training will happen, initially when I say the burger look tasty and crispy, this entire information will go over here. Since this is a new information, right? From the previous information, I may remove something. Let's say over here also we have a 3-dimensional vector. Let's say about good, bad, or healthy. So good was 0.0, bad was 0.2, healthy was let's say 0.1, previous sales state. Now the burger looked tasty and crispy. When this information is going, now input gate, what it is going to do, it is going to convert this entire vector where the good value will increase, okay? It will increase to 0.4, let's say, I'm just taking it as an example. When I talk about bad, this will decrease, okay? And when I'm talking about healthy, right, this may have some value like 0.4, right? Then when I pass this third sentence, I need to add some more information, I need to skip some more information, right? So from this entire cell, what I will do when we go to the next timestamp, I may decrease this value now, right? Because now it is saying not good and not good for health. So what will happen? We will add some information, we'll forget some information. So if you're forgetting some information, now we're saying that, hey, this is not good, the burger is not good for health. So this value will become 0.2. Similarly, this second one is specifically for bad, this will increase to 0.4. And if I say healthy, since I've written previous 0.4, but it says it is not good for health, this may become 0.1. Okay. So this is how the entire the forget get, the input get, candidate get, and the output get actually works. But you really need to remember, forget get will help you forget some of the information based on context switching. Only the important information that will be relevant for the long-term context that will be used, and it will keep on going on, right? So I hope you got this complete idea. This was a quick way of making you understanding training data with LSTM RNN. I tried my level best to explain you all these things. Okay. So yes, this was it. I will see you in the next video. Hello guys, so we are going to continue the discussion with respect to RNN, and in this video we are going to see a variance of LSTM RNN. Now we have already seen the entire LSTM architecture, but in some of the research paper you will also find this kind of architecture that I have actually mentioned over here. Okay, now please focus on the diagram. I would always suggest whenever you want to check different variants, right? You know what is RNN, you know the generic representation of RNN, you know about LSTM RNN. Now just pause for hardly 10 to 15 seconds and just focus on this diagram. Okay, I'd again suggest if you really want to learn all these things very much properly, you really need to focus on all this representation of different variants, right? And just think within yourself like how it is different from LSTM RNN. Okay, because here also you have this forget gate, you have this input gate, you have this output gate, but along with this you'll be seeing some lines. So what will happen if you get this kind of line? Just take 10 to 15 seconds and think about it. You can pause the video and you can think. But I will go ahead and continue the explanation over here. Now, if I talk about LSTM RNN, so it's not like LSTM RNN is a very new concept, right? So LSTM RNN came in somewhere 1970s to 80s, okay, at this point of time. Then different variants, LSTM variants came. Like this is one of the variant. We will discuss about this, and this was introduced by Gers and Shimad Huber. I guess I'm pronouncing it right. If I'm not, I'm extremely sorry. Okay, so this type of variant specifically came in 2000, and I have seen a lot of research paper where they have specifically used LSTM RNN. So in some of the research paper, I had seen this diagram. Okay, that is the reason I'm teaching you this different kind of variants also. Okay, so obviously this is another kind of variant, and you can just consider that. Okay, in some of the research paper you'll find this, and in some of the research paper we'll find the normal LSTM RNN what we are actually seeing. Okay, now. Let's go ahead and focus on this entire diagram. Okay. Now here you can see that the input gate, the forget gate, the forget gate, the input gate, the memory candidate, the candidate memory, and the output gate are almost same. You also have the CT minus one, you have CT, HT minus one, you have HT, you have XT. Everything is same. But the additional thing that you specifically have is this line that you are sending from the memory cell to both the forget gate and also to the input gate along with the candidate memory, and you're also sending it to the output gate. Okay. So what is basically happening in this variant? From this particular variant, you can actually see a line that is probably coming up from the memory cell to the, again let me repeat it, to the forget gate, to the input and the memory candidate memory, and also to the output gate. Okay, so this all information are specifically coming. This connection from memory cell to forget gate to input gate, and you are also combining later on. This is just going to the input gate right now. Okay, so I'll not go ahead and say that hey we have to include candidate memory. Candidate memory is done with a pointwise operation. Along with this, you also are sending it to the output gate. Right? These connections are called as, very important word that I'm going to use, and you'll also see in the research paper, which is called as pip hole connections. Okay, so this is basically called as pip hole connections. Very important. Okay, pip hole connections. Right. So this is specifically called as pip hole connection, and as the term says, right, what is this pip hole connections? Let me just give a simple definition over here. Pip hole connection is nothing but and you see this, okay, they will be providing this entire information in some of the research paper, and some research paper will not be getting it. Okay, so here pip hole connection means that through this architecture we let the gate layers look at the cell state. Okay, so this is one additional thing, right, that we are specifically doing. We are saying that hey, when you are from this architecture, we are just giving some functionality to the forget gate, saying that hey, if you want to make this memory cell forget some of the information, you can also take the previous context or previous information that is available in the memory cell to decide what information you need to make it forget. Right? We are just saying that hey, go ahead and look at the cell state and then probably take a decision. By this, they will be able to take much more good decision with respect to forgetting, with respect to adding some information to the memory cell, and with respect to getting the output. Okay, so this is the entire funda behind this particular variant. And here you can probably see the equations. Right, we need to calculate this f of t. This is there. We need to calculate I of t, and we need to calculate O of t. Now in f of t, only this term is basically getting added. Right, these three important terms are basically getting added. Right, before it was this two. Then we also are combining this. Like we are also combining C of t. Let's say C of t are 4 dimensions. Sorry, 3 dimensions. Let's say HT of minus 1 are 3 dimension. Let's consider in this way. So it will be 3 dimension. And you also have X of t. Let's say this is 4 dimension. So we are going to combine everything, and then we are going to give it to the neural network. Let's say there are 3 neurons. And let's say after this we are going to pass it to the sigmoid for the forget gate, and then finally I'm going to get the output. So this will get connected to each and everything right over here, and you can further do the connection based on this. Right. So this indicates my, if I'm just considering 3 dimension, this is my CT minus 1. This is my HT minus 1 for the forget gate for the first operation to calculate f of t. So this is my f of t, and then this is my X of t. Okay, so this is how we are combining, and similarly I of t we are combining CT minus 1 over here. O of t we are combining CT, because after both this operation we will be able to get CT over here. We will be able to get CT over here, right? So this was about one of the variant. Let's talk about one more variant. Okay, so this specific variant. Okay? Now this variant is also amazing. Over here, this is I can just go ahead and write. This is another variation. Okay, where we are coupling. This is very important. Where we are coupling, or where we are combining forget and input gates. Okay, where we are combining forget and input gates. So here you can see that. I'll just go ahead and provide you the definition of what we are specifically doing. Here we are saying instead of separately deciding. See, in my previous LSTM, we had a separate forget gate, we had a separate input gate. With the help of forget gate, we were separately deciding what to forget, right? And with the help of input gate, we were separately deciding what to add to the memory cell, right? So instead of separately deciding what to forget and what we should add new information, new info. Okay, we make this decision together through this particular variant, right? We make this decision together, right? And this is what we are doing. Forget information is also going away, and some kind of operation is basically happening. Okay, so here the goal is, okay, the goal is very simple. I'll just go ahead and write my goal. The goal is very simple. The goal is just to make sure that we only forget when we are going to input something in its place. So what does this sentence mean is that whenever we are inputting something, then only we are going to forget something. Okay, so if I want to probably give a conclusion over here, I can also write we only input new values to the state when we forget something older. So this is the entire funda. Okay. I have to. So this is one kind of operation which is basically doing this entire functionality. That's it. Okay. And by this you probably get another variation, and this is nothing but we are trying to combine forget and input get in such a way that whenever we don't have any information to remove from the memory cell, then we don't add new information. When we remove some information, then only we add new information from the input get. So I hope you like both this particular variant. Now there is also one more variant which is called as GRU, gated recurrent unit. Okay. And this is also again a different variant of RNN. Why we use this, we will talk about the advantages and disadvantages. And here also if you see, here you can actually see what was the kind of operation that we did. So when we are calculating, okay, C of t, that is this, we take f of t multiplied by, that is point-wise operation. So this is my point-wise operation over here with ct minus 1. So this is fine. Plus what we do, we say, hey, 1 minus f of t, we are going to multiply with c of t, whatever output we are getting from this particular tanh, right? And here you can see 1 minus f of t is nothing but this. We are just subtracting 1 over here. We are multiplying with, we are doing a point, we are basically taking c of t, we are multiplying it over here, and then we get this entire information, right? So this is nothing but this is my point-wise operation. So this basically indicates that through this operation, we add new values. We add new values only when we forget. Only when we forget from the forget date, right? That's it, you know. So I hope you're able to understand this video with respect to variance. In our next video, we will be talking about gated recurrent neural networks, gated recurrent unit, and we'll try to understand what are the advantages and disadvantages. But I would suggest you please just check the diagram, see the variation from the other diagram, that is like LSTM RNN, and I will definitely say you guys, LSTM RNN is must to understand anything. The 5 to 6 videos that I have explained about input, output, how the training basically happens, everything you really need to know. Okay. So yes, this was it from my side. I will see you all in the next video. Thank you. Hello guys, so in this video we are going to discuss about gated recurrent unit, which is again a variant of LSTM RNN. This GRU RNN was introduced by Coe et al. At 2014. Okay, now just imagine in 1980s LSTM RNN was there, then we saw some variants in 2000, right? Now in 2014 you'll be able to see that hey, we have this GRU variant. Now since this variant, this GRU has just come recently in 2014, hardly 10 years back. Right now it is 2024, right? It has some very important meaning, and we'll be discussing why do we use this GRU. Okay, so let me just go ahead and explain some of the things. So see, in LSTM RNN, you know that we have a separate cell, memory cell, and we have a separate. So this is for my long-term memory, which or let me just go ahead and draw it below so that you'll have sufficient space to understand this, right? So let's say this is my long-term memory, this is my short-term memory, okay? And I've already shown you we have this forget gate, we have this input gate, we have this output gate, right? So I'll just give some notation over here. This is ct minus 1, this is c of t, this is ht minus 1, this is h of t. Then we do some pointwise operation, this will be plus over here. And let me just go ahead and check it because it's been, see, this was this, right? Then we use the tanh, and then we specifically do this. I could use this particular image, okay? So here, what I will do, we'll just go ahead and use this tanh and then a pointwise operation. So here you have all the information going right? Now understand one thing. This line is for my long-term memory, and this is for my short-term memory because this is my hidden state that is basically mentioned over here. So this is my short-term memory. Now you know for every gate. So as I said, this is my forget gate, right? So this is my forget gate, this is my input gate, and this is my output gate. Now for every of this gate, you know that we have some weights. So here I will go ahead and write W of f, here W of I, then here you have W of O. Okay. So at the end of the day, with respect to this particular gate, this LSTM RNN variant, you'll be seeing that one of the major problem is that this LSTM RNN architecture is quite complex, right? Why it is quite complex? Because here we are using 3 gates first of all, right? Here you'll be able to see that we'll be using this forget gate, we'll be using this input gate. Now obviously along with this we also have this candidate memory, and we have this output gate. Now when we have this many number of gates, you know that we also have 3 important weights. One is W of f, one is W of h, and one is W of o. This is many number of weights, right? Sorry, I'll just go ahead and write these weights again. So I have W of f, W of I, and I have W of o, right? And even though if I consider that in my input I have 100 dimension, in the hidden layer I have 100 hidden nodes, right? So this weights will keep on getting increasing. So whenever this weights, and obviously bias will also be there. Now what do we consider these weights and bias? These weights and bias are nothing but these are called as trainable parameters. Trainable parameters, right? Now because of this complex architecture, you'll be seeing that these trainable parameters will keep on increasing, right? Because that many number of parameters is specifically required, and whenever trainable parameter increases, obviously the training time will also be increasing. And this is basically happening just because of the complex architecture. We have so many number of gates, and we are having so many number of weights, so we are having so many number of bias and forward and backward propagation, and we keep on doing with respect to time, right? So see, LSTM RNN does a good job in solving long-term dependency. That is very much clear. But still, the architecture is very complex, and because of this, you'll be having more trainable parameters. When you have more trainable parameters, you have more training time. Right? Now, what researcher Coe et al. Did in 2014, I hope I'm pronouncing it right, guys. If I'm not pronouncing it right, please apologies. Right? Sorry for that. Okay. So what in GRU specifically done is that instead of using 2 memory, like long-term memory and short-term memory, here what it has been specifically done is that hey, we will see again for handling this long-term and short-term memory, there will be different parameters that will be assigned. More operations will be specifically done. You know what they have actually done in GRU? They have combined this 2 memory cell. See, this is just one memory cell which is representing hidden state, and here there is no long-term memory cell, right? This cell that you'll be seeing, it acts as both long-term and short-term. It acts as both. Okay, and from this only we pass this information. This is my input gate over here. This is my you can see over here, right? This I'll not say input gate. So see, this is basically called as, and here you also need to understand with respect to the gates. Okay, so Z of t over here, I will denote it over here, like how we had this forget gate, input gate, and output gate. Here, when I consider this architecture, here you'll be seeing that we first of all find out Z of t. So Z of t is nothing but we take this ht minus 1, we take this x of t, and then we pass it to the sigmoid activation function. And here we go ahead and apply this W of z weights, right? So when Z of t is basically calculated, this Z of t is nothing but it is basically called as update gate. Okay, Let me just go ahead and write this information. This is called as update gate. Update gate. Okay. Now, when we go to the next one, here you can see that it is R of t. How do we calculate R of t? We take x of t, ht minus 1, and then here we are assigning another weight over here. And this weight will be nothing but it will be w of r. Right. Now, this value that we are computing R of t, this is basically called as reset gate. Very much important. This is basically called as reset gate. Okay. Now, reset gate, what is the functionality? I'll give you a brief functionality and information what this specifically does. We will be getting to know all about that. Okay. And then the final one that you have is nothing but h of a temporary hidden state. I can basically say this is a temporary hidden state. I'll just name it. Okay. Temporary hidden state. So let's do one thing. First of all, let's understand how this operation of R of t is there, Z of t is there, and H of t is there. H mode of t is there. H hash. Like I'll say H this upper symbol. Okay, I'll give this kind of notation over here, which I'm writing it as temporary hidden state. So first of all, everybody's clear with Z of t because here it is very much simple. We're combining ht minus 1, we're combining x of t, we're passing it to this sigmoid activation function with sorry, over here, this one. Right? We are passing it to the sigmoid activation function with Z. Okay. Z over here. Z of t, we are basically getting the output. Here we are going to apply a weight which is called as W of Z. So let me just go ahead and write W of Z. Okay. So this is one. Now let's say R of t, which is nothing but reset gate. This is nothing but update gate, right? Now when we go to the reset gate, in reset gate, what we are doing, we are taking this W of R, whatever is the weights over here, and we are combining ht minus 1 and x of t. So this is also very much simple, and then we are passing it to the sigmoid activation function, and finally I get my R of t. Now when I get my R of t, you'll be seeing that I am doing a pointwise operation over here. So pointwise operation with what? With ht minus 1, right? Once I do this pointwise operation with ht minus 1, along with x of t, I'm passing this entirely to my tanh activation function. And with the help of tanh activation function, this is where I'm getting my temporary hidden state. Okay. And then what we do by doing another point operation with z of t, right? So z of t is also there. And by doing another point operation with z of t, I'm updating my final h of t, which is my memory cell for both long-term and short-term memory. So this is the entire operations that is specifically done, right? Understand the dependency, right? One or the other dependency. X of t, z of t is used over here along with h of t, right? So here we are doing dot operation. So this is my dot operation that we are doing. And then in order to calculate h of t, I'm also subtracting some information, 1 minus z of t, and I'm doing dot operation with ht minus 1. So that is what you're able to see over here. Okay, step by step. Again, let me repeat it, and we'll try to make it much more clearer once I make you understand why this entire steps is done. So first of all, you need to understand z of t is nothing but it is called as update gate. R of t is nothing but it is called as reset gate. H mode of t is nothing but temporary hidden state. So first of all, we go ahead and compute z of t. How to calculate z of t? It is nothing but we take this ht minus 1, we combine x of t, then we pass it to a sigmoid activation function. Before passing it to the sigmoid activation function, we multiply with weights w of z, and finally I get z of t. Now this value, so z of t will be used where I'll talk about it. Okay? So first of all, we have computed z of t. Okay. Now the next one we are going to compute R of t. R of t is very simple. In case of R of t, we take ht minus 1, x of t, we apply weights, multiply weights, w of r t, because this is our neural network, right? Which I've already discussed. Then we pass it to the sigmoid activation, we get R of t. Okay. Then what we do? We, in order to compute this h dash t, right? We take this ht minus 1, we take this R of t, we do pointwise operation. So that is where this pointwise operation is done. Then we take x of t, we combine both of this input. Then we multiply by what? We multiply by weights. Which weights? So that will be w weights over here. Then we pass it to the tanh. Then I get h dash of t, which is my temporary hidden state. Now what I do? I take the output from my update gate. I take the output from this temporary hidden state. I do a pointwise operation, and then I send it over here, and then we do a pointwise plus operation with ht minus 1 and get the memory back. Before that also, from the update gate, I subtract some of the information from 1 minus z of t, so from this particular information, and then do a pointwise operation and send it to this particular information, right? So finally, in order to get h of t, I do this two important operation, right? Now let's go ahead and understand what does update gate, reset gate, and temporary hidden state actually do. Okay, so let's go ahead. So guys, now let's go ahead and discuss more information about this update gate, reset gate, and temporary hidden state, which we also say it as candidate hidden state. All the notation is specifically given over here. Okay. Now, what is the importance of this reset gate? Okay, here I'm going to basically denote by R of t, which is basically given over here, R of t. And you know R of t, how it is calculated? Sigmoid of WR, and we're combining ht minus 1 and x of t, and we're passing it to the sigmoid activation function, and then we specifically get R of t. Now R of t, we basically say it as a reset gate, and its main responsibility is, let's say for my ht minus 1 line, right, which is my current memory cell. Okay, I want to see this R of t, as I said, right? Let's say I'll just go ahead and write over here. Let's say I'm getting the R of t after this sigmoid, right? And for this, I'm passing my ht minus 1 and xt, right? And once I give this specific output, once I get this particular output from the sigmoid, right, you will be seeing that this reset gate will be responsible in resetting some information, from ht minus 1, which is nothing but our memory cell. And when I say memory cell, this is the combination of long-term memory and short-term memory. Okay, so this is what R of t will specifically do. So if you go ahead and see over here, how we're calculating R of t, it is nothing but sigmoid of W of R, W of R multiplied by this ht minus 1 comma x of t, right? We are combining both these things. Now, the main aim of this reset gate, why I'm saying, once we do this calculation, here you can see that I'm taking this ht minus 1 and we are combining, or we are doing a pointwise operation, pointwise multiplication operation. See, whenever you see pointwise multiplication operation, always consider this as resetting some information or forgetting some information. Now, what does this resetting some information basically mean? Let's say from ht minus 1, if I just go ahead and consider some 4-dimension vectors, right? So let's consider that this is my ht minus 1, and here I have values like 0.6, 0.5, 0.3, and 0.9. Okay. Now I will go ahead and calculate my R of t. Now R of t may be some values like this. It can be 0.2. Let's say that we are just going to calculate 0.4, 0.8, and 0.2. Okay. Now this indicates when we do this pointwise operation, in short, we're just going to multiply this, right? We're going to multiply this. When we are going to multiply it, understand one very important thing over here. When we multiply these two values, what we are specifically saying that, hey, there is some 0.6 value, and we are just multiplying with the 20% of this value. Yes. right? So once we probably multiply it, I will be getting something like this 0.12. Okay. So here you can say that from this 0.6, I'm just taking 20%. I'm resetting this particular value. I'm forgetting some information through this reset way, right? Similarly, over here, if I say 0.5 multiplied by 0.4, so here you'll be getting 0.20. What does this basically indicate? From this 50%, I'm taking only 40%. I'm resetting by 40%, right? So when I'm resetting by 40%, I'm only getting 0.20. Over here, I'm saying, hey, go ahead and reset this 0.3 by 80%. So this will be nothing but it will be 0.24, right? So something like this. So you can just consider that I'm trying to reset some value out of it, okay? And this is how I'm actually able to do it, you know? Now, when I'm resetting by 80%, I'm getting this specific value. If I'm resetting by 40%, so 40% of 0.5 is nothing but 0.20. When I'm resetting this 0.2, that 20% of 0.6 is nothing but 0.12. Similarly, what is 20% of 0.9? You know, so you can go ahead and do the multiplication. It is 0.18. So here, what I'm saying, I'm basically resetting the value. I'm removing some of the context, and this resetting is happening based on the context. I'm saying, hey, I got my new x of t, let's say, and based on this x of t, I need to reset all this particular value, and this is what this pointwise operation will specifically do. Okay. Now, once we reset it, you'll be seeing that we're sending this information to our tanh, right? So tanh over here, it is sending, and we're calculating h dash t, which is nothing but it is our temporary hidden state, or we can also say it as candidate hidden state, right? So that is the reason you'll be able to see that when we pass this information, in short, we're just passing the resetted value, right? After we probably perform the resetted value, we are passing this to this particular tanh, okay? And we will be getting this h bar of t, okay, once I pass this, okay? Now, let's go ahead and see. I think this is very much clear for everyone, I guess. So the first operation where we calculated r of t. Now, let's go and see with respect to z of t. How do z of t is calculated? So we'll take this ht minus 1, we'll take this x of t, we'll pass it to sigmoid activation function. And here another weight is applied, w of z, okay? So here we have calculated this. Now, this z of t and whatever h bar of t will be coming up, right? This both are combined together to get this value. So guys, now let's go ahead and talk about this gate, which is called as update gate, right? So update gate is nothing but this gate, and here you have basically temporary hidden state. Okay. Now see guys, it is very much simple. First of all, you need to understand from ht minus 1, I am able to get ht hat, and then from this we are getting ht. Okay. If I combine x of t, right? If I combine both of them, right? Let's go ahead and combine this both of them, and if I combine this and if I pass it to a sigmoid activation function with some weights, I will be getting, first of all, which gate over here? I'll be getting r of t, right? R of t is my reset gate. And with respect to this reset gate, further, you'll be seeing that once I get this r of t, right? Once I get this r of t, I'm doing a pointwise operation. So here you can see I'm doing a pointwise operation again. With this, I'm passing this entire information to my tanh to get this value. Okay. But here you should also remember, here I will further pass this x of t also. Okay, x of t over here. So once I do this operation, that is what is happening, right? ht minus 1 with this operation, and here you can see x of t is passing, and we are passing to the tanh neural network. So hidden neural network where the activation function is tanh. Okay, and here I'm actually able to get h of t. So we basically have to do all this particular information. Now this is very important. From ht minus 1 to ht, we are making a transition, and this gate that we will specifically say, I'll talk about that also. Now from h of t to come to ht, this is the most important step. Okay, and for this step, what we do is that we combine both of this input, then we pass it to the sigmoid activation function, and sigmoid activation function basically means here I have a hidden layer, okay, which will have a sigmoid activation function. And then I get the output over here. This output is nothing but z of t, right? So here I'm just going to go ahead and write z of t. Okay. Now this z of t along with the output of ht, we will do this pointwise operation. Now this pointwise operation that we are specifically doing over here, right? It is between an update gate and a temporary hidden state. My final state is h of t, right? Update gate basically says that what context information needs to be added. But this will be completely dependent on my candidate hidden state. Okay, and candidate hidden state basically talks about the current context. I'll say, hey, if the current context is important, then I will add this information with less information from z of t. So I'll take less info from this, and I'll add more info from the current candidate hidden state. Okay, and that is the reason you'll be able to see over here my h of t, which is my final h of t, which I'm adding it up. It is nothing but 1 minus z of t multiplied by 1 minus z of t. See, 1 minus z of t basically means what? First of all, I'm giving this input on the top memory cell, right? So here you'll be able to see that I'm coupling forget gate with this temporary hidden state. That is what we saw in this variant, right? If you remember coupling forget and input gates here, how we coupled two gates. Similarly here, we are coupling this particular update gate with the temporary hidden state. And the operation is same thing, right? So what I'm actually doing over here, 1 minus f of t. See, 1 minus f of t is further getting multiplied by c of t. Okay, sorry, c of t over here, and this f of t is basically getting multiplied like a pointwise operation with ct minus 1. Similarly over here, 1 minus z of t will basically get done as a pointwise operation with ht minus 1 plus the remaining information based on this context, whatever context needs to be added, right, is getting multiplied by h of t, right? So here, sorry, h bar of t, and finally both this value will get added over here. When both the value gets added, I'm getting h of t. Now what does this basically mean? This basically means very much simple, right? So I'll just take this equation over here. 1 minus z of t multiplied by ht minus 1. That basically means from this particular update gate, what information we should include. That is completely decided based on this temporary hidden state. So in order to understand just this equation, here this equation basically indicates 1 minus z of t multiplied basically means pointwise operation with ht minus 1 plus z of t h dash of t. So this basically includes the information of the current context. Let's say the current sentence that we are getting is very important. I want to include this. How much I want to include it, it will be decided by this value. And the more context that I include, the lesser context I should be including from here. The lesser context from here if I include, the more context I will be including from here. So this works in a much more coupled way. This is what I really want to talk about. Coupled way. So in short, to update from ht minus 1 to ht, this memory cell, whenever we need to update, this is exactly decided with the combination of update gate and your candidate memory gate. Okay, it is decided from both of them. This indicates h bar of t. This indicates, let me talk about the symbol, that is nothing but z of t. Z of t. And one more gate that we specifically had was nothing but our reset gate. This basically indicates how much information we need to reset from this memory cell. Right? So this is the entire context behind GRU. And already I've spoken about how the training usually occurs in LSTM RNN. Similarly, the training will also occur based on all these equations. And here there are less number of weights when compared to LSTM RNN. So this architecture over here, the training also with the terms of optimization is better when compared to the LSTM RNN. So yes, this was it from my side. I hope you like this particular video. I will see you on the next video. Thank you. Hello all. So we are going to continue the discussion with respect to our LSTM and GRU. And in this videos and in the upcoming series of video, we are going to develop some amazing end-to-end projects. In this particular project, we are going to probably talk about the next word prediction, using LSTM. So whatever concepts we have actually learned from LSTM, by using those concepts, we are going to see how in a practical way we can probably go ahead and implement this specific project that is called as next word prediction using LSTM. And after completing LSTM, we will see what are the step-by-step mechanism to probably solve this particular problem statement. And then we'll also apply the same problem statement with GRU. Okay. So let's go ahead and let's see the project overview. So here you can see this project aims to develop a deep learning model for predicting the next word in a sequence of words. The model is built using long short-term memory, long short-term networks, which are well suited for sequence prediction task. The project includes the following step. Data collection, we use the text of Shakespeare Hamlet, okay, as our dataset. We will specifically use this particular dataset. This rich complex text provides a good challenge for our model because again, this particular, if you probably go ahead and see this particular text, right, it's not just a normal English, right? It'll be very difficult just to understand. So we'll try to train our entire model with this particular dataset. Then we have data pre-processing. In data pre-processing, the text data is tokenized, converted into sequence and padded to ensure uniform length. So we will be seeing this data pre-processing technique how to perform it, and we'll also try to generate a pickle file out of it. Okay, the sequences are then split into training and test sets. Then you have this model building where we'll be using an LSTM model is constructed with an embedding layer, two LSTM layer, and a dense output layer with a softmax activation function to predict the probability of the next word. Then we will go ahead and do the model training. The model is trained using the prepared sequence with early stopping implemented to prevent overfitting. Early stopping monitors the validation loss and stop monitoring when the loss stops improving. Okay. Then you have this model evaluation. The model is evaluated using a set of example sentences to test its ability to predict the next word accurately. So finally, once we do all these important steps, then we are going to deploy it by using a Streamlit web application. Okay. And in this Streamlit web application, what it will do is that will allow users to input a sequence of words and then get the predicted next word in a real time. Okay. So all these things we will specifically be doing. Again, this will be really an amazing project altogether. We will be developing this in such a way that we will be able to understand this completely step by step. First of all, we will go ahead and experiment it. So here you'll be able to see that I've actually went ahead and created LSTM RNN folder already in our requirement.txt. Whatever libraries we wanted, we will use this. Okay. So first of all, what I will do is that since I'm working in the same environment file, I will just go ahead and install this pip install minus our requirement.txt. But before that, I would also like to have one more very important library, which is specifically called as, if I probably go ahead and see over here in the requirement.txt, I have to use one more library, which is called as NLTK. Okay. Now this NLTK library will be important if I really want to download this specific dataset. The dataset is basically present over there. Now quickly, let me just go ahead and do the installation minus our requirement.txt. Please don't forget to make the environment variable how we have created for this VNV, right? So this is the first step. We have understood about the problem statement, what we are going to do, and now we have also went ahead and installed the NLTK library. Okay. Now in our next video, we will start step by step. First of all, we will try to complete data collection and data pre-processing. We'll save a pickle file, and then we will move towards model building. So I hope you understood the problem statement. I hope I've also given you an idea how to probably create this particular folder. And in the same VNV environment will work, where we have actually worked with a simple RNN classification. So please make sure that we also use the requirement.txt, what we have given in the ANN classification. Only one library you need to install, that is NLTK. Okay. So yes, this was it. I will see you all in the next video where we will be starting our data collection phase. So I'll see you in the next video. Thank you. So guys, let us go ahead and start the data collection mechanism over here. Okay. Now in this data collection mechanism, first of all, we definitely require some kind of input data, right? And without input data, it will be very difficult to work, right? So first of all, what I will do, I will just go ahead and write import NLTK. And in NLTK, I have a very important package, right? So I'll say NLTK.download. Okay. We will be specifically using this called as Gutenberg. Okay. And in this Gutenberg, we will be seeing there'll be one text file, and we'll try to load that particular text file. So quickly, I will just go ahead and write from NLTK.corpus import Gutenberg. Okay. So I'm just going to specifically use this Gutenberg library. Along with this, I will just go ahead and import pandas as PD. So I'm also going to use pandas as PD. Along with this, the next thing is that we will go ahead and load the dataset. Now, in order to load the dataset quickly, I will go ahead and write data is equal to Gutenberg.raw. And here we inside this Gutenberg package, there is a raw dataset which is called as Shakespeare Hamlet.txt. Okay, so we will try to pick up this specific dataset. Okay. Now this particular dataset is already present inside this package. Now we will take this dataset and we'll save to a file. Okay. I'll go ahead and write with open. And let me quickly go ahead and write my hamlet.txt. I will create a new file. I'll say, hey, open this in my write mode and use a context called as file. And I will just go ahead and write file.write. And whatever data I'm actually getting from that particular txt file, I'm just going to write in this. Okay. So this is a very simple way of doing the data collection. Over here in the Gutenberg package, there is a txt file which is called as 6px-hamlet.txt. Okay. So once I execute this, you'll be able to see there will be one txt file that will get created. Okay. I'm getting an error. Let's see what is the error. Partially initialized module has no attribute internals, most likely due to circular import. Okay. Let me do one thing. Let me restart this kernel. Okay. Sometimes this kind of issues will definitely come. So I'll just go ahead and execute it. So here you can see NLTK Gutenberg is already up to date. Okay, and now here if you see Hamlet.txt. Okay, so why I got that particular error because I had before starting the recording of the video I had imported it once and I was just trying to do it. So now I just restarted the kernel and now you can see over here I'm able to get this particular Hamlet.txt. Now this is what is the Hamlet.txt, the tragedy of Hamlet by say William Shakespeare 1599, and it's a huge data set. And we'll take this entire data set and we'll train with LSTM RNN. Okay, one more thing that I really want to go ahead and tell you: if you do not have a powerful system, please try to execute all this code in Google Colab. In Google Colab, you have 3 GPUs. Right now, in my system, I have a powerful system workstation, so I think I will be able to install all this and work with this in my local machine. Okay. Now, this is the first step. Now we will go ahead with data pre-processing. Okay. So quickly, let's go ahead and do this. So for data pre-processing, I'm going to import NumPy as NP. Okay, one of the library. Along with this, what I will say, I will go ahead and write from TensorFlow.keras.preprocessing. Okay. Text. I'm going to import tokenizer. Now, with respect to this, I will also go ahead and import from TensorFlow.keras.preprocessing. dot sequence. I'm going to go ahead and import pad underscore sequence. Okay. See, I'll talk about why we are using this particular library. Okay. Everything will make sense once I'm first of all let's go ahead and import it. Okay. Then I'll also go ahead and write from sklearn dot model selection import train test split. Okay. So this is specifically for train test split. Okay. Now let me talk about the first one. Tokenizer is just a library that is present inside TensorFlow.keras, which will actually help you to convert your text into vectors. Padding sequence specifically makes sure that all the sentence length will be same in the while we are training the entire LSTM and this is specifically for doing a train test split. Now I have to apply. I'll go ahead and load my dataset and I have to apply this entire tokenizer and padding sequences specifically in our dataset, right? So I'll go ahead and write with open and here let me just go ahead and write hamlet.txt. Here I'm going to basically use my read mode and I'll say hey as file and I'll just go ahead and write text is equal to file.read and here we're specifically going to use this dot lower. Okay, so first of all I'm just lowering all the text and probably taking in the specific variable. Okay, after this I will go ahead and tokenize the text. So in order to tokenize it I will say tokenizer will be my variable. I will go ahead and initialize this particular token to my tokenizer object or tokenizer class. After this you'll be able to see that I will quickly go ahead and write tokenizer dot fit underscore on underscore text. Okay, so this is a function which we are specifically going to use this, and this text needs to be given in the form of list. Okay, so this is a function that will be specifically used in we just need to use this fit underscore on text so that it will apply this entire tokenization on the text that I'm actually giving. Okay, now we will just go ahead and calculate our total words. So let me just go ahead and write total words is equal to length of tokenizer dot word index. We will get the word index. Okay, so word underscore index, and since we know that it is starting from 0 index, so I will just go ahead and write +1. Okay, now if I go ahead and see my total words, okay, there is it is saying that hey no module name TensorFlow.keras.preprocessing. So here guys I've just made a minor mistake where I've done the spelling change. Instead of writing processing I've written this. Okay, so double S it should be like how we have written for the top one. Right now let's go ahead and execute this. Now the total number of words that I'm actually getting is 4818. Okay, and you'll be able to see that if I just go ahead and write tokenizer.word index, right, you'll also be able to see all the word index. Like for the number is 1, the index is 1, then and you have the index is 2, for 2 you have the index is 3, of 4, like this for every word you'll be able to see the indexes. Okay, now this is what my tokenizer work is specifically doing. Now let me quickly go ahead and make sure that we have to try to create some input and output sequence, right? Now how do I actually go ahead and create input and output sequence for this particular data set? But here you can see with respect to every word I'm able to get an index by using this tokenizer. Okay, and that is why this tokenizer is specifically used, right? So when we are fitting it over here, we are basically creating indexes for words. Okay, perfect. Till here, I think everybody's clear. All right, now let's go ahead and create my input sequence. So I will go ahead and create my input sequences. Okay, so input sequences basically means I will have input text and then I should have for that input what will be the next word, right? Something like that. So I will go ahead and create a list which will say input sequences is equal to this list. I'll say for line in text dot split. I will split this entire text with respect to a new line. Okay, for every line. Okay, then I will go ahead and write token underscore list is equal to, and I will use the same tokenizer and there will be something called a text to sequence. There's a function which is called as text underscore to sequences. Okay, and I will take every line for this. Okay, every line, and from that particular line let's take the 0th index. Okay, inside this particular token list. Okay, so let's see, you'll be able to understand the output. Okay, what will happen, just wait for some time. So I will go ahead and write for I in range. Okay, I'll say 1 comma the length of token underscore list. Okay, since I'm going to add every tokens inside this, okay, I'm just going to write for every line with respect to all the elements. I will say n underscore gram underscore sequence is equal to token underscore list with respect to colon I plus 1. Okay, you'll understand it what exactly we are doing. Okay, so here input sequence dot append will be nothing but n gram sequence. Okay, now see what we are exactly doing over here. We're splitting each and every line. Okay, we take that particular line and we apply to this particular tokenizer. And if you don't know about text to sequence, okay, so this is what it is going to do is right, it will just going to convert that text into some sequences wherein we'll have some kind of vectors also. I'll show you. Okay, just wait. Like finally you'll be able to see what will be the output. So let me execute this. Now you know this will basically be my input sequence. Now if you see the input sequence, right, so for the first sentence, right, let's say this is my first sentence, actus primus sinus primae, right. So first of all, see I'm able to get this 1687, right. So in short, what this is basically doing is that it's converting every word into sentence line by line, right, line by line, and we are getting that particular value. Now see, first sentence is basically having 2 words, second sentence is having 3 words, then you're having this, then you're having this, and this is how it is basically getting divided. Like all the sentences basically converted into an input sequence. Okay, so let me do one thing. Let me just create this variable like this: input underscore sequence, input underscore sequence. So this is the kind of data preprocessing that we really need to do. Okay, perfect. Till here, I hope everybody's fine. We have just converted our every sentence into a sequence of indexes. Now, the one thing that we really need to do is about a pad sequence. We have to make sure that all the sentences are of equal length, right? So for this, I will just go ahead and apply my pad sequences. Okay, here I'm going to basically use max underscore sequence underscore length is equal to max of. I'll just go ahead and apply this max of. I'll use one list and I'll ask length of x, and I'll write for x in input underscore sequence. Now what I'm actually going to do is that for every see, when we are saying we are iterating through each and every sequences for every sentence, and then we're calculating the length, right, and whatever max length we specifically get right over here. So if I just go ahead and execute and see this max underscore sequence underscore length, you'll be able to see that 14, right, 14 is the maximum length with respect to all the sentences that we have over here, right. Now what I'm actually going to do, I'll take input sequence something like this. I'll apply this input sequences and I'll say hey, go ahead and use this np.array, okay, and I will apply this pad sequences in all the input sequence, okay, all the input sequence with max length is equal to nothing but this max sequence length. Okay, the reason why max sequence length, I'm basically saying, hey, make all the sentences to maximum 14 indexes or 14 characters. And here what kind of padding I will be using? So padding will be nothing but it will be something like pre-padding or post-padding. It is up to you. Now if you go ahead and see the input sequence, now every sentences will be of the same length, and the maximum length will be of 14 sentences, and we have added 0 in the front, right? So that is the reason you'll be able to find this kind of input sequence, right? So here we have specifically done the prediction. Okay, now it's time that we divide this entire data set into training and test data set. Now see, training and test data set, how should we specifically divide? In my x-axis, I consider for the first word, right? Here I will probably take just one example. What I will do is that I will just take let me write it over here. Okay, so here I'll say create prediction predictors predictors and label. Okay, so here I'm going to write import TensorFlow as TF. Okay, I will just go ahead and write my just a second import TensorFlow TF. Okay, now once I import TensorFlow TF, I will go ahead and use my x and y coordinates. So this x will be my independent features, y will be my dependent feature. I will go ahead and write input sequences, input underscore sequences. I will take all the words and just remove the final word. Okay, and in the output sequence, which is my y, I will take this input sequences. I will take all the words and I'll just take the last word. Okay, so the last word will specifically go to y, and the first word will specifically first all the words till the last will go to my independent feature. Okay, now similarly, if I go ahead and write y, I'll just go ahead and say hey tf dot keras. So I'll just go ahead and write tf dot keras dot utils dot to underscore. Or first of all, let me just go ahead and execute this. Okay, so here you'll be able to see this is my x. Okay, all the input features, and when I go ahead and see my y, so here you'll be able to see this indexes. Okay, with respect to so many number of indexes will be there. Okay? Now for this y, we cannot just keep this into indexes, right? Based on the number of classes, some words may be repeated, some words may not be repeated. We'll try to convert this into categories. So in order to convert this into categories, I will say tf.keras.utils.to underscore categorical. Here I'm going to basically take y, comma number underscore classes is equal to total underscore words. Okay. Now if I go ahead and see my y, it will be like completely wherever this particular index will be present, that will be 1, remaining all will be 0. Wherever this index will be present, that will be 1 and remaining all will be 0. Wherever this index is present, that will be 1, otherwise remaining all will be 0. So we have actually converted our output feature with respect to all the categories, right? Now it's time that we go ahead and split our data set into train and test. So here you can go and do this. I've taken train test split, xy, test size is 0.2. Okay. So once I execute this, now we are going to we are ready to probably go ahead and train our LSTM RNN, right? Train our LSTM RNN. So this process of LSTM RNN training is going to definitely take time. Till here, I think we have done the data ingestion and data pre-processing. We have our input features with respect to the index, and we have our output features, right? Now it's time that we go ahead and train our entire model, and that will be shown in our next video. So I hope you like this particular video. This was it from my side. I will see you in the next video. Thank you. So finally, guys, I'm quite excited that we'll finally train our LSTM RNN, and this step by step we'll see again how to probably go ahead and train it. Already we have done the data pre-processing and data ingestion part. Now let's go ahead and do this. So first of all, I will go ahead and import from TensorFlow. Okay, dot keras dot models import sequential. Okay, so we are going to specifically use sequential. Along with this, I will go ahead and write from TensorFlow dot keras dot layers import embedding. Okay, embedding, and then along with that we'll also use LSTM. Then I'll go ahead and use dense. Right, we require an embedding layer, we require an LSTM layer, we require a dense layer. And let me go ahead and use one more, something called as dropout. Dropout is specifically to disable some of the neurons while training, so that your entire model does not overfit. Now I'll go ahead and define the model. Okay, so first of all, I'll go ahead and initialize with sequential. Okay, then I will go ahead and add my embedding layer. I hope I've actually covered everything as such, in the course itself, embedding, and then I have my total underscore words, comma, let's say here the number of dimensions that I'm going to take is 100, and my input length should be input underscore length should be my max sequence length. Okay, this is what we are specifically using for our embedding layer. Then let's go ahead and add model.add with respect to LSTM. I'm going to add my LSTM layer. Let's say I will go ahead and use 150, and along with this 150 neurons. Okay, we'll also go ahead and write return underscore sequences is equal to true. Okay. Along with this, I'm also going to go ahead and add my dropout layer. So let me just go ahead and add some dropout layer. Where I'm saying just go ahead and make sure that you disable 20% of the neurons, hidden neurons, when you are training the neural network. Along with this, let me just go ahead and add one more LSTM layer. If you want, you can add one more. Let's see whether it will be able to perform well. And here I'm going to use the number of neurons as 100. Okay. And then finally, I will go ahead and add model.add. And quickly, let's go ahead and create my dense and the total words. And here I'm going to use my activation function. Activation is nothing but softmax, since it is an multi. See over here, I'm using softmax. The reason is very simple, because with respect to the softmax, here my activation function, because my output, right, it is multi-class. It is not a single class, right? So that is the reason I'm using softmax. Otherwise, I would have used SIGMAT. Okay. Now we will go ahead and compile the model. So this will be the next step for compiling. So I will go ahead and write model.compile, and the loss that I'm actually going to use is nothing but categorical cross entropy, since it is multi-class. Okay, cross entropy, and the optimizer that I'm actually going to use, optimizer will be nothing but it will be Adam. Okay, and the metrics that I'm actually going to use is nothing but accuracy. Metrics will be accuracy. Okay. So finally, I can go ahead and check my model.summary. So let me go ahead and write model.summary. So overall, once I execute this, you'll be able to see I'm getting some kind of errors. So what is the error? Let's see. Got an unexpected keyword argument dropout. Okay, I should be writing this in this way. It is not a keyword argument, but instead it is a like how we have a separate layer like that. Okay. So now you can see over here, my embedding layer is my first layer, then LSTM, then dropout, LSTM second layer, and then finally this is my output layer, right? And total number of trainable parameters is how much, right? So this is somewhere around 12,19,418, right? So these are my total trainable parameters. Now it's time that we go ahead and train our entire model, right? Now to train the model, I'll just go ahead and write like this. So let's go ahead and train the model, and here I'm just going to use my history. Okay, is equal to model.fit. And with respect to this, I'll go ahead and write my X train or my Y train. Let's use around at least 50 epochs, and this is going to take some time. It's not going to happen very fast. And if I also go ahead and use this 50 epochs, right, it is also not going to probably give you the 90% error. And for that, I think we need to run it for 1 hour. Okay, but obviously, I will just try to show you with respect to 50 epochs. So my validation data is basically having my X test, and here I'll use one more bracket, and this will basically be my Y underscore text. And I will just go ahead and use my verbose is equal to 1 so that it gets displayed. Okay, so this is my history with respect to the model fit. Now quickly, let me just go ahead and execute it. So now my execution is started. Input 0 layer with the layer none, 14. So guys, over here, one issue over here that we are specifically getting is saying that hey, input 0 place sequential 1 is incompatible with the layer expected shape none, 14. But we have given this found shape none, 13. The reason is very simple, because here I've given this max sequence length. Here I'll just give it as -1. Okay, so that is the reason I think that is happening. So let's go ahead and execute this quickly, and here we will go ahead and start the epoch. Okay, so please make sure that you see this particular code, and I'm also going to keep the error similarly like that so that you'll be able to fix it. Okay. Again, if I probably see my max sequence length over here, it is basically starting from 0, right? So when we are starting the indexes from 0, then we to get the actual length of the indexes, I'm just doing it as -1. So here you'll be able to see my epoch has basically started. I'm in epoch 2. My accuracy is 0.03 right now. I hope so. It should keep on getting increases. So there's just 3% accuracy. and obviously you'll be getting this accuracy because hamlet.txt is very complex. It is not that simple. Okay, so now you'll be able to see that it will slowly increase. Now see, from 0.038 it is going to 0.046, then 0.55. I hope I've used everything right. Accuracy is the parameter. Okay, perfect. But it will increase. You just need to run it for many epochs. At least 100 epochs if you run, you'll be able to gain some very good accuracy. So now the accuracy, the loss is also decreasing over here. Here also the loss is decreasing. So let this continue this specific epoch, and I think once the training gets completed, then I will show you the final accuracy. So with respect to only 50 epochs, you can keep on increasing the number of epochs to 100 and do it. And anyhow, you can also go ahead and apply this early stopping if you really want. Okay, so with respect to that, you can go ahead and apply early stopping if you want. Okay, but again, I did not apply it over here. If you want to apply, I'll just give you the code with respect to early stopping also. Okay, how to probably do it is early stopping and where to add the particular parameter as you go ahead. Right. So if you really want to just implement early stopping quickly, I will just make a code over here and I will define this code over here itself. Right. So first of all, let me just copy and paste this. Okay. Now first of all, it will tell you to hey, go ahead and import this early stopping. So we will go ahead and do this. And in the callback, so TensorFlow.callback will be implementing this early stopping. When you're doing the fit, over here, when you're basically giving this particular when you're doing this particular fit, right? At that point of time, you can add this early stopping, right? You can just say, hey, my callback is something like this, right? I'll be able to add this particular callback. Okay, that's it. Then automatically the early stopping will be enabled. But I think this loss will keep on decreasing as we go ahead. So let us wait until this entire training gets happened, and then we will go ahead and do the prediction. Okay. So yeah, in some time I'll see you all. Thank you. So guys, here you can see the training has been stopped in 50 epochs because I only did till 50 epochs, and here I'm able to get an accuracy till 40%. It started from 0.03, right? 3% till 40%. So if you probably do for another 50 epochs, I think the accuracy will keep on increasing. Okay. Now what we'll do is that we'll try to create a function, okay, which will be able to predict the next word. Now see this. So this is nothing but prediction the next word. Here we need to give the model tokenizer, text, and max sequence. Okay. So first of all, we'll use the tokenizer. We'll convert that into sequence. How we did it. We'll say, hey, if length of this particular token list is greater than or equal to max sequence length, right? At that point of time, we will just make sure to ensure the sequence length matches the sequence length minus 1, right? So this is the operation that we are specifically doing. We'll take the token list. We will give the indexing from this particular value, right? Like max sequence length minus 1. And most of the time, you'll be able to see that when we get this particular value from this value till the end, we are going to take that entire token list, right? Then we are going to apply the pad sequence where we'll specifically use pre-padding. Then we will go ahead and use model.predict on this particular token list, and we will get the predicted word index wherein we'll say, hey, whichever has the highest probability with respect to all the outputs, take one. Take that specific value and show me that particular index. And then I will convert that particular index into a word. So I'll write for word comma index in tokenizer.word underscore index.item. If index is equal to predicted word, return that specific word. Now you'll be able to understand it once I probably go ahead and execute it. Let's say this is my input text. Okay, my input text is that I will say, hey, to be or not to be. Okay. Suppose let's say this is my input text. I will go ahead and write this is my print. F. I will just go ahead and write my input text. This is colon, nothing but here. I'm going to basically go ahead and give my input text. So this will basically be my input text over here. Okay. And then I will go ahead and write max sequence length. Max sequence length is equal to model.input of input of shape of 1 plus 1. Okay. So plus 1, you'll be able to see that this will basically be my max sequence length because I have to make sure that whatever max sequence length we have initially taken, that needs to be same thing, right? Then we will go ahead and predict our next underscore word. And here I will just call my predict next word function. Here I will give my model, then my tokenizer. Okay. Tokenizer. And along with this, I will also go ahead and give my input text. Okay. And then finally, let's go ahead and give my max sequence length. Right, these are the parameters that I need to give, right? And that is the reason I'm giving this. Okay. And finally, let's go ahead and print. And here I will just go ahead and write my next word prediction, which will be equal to my next underscore word. Done. Let's go ahead and execute it. So to be, not to be, next word predicted is considered, right? It is good. To be or not to be considered, right? So this looks like a very good word. Okay. Finally, after doing this, I will go ahead and save my entire model. So quickly let's go ahead and save the model that I've actually created. Okay. So I'll write model.save, and here I'm going to basically use next underscore word underscore LSTM. Okay, .h5 file. So this will basically be my file. Other than that, I will also go ahead and save the tokenizer, right? So tokenizer also needs to be saving because we need to use the same tokenizer what we have created. So here I will go ahead and write with open tokenizer dot pickle file. I'll open this particular pickle file and it will be in my write byte mode. I will say as handle. Okay, this will basically be my context. Let me just go ahead and write pickle.dump. And here, let me just import pickle because I will be requiring pickle. Okay, pickle.dump. And here we'll dump this entire tokenizer, comma, handle, comma. I'll use a protocol also over here. This protocol will be equal to, and we'll use pickle dot highest protocol. Okay. Okay, one assignment, just try to find out why this specific thing we specifically use. Okay, so this will be an assignment for you. Come on. So has no attribute dump, dumpy. It is written dumpy. I should have written dump. Okay, so once it is executed, now in the same folder you'll be able to see my next word lstm.h5 and tokenizer.pickle. Okay, so here is all my things, and I can go ahead and use more text if you want. Okay, to be bad is better than. Okay, I'll just try to go ahead and predict it. It says to be bad is better than and. Okay, so since the model accuracy is a little bit less, all the time you're not going to get the right output. Okay, so you can go ahead and try it out. But I'll just go ahead and use some more examples from here. Okay, let's say I'm using this. Okay, I don't know like what exactly these words are, but I'll just try to use this whether it'll be fine or not. Let's see. Okay, I'll use this particular sentence and then we are going to do the prediction. Fantasy. See, it's coming. Fantasy, right? The prediction is absolutely right, right? Mar Horatio Ciais, but our fantasy, right? This is good. Let's see some more things. I'll say, well, born last night of all when you and same starry. I don't know whether this is English or something else. Okay. Okay, same. Let's execute it. Cosine. It came as cosine. Okay, the exact input here we have to get started, but it got cosine. That's okay. So I hope you're able to understand this now. In our next video, I'm going to create a Streamlit app, and we will use all these things, all these functions. First of all, we'll be loading our h5 file and all, and we'll try to convert that into entire end-to-end project using Streamlit. So yes, this was it from my side. I will see you all in the next video. Thank you. Take care. So guys, finally, now let's go ahead and create our end-to-end web app using Streamlit. So here in the LSTM folder, I will just go ahead and create my another file, which is called as app.py. Okay. Now, first of all, this will be a Streamlit app. So let's go ahead and import all the important libraries. So this will basically be my important libraries that I need to load. Pickle, NumPy, Streamlit, and we'll also be using this load model so that we'll be able to load the X5 file. And then we'll also be using the span sequences. Okay. Now the first thing is that we will quickly load the LSTM model. Okay. And then I will be having model is equal to load underscore model. And then I will go ahead and use my H5 file name. It is nothing but next word underscore LSTM. Okay. So here I'm going to write next word underscore LSTM dot H5. Okay. Then you'll also be able to see that I will load the tokenizer. Okay. Tokenizer. And here I'm going to write with open. It is nothing but tokenizer dot pickle comma read byte mode as handle. Okay. And then I'm going to basically use tokenizer is equal to pickle dot load with respect to our handle. Okay. So I'm going to specifically use this. And here now what I will do is that once I've loaded this, the same function I will go ahead and copy and paste it over here to predict the next word, right? And here how we are basically taking the texture sequence, then we're checking the max sequence length, and then getting the token list and predicting the word based on the index that I'm actually getting, right? So this we will be specifically using it. Okay. So I'm copying and pasting from the same IPv4 file. Now I will go ahead and write my Streamlit app. And now let's see, I'll go ahead and write st.title, next word prediction with LSTM and early stopping. Okay. Now quickly, let's do one thing. Let me just go ahead and write input underscore text is equal to st dot text underscore input. Okay, text underscore input. And here we are going to basically tell enter the sequence of words. Okay. And let me just go ahead and write one of the word over here by default. Okay, so it should be something like this, to be or not to be. Okay. So this will basically be my default value that will be present inside my text input box. So here I will just go ahead and create my button. I'll write st dot button, and here I'll go ahead and write predict next word. Okay, done. After this, what I'm actually going to quickly do is that I'll say, hey, if this button is clicked, right, then first of all, I will do these three important things. Okay, so one is get my max sequence length plus one, retrieve the max sequence length from the input model input shape, then predict next word where we are passing model, tokenizer, input text, and max sequence length, and finally, I'm just going to predict the output. Okay, so finally, guys, let's go ahead and run this entire project. So I will just go ahead and open this with my LSTM RNN, and now let me just go ahead and write Streamlit run app.py. Okay, Streamlit. Okay, so once I execute this, here is my entire Streamlit app. Okay. And it'll take some time to load all the models and all. So I think it should be loading the models over here. So here you can see TF enable all this. Yes, perfect. Okay. Again, it depends on your system, how fast you're able to load it, how bigger the specific model is, because in the initial stage when you're loading it, it obviously needs some time, right? And here you're getting also some warnings. The name tf.get default graph is deprecated. Okay. So here is my entire application. Next to word prediction with LSTM early stopping to be or not to be. Predict the next word, and I should be able to get something like crack over here. To be or not to be is like crack. To be or not to crack. Okay, this looks good. Let us try some more words for our page. So I'll go over here. I'll open my Hamlet text. I'll say barn, do meet, something like this. And let's predict the next word. So, well, good night. If you do meet two, it has basically come as two. But again, I think I will just go ahead and use one more word. But again, if the accuracy keeps on increasing, I think we should be able to get the Mar and Lingnan to the profound nest. Okay, so this also is a good meaning if you probably go ahead and see. So, welcome, good, something like this. Okay, I'll just go ahead and predict one more thing. Friends, this is also nice, right? Welcome, Bar, welcome, Horatio, welcome, good friends. So I hope you were able to understand this entire project, guys. And yeah, this was it from my side. Go ahead and write out. And again, if you want more better accuracy, keep on training for another 50 bucks. You will definitely be able to get a good result out there, right? So yes, this was it from my side. I will see you all in the next video. Thank you. Hello guys. So finally, we will also see how you can implement this entire project with the help of GRU-RNN. There is only one difference that you really need to use over here, right? So if you see over here, we are completely implemented with the help of LSTM-RNN, right? We imported the LSTM layers and all, right? Along with this, in the layers itself, you also have an option to add GRU. Okay. So if I just go ahead and use this attribute called as this library called as GRU, so it should be capital letter. So here you'll be able to see that this GRU you'll also be able to use for a specific GRU-RNN instead of LSTM-RNN. And if I really want to write the same thing with respect to GRU, so here I will just give you with GRU-RNN. Okay. Here I can just copy paste over here. Okay. And remember the GRU is imported over here. Instead of writing LSTM, you can go ahead and write GRU here itself. Okay. Similarly here you can go ahead and write GRU, right? So as you know, this is a different variant of LSTM-RNN, so you can specifically use this and you can go ahead and execute this, right? If you really want to work with GRU-RNN itself, right? This is the only change that will happen. And based on this, whether you're using this or whether you're using LSTM-RNN, you can go ahead and update that and you can go ahead and continuously train it. Okay, so this is the only difference with respect to the adding layers with respect to GRU. Now, with respect to an assignment, I will just go ahead and give it to you. Please go ahead and solve this entire problem statement with the help of GRU-RNN and see how much difference you are able to get with respect to the accuracy. But if I talk with respect to GRU over here, you have less number of gates when compared to the LSTM-RNN. So this is the only difference with GRU and LSTM. I hope you like this particular video, and I hope you like this entire series of videos that we have created this amazing project. So yes, this was it from my side. I will see you in the next video. Thank you. Hello guys, so we are going to continue the NLP with deep learning series. Already till now we have discussed about simple RNN, right? And we saw the practical implementation already, right? And we saw complete legal deployment. So this entire implementation with deployment we have also seen. Inside the simple RNN, we also discussed about something called as embedding layer, which was specifically used to convert your text into vectors, right? Then we went ahead and understood about LSTM, GRU, variants of RNN, right? And along with that, other variants also we saw. And I've also completed the practical implementation for this. Right? We understood what were the problems in simple RNN, and then with respect to that, we also understood about LSTM and GRU variants. Now coming to the third one, which is today what I'm actually going to discuss about is something called as bidirectional RNN. Okay, it can be RNN, it can be LSTM RNN. Okay, I'll write RNN or LSTM RNN or GRU RNN, but it will be bidirectional. Okay. Now first of all, I will just try to make you understand why bidirectional RNN or bidirectional LSTM RNN. Okay, and then we will probably go ahead and discuss about the architecture, and we will solve this. Okay. Now first of all, let's go ahead and talk about our simple RNN. Right. In our simple RNN, what we used to do, like or simple RNN or LSTM RNN, what we used to do. So here was my input, here I used to get my output, and here was my hidden state. And with respect to that, if I unfold this with respect to time, right? If I just unfold it, so it would look something like this, right? So this will be my, with respect to t is equal to 2, then I have t is equal to 3, then I have t is equal to 4, like this. I may have a lot of the same hidden neurons, hidden states, right? So over here you'll be able to see I will pass at t is equal to 1, I may go ahead and pass x11, then I may pass x12, then similarly I may pass x13, and finally I may pass s1n. Right? This is with respect to the first sentence, right? And you know that here also for every neuron, right, we will also be getting an output, and finally whatever output we are specifically getting over here, let's say if I just want to predict one kind of output, if I just take an example with respect to sentiment analysis, so this will be my final output y hat. And before I get to y hat, here I'm going to just apply a sigmoid activation function, right? Here I may go ahead and apply my sigmoid activation function. So let's go ahead and apply this. Right, so this will basically be my sigmoid. If I just have a binary classification, I used to get y hat, and then we used to basically go ahead and compute our loss, and based on our optimization, we used to reduce this loss. Okay, and by default, some initial weights also we used to transfer. And here, with respect to the weights, what all weights we used? One was our input weight, one was our hidden weight, and this is also my hidden weight. This is also my hidden weight. And here you will also be able to see that I will get this as my output. I can just consider drawing it over here. Right, so let's say, I hope everybody remembers this architecture, right? So I may take this as my WO output, and then pass to my sigmoid and get my y hat. Okay, and then what we used to do is to basically go ahead and compute our loss. Okay. Now, in this scenario, right, and when we just consider this is basically my hidden state. So in the input also, I will be giving some kind of weights, and this will also be my hidden weights, right? So three types of weights we were specifically using: input weights, hidden weights, and WO for output weights, right? And with respect to this, I had my output something like O1, O2, O3, and O4, right? Whatever outputs we are basically creating. Now, let's take one specific example. And before that, I just want to talk about various problem statements that you can solve with RNN, okay? Like there is one kind of RNN which is called as one-to-many RNN. Okay, one-to-many RNN. I'll just first of all categorize them, okay? Then I have something called as many-to-one RNN, okay? And the third one is like many-to-many RNN. Okay, many to many RNN. Okay, and the fourth one is something like one to one RNN. So these are the different types of RNN we specifically use. Okay, one to many RNN, many to one RNN, many to many RNN, and one to one RNN. Now, in order to explain you some of the examples, I'll first of all go and show you these are the variants or these are the types of RNN that I can say with respect to problem statement. Okay, and we will go ahead and discuss some of the types, and then we'll go back again to our LSTM RNN. We'll try to discuss. Sorry, we'll go towards this bidirectional RNN and discuss more about it. Okay, so first of all, let me just quickly go ahead and give some of the examples of one to many RNN, many to one RNN, and all with some real world examples itself. So guys, so here is one of the diagram that I'm specifically using to explain you about one to one, one to many to one, and many to many. And there is also one more variant of many to many. Okay, so we will just go ahead and discuss about this, and let's take one example for at a time. Okay, now with respect to this particular RNN, you should be able to see that there is one input and one output. Okay, one input and one output. So we will discuss one example for this. Okay, so here I'm giving one input and I'm getting one output with respect to this particular RNN. Okay, if I probably go ahead and see one to many. Okay, one to many. So here in this one to many, you'll be able to see that I'm giving just one input, and based on this one output, okay, it will basically give you several outputs. Okay, so here your output are many. Okay, now in order to talk about an example over here, okay, one input and many outputs. Okay, so that is the reason we say it as one to many. Okay, let's say I give an example in Google. Like if you probably there is a concept of something called as image captioning. What does image captioning mean is that whenever I specifically give one image, okay, when I specifically give one image captioning, when I give one image, the model should be able to tell or give a text information about that particular image. Let's say if I am giving a image which has a dog and a cat, right? So here, let's say there is one dog and there is one cat, right? So this model should basically be say after giving this particular image, there is a dog and cat in the image, right? There is a dog and cat. So this is basically called as image captioning. In this, we're just giving one input, but we are getting many outputs in form of words. Okay. Now similarly, if I go ahead and see many to one, okay, in many to one, you'll be able to see that over here. I have multiple inputs and I have one output. Okay. Now this was example. If I probably go ahead in the Google search, Google image search, I search for input. Let's say a cat eating food. A cat eating food. So if you go ahead and search this in Google search image, you'll be able to get an images of dog eating, of cat eating food, right? You'll be able to get this specific image. Now in this case, you are able to generate one output with respect to multiple inputs, right? So here your inputs are multiple, your inputs are many, and your output is one, right? Similarly, here you have many to many. So these two examples that you can specifically consider is like your language translation. So in language translation, if I want to convert one language to the other, I may give many inputs, right? And similarly, I will be able to get many outputs, right? Based on the sentence that we are actually working with. Now, these are some of the types of RNN that everybody should probably know about, okay? And the reason why I'm talking about this particular RNN, let's say if I have a use case, which is like many to many. Now, let's go back to this particular use case, okay? I'm just going to probably take this entire diagram, okay? I'll copy this, again, go back and explain it over here. Now, in this particular case, if I am considering all the outputs, right? If I'm considering all the outputs here, let's say this is my Y1, this is my Y2, this is my Y3, this is my Y4. With respect to all the inputs, if I'm considering all the outputs, if I require all the outputs, then I will specifically use many to many. And if I'm considering all the outputs, here I can basically go ahead and use sigmoid or softmax, any types of activation function like how I have actually applied over here, okay? So, why I am teaching you this? Let's take a specific example. Okay, so I will take a text example. Now, that is where your bidirectional LSTM RNN or bidirectional RNN will come. Okay, so my name is Krish. I'll say, hey, Krish. Okay, I'll just write a sentence. Likes to eat one word dash in Bangalore. So I'm giving this specific example. Okay, Krish likes to eat. Okay, one word. I need to predict this word in Bangalore. Okay, so let's say at x t is equal to 1, I give this word. At t is equal to 2, I give this word. T is equal to 3, I give this word. T is equal to 4, I give this word. Okay, let's consider that I'm giving this. Okay, so I'll just say instead of writing eats 2, I'll just go ahead and write eats. Okay, Krish eats dash word. Okay, so first word goes over here, second word goes over here, and I need to basically do the prediction for the third word. Okay, prediction for the third word, and that is what I really need to predict it over here. Now, in this scenario, please note, okay, if I want to probably calculate this particular word, if I use, or if I need to predict this word, if I use simple RNN, or LSTM RNN, or GRU RNN, right? In all these three cases, this prediction will be dependent on these two words, right? On the previous context, right? But here, you'll be able to see this specific example. If I really need to do the prediction for this particular word, I also need the context of the upcoming words. Because if I write Krish eats dash in Bangalore, so in Bangalore, what is famous? I will read that, right? Let's say there's also one more sentence. I will go ahead and write over here. Krish eats something in Paris. So if I take this word, now you know that if my first real training data says that I eat dosa, okay, if you don't know about dosa, I think you can go and search in Google. Krish eat dosa in Bangalore because dosa is very famous, right? Now, obviously, in my training data, I will have dosa, right? And over here, you'll be seeing that in my training data, I may have something like this. I may want to eat pizza in Paris because pizza may be famous in Paris, right? So here, you will be able to see that this word, if we are trying to predict, it does not only depends on the context of the previous word, but it also depends on the context of the forward word. Because when the country changes or when the city changes, you'll be able to see that this specific word may also change. So in this scenario, if I really want to predict a word in between, here I need to also have the context of the upcoming word. But in this scenario, I don't have that. If I use simple RNN, LSTM RNN, GRU RNN, I am not able to do that. I'm not able to get it. So how do we fix this particular problem? So fixing this specific problem is what bidirectional RNN is actually doing. Now, in the case of bidirectional RNN, what will specifically happen? We will discuss. So let's go ahead and take this again. Okay, I will just go ahead and drop this for now. Okay, so here you'll be able to see this. I don't know what has happened, but let's go ahead and draw this again. Okay, I will go ahead and draw this. So first of all, I will go ahead and draw simple RNN, and then I'll try to convert that into a bidirectional RNN. And how? With the help of further context, we will probably predict the words. Okay, so let's say this is my LSTM, or this is my RNN with respect to unfolding with respect to time. Okay. And here you have this. Okay. Now in this, I pass my input. With respect to this, I get my this. Here is my input. Here is my input. And you know that since we are trying to solve a many-to-many problem, it can be many-to-one. It can be any kind of problems. Okay. So here, what we are basically going to do here is my output. Okay. Now you know that if I have a sentence like this, right? Krish eats dash in Bangalore. Right? I need to predict this particular word. In this case, I will give my x11, x12, x13, like this up till the x1n, whichever is the last one. Right? Here you know that what we will be having. Here we'll be having our input weights. Here hidden weights. Here input weights. Here hidden weights. Here input weights. Here hidden weights. Okay. Similarly here. Input weights, and here finally I'll get my output weight. Okay, and with respect to this output weight, it will pass to the same activation function, whatever activation function. Now in this case, what we do, we pass one by word, one word at every time step. T is equal to 1, T is equal to 2, T is equal to 3, T is equal to 4. So this is my RNN, a simple RNN, right? Or if I take LSTM RNN, this will probably be changing inside that, but the flow will be almost like this, right? Now what does bidirectional LSTM says? Hey, if I want, so let's say this is y1, y2, y3, y4. Okay, it says that hey, if y3 wants the context of the upcoming words, it is better that you use one or RNN and make sure that instead of passing the words from front, you pass all the words from back. Okay, so what it is saying? Hey, go ahead and try to create another RNN. So here I will go ahead and create another RNN, which will look something like this. So let's say this is my RNN, this is my RNN, this is my another RNN, this is my another RNN. Okay, now I will consider all this RNN. Then what I will do, along with this inputs, I will also pass this input here. Okay, and here I'm going to get my output. It will get combined to this particular output. Along with this, you'll also be seeing that I will pass this information one by one. I will pass this information. See, this needs to be also getting connected, right? Without the other RNN, if it is not connected, then it will be of no use, right? So what we'll do, we will try to connect this RNN with this RNN with this, then we'll connect this RNN with this, like how it is connected over here with respect to the hidden state. Okay, and whatever RNN is basically coming out as an output, this will get combined to this y3. Okay, so this will get combined to y3. Let me just complete this drawing, then you'll be able to understand more and why we are specifically doing this. And you should know that all these words that I'm actually passing, right? All these words, this should also get connected to this. It should also get passed to this. So here are all my words, right? Right. So this is the entire architecture of a bidirectional RNN, or it can be LSTM RNN. If I just change this hidden layer from RNN to LSTM RNN, it becomes bidirectional LSTM RNN. Okay. Now see, focus on this entire architecture. First of all, I will use this white colored RNN or LSTM RNN in the forward propagation by passing this word. So this will be my x11, this will be my x12, this will be my x13, x14, x15. Okay. So I will be passing every word over here one by one, right? In this direction. In the other RNN, I will be passing from backward direction every word. So here you can see my last word at t is equal to 1 will get passed over here, right? From in the backward direction. Then my next word will get passed over here, right? Then my next word will get passed over here. So with respect to timestamp, in the reverse direction, if I go from this direction, this will be t is equal to 1, this will be t is equal to 2, this will be t is equal to 3, this will be t is equal to 4. And I am just reversing the sentence. So first Bangalore will get passed over here, then in will get passed over here, then we will also go ahead and calculate the y hat, right? And this will basically get concatenated, this will get combined, right? So I hope you are able to understand this entire flow. Now, what is the use of this? Let's say if I want to do the prediction for y3, right? Let's say I want to do this prediction of this blank, Krish eats dash, okay, some blank statement. So here you can see that now to predict this, I will be having the context of x12. I will be having the context of x11. Along with this, you'll also be seeing that I will also be having the context of this particular words because this RNN, when it is running from the reverse direction, that entire context of x14 and x13 will be available. And when it says, okay, Krish, and Bangalore is also coming from this particular direction with respect to the vectors, it will definitely be able to understand that, okay, the food that's probably famous in Bangalore, that will only get predicted. Okay, so this is the entire funda behind bidirectional RNN. Right, I can go ahead and create my hidden layers over here. Right, it is very simple. What we are doing, we are combining things. We are just combining. Whatever output we are basically getting, if this is my output, I may apply sigmoid activation function over here, or this is my output, I may apply sigmoid activation function. But here, I'm getting the context of the previous word, and I'm also getting the context of the upcoming words, and based on that, I'm able to do the prediction. So if I know Bangalore, if I know Krish, if I know Paris, if I know Krish, then this RNN will be able to perform well when compared to the simple RNN and LSTM RNN. And that is the biggest difference with respect to the simple RNN and LSTM RNN. Now, one assignment that I definitely want to give it to you. Okay, I know it is a little bit difficult assignment I'll give you. You need to come up, just keep on exploring, see the research paper. Okay, you need to come up with forward propagation equations, like how we wrote the equation for LSTM and simple RNN. And similarly, what will be the basic equations for this forward propagation? I need to know this first of all. Okay, so here you'll be able to see I am combining this with this, right? So this will also be, there will be some weights, right, which I'm actually passing. This will be my x11, I'll be passing to this. Okay, it will not be y of I over here, w of I, but this will get connected. So here I'm passing this input also, I'm passing this input also, along with this input I will be passing over here, right? This is the same words input I'm actually giving. That basically means that the same word which I'm passing over here, that word will also go over here, right? So just see what will basically happen with respect to every output. What will happen if I'm getting O1, O2, O3, O4, because this is also getting combined to this, right? So just come up with the forward propagation equation. See research papers, come with different ways and try to do this. Okay, this will basically be an assignment to understand, but this is how your entire bidirectional RNN actually works. Okay, so I hope you're able to understand. I try to simplify this as much as I could, but again, the main aim is over here that we need to provide the forward context to the output for doing the prediction. It will actually help us to do the proper prediction. So yes, this was it from my side. I will see you all in the next video. Have a great day. Thank you. Take care. Based on the output, right? Oh, sorry, based on the input that I have. So here, this line that you see, this is basically your long-term memory, right? If you remember in LSTM, it is your long-term memory and this is your hidden state, right? So along with this input, whatever operation basically happens inside the LSTM, if you remember, we in the LSTM, we have something called as forget gate. We have this input gate, right? We have something called as candidate input. We have discussed all about this. Third thing that we specifically have is our output gate, right? So all this gate, what operation it basically does, it does like what context needs to be added in the longer memory cell and what context needs to be removed from the memory cell. Along with that, what needs to be retained in the short-term memory cell, which is nothing but the hidden state. As I said, this is my long-term memory, right? And this is my short-term memory. Right? We use this long-term and short-term memory. Now, whatever operation is basically going to take with respect to that input. Now, see, there is an input which is called as thank you, right? And I need to convert this word thank you, let's say, into French, which is basically written as gracias. Okay. Now, in order to convert this, how my input data will look like. So this will specifically be my data set. In my data set, I will be having my English word and I will be having my French word, right? Now, with respect to this English and French word, the first word will be something like thank you, and the conversion that you specifically have is something like gracias. Okay. I hope this is written in French. Okay. Now, what does over here you'll be able to see that inside this LSTM, I will be passing my entire sentence. Okay. I will be passing my entire sentence. Along with this sentence, what I will do, I will add a special character like SOS and ENDOS. SOS basically means it is just to indicate it is the start of this particular sentence, and EOS basically indicates it is the end of the statement, right? Similarly, for this French word, I will also go ahead and write SOS, gracias, and we will write it as EOS. This is important just to make sure to indicate the neural network what exactly is the start of the statement and end of the statement. Okay. Now, this thank you is basically getting converted into a vector. Okay. So let's say over here by using all these characters, now how many characters I have? 1, 2, 3, 4. Now, if I'm using a one hot encoding, right? So first word that is probably going to go into the LSTM. So what we are basically going to do, this will basically be my LSTM in my encoder. Okay. So let's go ahead and draw this. So if you want, I will draw it properly. Okay. So this is my entire encoder. Just to give you an idea how the entire training basically happens. So this is my encoder. Now inside my encoder, you know that what I use LSTM, right? So this is my LSTM. Inside my LSTM, you know that I should have two memory cell. One is for long term and one is for short term. This is indicated by CT. This is indicated by HT. Okay. Here, forget gate, input gate, and output gate. All the operation is basically going to happen, right? Whatever output that is probably coming from here, I will not be taking that. So what we do in the encoder stage is that very simple. We give every word one by one to the input over here to the LSTM, right? So let's say the first word that I'm actually going to give is nothing but SOS. So this SOS word, how do I give it? Okay. Let's say if I'm passing SOS word, right? First word is SOS. So in the first instance, SOS when I pass, this entire embedding will basically happen, right? Here we can use word2vec, here we can use any kind of embedding techniques, right? But the most efficient one is embedding technique with respect to embedding layers, right? So here I have SOS. So for SOS, since I have total 4 words, this will be 1 and remaining all will be 0. Let's say that I'm just using one hot encoding, right? So in this particular word, my SOS is getting passed, okay? And then in the next step, what it will do, when time is equal to 1, it will go to my next LSTM, right? Now in this LSTM, what I'm actually going to pass my next word. My next word is nothing but thank you, right? Now in the case of thank you, this will be 0, 1, 0, and 0, right? So this will basically be thank you according to one hot encoding, right? If I directly use word2vec, I will be getting a different vector dimensions, right? Then coming the next third word, okay? So this operation is specifically happening. Then in the third instance, I will pass my third word, right? In this particular third word, I will just go ahead and pass u. U is nothing but it will give this particular input as like this, and here instead of writing thank you, I will just pass u over here. This will be my third word, right? Now similarly, my fourth word, what will happen? Again, it will go to the next LSTM, and this is my entire encoder now, okay? Encoder, right? So here I'm actually going to pass my fourth word, which will be my end of statement 0001. This is nothing but end of sentence, right? Now this is how we go ahead and pass it over here. And after this, the operation that we are basically going to do, we will be getting our CT and HT. So this will be my CT and HT. What does CT indicate? CT indicates my long-term memory, and HT indicates my short-term memory, right? Short-term memory. Now this long-term and short-term memory combined is basically called as context vectors. Context vectors. In short, all these vector operations will probably taking place inside this, all the operations, because inside this we have this forget gate, we have this input gate, we have this output gate. So with respect to all this timestamp, when I'm passing with t is equal to 1, t is equal to 2, t is equal to 3, t is equal to 4, right? I'm passing this particular sentence one by one, right? So this is what exactly happens inside the encoder, okay? It is not like you have to learn decoder separately. Decoder will also happen at the same time. Now see this, okay? So encoder, what it has done is that it has taken all the words inside the sentence and it has helped us to generate the context vector. How did it generate the context vector? Whatever operation is present inside this with respect to forget gate, with respect to input gate, with respect to output gate, right? All these 3 operations that it has, right? And with respect to that, I need to combine this. I need to add some input in the CT, otherwise remove some context from the CT, right? We finally get this entire CT and HT, right? Now we will go ahead and create our decoders. Now in the case of decoder, what will happen? See this, okay? So in the case of decoder, let's say in our training data set, in the French word is gracious, right? So what we will do over here, again, we will go ahead and use one LSTM, right? Now in this particular case of LSTM, what is basically going to happen? Now see this, in decoder stage, what is basically going to happen? This entire CT and HT will get passed. We're going to pass this entire vectors to this. Now you know that we have transformed our training data. So this I'm considering as my training data, okay? Now for the training data also my output, this is my output, right? And this is my true output. We basically say it as y truth, right? Not y hat. Y hat is your prediction. Now in your y truth, you know that there is SOS, right? There is gracious and there is EOS. Along with this context vector, what I will do while training it, So for the first instance, I will go ahead and pass my input. In this case, first one that I'm going to pass is my SOS. Now, since there are only 3 words in the output, like that in the entire data set, you may have many words, but I'm just considering as an example. There are 3 words. So SOS is indicated by 101, 100 in this particular case. This will basically get passed over here, right? How did I convert this? Again, by using the same one-hot encoding technique. We can replace this entire technique by embedding layer, but just to give you an idea what exactly is happening, I'm actually writing it over here, right? Then, with respect to this particular output, what we do over here, we pass it to a fully connected layer with softmax activation function. Okay, so let me just go ahead and talk about it, right? You know what operation is basically going to happen over here, because here also there will be forget get, there will be input get, and there will be output get. After we get the output, we basically pass it to softmax. Why softmax? Because you'll be able to see that I am having these 3 words, right? I'll be showing that I'll not be having 3 words, but I've added this start of sentence, gracious, and end of sentence, right? So with respect to softmax, I will be getting, let's say, 3 outputs over here, 1, 2, and 3. Okay. Now with respect to this output, let's say my vectors look something like this. I'll get the vector something like this values. Let's say over here. Or let me define it something like this. So this will basically be my y hat. Y hat basically means predicted value. And this y hat, since we are using softmax, why we are using softmax? Because this is becoming a multi-class classification. So with respect to SOS that I'm actually giving, what should be the output that I should get along with this context vector? So let's say that here I'm going to get 3 coordinates. Let's say I'm going to get 0.5. I'm going to get 0.1. I'm going to probably get 0.4. I'm going to get 0.5 and I'm going to get 0.4, right? So when I got these 3 vectors, we will just go ahead and see which value is the maximum in this vector. If it says 0.5, that basically means it is going to give us the output as gracious. Okay, so here what we do, we will convert this back into this particular output, because the second index or second vector that is basically there, it is for this particular word gracious, because it's present over here, right? So this is how we are able to get the y hat. Okay, yeah, there may be scenario that I may not get this particular value also. I may get the third value having a highest value with respect to probability, right? Because when we are using softmax, here we are basically going to get the probability of y hat, right? And right now, since this is a multi-class classification based on 3 different vectors, whichever vector value is high with respect to the probability, I'll say vector value, but I'll say this is the probability value, right? Again, let me repeat this. So here, once I get the output, I'm going to pass this to a softmax activation function, and we know that over here there are 3 words: SOS, gracious, and EOS. With respect to this particular SOS, along with context vector, it should predict something. And let's say if it gives this 3 output that I've got over here, let's say if it gives this 3 output, okay, since we are actually getting this y hat, if it gets this 3 output, one is 0.1, one is 0.6, one is 0.3. Now in this case, the probability of 0.1 is for this SOS word, the probability of 0.6 is for gracious, and this probability of 0.3 is for EOS. So whichever will be the highest probability, that will be my predicted output. So here I will be specifically getting gracious. Okay. Yeah, there may be scenario that I may get another probability. I may get 0.1 over here, 0.3 over here, and 0.6 over here. In this particular case, what will happen? The prediction will be end of sentence. So if I'm getting end of sentence, that basically means I will not go further, right? But again, during the back propagation, I'll propagate, I will update all the weights that is involved over here. And then we will again do the forward propagation, and we will make sure that this y minus y hat should be less, right? Or should be reducing, right? So let's say I got gracious over here. So this is my start of the sentence. I got, I did all the calculation inside this, whatever happens in the LSTM layer, and finally I got the softmax and I got y hat. So in the next step, what happens is that it will probably go to my next LSTM over here, because I've got the right output that is called as gracious. Now with respect to this particular gracious, what I will do, I will pass this output back to my next LSTM, right? And you know that this HT and CT will also be going over here, right? Then along with this, again, we will go ahead and pass this to our softmax. Now with respect to the softmax, if my training is going on well, I should be able to get my y hat over here with respect to the probability that I have. And here my output should be end of sentence, right? Because gracious, after gracious, I don't have any other word, right? But here, my next word that is probably going will be nothing but gracious vectors, okay? Whatever vectors is over here, that is 0, 1, 0, right? And finally, when I get end of the sentence, that basically means I have to stop training over there. Okay. Now, this is the best way of training, right? While I'm getting the exactly accurate value. But here you'll be able to see that if I try to break this up, right, with respect to the decoder, I will be having y hat, right? I will be having y hat. This y hat will again be happening with respect to the timestamp of t is equal to 1, 2, 3, right? Now, with respect to t is equal to 1, let's say over here, with respect to t is equal to 1, t is equal to 2, t is equal to 3, we will be having our y truth value, we'll be having our y hat, right? There will be these 3 vectors, there will be these 3 vectors, right? Again, here will be 3 vectors, here there will be 3 vectors. Again, there will be 3 vectors, here there will be 3 vectors, right? Now, during this particular scenario, after we do the forward propagation, what we do, we basically calculate the loss. And loss is nothing but y minus y hat whole square, right? It can be whole square. We're just trying to find out the difference. And our main aim is to reduce this loss, right? So what we do in this particular case, once we find out the difference, we will try to calculate the average, and then what we'll do is that we'll try to reduce this particular loss. And when we are reducing this loss, how do we reduce it? We again have to use something called as optimizer, right? Now, when we are using this specific optimizer, it is just going to update all these weights that needs to be updated inside all these things. Then in the back propagation, all the weights will get updated. Then again, we will do the forward propagation. But you understand one thing over here is that over here, during the input, we need to pass all the inputs first. Then the output from the last layer, or output from the last LSTM with respect to time, that context vector gets passed to the decoder. So this basically becomes the encoder, and this is my decoder, right? So this way, the entire training of the sentences happens. And that is what is basically shown over here. We have the softmax activation function. Again, we pass it to the same softmax activation function. We are unrolling it, right? If the loss is high, then we have to again do the back propagation, update all the weights in this LSTM from till this encoder, from the first stage of encoder. And again, we have to probably do the forward propagation and do the same thing again, find out the softmax activation function, what values I'm actually getting. The most important thing is that how do we convert this into vectors? Okay, so if I really want to probably draw this particular diagram in a much more easier way, so this actually becomes my encoder. Okay, then this is my decoder. Okay, and with respect to the encoder and decoder, I will be having my LSTM RNN unroll with respect to time. Okay. Now, you know, in this LSTM RNN, I have 2 important lines that gets passed, and this 2 important line will be responsible in creating my context vector. This is the inputs that I'm actually going to give. Here, we are going to use an embedding layer, which we have already discussed about, embedding layer, right? And with respect to this embedding layer, I will be passing my x11, x1, sorry, here, embedding layer, I will be passing my x11, x12, x13, and let's say my x13 is end of sentence. Okay, then whatever output that I get, this is nothing but this is my context vectors, right? The same output is my context vector. Then here we again go ahead and create my LSTM for the conversion sake, whatever we need to generate. This will be passed towards this, right? Along with this, we will start over here with SOS, right? Here again, we will be using another embedding layer. In this embedding layer, I will be passing my SOS first. Okay, so here also first SOS needs to be passed. Okay, then whatever output I get after performing my softmax. So let's say here I'm going to write my softmax, right? The same thing will probably get passed to my input. Okay, so here I'll just rub this because this input will be only till here. Here only I'll be using my embedding layer, but the same vectors will get passed over here. Then again, I'll be getting an output. Again, the same vectors will be passed over here. And here finally we get our EOS, end of statement. And this is how we probably go with the entire forward and backward propagation. This part is basically called as encoder. This part is specifically called as the decoder, right? So I hope you got an idea of encoder and decoder, what exactly it does. And usually we use an LSTM over here. Context vector are nothing, but it has just like an arrays itself with respect to the calculation. But whatever sentence we are probably passing, right, it probably will give you the entire summary of this particular sentence or context of the sentence, right? So I hope I know there's so many things written, but understand the context. But other than this, the forward and the backward propagation will be almost same. So yes, this was it from my side. And here we have actually discussed about the encoder and decoder architecture. In the next video, we will talk about the problems of encoder and decoder architecture. So yes, this was it from my side. I'll see you in the next video. Thank you. Hello guys, so we are going to continue discussion with respect to encoder and decoder sequence to sequence architecture. Already we have seen how it exactly works. We have seen the architecture with its complete in-depth intuition. But let's go ahead and let us try to understand the problems with encoder and decoder architecture, sequence to sequence architecture. And we'll just try to understand the problem. And in order to solve that particular problem, what we are specifically going to use and what architecture change will specifically happen in this encoder decoder sequence to sequence architecture, that also we will be seeing in the upcoming video. So let me just go ahead and let me quickly go ahead and create a generic structure again. So this is my encoder, right? Now with respect to the encoder, you know that let's say I'm using LSTM. So over here I have my LSTM, here also I have my LSTM, and similarly here also I have my LSTM. Let's say with respect to time, I have just drawn T is equal to 1, 2, 3, 4, right? And here you know that we specifically use embedding layer. So here I'm going to basically use an embedding layer. So embedding layer, okay. Now with respect to embedding layer, here we are going to give x11. Let's say this is just for the first sentence, x12, x13, and this will basically be my x14, which is end of sentence. Okay. Now you know that this entire information will be going over here in the terms of vectors. So here a vector will be created. Here also a vector will be created based on this embedding layer. Here also a vector will be created, and finally here also a vector will be created. Okay. Now when we are discussing specifically with respect to this, you know that here whatever output we are going to get, okay, we do not consider this. So here the final output will be considered, which will basically be my W. Let's consider this as W. This is my context vectors, right? And usually this context vector is represented by your two important lines. One is your long-term memory cell and your hidden state. So I will just combine this specific line over here, right? And this line only needs to be forwarded to the next decoder, right? So with respect to any use cases which has this entire encoder and decoder architecture is usually solving a sequence to sequence problem statement, right? So here let's consider this is my decoder, and here again I will be having my LSTM, okay, and let's say in this case I'll just go ahead and draw 3, right? So what is basically going to happen, this entire line will get passed to this, okay, and here I will again pass my SOS, let's say start of the sentence, okay, I will get my output. This state will still be passed to the last layer, but this particular output over here, let me just go ahead and create this will basically go ahead and pass to a softmax activation function, right? And with respect to the softmax activation function, I'm going to get the output. Then this output will further get passed to the input to the next LSTM. Similarly, this will get passed over here. Again, with respect to the output, I will again go back to the next one. And finally, I get my last output, which may be my end of sentence, right? And this will be my y hat, right? It can be y1 hat, y2 hat, right? Now, this is the entire architecture of an encoder decoder, right? But now let's focus on this context vector, okay? So when I say this is my context vector, I'm also considering it over here itself because there will be two lines that will be passing, right? One is my CT, one is my HT. Okay, if I combine both of them, this exactly becomes the context vector, right? So that is the reason why I'm representing this. So I'm just going to consider the output of the last LSTM with respect to time. Let's say this is the last time where I'm getting the sentence, so this will be the context vector. But understand what is the importance of this context vector. This context vector represents the entire sentence, right? This entire sentence that we are passing, right? Now, if this is a smaller sentence, right, this context vector will be more than sufficient to represent this particular sentence. But what did researcher do? Researcher, when they were testing, right, they used sentences of varying length to test it, right? Sentences of varying length, right? And they used a performance metrics. Again, if you go ahead and see the research paper with encoder and decoder, this research paper was something related to BLEU score, okay? And here on the left hand side, this will basically talk about sentence length. Now, when they use this encoder decoder architecture, you could see that they drew a graph which looks like this, right? That basically means as the sentence length kept on increasing, after a certain point, over here, let's say this is 30, 40, 50, and the sentence length went till high, the accuracy started decreasing, the BLEU score started decreasing, right? And this specific score is the performance metrics to test how your model is performing with respect to sequence data, right? So this was the problem. And why this is specifically happening? Because they understand the context vector that we are probably considering, we're not taking this output, right? We're not taking this output. Instead, we're just taking the last output, whatever context vector it is basically creating. Now, this context vector, will have more information with the nearest word that is just passed in this particular timestamp, in the nearest timestamp. If this is my T4, T is equal to 3, T is equal to 2, T is equal to 1, you'll be knowing that this context vector will talk about will have more information about those words which will be to the nearest timestamp, right? At T is equal to 4. But what about at T is equal to 1? And if my sentence keeps on becoming bigger and bigger, let's say if this is T is equal to 100, if there is T is equal to 1, the single context vector will be having more context information of the recent words that are there with respect to the timestamp. But what about those words that came at T is equal to 1, T is equal to 2? It'll have less context because here the context vector will be having limited information about it. So the context vector that is used to represent the entire sentence will not be sufficient, right? And that is the reason why for longer sentences, the BLEU score was very, very less. And this was the problem with the encoder and decoder sequence to sequence architecture. So how do we specifically fix this problem? For fixing this problem, we have another new amazing mechanism which we will be talking about, which is called as attention mechanism. And this attention mechanism, we will talk regarding it, sequence to sequence networks. We'll try to understand the architecture in the next video, what exactly change we really need to do in this encoder and decoder. Because this is my encoder, right? This is my decoder. The work is very simple. My encoder will encode the information and my decoder will decode back that particular information. That is why we use cases like text generation, sentence generation, language conversion, right? Different kind of use cases. So we will try to understand what exactly is this attention mechanism. Just to give you a brief idea, right? Whenever we have a longer sentence or longer paragraph, along with this context vector, right, that we are specifically passing, we will pass additional context. How do we pass this additional context? We'll see about it. What architecture diagram will be changing? We'll see about it. But just to give you an idea, here is the research paper that we'll be discussing about neural machine translation by jointly learning to align and translate. And over here, if you go ahead and see this architecture, this is my encoder, this is my decoder. We'll be discussing about this particular architecture and how this architecture is different from the previous one. Here you can see in the encoder, you just don't have only one LSTM layer. You also have bidirectional LSTM layer. So here also you have this, here also you have this, and then you probably combine all the information. You pass that additional context to your decoder, and that is what we are going to go ahead and have a look, right? And then we'll be understanding about each and every equations as we go ahead, right? Because whatever output you'll be specifically predicting with respect to the decoder, here you'll be having the context of the previous state. You will have this additional information that is probably coming up, and along with that, whatever you will be your previous output, that will also be there, right? So we will try to combine all those things and we'll try to see. But before that, let's go ahead and see, and I hope you have understood what is the problem with respect to your encoder and decoder sequence architecture. And that is what I'm going to discuss in the next video, where we'll discuss about attention mechanism, how we will provide some additional attention while training this entire models. So yes, this was it from my side. I'll see you on the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to attention mechanism. Already in our previous video, we have seen the problems with encoder and decoder sequence to sequence architecture, and we also understood if we have a context vector, like if we have a longer sentence, right, or longer paragraph, whenever we try to give the specific paragraph over here word by word, the context vector that is created by the encoder, sometimes it will not be sufficient enough for the decoder to probably get the output. So based on that, we also saw that the performance metric which was used by researchers, which is called as BLEU score, as the sentence length was increasing, you could see the BLEU score was also going down, right? So in order to overcome this disadvantage, we are specifically using something called as attention mechanism. And the main idea behind attention mechanism was that for longer or shorter paragraph, along with the context vector, we will go ahead and provide more context, right? So this was the entire idea over it. Now for this, we will specifically be using this particular research paper to understand. This is an amazing research paper, neural machine translation by jointly learning to align and translate. Anyhow, I will be giving you the specific link. You can also go ahead and explore it. But if you just go and search, you'll be able to get the link, right? And over here, the researcher was Yoshio Bengio. I hope you know him. He's a famous researcher and scientist in this specific field, specifically in the field of NLP. Along with that, you have, it's very hard to pronounce, so I don't want to really pronounce it, but I'm extremely sorry. I may pronounce it wrong, right? And they are respected personalities. I don't want to do that. Okay. So we will discuss about it, like how this attention mechanism is solving the specific problem. And if you go down, this is the main decoder general description. We will try to change the architecture of encoder and decoder. What it will basically be changing, we'll talk about it. Okay. So first of all, let's go ahead with a simple example over here, right? So before we go ahead, let's go ahead and probably discuss the encoder decoder architecture once again, and then we'll try to understand the problem, and quickly we'll see what kind of changes is basically there with respect to this architecture. The reason why I'm again going back to encoder and decoder architecture, because here in the research paper there's some different kind of notation that is used. Okay. So here what I'm actually going to do, let's go ahead and probably create the LSTM in the encoder. So this will be my H1 tag. Sorry, not H1. So this is my LSTM neural network. So this will be my H2 with respect to time. Then I have my H3. Okay. So let's say that I have this 3 text that is probably going on. So this is my X1, this is my X2, this is my X3. Okay. Let's say over here, I'll just go ahead and write hello. This is the text that I'm actually sending. Hello, what's up? Okay. I'm giving this particular text. Now, if I consider this as my encoder, right? So the outcome of this particular encoder will be that. Obviously, we'll take this text and we'll use the word embedding layer and convert that into vectors and pass it to the hidden layer, right? Hidden layer, which is LSTM. Then once I probably go till the end of the sentence, that is what's up. So at the end of the day, from here, we will be able to get 2 important information. One is S0. S0 is nothing but your hidden state. And along with this, we will also be getting one more very important parameter that is called as C. C is nothing but context vector. Now see why I'm using this notation, why I did not use the previous notation like this, because in the research paper also I have this S0 and all. So it will be very easy for you all to understand. So from this, I will be getting 2 important information. One is S0, that is the hidden state. Okay. And then I have something called as C. Okay. C is nothing but it is my context vector. Okay. Now, the next step will be that from this S0, now this is my encoder stage, right? Encoder. And first of all, we will wait for all the inputs to come in the encoder. All the internal processing will basically happen, because there are 3 amazing gates over here for get input and output gate. Once you get this context vector will further get passed to the decoders. Now, with respect to the decoder, first of all, I'll just go ahead and create one decoder over here. I will just go ahead and create 3 LSTM neurons, okay? With respect to time, I need to probably create this also with respect to time, right? So here, I'll use some another color, let's say. So this is my first, second, and third. I need to convert these 3 words, right? So what used to happen in the decoder over here? So this is my entire decoder, right? Let's go ahead and divide like this, okay? Inside this decoder, first of all, we used to pass this S0. So S0 will get passed over here, right? Then the C used to get passed over here, okay? And along with this context vector, what used to happen is that our first input that we were passing, right? Our first input used to be Y0. Y0 is our truth value. Let's say this is the SOS, start of sentence, okay? So this used to get passed over here. If I'm not passing this SOS, then whatever is the truth value with respect to my first sentence, right? In my training data, let's say in my training data, I have these values, right? I have something like this. And inside this, I have this English text, hello, what's up? And inside my French, I'll say gracias, something, okay, some text, okay. Now in the first Y0, I would pass gracias, okay. So this was gracias that was passed over here. Now as soon as this gracias was passed, by using this context vector, along with this context vector, it'll get passed in the LSTM, okay. And this LSTM will be responsible in finding your Y1, right? And Y1, how do you calculate it? Because here another softmax will be there, right? So if I just go ahead and see, there will be another softmax over here, right? So this will basically be my softmax, okay. Now once I calculate the Y1, okay, this is Y1 hat, okay. Then we used to pass this Y1 hat to my next next LSTM, right, to calculate the next word, right? Along with this, what we used to also do is that we used to take this entire context vector and again pass it over here, right? And by using both of them, we used to go ahead and calculate our y2 hat, right? Similarly, to calculate the y3 hat, I will go ahead and pass, just a second, I will go ahead and pass this to my next neuron. Along with this, I used to also pass this my context vector, and then finally I used to get my y3 hat, and which can be actually my end of sentence, right? So this way was the entire process of the encoder decoder. I missed this line previously, so I'm again writing it down. So this was my encoder decoder architecture, right? And what was the problem with this architecture? It's very simple. This, if my sentence is very long, this context vector will not be able to capture the essence of the entire sentence, right? Because obviously, if my sentence is of a length of 100 timestamp, right? 100 timestamp. So I'm probably going with till t is equal to 100. During that particular case, whatever context vector will be created at that point of time, only this will be able to capture with respect to the nearest timestamp. When it is t is equal to 1 and all, we will not be able to capture the essence, right? And because of this, you could see that from the blue score, when the sentence length was increasing, it was not able to give us a good accuracy. So what exactly were the changes that were made in this, in this attention mechanism? Okay. Now I will just follow this particular architecture. So here you'll be able to see this amazing diagram. Okay. And this amazing diagram will try to understand what exactly it is. Okay. So first of all, over here you'll be able to see that this is my encoder. Okay. This is my encoder and this is my decoder. Okay. Just to give you a clear idea, this exactly is my encoder. Okay. And this exactly is my decoder. Now, what exactly is the difference between this encoder and decoder, and why there is so much architecture difference? Okay, so to make you understand again, what is the architecture difference that we'll discuss in attention mechanism? Okay, so in attention mechanism. Now, attention mechanism main idea is to provide more context to the decoder to probably do the prediction. Okay, so here what we will do is that in the encoder, first of all, I will go ahead and use, let's say over here, instead of just using a simple LSTM, I will be using bidirectional LSTM. So let's say this is my one LSTM, this is my second LSTM. I hope everybody knows what is bidirectional LSTM, right? So here I will just use this. Okay, please focus on the diagram, and this architecture will completely make sense what we are exactly doing. Okay, perfect. Now over here you'll be able to see that I will be giving my input over here, right? And this input will also go over here, right? This is my H1, okay? And I'll say this is my H1 with information going in this direction. This is my H2 going in this direction. This is my H3, then with the information going in this direction. And in bidirectional, what happens? We will also be having our H3 same way over here, right? With respect to time, right? So here you can see H1, H2, H3, H3, right? H3, H3, H2, H1. So here what I will do, I will go ahead and write H3, but my information will going from the reverse. H3, H2, reverse, H1. Reverse, right? So what exactly this architecture is of? This architecture is of a bidirectional RNN or LSTM RNN, right? Wherein I will take up any text, right? If I say hello, what's up? Okay, what's up? So in X11, here I'm going to pass hello, right? This information will get passed to both the LSTM RNN, okay? But before this is getting passed, you'll be able to see from the reverse direction, your text will get passed also, right? So here is my second input, here is my third input. So with respect to t is equal to 1, I'm going to pass hello. With respect to t is equal to 2, I'm going to pass what's, okay, t is equal to, and what's up at t is equal to 3, right? Similarly, at t is equal to 1, we are just going to pass this information first of all in the reverse direction. Similarly, as t is equal to 2, we are going to pass this information, and at t is equal to 2 and t is equal to 3, I'm going to pass this in the reverse direction, right? So this is what happens in the bidirection LSTM RNN, and the major aim is that we will also be able to provide the further words context, right? Just imagine this in terms of when you have a larger word, right? So once we do all these things, right, and you know that this will be interconnected, right? So here I will be able to get the output. So let me just go ahead and define this. So this and this will get combined. Okay, this and this will get combined. Over here, this and this will get combined. Whatever output we are specifically getting, and this will get combined. Okay. Now, if we go ahead, right, as you all know, with respect to this, the further information that we specifically have from this hidden layer, right, when it is getting combined, here we will be able to get S0, right, which is my hidden state. This is perfectly fine. Okay, let me do one thing. Let me just take this diagram a little bit below. Okay, so I'll just copy this and let me take it over here completely. Okay, because I need to draw a lot of things on the top. Okay, so I will just copy this over here. I'll paste it over here. Okay, now what will happen is that as I get this particular value as S0, okay, you know that from here I'm getting my output. Let's say my output over here is H1, here my output is H2, here my output is H3. Now previously what we are doing is that in the encoder decoder, we are not taking this particular output, right? We are not taking this. We just created one context vectors, right? But this output also we can specifically use, and we can provide this particular output or context, or we'll convert this output into some kind of context and give it to our decoder. That is the main idea over here. Okay. Now what we will do from this, see further thing what we are going to do over here, and this will be very amazing. So first of all in the decoder, this is the, so first of all in the encoder, this is the chain. Okay, so this is my entire encoder. Here I'm actually passing my bidirectional LSTM RNN so that I will be able to also provide the further words context. Right. Now in the next step, what we are going to do is that we will create something. Okay, so let's say I will just go ahead and combine some information. Let's say I'm going to probably go ahead and use some notation. This is my first notation, this is my second, and this is my third. Okay. Now in this node, right, we are going to pass this H1. Along with H1, we are also going to pass this H0. Okay, so here we are specifically going to pass S0. So this will basically go over here. Along with this, it will also go over here. This will also go over here, right? And this H2 tag information, the hidden state from the output of the H2 will be going over here, and S3 will also be going over here, right? So this is the first information that is basically getting passed, so that we'll be able to convert this into entire context. Now what is happening? The output of this is going over here. Along with that, my hidden state, right, is also going over here on this particular node, right? Now the next important thing that actually happens, and let me just denote this. Okay, so let's say with respect to words, this is my E11, this is E12, and this is E13. I will explain you what exactly is the importance of this. Okay, now what we do is that once we have this entire information, that is a combination of H1 and S0, H2 and S0, S3 and S0. Okay, we pass this entirely to a softmax. When we are saying that we pass it to a softmax, that basically means here we are going to train it with a ANN softmax. Okay, softmax. So in short, what is basically happening is that here we will create a feed forward neural network, and we will try to create and the output will be using the softmax, right? So here inside this feed neural network, we'll be giving the combination of H1 and S0, which is my hidden state, and then this will probably getting trained. And over here in our output, whenever we try to pass it to the softmax, it is basically going to have a multi-classification problem statement. Now, with respect to this, you'll be able to see that here we will be getting some important nodes. Okay, and what are the nodes? So what are the information that we'll be getting? It is nothing but A11, and let me just go ahead and write this as A12, and this will be finally A13. I'm giving some notation over here, right? Now see this entire architecture and imagine over here, right? Same architecture over here. We had our bidirectional, right? LSTM RNN, and from this we generated this 81, 82, 83, 80T, right? And this is what we have actually generated from it. And this is how the entire generation is basically happening, right? We are taking this hidden, we are basically taking the output of each and every LSTM hidden output, considering both bidirectional and over here you'll be able to see with respect to this LSTM. We're combining this with our S0, combining basically together we are giving this to our ANN, and then finally you'll be able to see that we are passing it to the softmax and we are getting this particular output, okay? Now, this step, right? This step that you'll be able to see over here where I'm combining all these things, these are basically called as alignment scores, right? Yes, we are aligning all the scores, okay? And over here you'll be able to see that this is a ANN. This is an entirely ANN, that is artificial neural network, okay? I'll talk about what is the importance of this. Then in the next step, we basically create our attention weights, and I'll talk about the importance of this attention weights. These attention weights are very much important. See, attention weights is all about how much context we really need to give it to the decoder in order to do that specific prediction. So here what we do is that whatever output we get from H1, right? This output, we will take this output and we will combine it with A11, and here we will be doing a pointwise multiplication operation, okay? Similarly over here you'll be able to see with respect to A12, we will take this H2 output, and we will do a pointwise operation with respect to this, and similarly with H3 output we will do a pointwise operation with respect to this. And this is what this diagram basically says when we say this pointwise operation, right? So here the same thing is basically happening. Now let me talk about the importance of this A11, A12, A13. What is the importance of this? This is basically used in deciding how much context of H1 I should probably consider, how much context of H2 I should probably consider, right? How much context of S3 I should probably consider. This entirely A11, A12, A13 is created from this particular ANN, wherein we are combining H1 and we are combining the hidden state, right, together, and then passing to the softmax activation function by using a feed-forward neural network, right? Feed-forward neural network. So here, according to the research paper, we are just trying to say that how much context you really need to pass from one stage to the other stage, okay? Now, if you're clear with this finally, what we'll do is that we will combine all these things. We'll take all these values, and then we will again do a pointwise operation over here with respect to plus, okay? And here we are going to compute our context vector. We are going to compute our context vector, and the context vector formula is very simple. It is nothing but CT is equal to summation of I to whatever value it is, 1 to t, okay? A of t, and then you basically A of t of I, H of I, right? A of t of I basically means 1, 1, 1, 2, 1, 3 like that. H of I, right? H of I is nothing but we are specifically multiplying with all the hidden states, okay? So once we get this, and this is finally the operation that you'll be able to see over here with respect to plus, right? This is what we are able to get it. I know, see, there are a lot of hidden things that you'll be able to see, and this is where, see, your context vector is basically calculating, and this context vector is coming from AIJ. AIJ is nothing but it is a softmax activation function, right? And then you also have this EIJ, and that is what I have actually written over here. EIJ. EIJ is what? EIJ is nothing but A multiplied by A activation function on S of I, comma H, right? S of I is nothing but your hidden state, right? And S of J, right? S of I is nothing but your hidden state along with H of J. H of J is nothing but all your hidden states, right? And this is where step by step we have basically calculated. But now the time comes is that you need to understand what happens in the decoder. So once you get this C, this plus, once you add it, here you're going to get your context vector, okay? Or let me just go ahead and draw it downwards, okay? So I will just go ahead and take this, and this will be your context vector C, right? Now we need this S0 and SC for our first decoder, right? So in the decoder, my first node will be S1. Let's say this S1, this S0 is getting passed over here, okay? Now when it is getting passed, we will also have to give our C, okay? Along with the C, we will also give our Y0, right? Y0 value, which will be our truth value. And then again over here, our softmax layer will be used. And with respect to this softmax, I will be passing it over here and getting my Y1 hat, okay? Now here you'll be able to see that how much context we are getting. See, all this context is basically getting combined based on proportion. Like A1 on A1 to A1 is basically saying how much from H1 I have to probably take the context, from H2 how much I have to probably take the context, from S3 how much context I need to take, right? And here you'll be able to see with respect to S1 I'm able to get this, right? Then you'll also be able to see Y1 over here. Now what will happen in the next step? See, in the next step, I need to pass this information to S2, right? Which will be my second layer. But now here, what will be the information that will be going? Think over it, okay? What will be the information that it will be going, right? So first of all, I need to see over here, very simple, you'll be able to see I'm getting the information of S0 to S1, right? Then if I really want to do it for S2, right? First of all, again, I need to generate this particular context vector. Now for generating this particular context vector, what I will do is that very simply, I will, instead of passing just from S0, I will remove the line from S0 and I will take this and pass it from S1. Now this will go and generate my new context completely, right? New context completely, and this new context will then pass to my S2, right? And this context that I'm actually going to generate, it will be my C2, right? So this was C1, now this will be C2, which I'm actually passing. C1 was getting passed over here to S1, right? Along with this, I will take this Y1, I will also pass this information to my S2, right? So this will basically be my Y1. Again, I will go over here, calculate my Y2 hat, right? Y1 and Y2 hat. Then again, when it goes to the last timestamp, which is S3, this will go over here. But again, what we are basically going to do, instead of S1 passing the new information or state information, we will go ahead and pass from S3, right? So here we will go ahead and pass from here, and this will probably go ahead and generate our new context C3. Now this C3 is going to get passed over here. Along with this, I'm also going to get passed Y2, and finally I will be able to get my output Y3 hat, right? So this is the entire process of this entire research paper. Isn't it amazing, right? Now this is a beautiful diagram that I tried to explore from multiple research paper and all, and got a complete idea about this, how things basically happen, right? And this is really important for every one of you out there who's specifically doing. But with respect to this, what is the nice thing that is happening every time whenever a decoder is predicting something, it is again going and calculating the new context information, right? For every timestamp. Because of this, we are able to also perform our work with a larger data set, right? And this is the most important thing with respect to this particular architecture that is called as attention mechanism. Okay. Now, one final thing that I really want to show it to you is that in this research paper, when we are discussing, right, there is also something called as this particular score, that is BLEU score. And here you can see with the help of a sentence length, when we did RNN search of 50, the BLEU score of the generated translation or tested with respect to the length of the sentence, the result on a full test which includes sentences having unknown words to the model, its blue score remained almost constant, right? It did not come down, right? And there is also one more thing over here. If you probably see the example with respect to A11, A12, A13, right? So here with a specific word, what is the translation, and that is what the specific color shows, right? You can probably go ahead and see about this particular research paper, but I hope you got an idea that how this entire things work, right? I know there are multiple steps. It is a very complicated attention mechanism, but this is what is the base of what we will specifically use in transformers, right? Which is very much important and which is the base of every generative AI models that we use currently, right? So I hope you got this entire idea. Again, just go and see this particular research paper. This is first of all my bidirectional. Then I went ahead and here you can see E of ij. We can go ahead and see from here. E of ij is nothing but this. What we are basically doing, we are using this S of 0 and H of I. We are passing it through an ANN, and from that softmax activation function, I'm getting A11, A12, A13. This is basically saying that how much context of H1 I have to probably go ahead and take and probably create my attention weights, right? So I hope you like this particular video. Again, in order to show you good examples, I also have one more website, okay, and probably I will also give you this particular link in the website. Okay, I'll just reload this. Introduction to attention mechanism. Let's say this is with respect to our encoder decoder. So I'm passing this H1, H2, H3. We go over here. Then over here you'll be able to see that I'm creating one S0, which is my hidden state and context vector. And this is basically getting passed. And this is actually going and generating all the sentence text. This was basically happening in sequence to sequence encoder and decoder architecture, right? Now in the next step, how we are basically doing. So here is your entire diagram. How we are calculating the CY3. This S of 0 is going over here. Then you have this softmax. Then A11. Then finally we see this multiply attention weights. Then we create this particular weights of attention weights. Then we go ahead and create our CT, that is the context vector, right? With respect to timestamp C1, I'm passing this information. Then we'll go ahead and create C2. So here you can see S1 is going in when we calculate the S2, right over here. Then here you can see Y2 is already coming up, right? So I will give you all this specific information and you can go ahead and check it out. But again, super thanks to this particular blog from which was published in 12 May 2021, Introduction to Attention Mechanism, right? So yes, this was it from my side. I hope you like this particular video. I will just go ahead and give you this link quickly somewhere. I'll paste it, right? And this is the link that you really need to refer, right? So yes, this was it from my side with respect to attention mechanism. I hope you like this particular video. I'll see you in the next video. Thank you. Take care. Bye. Hello guys, so we are going to continue the discussion with respect to NLP with deep learning. In this video and in the upcoming series of video, we are going to discuss about transformers. Now, transformers is a very important topic. Please keep a note of that. If you really want to excel in deep learning, specifically with respect to NLP task, then transformers is the thing. In this video, I'll just show you a plan of action, like what all things and how we are going to cover this entire topic. Till now, we have already discussed about RNN, LSTM, GRU, RNN. We understood what are the problems over here, right? Then we went to encoder decoder architecture, which was in sequence to sequence learning. Then over here also we faced some kind of problems, and then we tried to solve that particular problem through this attention mechanism, right? Again, on all this architecture, there was some of the other differences, right? And now finally, we will first of all understand what is the problem in attention mechanism and what kind of problem we are solving it with the help of transformers. The plan of action will be that first of all, we will go ahead and understand why transformers. Then we will see the architecture of the transformer. So this is a detailed architecture which is basically shown on the right hand side. And this architecture looks really cubism, right? Probably if you're seeing it for the first time, there's so many things over here, and it does not even match from the architectures which we have learned in encoder, decoder, or attention mechanism. Don't worry, we'll break this down the entire architecture. So in this architecture also you have this encoder, you have this decoder, but inside the encoder and decoder there are many more things that is actually included, which we will be discussing about it, right? So the plan of action will be that first of all we'll try to understand why transformers. Then we will go with the architecture of transformers. Where in the first model that we're going to cover is something called as self-attention. In this self-attention, you'll be seeing this QKV parameters. So we will also be understanding what exactly this is. Okay, we basically say this as query key value pairs. Okay, what exactly it is, we'll discuss about it. Then we will be talking about positional encoding, right? This is also a very important topic in this architecture. Then we will be covering about multi-head attention, and finally we will be combining all these topics to understand the working of the transformers. So this is the plan of action how we're going to cover this particular topic. But just to give you an idea why transformers is really important, because right now if you have heard about generative AI, right, and the kind of LLM models or multi models that are available in generative AI, right, most of the models, these are basically trained on by using this transformer architecture, right? Specifically if I talk about some of the models like BERT, or if I talk about GPT, right? And if you know about GPT, right now ChatGPT has, OpenAI has come up with this amazing models, right? OpenAI, specifically your ChatGPT applications. And right now the model that it is using is nothing but GPT 4.0, right? 4.0. So this specific model, it is based on the transformer architecture, but it's trained with huge amount of data. And obviously, if I talk about this GPT, it is like this GPT-4 is using this GPT architecture along with the transfer learning with respect to this particular architecture, which is trained with huge amount of data. So we will be covering all these topics, but in this video, I just wanted to give you about the plan of action, how we are going to cover each and every specific topics. So yeah, this was it. In my next video, I will be talking about why transformers. And again, before that, we really need to again revise this encoder decoder architecture and attention mechanism. And what is the problem that we are facing over here? We will be talking about it. Okay. Yeah, this was it. I will see you all in the next video. Thank you. Hello guys, so we are going to continue discussion with respect to transformers. So this is the first topic that we are going to pick up and we are going to understand. So here I've also given the definition, so that is the reason I've written what and why in transformers. So if you really just want to understand a simple definition about this particular architecture, it is nothing but in transformers in natural language processing are a type of deep learning model that uses self-attention mechanism. Please keep a note of this because this is really important. To analyze and process natural language data, they are encoder decoder model that can be used for many applications, including machine learning translation. Now, if I talk about machine learning translation, this is specifically something called a sequence to sequence task, right? Now, when we say sequence to sequence tasks, let's say I want to solve a problem statement. One of the example that we can probably take is like language translation, right? Language translation. And if you probably go ahead and see an example of Google Translate, right? This is a task of sequence to sequence task. It is a sequence to sequence task because if I really want to convert from English to French, right? English to French. So in this scenario, you'll be able to see that my input with respect to English will be many words. I will be having many inputs over here. It will be many. And my output will also be consisting of many words. So this basically becomes like a many to many sequence to sequence task, right? Now, when we have the sequence to sequence task, and obviously length of the sentences is also a meaningful thing over here, right? Length of the sentence. Now, as the length of the sentences increases, we should be able to solve this particular problem again with a very good accuracy. So in this kind of task, usually transformers is used. Okay, but you may be thinking, Krish, fine, you have also told that in the previous architecture of encoder decoder, you told that this is also used for sequence to sequence task. And if I talk about encoder and decoder, like they were, if I just probably go ahead with this particular diagram, so I had an encoder over here, right, and I had a decoder over here, right. So in encoder and decoder, what we used to do, we had our LSTM right over here, and based on this LSTM, when we used to go ahead and pass this entire sentences, okay. Please remember, we do not take the output in this, right? So if I just go ahead with a basic architecture of encoder decoder, you'll be able to see that if I used to give my words over here, let's say x1, x2, x3, and this words we used to give based on timestamps. T is equal to 1, t is equal to 2, t is equal to 3. So let's say this is my sentence 1, which is having this particular words, and again we used to convert this entire words by using some embedding layer, okay, convert this into vectors, okay, and then pass it to the entire LSTM. So this was my LSTM over here, right? And this is my encoder, and this is my decoder, right? So after doing this, finally you should see that we were able to generate one C vector, that is context vector, right? So here I will just go ahead and generate this context vector, and based on this context vector, we used to provide it to our next decoder layer, right? Next decoder layer, which used to have this LSTM. Okay, so here is my decoder completely. I will pass it over here. I will pass it over here. And then with respect to this particular decoder, I used to also get my output. And here we used to use some kind of softmax, right? Now, this was the basic architecture of the encoder decoder, right? And this is what we used to do. This context usually used to define when we are passing every words based on the timestamp. The final context that we used to get at the end of this particular sentence used to represent this entire sentence itself, right? Which is consisting of this entire words. And this context was further sent to our decoder model. And this decoder model would use to do the prediction based on this context that we have. And along with that, we used to also calculate the loss. Everything was discussed, right? Based on the encoder architecture. But one problem we understood from the encoder decoder was that this context was not sufficient to represent this entire sentence if the sentence length increases. If the sentence length increases. If this increases, the C context was not at all sufficient, right? And this was the problem with respect to the encoder decoder architecture. And that is the reason you could see that our blue score was decreasing as the length of the sentences was increasing. So this I've covered in my previous video. I would suggest if you want to quickly revise it, you can go ahead and do the revision. Okay. Now for this, we also had seen an architecture. So here was my sequence to sequence learning. This was the entire research paper of this, how the entire working actually happens. Each and everything was explained clearly over here, right? So after this, what we did is that in order to solve this problem of the context that we had, like our main idea was that, okay, we should not create the entire context at once and probably send it to the decoder model. Instead, what we can actually do is that we can use something called as attention mechanism. And that is where this research paper came, right? So based on this research paper, what we exactly did was that the plan was very simple. Instead of just giving a single context, we had to actually provide an additional context to our decoder. And this was the architecture we specifically discussed about. And if you remember, in our previous videos, we have discussed the entire mechanism of how this attention mechanism actually works, right? And we discussed about this entire research paper over here. So here was the entire working, wherein along with a single context, we also have to provide additional context, create our alignment scores, create our attention weights, and then pass it to the decoder. Okay. And that is what we specifically solved it with the help of attention mechanism. So let me do one thing. Let me just take this screenshot, okay, so that you will be able to see this reference over here. So here I will just put this reference, and here also I've added this additional reference. So this was all possible because of your, the attention mechanism, right? So this is the entire working, right? And with the help of this, what we were able to do is that we were able to provide additional context to the decoders. And then this decoders, what they were able to do is that they were able to do the prediction, and the problem with respect to the long sentences, right? The problem of accuracy that we were facing, it started increasing, right? Because of this research paper. But still, let's understand with this attention mechanism, okay? So here we are using bidirectional LSTM, and here also we are using LSTM itself. One problem that we see with this attention mechanism or encoder decoder, okay? Attention mechanism or encoder decoder is that we pass every word based on timestamp, right? So here, parallelly, we cannot send all the words in a sentence, right? And again, because of this, see, over here you'll be able to see even in encoder decoder, we used to send the words based on timestamp, right? Now when we are sending the based on timestamp, T is equal to 1, I'm sending one word, T is equal to 2, I'm sending another word, right? Similarly over here in this bidirectional LSTM also I'm sending one word at various timestamp. We won't be able to do the entire execution or this entire training parallelly, right? And because of this, yet your attention model is not scalable. When I say scalable, that basically means if my data set is huge, right? Still, the encoder decoder attention mechanism will not be scalable with respect to training. And this is really important to understand because the new models that we'll be seeing with respect to transformers uses something called as, they never use this LSTM RNN in encoders or decoder, right? What they use is that they use this something called as self-attention module. And because of the self-attention module, you'll be able to see that all the words will be parallelly sent to the encoder for further processing, right? And that is what this architecture comes into existence. See over here in the input embeddings, right? You're sending all the input all at once. So it is supporting this entire parallel execution. And that is where, because of this, we'll also be learning about one more topic which is called as positional encoding. We'll discuss about this as we go ahead, right? And this will also play a very important role for this when we're sending all these words parallelly, and how each and every word vectors is going to get computed. We'll discuss about this. What exactly the self-attention module will be doing, we'll be discussing about it, right? Now, you should definitely understand over here is that in attention mechanism encoder decoder, we are not able to do this. Hence the word scalable. Now, when we say scalable, that basically means why these transformers are really performing well is that as we keep on increasing the data set, you'll be able to see that we are able to get some amazing models. Amazing state-of-the-art models. I say SOTA models, right? So state-of-art models we'll be able to get, specifically with respect to NLP task. Now, this is not just restricted to NLP task. With the help of transfer learning, right? With the help of transfer learning, transformers are even used in multimodal. Okay, they are used in multimodal tasks. Multimodal task basically means task that has both NLP plus image. So here also they are able to perform really, really well. Okay, how it is able to perform and all we will understand once we understand the entire architecture. But this is the major important thing that you really need to understand. Why transformers? What was the problem that we had in our previous models like encoder, decoder, and all? And this is one of the very important problems that we have, right? So just defining all these things, since it solves all these problems, you'll be able to see now everywhere, this entire transformers have really changed the AI space. Now you'll be able to see a lot of SOTA models, right? And this SOTA models is nothing like, let's say, some of the transform models that we have, which is already trained in huge data sets like BERT, GPT, right? Now what companies are doing, if they really want to create their own model, they don't have to train it from scratch. And these models are trained with huge data, trained with huge data, right? They can directly just use transfer learning. And with the help of this transfer learning, they are creating this amazing sort of models, right? State of art models, right? And the architecture, this is completely based on transformers itself. And as I said, multi-model task, the same architecture is also used with respect to images. So if you see in OpenAI, some of the application like DALL-E, right, they actually just based on a text, they're able to generate the images, right? Entirely, it is completely based on transformers. So just to give you an idea, this will also be very much important because based on this architecture, various LLM models are also used in generative AI. Okay, generative AI. LLM basically means large language models. So I hope you got an idea. Just take this into consideration. This is a very important thing that we have discussed. Parallelly, we cannot send all the words in a sentence in attention mechanism or encoder decoder. But with the help of transformers, we are not at all using LSTM-RNN. Instead, we are using self-attention module. And this self-attention module functionality will be that we will be able to send all the words right parallelly for the processing. What exactly happens in the self-attention module, we'll discuss more about it. Okay. So I hope you got an idea about this. One more very important problem that we see in transformers, that is with respect to contextual embedding. Contextual embeddings. Right. Now, what exactly happens in contextual embedding? We'll discuss about this. Okay. Now, with respect to the contextual embedding, let me just give you an example in order to make you understand this. Okay. Let's say I have a sentence. My name is Krish and I play cricket. Okay. Now, let's say over here, when I pass this entire information, right, in my embedding layer, let's say this is my embedding layer. Now, you know, in embedding layer, when we pass it, our main task will be that from this embedding layer, for every word, we should be able to get vectors, right? Some vectors. So if I pass my, then name, I should be getting another vector. Is, I should be getting another vector. Krish, I should be getting another vector. And I should be getting another vector. Based on timestamps, I will be getting this kind of vectors. And understand, if you're specifically using embedding layer, and let's say if this embedding layer is using some embedding word embedding techniques like word to vec. For every word, we are going to get a fixed vector. Okay, so this if my is there, then I will be getting a fixed vector of some dimensions. Similarly, name is there, I'll be getting a fixed vector. Okay, is there, I'll be getting a fixed vector. Krish is there, I'll be getting a fixed vector. And is there, I'll be getting a fixed vector. I will is there, I'll be getting a fixed vector. Right? And similarly, play is there, I'll be getting a kind of vectors itself. Right? All these words will be represented in some kind of vectors. Now, I need to make you understand about contextual vectors. What exactly is this contextual vectors? See, it is always a good idea that if you are able to get a vector, it is fine, right, for everyone. But we should always try to get a vector whenever we have a longer sentences based on the relationship with other words. Now here you can see my name is Krish and I play cricket. Okay, I is obviously related to Krish. There are some kind of relationship, right? So if I probably give the same word on my contextual vector embedding, then all the vectors that I will be getting, this vector should be having some kind of relationship with respect to the other words. Like Krish and I, here there's a very strong correlation, right? So some context will be there. I play cricket, so cricket is also there. So this cricket vector, I should not be getting a fixed vector itself. I should be getting a vector which should be related to Krish. Based on this particular relation, there should be some changes in this particular vector which suggest that, hey, there is some contextual dependency in this particular word, right? And this entire problem is solved by our self-attention. And because of this, you'll be able to see that our transformers will be damn more accurate, right? And we'll be talking more about the self-attention model in the upcoming video. But if I talk with respect to the most two overall problems, why transformers are specifically used. One is, here in transformers, parallel you can send all the words for processing, because of which it makes the entire model scalable with respect to training with huge data sets. Okay. The second thing is that it has this contextual embedding thing, right? Which was basically missing in encoder and decoder. Because in encoder and decoder, we just used to use an embedding layer, we used to pass each and every word, get a vector, and further do the processing with respect to this. But now with the help of this self-attention, we'll be seeing that we'll be able to even create contextual vector embedding. Now in our next video, we are going to deep dive more into this and try to understand how this entire architecture basically works. And step by step, we'll try to get each and everything as we go ahead, right? So yes, sir, this was it from my side. I will see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to transformers, and in this video we are going to discuss about the architecture. Over here on the right hand side you can see this complex architecture over here, okay? And obviously you may be thinking this is very, very difficult, but what I will do is that just directly going and seeing this architecture, instead of this I will try to break down the entire architecture step by step. And as I said, what all things we are going to learn, right? That entire plan of action that I've actually created to understand the architecture of transformers, then we'll be understanding self-attention, positional encoding. We'll go step by step with respect to this. To start with the basic transformer architecture, let's consider this particular block diagram. So this is my transformer. This transformer will be used to solve our sequence to sequence task, okay? And in this case, the task that I'm probably considering will be language translation, and I will be translating, let's say, from my English sentence to my French sentence, okay? So I'm planning to do this particular task, okay? So here when I say input, that basically means I'm going to give my English sentence, and this is probably going to convert into a French sentence, okay? So this is what a transformer does just by seeing this block diagram. But the main thing will be that what is inside this particular block diagram. So let's go ahead and first of all see this, what is inside this particular block diagram. So if you go down here, inside this block diagram, that is the transformer, you have something called as encoders and decoder. So this also follows a encoder and decoder architecture. Okay? It follows this specific architecture. Now, what is inside this encoder? When we say encoder, is there only one encoder? Or when we say decoder, is there only one decoder? Nothing as such. Inside this encoder, you may have multiple encoders like this. Okay, like this, you may have multiple encoders. And your text input that you're specifically giving over here in this encoder will be going from one encoder to the other encoders. Okay, something like this. So this is my entire encoder over here. So this entire encoder I have actually drawn in this particular way so that you'll be able to understand. Okay. So here I will be having multiple encoders step by step. Like in the research paper, that is attention is all you need. Let me just show you the research paper. So this is the research paper that we will be looking at. Attention is all you need. And this particular research paper, if you probably go ahead and explore it, right? Here specifically we are going to talk about this particular transformer, where we'll be learning about positional encoding, self-attention, multi-head attention, feed forward, all these things, right? So this is what is scaled dot product attention, multi-head attention. So based on this particular research paper, I will be probably explaining each and everything. So as I said, when we talk about an encoder, so here I will be having multiple encoders where my information will be passed from bottom to top completely. And then from this entire encoder, I will be passing all the information to the decoder. Similarly, decoder will also have, it's just not like one block, it may have multiple decoders. Okay, like this, it may have multiple decoders one by one. Okay, what is inside this decoder we will get to know in some time. Okay, and one by one we'll be passing this particular decoder information on the top, and finally we should be able to get our output. Okay, so this is what exactly it is. Okay, and you'll be able to see that from encoder we'll be passing the information to the decoder also. Okay, and this entire architecture, when I say, right, in the research paper it is shown that we are going to use 6 encoders. Okay, 6 encoders, and parallelly there will be 6 decoders. Okay, so what is there in the research paper also? It's not like it needs to be 6, but in the research paper when they created the research they have used 6 encoders and 6 decoders to do this entire task. Okay, now here in the encoder I will be giving how are you, and then in the decoder it should be able to give me the French translation of this English sentence. Okay, now the question rises, what is inside this encoder? We should definitely understand. So inside this encoder, if I go to my next block diagram, here you will be able to see in a single one encoder, in a single encoder. So inside this particular encoder, you'll be seeing that there will be one self-attention layer and there will be one feed-forward neural network layer. Okay. Again, try to understand this basic level of understanding. I've drawn this particular diagram in a very simple way. So there will be one self-attention. We'll be understanding what exactly is the self-attention. We'll try to see like what is the exact working of this as we go ahead. Then from the self-attention is connected to the feed-forward neural network. And if I consider just a single decoder, right? So inside a single decoder here, you'll be able to see that I will be having a self-attention. Also, I'll be having a feed-forward neural network. But along with this, I also have an additional layer which is called as encoder-decoder attention. Okay. So we will be understanding this entirely. Don't worry, but we just need to understand this basic architecture, what exactly it is. Now, let's go ahead and let's try to see what this self-attention actually does. And that is what we're going to discuss in this particular video. Okay. Why this self-attention is basically used. Okay. Now, with respect to the self-attention, you'll be able to see that if I go down and if I still explore more about the encoder. So here, this is my encoder. Okay. This is my entire encoder. As I said, in my encoder, I have a self-attention and then I have a feed-forward neural network. Now, let's say that I have a sentence over here. How are you? Okay. So this is my sentence that I'm actually giving it over here. How are you? Then this self-attention, first of all, we need to convert all the words into vectors, right? So this is my vectors. This is basically getting converted. And here we can use vector embeddings or we can use an embedding layer, whatever layer we specifically want, right? Let's say here we have like embedding layer. We have an embedding layer. And this embedding layer is responsible in converting a word into vectors. So each and every word is basically converted into a vector over here. Now, as I pass these words to the self-attention layer, this will convert this particular vector into a different vector. And this vector is basically called as contextual vectors. Okay. So let's understand the differences between this vector versus the contextual vector. This is really important to understand. Okay, we'll try to understand this in this coming section itself, right? So here the self-attention is doing a very simple task. It is taking a vector of words and it is converting this entire vector into another vector like z1, z2, z3. And this vector is nothing but it is called as contextual vector. Why do we say this as contextual vector? Because these vectors are not similar to this particular vector, but these vectors, you'll be seeing that it will be with respect to context of different words also. It will consider the context of different words also. Okay, and that is the reason we will probably be getting a different vectors over here, which we specifically call it as contextual vectors. Okay, so I hope you got an idea about this. Okay, and once we get this contextual vector, we send it to the feed-forward neural network. So this feed-forward neural network here, you can see over here, I will be passing this particular vectors over here. Here, okay, and each and every vector will be passed to this particular feed-forward neural network, and I should be able to get my output. Let's say this specific output that I'm getting, right, I will be considering it as my another vectors. We will discuss about it, why exactly this is required, and then this will be sent to my next encoder. So I will just try to draw this, or I will just try to draw in this way. So this will be sent to my encoder 2. So this is my encoder 2, this is my encoder 1, okay, and here it is be sent to my encoder 2. Then again the encoder 2 will be having a self-attention. Okay, so here it will specifically have this self-attention again. Along with the self-attention, it may also have a feed-forward neural network. So it will still keep on continuing. So I will not draw this diagram because you know that what it will be available in my encoder 2. Okay, perfect. So this will be passed over here. So here you can see that I will run this, and this information is going to pass over here. Okay, and this is my neural network. This is my feed-forward neural network. Okay, and here you can see all this information is basically passed through this. Is passed through this. Okay, so this is the entire basic architecture about the encoder itself. So let me just go ahead and repeat it. So initially I had a transformer. The transformer is nothing but it is a combination. It is having this encoder and decoder architecture. So here I will be having my encoder. Here I will be having my decoder. Now inside my encoder, like this encoder, you can have multiple encoders like this, 1, 2, 3, 4, 5. And even in the research paper, they have used 6 encoders. And similarly in the decoder, you'll be seeing that I'll be having 6 decoders over here, which is stacked one by one. Okay. Then what happens inside this encoder that we have? It has 2 important layers. One is the self-attention layer, and then you have the feed-forward neural network layer. The self-attention layer, we don't use LSTM or RNN like how we used to use in the encoder decoder architecture. Instead, we have this self-attention layer. In the decoder also, you'll be able to see that I'll be having self-attention feed forward, but between that, there'll be something called as encoder decoder attention. Okay. Then if I go forward and try to understand what exactly the self-attention does, it takes a fixed vectors, right, of a word, and then it converts this entire word into contextual vector. The contextual vector is very simple. Why we are actually changing it is just giving an idea that contextual vector means what. All these vectors that is basically getting converted over here, or whatever vectors you're getting, these vectors will be defined in such a way that it will be based on the context of other words. Okay. Here, what is the difference between this vectors and this vector is that here we don't have any context, right? Here they are fixed vectors. If you're using some embedding layer, how word is basically determined by a vector that will get converted, right? How R is defined, that will get converted. How U is defined, that will get converted. But by using self-attention, the vectors that I'm able to get is that how we'll be having a vector considering the context of the other 2 words. Okay. Similarly, this particular vector that I'm actually getting, it will be based on the context of other words, how and you. Similarly, the third one, right? And that is nothing but my contextual vector. Now, why do we require contextual vector? As I said that whenever you have a longer sentence, it definitely helps you to work. It helps you to get a model that will provide you an amazing accuracy. Okay. And that is the reason we are using this, right? And the next important thing, as I said, when we were discussing in encoder decoder, we cannot pass the words parallelly, right? One by one we pass it, then we generate the context. But in this case, since we are using the self-attention layer, here all the words will be passed parallelly. Okay, all the words. So at a time we are passing it, and this makes this entire architecture scalable. Now, my next important discussion in this particular video will be that let's discuss more about self-attention. Okay, now what exactly self-attention does? We will try to discuss this at a higher level. Self-attention at a higher level. And that is what we are going to discuss in our next video. But I hope you got an idea with respect to the architecture, what exactly it is. The first thing that we will be discussing that how this entire vector is basically getting converted into a contextual vector. And why contextual vector is required? Because it gives a proper context of the words that I'm actually passing, and all the words are basically passed in a parallel mode, right? So yes, so this was it. I will see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to self-attention, and already we have seen basic architecture of transformer. Now we are going to deep dive into the self-attention layer and we'll try to understand how exactly this works. Now this session and upcoming session, we are going to probably discuss a lot about self-attention, where we'll also be solving like how this entire self-attention layer actually works, all the mathematical intuition behind it, and through this I am definitely sure that you'll try to understand, or you'll get to understand how the contextual embedding is specifically created. Okay, so again, the idea behind self-attention, what exactly it is. So first of all, here you'll be able to see that. Let's say I have the self-attention layer. Okay, now with respect to the self-attention layer, whenever we give any vectors, right? Let's say the word is like the cat sat, right? Let's say if this is my sentence that I'm actually giving, okay? Now with respect to this particular sentence, you'll be able to see that when I'm giving this specific sentence, this words that you'll be seeing one by one, which I'm actually giving, this will first of all get converted into vectors. So let's say I'm converting this into vectors, and here also we will convert this into vectors. Let's say that right now, the default vectors for the is like 1, 0, 0, for cat is 0, 1, 0, and for sat is 0, 0, 1, okay? Now as soon as we pass through this embedding layer, not embedding layer, it's the self-attention layer. Okay, as soon as we pass through the self-attention layer, then from here we should be getting the output. Now the output that we should definitely be getting over here will be another vector, and this vector that we specifically get, this is our contextual embedding. And why do we say this as contextual embedding? Because see, here we are going to take the importance of different tokens, right, in the input sequence, and we are going to create this particular vector. So right now, if I just consider this as an example, let's say this vectors gets converted as 0.8, 0.3, 0.4. Then this particular vectors gets converted to, you can just say that as 0.4, 0.6, 0.2. Okay, I'm just saying as an example, and this particular vector gets converted as 0.3, 0.4, 0.8. Now, what is the importance of getting this specific vector? It is very much, it is just simply, you can consider that here, the entire, here the self-attention, what it is basically doing is that it is also specifying some importance of the other tokens or other words, and it is displaying or it is creating this particular vectors. Okay, so first of all, let's see this entire definition. So here it shows self-attention is also known as scaled dot product attention, is a crucial mechanism in the transformer architecture that allows model to weigh the importance of different token in the input sequence related to each other. So here we are just not going to keep our embedding vectors fixed. Instead, we are going to change all these embedding vectors into contextual embedding vectors based on the importance of all the other words, right? And this is what we are doing. And why do we do this? Because see, with respect to different sentences, different paragraphs, right? All the paragraphs, all the sentences will have different context. There may be importance of some other word. One word will be dependent on the other word itself, right? And because of this, right, you'll be able to see that we'll be able to efficiently create applications like language translation, right? Language translation and all, right? Language translation or text summarization. This kind of use cases we will be specifically be able to create. Now, how to convert this to this, right? And the entire self-attention works on the concept of scaled dot product attention, right? So this is the entire operation that it specifically takes. Here, one by one, we will be discussing what is this Q, K, V, right? These are some vectors. Why do we use these specific vectors? But at the end of the day, this is the entire operation that we are doing. Now, what we're going to do is that we're going to see that how the self-attention layer is going to convert this vectors to this vectors, right? Which is the contextual embedding. But here, just to give an idea, this vectors has basically been changed because considering the importance of different tokens. Okay. Now let's go ahead and let's talk about self-attention in details. So let's go ahead and discuss about self-attention in much more detail, right? And over here, our main aim is to convert this particular vectors into contextual embedding vectors, right? Now see one thing. Converting this particular word into a vector, right, into a dense vector like this. Here, for this particular scenario, we can use embedding layers, right? So in embedding layers, what happens based on the dimensions, right? We will be able to get a fixed vector for each and every word, right? Like for the cat, sat, right? We can actually get the fixed vector. But getting this contextual embedding vector based on the context of other words, it depends on the entire sentence, or it depends on the data set that we have, right? So how, with the help of this sentence or data set, we will be able to convert from this vector to this vector, right? So for this, there are multiple steps that we really need to follow, okay? So let's talk about this specific step, and that is where this entire scaled dot product attention will come into existence. So the first important thing that we really need to do is that we need to create, or we need to derive 3 important vectors. So I will first of all talk about this inputs. So in the first step, we need to derive our 3 important vectors. One is queries, then I have keys, and then we have something called as values, okay? So queries, keys, and values, right? Now, what is the importance of this query, keys, and values? That we will try to understand, okay? For every word, if you're trying to convert that into a contextual vector, for every token, we specifically create a model, right? And this model will be computing these 3 important vectors. One is queries, one is keys, and one is values, vectors, okay? So guys, now before we go ahead, let's go ahead and understand or see the basic definition of this queries, keys, and values vector, and what is the importance of this, okay? So here you'll be able to see, first, we will understand about query vector. Now, what exactly is a query vector? A query vector represents the token for which we are calculating the attention. Let's say for the first word that I'm actually passing the, if I really want to probably calculate the attention for this, which is the output vectors, right? Which we say it as contextual embedding vectors also, right? So in order to calculate this, we will specifically specify this vector as our query vector, okay? Then they help to determine the importance of other token in the context of the current token, right? So in this particular token, the importance of the other token will also specify the final vector that we'll be able to get. Now, what is the importance over here? Focus determination. This is the first importance. Queries help the model decide which which part of the sequence to focus on for each specific token, because there will be multiple tokens in a sentence. By calculating the dot product between a query vector and all key vectors, the model assesses how much attention to give to each token relative to the current token, right? So what we do is that we multiply this query vectors, or we do a dot product, I'll not say multiply, we do a dot product of query vectors to key vectors, and this helps us to determine how much attention to give to each token related to the current token, right? So if I have cat, right? If I have sat, let's say this is my 3 words. So this initially becomes my query vector for this particular, if I'm calculating the attention for this, and the final vector that I'm actually going to get is that when I multiply this query vector with the key vector, right? The model will be able to assess how much attention to give with respect to all the other tokens that are there relative to this particular token, right? So that is what query vectors will talk about, right? And as we see more examples, you'll be seeing that I will be solving step by step, like how this entire query vector will be calculated, key vectors will be calculated and all. So second important thing is that with respect to contextual understanding, queries contribute to understanding the relationship. This is very important. Relationship between the current token and the rest of the sequence. This is the most important thing. Query vectors actually contribute to understanding the relationship between the current token and the rest of the token, which is essential for capturing dependencies and context. Okay. Then coming to the key vectors. What exactly is key vectors? Key vectors represent all the token in the sequence and are used to compare with the query vector to calculate the attention scores. Now, what exactly key vector is? It will have all the tokens that is probably there in the sentence, right? And it is basically a query will be compared to this key vectors to calculate the attention score. What exactly attention score is, we will discuss about it, and how to calculate it also we'll discuss about it. So let's talk about the importance of key vectors. Keys are compared with queries to measure the relevance or compatibility of each token with the current token. This comparison helps in determining how much attention each token should receive. Okay. Information retrieval. It also plays a critical role in retrieving the most relevant information from sequence by providing a basis for attention mechanism to compute similarity score. So what we do is that we take a query vector, we can directly query from this key vector itself, and based on similarity scores, we get the most relevant information based on the dependency of all the other words also. Okay. And finally, the value vectors. Value vectors holds the actual information that will be aggregated to form the output of the attention mechanism. Okay, so value contains the data that will be weighted by the attention scores, the weight sum of the values from the output of the self attention mechanism. So we will discuss about all these things as we go ahead, but I really wanted to put a basic definition of query, key, and value vectors. Okay. Now let's take one specific example, and by that you'll be able to understand how we are going to create this query, key, and value vector. Okay, so let's say I have an input sequence. So let's consider this is my input sequence, and the input sequence is nothing but it is having this word, the cat sat. Okay, so this is my input sequence. Right now, let's say we are just going to take the embedding dimension by the embedding layer. So the embedding size, I'm going to probably take it as 4. That basically means for every word, we will convert this into 4 vectors. Okay. And even for the Q, K, V vectors that we are also going to compute, let's consider this also as 4 dimension. Okay. So I'm just going to consider all this as 4 dimension. So here you'll be able to see that how we will be able to generate this K, Q, V. We will try to see. Okay. So first of all, the first step over here is something called as token embeddings. Okay. Token embeddings basically means whatever sentence we have, we will try to convert that into some kind of vector. So let's say I will be writing E of the embedding of the. Okay. Let's say that here there are 3 words, but I'm considering there may be 4 dimensions. So I will just go ahead and mention, hey, the is represented like this. Okay. Then I will be having E of cat. Let's say cat is represented something like this. And then I have E of sat. 1, 1, 1. Okay. So this is how the entire tokens is basically represented for this particular words, and these are my fixed vectors. Okay. Now the second important step is that see guys, one very simple thing that you really need to understand. If I want to convert one vector into a context vector, okay, by using the self attention. See, this is my one vector, right? Let's say if this is 1, 0, 0. I need to convert this into 0.8, 0.2, 0.3, right? This vector is basically getting created based on the context of all the other words also, right? So there is a huge dependency on the entire sentence, right? Because with respect to different data set, there will be different sentence, and based on different context, different dependencies, this vector will keep on changing, right? So we should definitely come up with a model wherein I will say this model as self attention, where I give one kind of input and I should be able to get my contextual embedding based on the sentence. This will have all the information about all the other words also, and that is why the reason we are using this query, key, vectors, value vectors. That is the reason for that, so that it has some information about the other words and sentences also. Okay. So now once we have done the token embedding, so that is what we are doing now. We will try to create this entire model, and I will also show you how this model will be trained. The second step is something called as linear transformation. Now what this linear transformation basically does. Okay. So here you'll be able to see we will create query, key, value vectors by multiplying. See, I'm telling you, we have to create a model. When we create a model, right, definitely a model needs to have some kind of weights. Because if I just want to convert a word into a fixed vector, we can directly use word to vec or some kind of embedding layer, right? And but here our scenario is something different. We need to create a contextual embedding based on the other words, and we need to do it in a runtime, right? So we have to probably train a model which will be able to take this particular fixed vector, convert that into a contextual embedded vector. Okay. So for that, we perform in the second step that's called as linear transformation. Here we create query, key, and values by multiplying the embeddings, by learned weights matrices. I will try to denote this matrices as W of Q, W of K, and W of V. Okay, weights of queries, weights of keys, and weights of values. Okay, now what does this basically mean? So this is very simple. Let's say if I have a vector, let's say this is my word of cat. Okay, I will take this cat vectors. Let's say it is 1, 0, 0. I will probably take a weight. Let's say this is my weight W of Q. Right. If I take this vector and do a dot operation with this, I should be able to get my key vector, query vectors. Okay. I should be able to get my query vector. So this will basically be my query vectors. Okay. So this is 1 cross 3. This is 3 cross 3. If I do a dot product, it will be nothing but 1 cross 3. Okay. Similarly, if I consider about my another weights, in order to compute the key value, the key vectors, I will multiply with a weights matrix or do a dot operation with respect to weight matrix for this particular vector, and I should be able to get my key vectors. Okay. So this basically becomes my key vector. And similarly, if I go ahead and consider my another weights, that is nothing but values, W of V, I should be able to get my v vectors. Okay, so this is what we are doing. So we create a q, k, and v by multiplying the embeddings. This embeddings will be done as a dot product with respect to this particular vector, then this vector, and this vector. Okay, and then we'll be able to get this k, q, v. But understand, here we have written learned weights. That basically means initially we'll go ahead and initialize the weights, and later on with the help of backpropagation, this needs to be learned to get the exact right kind of key queries, key, and value vectors. Okay, and that is what we are specifically doing. Now let's, if I really want to show you one practical application or example, let's go ahead and do one thing. Okay, so here is my token embedding which I've actually considered. Now let's consider my, I've initialized w of q, I've initialized w of q, w of k, and w of v is equal to identity matrix. So identity matrix in this particular case, if I'm taking 3 cross 3, this will have all the diagonal elements as 1 and remaining all as zeros. Okay, so this can definitely be an identity matrix. So let's take this identity matrix, let's probably initialize it. Now you'll be able to see that if I really want to compute the query of the, right? So the is nothing but you'll be able to see that right? So in this particular scenario, if I just take this the is nothing but this 1 0 1 0. Okay, so here I'm going to basically write 1 0 1 0. If I do a dot operation with 1 0 0 0 1 0 0 0 1, right? So in this scenario, if I do a dot operation with this entire operation, then I know with respect to the identity matrix, I'm going to get the same value. Similarly, key of the, right? If I really want to find out the vectors, again I'll be able to get the same thing. Then value of the, again I'm going to get the same thing, right? So in this scenario, you'll be able to see that with respect to the key, query, and value, if I'm multiplying this with my, or if I'm initializing an identity matrix, I'm actually going to get the same value. Okay, so this is the first step, right? Similarly, if I go ahead and compute, so this is my first thing where I have actually computed the key of the queries of the, key of the, and v of the, right? It'll be nothing but it'll be 1 0 1 0. And this, how we have actually computed, very simple. We have taken our vectors, the embedding vectors, and we have multiplied with the identity matrix. Okay, now we have done the dot operation. Now similarly for the other word, let's say the other word is nothing but q of cat and k of cat and v of cat. It is not compulsory that you need to initialize it as an identity matrix. You can initialize anything, but just for my computation, I made it like this. Right now, here you'll be able to see for cat what exactly it is. For cat, it is 0 1 0 1. Okay, so here I'm going to go ahead and write 0 1 0 1. Right, so this basically becomes my query, query vectors, key vectors, and value vectors. Right, for cat. Similarly, the third one that we are basically going to compute is q of sat, k of sat, and v of sat. So in this case, we'll be able to see that I'm going to get 1 1 1 1. Right, so all these particular vectors is there. Perfect. Now, once you have actually done this. This is the first step, right? The first step is basically to get the token embedding. Then we create QKV by multiplying the embeddings by learned weight matrix. Right now, it is still not learned. We have initialized it, but with the help of backpropagation, it will keep on getting learned. Okay. Now, the third step that we are going to basically do is compute attention scores. We compute the attention scores. Okay. Now, as I told you, how do we compute the attention score? It is very simple. And over here, we have told queries help the model to decide which part of the sequence to focus on for each token by calculating a dot product between the query and all the key vectors. The model assesses how much attention to give to each token. For doing this, we need to do a dot product of query vector and all key vectors. And that is how we calculate our attention scores. And why do we do that? It is very much simple to provide. See over here. Why do we do that? Because the model assesses how much attention to give to each token relative to the current token. So with relative to this particular token, that is the how much importance I need to give to cat and sat tokens. Okay, and that is how we basically go ahead and compute our score. Okay, so for computing the score, right? So let's say for the word, if I go ahead and compute the score will be nothing but query of the and key of the. So first of all, we'll go ahead and compute this. So I know my query is nothing but 1 0 1 0, and then if I want to multiply with k, right? K is also 1 0 1 0. So I will probably take a transformation of this, right? Because if I really want to do the dot operation, if my q vector is like this 1 0 1 0, I will probably do a dot operation by taking the transformation of this, and then only I'll be able to do the dot operation, right? So once I do this, I will be able to get the value as 2, right? So 1 multiplied by 1 plus 0 plus 1 plus 0, right? So finally you'll be able to get 2. So for the with respect to query of the and key of the, when I do the dot operation, I'm actually going to get the value of 2. Similarly, if I go ahead and calculate the score with respect to query of the and key of cat, right? If I do this particular dot operation, because we need to understand the context with respect to the other words also, right? And here is what I'm actually going to get it. So I'll be writing 1 0 1 0, and I'm going to do a transform operation with what? What is key of cat? See, what is k of cat? It is nothing but 0 1 0 0 1 0 1, and this will be the transform value. Now, if I try to go ahead and find out, I will be getting the output as 0, right? Similarly, if I go ahead and calculate score of query of the with respect to key of sat, right? Key vectors of sat. When we do the dot operation of q of the and key vectors of sat, here what we are going to get. Again, I'll go ahead and write 1 0 1 0, and again, what is key of sat? It is nothing but 1 1. This will be the transform value. So here also we are going to get the value as 2, right? So this is how we compute the score values, right? And why we are doing this again? Why we are doing this? It is very simple over here. It is basically to assess how much attention to give each token related to the current token. Okay, so we have got some kind of values over here, and this will actually help us to understand how much context, how much focus should I really need to give with respect to the other token, with respect to the current token that I've actually considered, right? So here I've actually got some value scores, right? 2 0 2. Okay. Similarly, we go ahead and compute for the token cat. Now for the token cat, we need to do the same thing, right? We need to do the same thing. That is go ahead and compute the score. Now the first score will be q of cat with respect to key of the, right? Now I have to probably consider whether there is a dependency, how much dependency I need to keep with respect to this, right? So here you'll be able to see that I will be able to compute it. Now here I will have 0 1 0 1, right? And this time I'm going to do a transform operation with what? A dot transform operation with. Basically I need to transform this and do a dot operation, right? So here you'll be able to see if I do the computation, I'll be getting the value as 0. Similarly, if I go ahead and compute the score of q cat with k cat, right? So here it will be nothing but 0 1 0 1, which will be a dot operation of 0 1 0 1 transform, right? And here I'm actually going to get the value 0. Then again, if I go ahead and compute this q of cat with k of sat, right? In short, I'm just doing a dot operation, right? So here I'll be having 0 1 0 1 dot 1 1 1 1 transform, and again I'm going to get the value as 2. Okay, right? So just by seeing this word, you can just understand sat is important for cat. So that is the reason I'm getting equal values for this particular score for cat with cat and cat with sat, right? This kind of dependency is definitely there, and I've definitely used identity matrix. But this all weight parameters is also get trained, right? Then similarly for the token sat, how do we go ahead and compute it? So we will go ahead and write the score, and here you'll be able to see q of sat, k of sat. Right, so sorry, k of the. We need to do the dot operation with first of all the query vector of sat with the dot with the key vectors of the. Right, so here I will be getting 1 1 1, which is my query vectors of sat. Dot operation of 1010, which is my transform operation, and here I'm going to get 2. Similarly, if I go ahead and compute this with sat and k of cat, I will be getting 2 over here. You can go ahead and do the computation, and then here you will be able to see k of sat. I'm also going to get a 4, right? So this is in turn the values that you'll be able to see, right? And this is my third step. So initial step, what we do is that first of all, we go ahead and compute. We take a token embeddings, then we do linear transformation and probably create this k, q wave vectors by initializing by a learned weights matrices of w of q, w of k, and w of v. In this scenario, I've just considered this as identity matrix. So let's consider it. Okay. Then I've shown you that how do we probably go ahead and compute this, right? When we do this particular dot operation. So I'll be getting the same values, and this is what I get it finally. Then we compute the attention scores, and this attention score is for a different purpose, just to how much focus I really need to give on the other tokens, right? So here I get all my token score values, right? Then my next step after this is something called as scaling. Okay. Now what exactly is scaling? Okay. See, whatever scores that we are getting, right? Whatever score that we are getting over here, right? You'll be able to see that I'm getting some values like 2 to 4, right? 0 to 2 and 2 0 2, right? And you can clearly see that why this scaling needs to be done. Why we are specifically performing scaling. Okay. First of all, I just need to understand what does exactly this scaling mean. Okay. So scaling, what we do is that we take up the scores and scale down by dividing the scores by the square root of dimensions of key vectors. Okay. So in our case, our dimension of the key vector is 4. So if I do square root of d of k, it is basically going to become 2. So guys, now let's understand why do we really need to consider scaling. Okay. So scaling, so let me just write it down. Scaling in the attention mechanism is crucial to prevent the dot product from growing too large. Now when we say dot product between what? Dot product between the queries and key vectors that we have specifically done with respect to this, right? Now, why we need to prevent this dot product from growing too large? Okay, and in most of the research paper, it is basically given to ensure stable gradients during training. So let's go ahead and understand this with an example. Okay, and if we don't scale, then what kind of problems we will be facing? And as you know that if dk basically means the dimension of the key vectors, if it keeps on getting large, here you'll be able to see that we will be facing two different kind of problems. Okay, and as the dimension keeps on getting large, if you don't try to scale with this value, and if the dimension is getting larger and larger, right, we face two different types of problem. One is gradient exploding, right? Here you'll be able to see that during the back propagation, this gradient will become very, very large, and because of that, your training will not be stable, right? And the second one is something called as softmax saturation. So when I say softmax saturation, this basically means the softmax function has become saturated when most of the attention weight is assigned towards just a single token, and other tokens, the weight will be assigned to near to 0. The weight will be approximately equal to 0. So we'll discuss about it. Don't worry. I will try to explain you with an example. Okay. So two problems we are going to face over here. One is gradient exploding and the softmax saturation. Okay. Now let's see one example. Let's say that I'm going to consider three vectors. One is q. This is nothing but 2, 3, 4, 1. And let's say I have another vector k1, right? 1, 0, 1, 0. And another key vector that is nothing but 0, 1, 0, 1. Okay. Now let's without scaling, let's do the dot product. Okay. When we do the dot product, so here what I will do, I'll be using k along with k1 of transpose. So if I do the dot operation, how it will be 2 multiplied by 1 plus 3 multiplied by 0 plus 4 multiplied by 1. 4 multiplied by 0. So here overall I'm actually going to get this value. Okay. Okay. 1 multiplied by 0. It should not be 4 multiplied by 0, but 1 multiplied. 4 multiplied by 1 and 1 multiplied by 0. So overall, if you see 2 plus 4, it will be 6. Okay. And similarly, if I do the dot operation with the next key vector over here, so this will be 2 multiplied by 0, 3 multiplied by 1, 4 multiplied by 0, 1 multiplied by 1. Okay. And if you see over here, 0 plus 3 plus 0 plus 1, it is nothing but 4. So with respect to this two dot operation, initially my key values were this much. Okay. Key vectors were this much, but now after the dot operation, I'm getting 6 and 4. Okay. Now, after the scaling, let's say that I'm going to apply a softmax, because that is what happens here also. So first of all, we need to apply scaling, and then after that we'll apply softmax activation function to get the final contextual embedding. Okay, that is what happens in the next step. So let's say here I have got two scores. One is the score of 6, the other one is the score of 4. Okay. Now let me do one thing. Here we are not going to apply any scaling. I'll just go ahead and write. You'll understand the problem. What problem you're going to face? Scaling not applied. So if I don't apply the scaling, you'll be able to see over here what? I will just go ahead and apply my softmax. Now softmax will get applied to both this number 6, 4. Okay. And here when we are specifically applying the softmax, okay. So here you'll be able to see that if you remember about the softmax formula, it is nothing but let's say e to the power of 6 divided by e to the power of 6 plus e to the power of 4. Okay, comma e to the power of 4 divided by e to the power of 6 plus e to the power of 4. When we specifically apply on this two. Okay, and here if I just go ahead and see to this, so let's say e to the power of 6, and here I will take e to the power of 6 as common, and I'll write 1 plus e to the power of minus 2. This is how we can represent it. Similarly, if I go ahead and write e to the power of 4, and if I take common as e to the power of 4, I'm going to get e to the power of 2 plus 1. Okay, so from here, if we do the forward calculation, since we are applying in softmax activation function, this will be nothing but it will be let me do one thing. Let me just go ahead and write 1 divided by e to the power of 6. E to the power of 6 will go off, so it will be e to the power of 1 plus e to the power of minus 2, comma, and this will be 1 plus e to the power of 2 plus 1. Right? This e to the power of 4, e to the power of 4 will get deducted. Now, once we are calculating this, here you will be able to see that the final output, if I do the calculation with the help of calculator, it is nothing but it is approximately equal to 0.88.12. Okay. So what has happened is that when we applied this softmax activation function on a score of 6,4, which we got as a product of query vectors with the key one vector of this specific word of any word. So here we have this key one vector, here we had this key two vectors, right? And when we do this, when we did this dot product, we got 6,4, we calculated the score. Here we did not apply any scaling. And finally, you could see that we could get a softmax. When we applied a softmax activation function, here you got a value of 0.88 and 0.12. Okay. Now, what does this value basically mean? First of all, this value actually means that most of the attention weight, okay, is assigned to the first key vector, right? Because the value is higher. This is higher than this, right? And very little to the second vector. Okay. Now let's understand what does this sentence mean. Most of the attention weight is assigned to the first key vector, that is 0.88, and very little to the second vector. Okay. And let's understand. See, one of the property I think you should be knowing if you have knowledge of deep learning, right? So one of the property of softmax is that whenever we apply a softmax to two numbers, right? Two scores are there. Here you can see the difference between the scores is very less, 6,4. But with respect to the output, here you are able to see that there's a huge difference. 0.88 I'm getting to the score 6, and 0.12 I'm getting to the score 4, right? And similarly, if I try to apply a softmax activation function on a number like 10,1, now in this case 10,1, you'll be seeing that there is a huge difference, right? And these values are basically coming from the dot product of q and k, right? And here you can see that I have not applied scaling, right? So one of the property, if I do not apply scaling, whenever I try to find out the softmax for this, again, if I try to find out the output, you'll be able to see that one value will be like 0.99 and one value will be like 0.01. Now in this scenario, again, this value is very high, this value is very less, okay? You should understand all the scores will be specifically used for updating that particular weights that we are using, right? The weights like W of Q, W of K, W of V. Now, when we are doing backpropagation, right, this small value, just imagine when this small score comes into picture, obviously we are going to face a problem of gradient, softmax saturation, right? So there will be one problem, that's softmax saturation, where my gradient is not going to get updated more because the value that I'm actually going to get is becoming very small. And during the backpropagation, I can also say this term as vanishing gradient problem, right? Vanishing gradient problem, where my weights are not getting updated. Vanishing gradient problem. So this is the property with respect to softmax. See, right now, I did not do any scaling, and I got this kind of value like 0.88, 0.12, even though my value of scores was 6,4, not much difference, hardly a difference of 2. Similarly, if I do a dot product of query and key vectors, I'm getting a very high value. Over here, if I apply the softmax activation function, just try to apply the softmax activation function, you'll be able to see that I'll be getting a very high value at one of the vectors, and the other value will be very small, right? So this scenario we usually face when continuously you'll be able to see when your dot product that you specifically do is coming as a large values. Okay. Now let me do one thing. Let me just show this by using or by scaling this value. Okay. So now I will just go ahead and write with scaling. With scaling, we'll try to apply the softmax activation function. Now here you can see with scaling, first of all, I will just go ahead and compute my scaled dot product. Okay. You know that compute scaled dot products, right? Now obviously you know my score 1, right? My score 1 was 6 and 4, right? Now for this 6 and 4, what we do, first of all, if I really want to scale it, right, I need to divide it by root of dk, right? I need to divide this number by root of dk. So I will take each and every number, I'll divide by root of dk. Root of dk is nothing but, it is root of 4, which is nothing but root of 2. So if I divide 6 by 2 and 4 by 2, I'm going to get what? 3, 2. Understand, my scores were initially 6, 4, but now I have scaled it with this value, that is root of dk, and then I'm actually getting 3, 2. Now if I go ahead and apply softmax on 3, 2, you just go ahead and do this calculation, how much you will be getting, okay? So again, I will do the calculation over here. E to the power of 3, e to the power of 3 plus e to the power of 2, comma, e to the power of 3, sorry, e to the power of 2, and this is e to the power of 3 plus e to the power of 2. Similarly, if I go ahead and probably do this computation, okay, you can take what all commons you specifically want. Let's say here I'm going to take a common of e to the power of 3 divided by e to the power of 3. I will take it as common. This will be 1 plus e to the power of minus 1, okay, comma, e to the power of 2, e to the power of 2 I'll take a common. Then here I'll write e to the power of 1 plus 1, okay, and this will get deducted. This will get deducted. So finally, what output I'll be getting if I do the computation, it is nothing but 0.73, comma 0.27, right? Now, before, when we did not apply the scaling, you could see that I'm getting a value as 0.88, 0.12. The difference is very huge. But now here you can see there is a less difference. So when we are now backpropagating, right, we will not face that problem of vanishing gradient problem, right? And here you'll be able to see the output, or this is also called as an attention weights. This is my attention weights. This attention weights, let me write a point over here. Here, the attention weights, are more balanced compared to the unscaled case. So if we are scaling, now we are getting a proper balance. Before, the difference was huge. I know here also you can see the difference is there, but at least in the backpropagation with respect to the other vector that we have, right, and when we try to update the weights, at least we won't face the vanishing gradient problem. Okay. So this is the most important thing, right? And because of this, if I just try to write down the summary for you, okay, let me just note down all the summaries point that I really want to specify over here. Because of this, there are two important things that you need to take a note of. Okay. So the first thing is that here you are stabilizing the training. Scaling prevents extremely large dot products, which helps in stabilizing the gradient during backpropagation, making the training process more stable and efficient. And second, you're preventing saturation. By scaling the dot product, the softmax produces more balanced attention weights. Now, there's a more balanced attention weight. This token is also having some importance, this token is also having some kind of importance, right? Before, even though we give any kind of values over here, the gap was very high when we're trying to create the softmax. And that is what is basically like creating a stable gradient, right? We specifically divide by this number. Now, you may be thinking, Krish, how did we come for this particular number, right? Why we are specifically dividing by root of d of k? So guys, for this, there is a one simple research with respect to variance. Okay. Whenever we do the dot product, as we keep on increasing the dimension, the dot product variance will also keep on increasing. Okay. So as this was keeping, and there's a research for this, guys, as this keeps on increasing, okay, here you will be able to see that if we divide by root of dk, this is making sure that even though the dimension increases, even the dimension is 2, 3, right? The variance for that particular dot product will be almost same. That is what this specific number is all about, right? And this is a small research in variance. I just have mentioned it so that you can refer it whenever you want. But I think for our understanding, this much is more than sufficient. Okay. So because of the scaling, one more point that I can specify over here is that scaling ensures the dot product are always kept within a range that allows softmax activation function to operate effectively, providing a more balanced distribution. Okay. So if I go again back with respect to all the steps, so my first step was scaling, and after scaling, we will just try to understand what is the next step. Okay. But here I've shown you multiple examples with respect to scaling, right? So if I just go ahead and show you what all things we discussed till now, first of all, we go ahead and do the token embedding, and then with respect to the token embedding, we do the linear transformation where we are going to find out three important vectors: query key and value pairs. I've told you about the discussion with query key value pairs, why it is important. Then we go ahead and compute this. Then we compute the attention scores, and this attention scores also play a very important role. Then we probably do the scaling part with respect to this. Okay. Now, once this scaling is done, right? Once we specifically do the scaling, then we calculated the weighted sum of all the values. Okay. That is what the next step is all about, right? And I know this may be somewhat confusing, but it's always good that we try to understand things. Okay. So let me go back to my previous problem statement here. If you remember, we had calculated the scores, right? All the scores, right? For compute attention scores, for the score of query of the with respect to key of the was 202. Like this scores we have actually computed, right? So let me do one thing. Let me just go ahead and apply softmax. But before that, we will do the scaling, okay? And then we will compute. And I will take only one word for this, okay? Or one word. I'll just try to show you with respect to one word, and then you should be able to understand. So the first step that we are specifically going to do is nothing but scaling. I've shown you one example of scaling. So scaling, what we will do, we will try to divide by root of d of k. Okay. In this case, it is 4, so this will basically become 2, right? Root of 4, which will become 2, right? Then we are just going to calculate our scaled score. So if I go ahead and calculate with the query of the with key of the, right? We had this value initially 2, and we are dividing this by 2, so I'm going to get 1, right? Similarly, if I go ahead and calculate our scaled score with q of the and k of cat. So here we are just going to divide by number 0 by 2, which is equal to 0. Then I have my scaled score. Then this is nothing but q of the comma k of sat. So initially this was 2, so I'm going to divide by 2, which is nothing but 1. Now once I do this division, you'll be able to see that again this value has got decreased, right? So similarly, all the scaling will be done. Similarly, you'll be seeing that scaling will be done. Similarly, scaling will be done for all other tokens. Perfect, right? Now after this, as I've already told you, the next operation will be specifically apply softmax. Now when I apply softmax here, you'll be able to see that, and this softmax will be applied to the scores that we have actually got, the scale scores. And then whenever we apply the softmax, we basically create our attention weights. So the attention weights is what we get, and this attention weights is nothing but my, so for the word, the attention weight will be softmax applied on my values like 1, 0, 1. So here, once I apply the softmax, you can go ahead and check it out. I've done the calculation, it is nothing but 0.4223, 0.1554, 0.4223. Okay, so here initially your value was this, right? With respect to the word, what was your initial vectors? See this? Your initial vectors was 1010. Okay, 1010. Okay, I missed out one. Oh no, we got it exactly right. So 1010 was your initial vectors, and now I'm able to get this as my contextual embedding vectors. Similarly, when I go ahead and calculate for the attention weights of cat, so this was the cat, right? Here, if I apply the softmax activation function, and the softmax activation function is applied on 0, 2, 2, then I'm going to get 0.1554, 0.4223, and 0.4223. Now, whatever vectors we are getting, this is considering the other vectors in context. Okay. Similarly, once we go ahead and calculate the attention weights for sat word, so again we have to go ahead and pass our softmax, and this will go to our 2, 2, 4. Okay. And here we are specifically going to get 0.2119, 0.2119, and this is 0.562. Right. So this is how we go ahead and apply the softmax activation function, and we get the attention weights. Okay. Now finally, see, this is just our attention weights, like what are the attention weights with respect to all the other values. But you remember, right? Initially we gave a 4-dimension vectors, and finally the output also should be a 4-dimension vector. So the final step that we are specifically doing is weighted sum of values. Now in the weighted sum of values, what we do is that we multiply the attention weights by the corresponding value vector, because somewhere that value vector needs to be used, right? Value vectors to get the final output. So for the token the, right? If I want to go ahead and calculate the weighted sum, so I will just go ahead and write the output of the will be nothing but it will be what is the attention weight 0.4223. So first one I'm getting 0.4223. This will be multiplied by value vector of the, right? Then the attention weight of cat, right? We will just go ahead and do this. See, the output, see, the other vector needs to be converted into some other vector, right? And it should be converted with respect to the context of cat and sat. So attention weight of cat. So what we're going to do, we're going to basically use the next weight, that is 0.1554. So here I'll go ahead and write 0.1554, and this much attention needs to be given to the value vector of cat. Similarly, the last one is 0.4223. This much attention needs to be given to the value of sat, right? Value vector of sat. So 0.4223, right? Similarly, once I probably go ahead and do the forward calculation. So here you'll be able to see I've used 4223. Value of the is what? So if you remember, what did we consider as the value of the? If you see this, so this is my k value. So value is nothing but the initial value that we have used, embeddings, right? So let's see the value. So for the it is 1010, for this it is 0101, and for sat it is 1111. Okay, so let's go ahead and write this. I'll do the calculation over here. I know there are many steps, guys, but please focus. I'm solving it completely step by step. 1010, then we will multiply. Sorry, we will add 0.1554 multiplied by v of cat, right? So v of cat is nothing but 0101. Then you have 0.4223, 1111. Okay. So now once we do this dot product, what values we are going to get over here? Very simple. Just go ahead and do the computation. So first of all, when we do this particular dot product over here, so the further calculation, once we do this particular dot operation, here we are going to get 0.42230, then again 0.42230, right? This will be my first vector. Then I have this vector 0.1554, sorry, it will be 0. Initially, it will be 0 because we are doing a dot operation with 0. Then I have 0.1554, then again 0, then 0.1554. Okay. And similarly here, I will be having 0.4223, 0.4223, 0.4223, 0.4223. Okay. Done. So once I get this, there's nothing but finally I'll be able to get 1.2669 and point. If I just do the plus operation with respect to all the numbers. Okay. 0.49s, 1.2669. You can validate it if I'm doing all the computation right. If not, you can let me know in the comment section. Okay. So this is basically my output. So initially, you'll be able to see that when I gave the keyword, which was having an embedding vector of 1010, after passing through the self-attention, it is giving us this keyword, that is nothing, this vector, that is contextual vector 1.2269.999, 1.2669.9999. Okay. So this is what is my contextual vector. Okay, contextual vector. Here, what we did first, we calculated our q, k, v values vectors. For this, we initialized w of q, w of k, w of p vectors, and again this will be trained. Then after this, we went and calculated our attention score. After calculating attention score, we scaled the value. Then after doing this, we passed it through a softmax activation function. And finally, we calculated the weighted sum of values. And how do we calculate this? It is very simple. After performing the softmax, whatever value we get, we have to multiply with v, right? And that is how we specifically get all these values. Okay. I hope you are able to understand this. And similarly for token cat and all, we can also do the calculation. I will leave up to you, like how you can probably do the calculation. But again, for token cat, you can follow the same mechanism. So here you have 0.1554, then you multiply by the vector of value of the, then value vectors of the, then you have the second 1.4223 multiplied with the value of the. And similarly, when you do this, you'll be able to get all these things, right? So this in short was your entire self-attention. Step by step, what all things we did, how the calculation was, everything I've explained to you. This entire weights will be trained. These are trained learned weights. I will say it as learned weights. And we have to make it learn based on the backpropagation, like how we specifically do for other neural networks. So I hope you're able to understand this particular video. This was it from my side. I will see you all in the next video. Thank you. Take care. Hello guys, so we are going to continue the discussion with respect to our transformers. Already in our previous video, we have discussed till self-attention, and we have also noted down all the steps that we specifically use in self-attention. So first of all, we go ahead and calculate our key, query key and value vector, and this is from a learned weights, that is w of q, w of k, and w of v. Then we calculate the attention score, then we calculate our scale scores. After doing that, we apply a softmax activation function, and finally we calculate the weighted sum of the values. And this is just done by multiplying with the vector v. Okay, so overall, you'll be able to see that initially when we're giving some kind of embedding vectors, we should be able to get some kind of contextual vectors over here, right? And this contextual vector is based on the context and the dependency of the other words that are present in that sentence. Okay, so this is one of the blog that has some amazing representation diagram, and the URL specifically. If I probably go ahead and talk about the URL, I will just also show you the URL over here. Again, I really want to give the credits, so it is nothing but Jalal Almar. So this amazing diagrams is basically covered with the working of the entire transformer. So you can definitely check it out and you can have a look onto this. Okay, now my idea is very much simple over here. What I really want to do is that I want to again show with the help of diagram what all things we did, right? So here you can see this is one of the diagram, and here in this video I'm also going to discuss about something called as multi-head attention. Okay, so this we are going to discuss about it, multi-head attention. Okay, now initially I have my words over here. Let's say this is my word one. What is the word? Like this can be the, this can be cat, right? This will be first, all my vectors will be available over here. We are multiplying, we are doing a dot operation with w of key, and this is how we get our query vectors, we get our key vectors. And remember, for each and every word that I have, I get a separate query and key value vectors, right? And similarly separate value vectors. We separately get all these things, right? And after we get this, what we do, we first of all do a multiplication operation with the query and the key, right? Then we divide it by root of dk, where we are specifically doing scaling. Then we apply a softmax activation function, and finally we do a dot operation with our value vector. And that is how we get our z value, which is nothing but it is my attention, self-attention for the word the, right? The vectors that we are specifically getting. Now, till here, I think everybody has followed this, and step by step, I've actually explained it, right? And we can actually say this one as our attention head. Attention head. Now, the idea with multi-head attention, what exactly is that? We'll have a self-attention with multiple heads. Multi-heads. Okay. Now this is fine. Here you can see I got one kind of vector for the, right? Similarly, can't you think that I can probably go ahead and create multiple attention heads for the same words, right? So here you can see I have taken thinking machine as an example over here. So this is my embedding vectors. Initially we went and we initialized some other weights like w of o of q, w of o of k, w of o of v, right? And we calculated this query q of o, k of o, and v of o, right? Similarly, and after this, what will happen is that again that same method, it will probably go to our, we'll calculate the score, then we'll go to the softmax, then we multiply by v, and finally we get our attention head, right? Or we get our final vectors after performing all this particular operation, right? So we get our contextual vectors. Here we get it, right? Now these vectors may probably take up dependencies with respect to other words. Let's say in this example, thinking machine is there. Or I can also take another example, this cat, sat, mat. Okay, if this 3 is there, right? Now finally you'll be able to see whatever vectors I get over here. This will be with respect to dependencies on this and this, right? Let's consider that as captured with respect to this and with respect to this, and it is probably given with this. Similarly, you can go ahead and create another attention head where it will be able to capture some more words importance, right? And for this, they will initialize another vectors, another weights like w1 of q, w1 of k, w1 of v. And similarly, they'll be getting vectors like q1, k1, and v1. So whatever vectors we are getting out of this may be different than this may be different than this. Here, some more other context importance is basically getting captured. Here, some more other context the importance is basically getting captured. So this can actually become my z0. This can become my z1. So similarly, I can go ahead and create multiple attention heads so that what will be the main aim of this particular multiple attention heads? It will expand the model's ability to focus on different positions. So here, we'll go ahead and write, it expands the model's ability to focus on different position of words or different position of tokens. this is what it says. Yeah. So here you can probably see, right? Z0 may contain a little bit more information of every other encoding, but it can be dominated by one word like sat, right? Here, Z0 may be like that. Z1 maybe like it may focus more on different words. It can be dominated by word like mat. So if you have all this kind of combination, right, then what will happen is that we will be able to get more and more information to our models, right? So here, this attention layer provides multiple representations of spaces, okay? And in case of multi-head attention, we have not only one, but multiple set of key value pairs. Multiple set of key value pairs, right? And each of this set is randomly initialized initially. Then after training, each set is used to project the input embeddings into a different representational subspace. Okay, that basically means it'll take a vector and it'll try to convert them. So overall, you'll be able to see that by using this, we may get this kind of diagram. See, so here, with a different set of QKV, we will be able to get this attention Z0 with a different set of QKV, and along with that, obviously W of K, W of Q, W of V. This weights will be also different. Similarly, we can go ahead and calculate this attention, which will capture other important thing in the token, right, with respect to the positional encoding. And then here you will be able to see different captures, different outputs, right? So this is the entire information about multi-head attention. So here we are just not focusing on providing one set of vectors with respect to this, but we'll have multiple set of vectors, and each of the other vectors that we are getting, right, which we also call it as attention head, will have importance with respect to other tokens that is available over here in the sentence. Okay. So yeah, this was it about multi-head attention. The concept is very similar. Whatever steps we are doing, instead of just getting one attention head, we will try to get multiple attention head, wherein we will try to train it with multiple that is queries key value pairs by initializing W1 of Q, W1 of K, W1 of V, right? Weights of Q, K, and V, and as many number of attention head will be there, that many number of weights can be parallelly done, right? So this was more about multi-attention head, so multi-head attention, and yeah, in the next video, now here you can see that what all things we have specifically discussed, right? If I go up, oh my god, I've written so many things for you all. So here you can see after performing this self-attention, I need to provide all this information to my feed-forward neural network, right? But here you can probably see now how my diagram will change by multi-head attention. Once I give how, right? After this self-attention, I will be able to get like this multiple heads of vectors, right? So this will be my attention head 1, 0, attention head 1, attention head 2, attention head 3, attention head 4, attention head 5, right? Similarly for this word, I may get other attentions. Now all this I need to pass it to my feed-forward neural network. So obviously the feed-forward neural network will consider this as just one encoding. So we need to combine this, and that is what we're going to see, that how we are just going to pass all these things to a feed-forward neural network and how the forward and the backward propagation is going to take place. That is what we're going to see in our next video. So I hope you like this particular video. I will see you all in the next video. Thank you. So guys, we're going to continue the discussion with respect to our transformers. So already inside encoder, we have discussed how the self-attention exactly works. And again, in our previous video, we have spoken about query, key, value vectors, and then how a score is basically calculated, attention score, how a softmax activation function is calculated, how a softmax function is activation function is applied, everything we discussed, right? Now, after we get the vectors, now see, in this scenario, right, when I've spoken about multi-head attention, for every word, I'll be getting like attention head 1, so I'll be writing Z1, Z2, Z3, right, Z4, Z5, and so much, like it can be 7 to 8 Zs, right? So if I say there are 8 attention head, I'll be getting 8 Z1, Z2, Z3, Z4s, kind of vectors by passing this specific word. Now the next step will be that I need to pass all this to my feed-forward neural network, so that I'll be able to do the further steps, right, inside this particular encoder. Now the problem is that before what we had drawn in the diagram here, I said that hey, we are just passing one word, I'll be getting one vectors, right? But here we are getting multiple vectors. So before we pass to the feed-forward neural network, we need to combine all the specific vectors and send it to the feed-forward neural network, and then probably do the forward and the backward propagation. So the feed-forward neural network is expecting a single matrix. So we need to find out a way how we can condense all this attention head into a single matrix along with some single weights itself, and probably do the entire task. So here you'll be able to see, right now I have multiple attentions like this, attention head 0, attention head 1 till 7, and here I have all the values, right? I have over here, I have over here, I have over here. All these values are specifically there. Okay. And when I say values, here you have this QKV, here you have separate QKV, right? Here also you have a separate QKV. Now the problem starts at how do we combine all these things before we forward it to the feed-forward neural network. So for that, here you can see an amazing diagram. We concatenate all the attention head like this. So Z0, Z1, Z2, Z3, Z4, Z5, Z6, Z7. We're considering that there is a 7 head attention. Okay. So we combine all of them. We do a dot product with W of 0. So this will be my W of 0, where I will be initializing a new weight for my feed-forward neural network. Feed-forward neural network. And after this, we go ahead and calculate our final Z. Okay. So after this, whatever Z we are probably getting over here, this will be a single Z, this will be my another Z, this will be my another Z, right? And this is what we're going to pass it to our next encoder, right? So all the multiple attention head, we're just going to combine it together to make sure that we capture all the specific importance. We give it to the feed-forward neural network, and along with this, we train a specific weight itself. And this is just for one word. Just imagine the one word that I've given, the, right? Or it can be cat. So from this cat, by using self-attention, I've created so many different heads, right? By using, and all these heads will have a separate key value vectors, everything will be separate, right? Then along with this, I'm taking a weight, forwarding it to the feed-forward neural network, then we'll train it to finally get our output, that is called as Z. Okay. And this is pretty much all to the multi-head self-attention. It is a handful of matrices, okay? And you'll be able to do it probably in this way. Overall, if you really want to check one more amazing diagram again from the same blog, I will also draw it for you over here, and this is how the things happen, right? From the entire self-attention till the feed-forward neural network. Okay. So here you can see that from this part to this part, right? From here, or from here, the entire feed-forward neural network actually takes place. So here is your 2 words that I've given, thinking machines. Then for all these words, you have this separate weights, so that we'll be able to get out separate Q, K, and V vectors, and finally you get your Z0. This is for the attention head 1. Then again, for this you have a separate vectors. For this you have a separate vectors, right? And for all the attention head, you'll be having a separate key Q, queries, key value vectors itself. And finally you get this entire weights, and you train it to your feed-forward neural network to finally get your Z. So this was my initial vector. This is what is my final vector that we're specifically getting. Okay. So this is our input sentence. We embed each word, split into 8 heads. We multiply X or R with weight matrices. You calculate the attention using the resulting matrix. Then you concatenate the result of Z matrices and multiply with the weight matrix W to produce the output of the layer. So with respect to one word, I will be able to get this. Like let's say thinking is there, then I'll be able to get this vector. Machine is there, I'll be able to get this vector, right? So this overall explains about the entire attention head. The reason of having multiple attention is that I really want to show you with one practical example. Okay, so here you can see I have over here one visualization diagram. I'll be giving this link in the resources section. Okay, here you'll be able to see that with respect to every word, right? And okay, this will not be a good diagram. So here you can see I have multiple attention. So this can be my attention head 1, attention 2 head, attention 3 head. If I click on each and every attention, you'll be able to see that every attention has a different importance word, right? It is trying to capture much importance with respect to all the words that we have. So if I go ahead and click, this is my other attention. This can be my other attention. This can be my other attention head. You know, it shows the importance of each and every word. So if I just go ahead and highlight over here, see, lay is basically very much highly dependent on, right? So these vectors that will be defining this lay will be specifically on, right? And similarly, if I go ahead and click on other vectors, let's say on is there, cat is there, see, mat is there, separator is there. Cat and mat are highly correlated, right? Correlated basically means there is a huge context dependency on that, right? So this actually gives an idea, and here also you can go ahead and check it out with respect to sentence to A, sentence A to B. Let's say the cat sat on the mat, the cat lay on the rug. If I want to probably see is there any dependencies, so cat is having a dependency on cat. If I probably consider sentence A to A, cat sat on the mat, so see on sat is the first word that it is having a dependency on. So it's, the main idea of self-attention is to get this all right, and with respect to different head, we'll be able to get this. Some more examples which I will be putting it here, right? You can probably check it out. So this is one attention head which you'll be able to see. So here I have a sentence: the animal did cross the street because it was too tired. Didn't cross the street, it was too tired. So here you can see when I highlight on it, it is dependent on street, tired, and animal, right? So some more words are specifically here. Similarly, if I go ahead and see with respect to other attention head, right? Once we calculate, you'll also be able to see this kind of context. So here it is dependent on the animal with different color, cross, right? So multiple attention head basically means you are able to get information from multiple heads itself with respect to the dependency on all the other words. So this was it where we have specifically discussed about multi-head attention, we have discussed about self-attention and all. Still, there are many more videos that are going to come, couple of videos. One is positional encoding, which we are going to discuss, and after that, we will also go ahead and discuss about the entire transformer architecture, because still we are just understanding some of the components in transformer, right? So yes, this was it from my side. I hope you like this particular video. I'll see you in the next video. Thank you. Hello guys, so we're going to continue our discussion with respect to transformers. Until now, we have discussed so many things. That is self-attention layer. We have discussed about what is multi-head attentions, you know, what all operation specifically happens inside the self-attention layer itself. We have actually discussed. Okay. Now in this video, we are going to discuss about a very important topic which is called as positional encoding. That is nothing but representing order of sequence. Okay. Now, see, this order of sequence is a very important thing. Okay. One of the major advantage of using transformer is that, okay, the major advantage, all these tokens, right? All these words tokens, it can process. It can be processed parallelly, right? This is the most important advantage, because at a time I can just directly go ahead and pass my x1, x2 word, and all this operation that specifically happens in the self-attention layer, it will just happen parallelly, right? And if I consider, because of this advantage, there is also a specific drawback. So now if I talk about the drawback, because of this advantage, it lacks the sequential structure of the words. What does that basically mean, right? Now, the sequential structure basically means the order, right? Obviously, since all the words are specifically taken by the self-attention layer in a parallel mode, all the word tokens are taken all at once, and all the processing is basically happening, it will not have any idea whether x1 word has come first or x2 word has come first, right? Let's say I take an example over here, right? I say, hey, lion eats tiger, okay? Or I can basically say, lion kills tiger, okay? So we can take this example. So this is just one sentence. The other sentence can be tiger kills lion. Now, because of this ordering of the sentence, of sentence 1 and 2, the meaning of the sentence completely changes, right? Anyhow, in both the sentences, all the three words are basically considered. And at the end of the day, if I pass this to self-attention layer, you know, and since right now my self-attention layer is also not taking care of the ordering part, both this sentence will be returned with the same vectors, right? With respect to all the words. But as you all know, this entire sentence is completely different because of the ordering of the word. So this is what right now my self-attention layer or this entire transformer architecture is missing, right? It is missing this information. So in order to prevent this, what we specifically do is that we use a concept of positional encoding, and this positional encoding will be responsible in representing the order of a sequence, okay? And that is what we are going to learn about. Because without this positional encoding, it will not know which word is probably coming first, okay? So the concept is very simple. What we will do is that, according to the research paper of attention is all you need, right? Attention is all you need. So what they have actually done is that they will see if this is my embedding vector, right? For this particular word, Similarly, we will go ahead and create another one vector, this vector, and we will see how we can generate this particular vector. And this vector will be nothing but, it will be the positional encoded vector. This is nothing but the positional encoded vector. And this positional encoded vector will be added with this vector. Similarly, this positional encoded vector will be added with this vector, and this vector will be responsible in telling which words are in which position exactly, okay? And that is what is the entire idea over it, right? So there are multiple ways how we can fix this particular problem. One of the ways is that, why not, with this embedding vectors that we are passing, let's say over here I've just taken 3 dimension, why not just add one more dimension and probably talk about the position of the words that are coming. Let's say for the first sentence, tiger comes first, so this position will be 1, then the second vectors that we are specifically giving, this position will be 2, along with the vectors that we are giving, and the third word basically is about lion. Let's say that we are giving one more word over here with the third index, right? So once I'm sending this information, here we are giving some kind of position, right? But do you think right now for a smaller text it is fine, but let's say if I have a book, or if I have a journal, or if I have a novel, right? Here there may be more than 1 lakh words. Now, if there is a more than 1 lakh words, obviously we are not limiting how many number of positions we'll keep on writing, right? And when we have so many number of words, and just imagine we are trying to add a vector with such a big number. So this usually causes a problem while we are doing the backpropagation while updating weights. And if we consider huge data, right? There is no limit of that particular word. So that basically means the right now, with respect to the position, it is unbounded. This position can have any number of words, right? So this is one of the problem, and we cannot directly use with this specific position. You may also say, hey, we can probably apply some kind of mathematical rule and we can try to replace it. But if we go according to the research paper, that is attention is all you need. Here, the idea is very simple. Here, we'll try to add a positional encoded vector, which will be of the same size, and then we will try to add this particular vector to this embedding vector itself, right? And that will actually give the position information with respect to the word that comes in the sentence. But now the question comes, right? How do we probably create this positional encoding vectors? Okay. So for this, the there are two different ways, and out of which we will be discussing one of the way which is even spoken in the research paper, which is written in the research paper. So types of positional encoding. Okay, so first one is nothing but sinusoidal position encoding. Sinusoidal position encoding. The second one is something called as learned positional encoding. Okay, so out of this two, okay, I will give a detailed idea about what exactly is sinusoidal positional encoding. We'll try to understand this. Okay, and sinusoidal. See, so let's go with the first one. That is nothing but sinusoidal positional encoding. And what exactly this is? This is basically a technique of creating that positional encoding vectors. So here it uses sine and cosine functions of different frequencies. We'll try to understand what exactly it is. Okay, of different frequencies to create positional encodings, and we'll solve this entirely with a good example also. Okay, and now because of this positional encoding, because of this positional, we'll not have this particular problem also. Like it will not be like unlimited, because the sinusoidal encoding, all the values will be ranging between -1 to +1, and at any point of time with respect to any number of vectors, okay, you'll be able to see that either we'll be getting the values between -1 to +1. Okay, so let's see this how this exactly works, and then we'll try to understand with a basic example. First of all, in order to compute the sinusoidal positional encodings, the formula is very simple. Okay, and here what we are doing basically, whatever vectors we really want to create, right, positional embedding vectors, all these values, let's say if I have a 4-dimension, all these values will be replaced, right, all these values based on the position of the words will be replaced by this formula. So this is positional encoding. It is nothing but position, comma 2 of I is nothing but sine position divided by 10,000 to the power of 2 of I d of model. We will try to understand each and everything. Okay, this is for the sinusoidal sine function. One more positional encoding that we'll try to calculate is nothing but position of 2 of I plus 1. Sorry, 2 of I plus 1. Yeah, this is nothing but cosine of same formula, that is position of 10,000 square 2 of I divided by d of model. Right, so this is the formula. Now here, let us break down this particular formula, because see, at the end of the day, we need to create this positional embedding vectors in such a way that the dimensions that we specifically have with respect to the embedding vector, the same dimension it should happen. So here, we will go ahead and write where P is equal to, where POS is equal to, is nothing but it is the position. Okay, I is the dimension. Okay, D of model is the, let me just clearly write this down. Okay, so here I will just go ahead and write where POS is the position. Everything will make sense once I solve a specific problem and show it to you. And then here I is the dimension. Okay, and then you have this D of model. It is the dimensionality of the embeddings. Okay, now what exactly this is and how we will go ahead and compute it, I will just show you this with a specific example. Okay, let's say here I have an example which says the cat sat. Okay, first of all we'll convert this into vectors. Okay, so let's say that this is my the is represented by a vector like this, 0.1, 0.2, I'm just initializing 0.3, 0.4. Okay, similarly I have this cat is represented by 0.5, 0.6, 0.7, 0.8. Okay, and then you have this sat is nothing but it is 0.9, 1.0, 1.1, 1.2. So this is the embedding vectors that we have. Now we will go ahead and create the positional encodings for this, because before giving to the self-attention layer, the same dimension, this is just a 4-dimension. So this entirely is like 4 dimension for each and every word. Similarly, we have to go ahead and create our positional encoding with the same 4 dimension. And we are going to specifically use this technique which is called as positional encoding with the sinusoidal learning. Okay, so here what we'll do, again we'll go ahead and probably use the formula. Okay, with respect to the positional encoding. So here I'll write PE. Let me use another color. So here I will just go ahead and write PE with respect to POS, comma 2 of I is nothing but sine of POS 10,000 square I of D of model. Okay, the same formula. And here I'm just going to write PE, that is positional encoding of POS, comma 2I plus 1 is equal to cos of POS 10,000 2 of I divided by D of model. Okay, perfect. Now understand over here. Okay, I have to generate 4 positional encoding vectors. Okay, so here for our example, okay, D of model basically means what? Dimension of model. So dimension of model is 4, right? 4 over here. So I will just go ahead and write for position pos is equal to 0 for this position. For this position, how do I place a value? Okay, so for this I will go ahead and calculate PE. My position is 0, comma. What is I over here? What is I? 2I comma 1, 2I plus 1. Okay, so for the first word you'll be able to see, right? For the first word, I have to represent this into 4 positional encodings, right? So I will iterate through this specific I, right? So here what I will say for position 0, if I want to calculate the position encoding for 0 comma 0, it is nothing but sine of 0 divided by whatever is there, 10,000 square. Square 2 of I. So I is 0 over here, right? So this is 0, right? So obviously this will entirely become 0. That is nothing but 0 itself. So here I will just go ahead and write 10 to the power of 0, right? Because I is 0 divided by D of model, again it is nothing but 4. So this entirely sine of 0 it will become, right? So here I'm actually going to get 0 itself. That similarly, if I go ahead and say positional encoding for 0 position, but first I like one ith position, okay? Ith position. How many ith position I have to really do? It is 0, 1, 2, 3, right? So for the first again, I will go ahead and compute sine 0 divided by anything over here will be 0. Sine of 0 again will be 0. Sorry, it should not be sine of 0. Just a second. It should be cos. Because for every position, you'll be able to see that I will be applying this position and then I'll be applying this position, right? So here you'll be able to see the PE, with positional encoding with 0, 1, okay, is nothing but cos of whatever cos function we are specifically writing. Position is nothing but 0. 0 divided by anything will be 0. So cos 0 is nothing but 1, okay? Similarly, I will go ahead and compute for positional encoding for 0, 2. Now 0, 2 again I will be using sine. Okay. See, you'll be able to see that if I have two embeddings, like if I have this 4 dimensions, whenever I apply a sinusoidal wave, right, like this, a sinusoidal wave looks something like this, and the cosine waves look something like this. So for each vector, we have to probably go ahead and find out the sinusoidal wave, sinusoidal values for that, and for the cosine values for that. That basically means if I want to find out the positional encoding for this 4 dimension vectors, here this one will basically be calculated as a combination of 2. So let's say this is my first combination, this is my second combination. That is the reason we are using this formula. This combination will be calculated. The first one will be calculated with this formula, and the second one will be calculated with this formula. And again, when we go to the next set of 2, this will be calculated by this formula, and this will get calculated by this formula. That is how it exactly works. Okay. The reason is very simple why we are using in this way, because we should not be getting a similar kind of encoded values. If we get a similar kind of encoded values, then we will miss the order of the elements. Right? We'll miss the order of the elements. This is really important to specifically understand. Let's say you say that, hey Krish, why to use this cosine? Instead, just try to use sine. Okay. The amazing thing about sine will be that all the values will be ranging between -1 to +1. Okay. But if I just use sine, there may be that for same 2 different values, I may get the same sign value, right? For this also I may get the same sign value. For this also I may get the same sign value. So that is the reason we may miss the order of the elements or of the tokens, and we don't want this to happen. So what we have done is that we have combined this with another cosine equation. Okay. Now what will happen for every vector? First, if this is computed by sine, the next vector will be computed by cosine. So let's continue this particular findings with respect to the positional encoding. So now my third one that I'm actually going to compute over here will be sine of 0, 2. See, I will be into 0, 1, 2 at this position. I have to use sine. Here I have to use cosine, right? So this will basically become sine of 0. And then we are going to use 10,000, 2 by 4. Okay. But again, here I'm actually going to get sine of 0. Then again, this will be 0. And finally, we will go ahead and compute the positional encoding of 0, 3. Again, we are going to use cosine. Again, this entire value will become 0, and this will be 1. So with respect to our first word, right, what is the positional encoding that we are getting? It is nothing but 0, 1, 0, 1, right? Now, similarly, if we go with respect to our position 1, right? Position 1 is with respect to our second word, right? So if we go ahead and calculate it, so let me just go ahead and write for position 1. So for position is equal to 1. Now I'm just going to use the same formula. First of all, I'll write position encoding for 1, 0. 1, 0 basically means my second vector. So this is for this, and this one will be my second vector, which will be represented by another 4 dimension. The positional encoding will be shown by, and this is for this particular word. The positional encoding is for this word. Okay. Again, I have that same operation that I have to do. And when I say position 1, that basically means we are going for the first word, right? And finally, after that, we'll go for the second word. So positional 1. Then again, we go ahead and compute it. It will be sine. Again, it will be 1 divided by 10,000. Okay. 0 divided by 4. Right? Why 0 divided by 4? Because I is 0. So again, I'm going to get sine of 1. Sine of 1 is nothing but it is approximate. If you go ahead and calculate it, it is 0.8415. So similarly, we will go ahead and calculate the post encoding of the position 1. So over here, we will go ahead and compute now the post encoding of positional 1 with the I value is equal to 1. So again, here, what formula we're going to use? We're just going to write cos, and let's see the formula. So I will also make sure that I will try to specify this formula over here so that you'll be able to refer this. Okay, so here I'm just going to copy it. I'm going to paste it over here. The next formula, again, I will select this and I'll paste it over here. Okay. So once I'm calculating this, okay, please try to understand over here. So I'll select this right now. Okay, so I'll keep it over here, and similarly this I will keep it here for my reference. Okay, so here when I'm calculating the position 1 and I is equal to 1, so if I really want to use the cosine value, so this I that you will be specifically getting, right? So here I will write position value 1, okay, 1 divided by 10,000, okay, to the power of 2 of I, right? So 2 of I is nothing but over here I'll just go ahead and write 2 multiplied by 1 divided by 4, and this whatever approximate value we'll be getting, we'll get it 5403. Similarly, you can go ahead and calculate the post encoding for 1, 2. Again, we have to use the sine formula, and with respect to the sine formula, just go ahead and write over here 1 by 10,000, 2 by 4. This will be approximately again equal to 0.01. And again, once we go ahead and compute it for 1, 3, again I have to use my cos value. Just try to do the computation. Okay, I'll leave it up to you. So here I will be getting my value as 0.995. Okay, so in short, here what we have actually done is that the word that we have specifically taken, right? Cat. First of all, I'll just go ahead and write with respect to the word. So for the word, so here you can see for the word, which was given by the vectors, right? 2, 3, 4. The vectors for the that we have actually used is 0.1, 0.2, 0.3, 0.4. So here if I go ahead and write, this is 0.1, 0.2, 0.3, 0.4. For this, we have converted this into some other encoding. And here, the positional encoding is nothing but this value that is 0, 1, 0, 1. Okay, so here we have specifically got as 0, 1 and 0, 1. So this is the positional encoding that we are able to find out for this particular vector, right? For this vector. Similarly, for the word cat, initially we had this vector, and after performing the positional encoding, you'll be able to see it was 0.5, 0.6, 0.7, 0.8, right? So here I will go ahead and write 0.5, 0.6, 0.7, 0.8. This we were able to get an encoding of the values that we got over here, 2, 3, 4, and the values were nothing but these all values 0.8415, 0.84, then you got 0.54, and then 0.01, and 0.995. Okay. Now this is how you have actually got the positional encoding, and through this way, what you are actually doing is that we have to probably sum up these values, right? So finally, you'll be able to see whatever self attention I will be giving, right over here, whatever vectors I will be giving in the self attention layer. Okay, it will be the combination of your vectors that we are specifically getting with the positional encoding. That is nothing but 0.5. Let's say sorry, not 0.5, 0.6, but instead I'll write 0.84. Let me just go ahead and remove this, and let's use an positional encoding. Here it will be 4 dimension again based on the problem statement that we have done. In the research paper, it is taken as 512 dimension. Okay, you can go ahead and check out the research paper. So 0.84, 0.54, 0.01, 0.9999. Okay, and this we have to sum it up with our vectors that we have actually calculated, right? So for the cat word, this will be the word that will be going on 0.5 plus 0.6 plus 0.7 plus 0.8. Similarly, for the other vector that we have, right, the ordering can be placed over here, also it can be placed over here, but we are handling it with the help of, because all the words will be going parallelly, right? Now this positional encoding is making sure that whatever values we are putting, it knows the order now, right? So for this, let's say the value was 0.1, 0.2, 0.3, 0.4. So So for this, you are actually getting nothing but 0, 1, 0, 1. And this is also going to get summed up. After the summing up is going to happen, then this entire value is going to go to the self-attention. And finally, we are going to give entirely this to our feed-forward neural network. And here we are going to get our Z1, here we are going to get our Z2, considering the multi-head attention is applied. But these values that we have actually got, these values that we have actually got. So here I just need to reverse this, okay? So this needs to go down and this needs to come up, okay? Because this is the positional encoding, okay? So this were my word vectors. So if you probably go ahead and see, with respect to the cat, this is the vector that is getting created. This is with respect to the, this is my positional encoding, making sure that what word is gone and which order it is gone. But in this case, you know, the has to come over here, cat has to go over there, right? And similarly over here, this is my positional encoding. Please don't get confused. I'll just change the order here itself, okay, purposely. But it won't matter a lot because anyhow I'm giving the positional encoding information, so that to make sure that which word is coming after what, right? And then we finally give it to the self attention, and here if multi-head attention is basically there, multi-head attention is there. You know what is exactly happening in the self attention, and all the multi-head attention will be given to the neural network, okay? That is feed-forward neural network, and finally we get this, that is Z1 and Z2, which will be our contextual vector. So this was the overall idea about positional encoding. But in short, if you really want to know about positional encoding, it's more about, you know, it's more about making sure that the order of the words is taken, the representation order of word or sequence is given to the self-attention layer in some way, right? You need to make them know, okay, this is the first word, this is the second word in the sentence. Obviously, this problem will not happen in RNN because RNN we give one word at a time with respect to timestamps, right? So this was one of the most efficient technique that we used. One more technique is something called as learned position encoding. Now, in the case of learned position encoding, what we do is that in this case, positional encodings are learned during training, okay? During training. Now, when we say during training it is done, that basically means we again need to create a positional encoding matrix over here, and it needs to get updated through backpropagation. Again, I don't want to discuss more about this because I think in the research paper also it is mentioned about sinusoidal position encoding, right? And this is nothing but it's a combination of sine and cos. We keep on creating this such that no two values with respect to our positions, no two values should get the same value over here with respect to the encoding. That is the reason we specifically use this. And this is how that calculation is basically done in order to calculate the positional encoding of a specific word. So I hope you like this particular video. This was it about positional encoding. In the next video, we are going to discuss about something called as layer normalization, and that is what we are going to discuss in the next video. So yeah, I will see you all in the next video. Thank you. Take care. Hello guys, so we are going to continue the discussion with respect to transformers. Already till now we have discussed about many things, right? We have covered something called as self-attention. Then after covering self-attention layer and how it exactly works, we have also understood about multi-head attention. Then after covering multi-head attention, we saw the problem with respect to the sequence of word, and for this we also understood about what is the importance of positional encoding, right? And we have actually seen a lot of examples. I have personally done all the calculations, how with the help of self-attention layer, how we can convert that fixed vectors that we specifically had from the inputs to contextual vectors, right? So all those things we have specifically covered. So in this video, we are going to go ahead and understand about something called as layer normalization. Now, layer normalization is one of the components. Now, if you see the architecture of the transformers, and this architecture is from the research paper, here you'll be able to see that initially I have my inputs. We convert this into some input embeddings. Then we add it with the positional encoding. And after this, we go ahead and create out multi-head attention. So here we specifically pass through our self-attention layer, right? Now, when we are creating this multi-head attention, now you can see the next step, what exactly after this it is, right? It is basically called as add and normalize, okay? Add and normalize. And this is what we are going to talk about, right? When we say add and normalize, the normalization technique that is specifically applied is called as layer normalization. So we are going to understand the mathematical intuition. Along with this, there is also one more topic that we really need to understand, which is called as residuals. Now here you can see that before going to the multi-head attention, whatever vectors that I get after adding the positional encoding to the input embedding, that is also passed to this add and normalize. So these are called as residuals, okay? Residuals. And this provides some additional signals, okay? Additional signals to the add and to the layer normalization, right? Layer normalization. It's just like this line is basically providing the information of this input embedding plus positional encoding vectors to the additional and normalization layer, right? So in short, that is the reason we basically say here we are saying add and normalize. So we are going to probably add this previous encodings that is probably coming from the input embedding and positional encoding, and then we are basically going to normalize, right? So that is basically the residuals that is getting added. So this is the information, whatever pre-hand we are able to get, that we are passing it to the next stage, okay? And that is what residuals is all about. But again, don't worry, we'll try to understand it, what exactly is normalized and how this addition and normalization takes place, okay? Now before we go ahead, let's understand where this addition and normalization will get added, okay? So here, again, I've taken this particular diagram from the blog, right? So here you initially have your input embeddings, okay? Layer by layer it will be there. This is for my word 1, word 2, right? Then for each of these words, based on the number of attentions, I will be initializing different weights, right? Then we probably go ahead and find out query, key, and value vectors for each and every attention. And finally, we get all the attention itself, right? Z0, Z1, and Z7. Now see one thing over here. Where does this, see, because this is the multi-head attention, right? And this multi-head attention, before we pass it to the feed-forward neural network, right? So here we will go ahead and apply our next step, that is nothing but add and normalize. So let me write it in another color, add and normalize. Okay. And this is where your layer normalization basically happens. Layer normalization basically happens. Now, what exactly is this layer normalization? We'll discuss more about it. But with respect to the kind of working that you'll be able to see, that over here, add and normalize is specifically happening. Okay. And here you can see once we also provide this before we go ahead, we also need to add our positional encoding. Okay. And this positional encoding will be like with the same shape, right? So let's say if this is my positional encoding. So here 1, 2, 3, 4. So this will be my positional encoding that will get added and it will be sent over here. Along with this, what happens is that this positional encoding information is also sent over here and it is added before the normalization takes place. Okay. And the reason over here why we do this, because we are providing the signals, this entire information to this layer. Okay. For more additional signals. So that is what residuals is all about. Now let's go ahead and understand about the layer normalization. So first of all, we will just get to know an idea about what exactly is normalization. And specifically with respect to deep learning, we use normalization in 2 different ways. One is batch normalization. And the other one is something called as layer normalization. batch normalization and layer normalization. Now let's discuss about this batch and layer normalization. So for this, I will take an example. Let's say I have a neural network with two inputs, okay? And let's say here in my hidden layer, I have two hidden neurons, and then finally I have one, right? So whenever this input is basically connected to the hidden layer, right, in this way, and then finally I'm able to get my output over here. So this is my output. Now what exactly is normalization? See guys, let's say over here I am having two features. Let's say my feature is like house size, right? This is my first feature. Let's say I'll go ahead and write area of the house, okay? House size and area. I'll say number of rooms in my second feature, number of rooms, and I need to probably predict the price of the house, okay? So this is my F1 feature, this is my F2 feature, and this is what F1 feature goes over here, F2 goes over here. Now, before we usually send our F1 and F2 input to this particular ANN, that is artificial neural network, or I can also say it as feed-forward neural network, right? Here I will be having some information, and one by one, I will probably send this information for training the neural network. Now, what usually happens is that the first step, and you know that, right? I will be having multiple values over here. Let's say I'll just go ahead and write what is the house size. Let's say it is 1200 square feet, okay? Number of rooms are 2, and let's say the price is 45 lakhs, okay? And I will go ahead and write, hey, my house size is, another house data that we have is 1500 square feet, the number of rooms are 3, and this is 70 lakhs, okay? And similarly here you have 2000 square feet, you have 3.5 BHK rooms, and here let's say the price is 80 lakhs. So all this information you specifically have. Now the first thing that we basically do, before we provide all these inputs, F1 and F2 for the training, right? What do? We do something called as normalization. One of the most common normalization we do, right? That is nothing but standard scaling. Now what does standard scaling basically mean? With the help of standard scaling, right? What we do is that we take each of these features, right? Each of these features, even the output feature if we want, and we apply a general standard scaling formula. And that we basically say it as Z-score. Now, Z-score, what happens is that the formula is very simple. We take every input, we subtract it with the mean, and we divide by standard deviation. Now, once we do this, if we are considering any feature, let's say if I'm considering house size, and if I apply this formula, all these values, you will be able to see that we will be getting in such a way where my mean will be 0 and my standard deviation will be equal to 1. Okay. So what is basically happening? Let's say if F1 is one of my distribution, after applying the standard scaling, this will get converted into F1 dash, and inside this F1 dash, here you'll be able to see my mean will be 0 and my standard deviation will be 1. Okay. Now, one thing that you really need to understand, right? Whenever we are applying this formula, this basically gets applied to this entire column. Okay, to entire column. So first of all, what we need to do in order to apply this formula, we need to calculate the mean for this. We need to calculate the standard deviation for this, and then for every number, we will go ahead and apply standard scaling. This is what happens when we try to provide our input over here, right? When we provide our input over here. Now, this scaling is fine, okay? And usually we do this. And what usually happens because of this, I will tell you. There's some very good advantages of using this. And similarly in deep learning, if I talk about deep learning, right? In deep learning, let's say my input is in the form of images. So there also we do some kind of scaling, and that scaling that we specifically do for the data is something called as min-max scaler. Now, in the case of min-max scaler, you know that all your images, right? Let's say I have some color images of this, of some 4x4 matrix, and you know all the values will be between 0 to 255. So what we do after applying this min-max scaler, we convert all these dimensions between 0 to 1, right? 0 to 1, 0 to 1. All these pixels that we have, right? If it's 4x4 pixels, so we try to convert this into 0 to 1. So this usually we do for the input data, whatever input data we specifically have. And what are the usual advantages for doing the scaling techniques, which we also say as normalization? First, let me just go ahead and write some of the advantages. The first advantage that I would like to write is about improved training stability. Okay. Now, what does this improved training stability basically means, right? See, before we are passing it to our ANN, right, all the information, we know that my data may be following a different kind of distribution. It can be this distribution, it can be this distribution, it can be probably this kind of distribution, different distribution it may follow, right? And when we actually convert this distribution into a distribution when all my information is centered near to 0, right? Because here what is happening? Here we are able to convert it to data where our mean will be 0 and it will be standard deviation equal to 1, right? So, and all the values that you'll be seeing, let's say initially when I probably check the distribution, let's say that I'm checking the distribution between my F1 and F2 feature. Now, you know my distribution is coming over here. Let's say it is coming over here. Now, what we're doing after applying scaling is very simple. We are taking this, and this is my F1 and F2. Now, here my magnitude was, I'm trying to bring all the magnitude over here, right? So here, what is the mean property over here? Your mean will be equal to 0 and your standard deviation will be equal to 1. This entire distribution will have this kind of distribution itself. Now, because of this, what will happen is that when we are doing the back propagation, okay, when we are doing the back propagation, we will definitely not face any kind of problems related to vanishing and exploding gradient problem. This is one of the properties that we usually get after doing the scaling. And right now, all scaling has been done in the center, right? If we had these huge values, there may be scenario that whenever we are doing some kind of multiplication with respect to the weights and all these values will be quite huge, okay? And because of this, what will happen is that the second important thing that may happen is that we will be able to get faster convergence. Because obviously these values are very slow, less, right? So if you remember the gradient descent with respect to our weights, we try to find out our loss, right? Now, since our values are already centered completely, right? This is 0 centered. All the data over here is like 0 centered, right? You'll be able to see that initially, if I compare with respect to our weights and loss, our loss when we are doing this, when we are probably doing the scaling, initially it will be very, very small. If we don't do this, there may be scenario that there may be a huge loss over here, and then our main aim is basically to come to the global minima, right? It can be from here, it can be from here, it can be from here, it can be from different position, right? So because of this, we are able to do the faster convergence. And the best thing will be that when we apply backpropagation, there will be a stable updates. Okay, perfect. Then one more important information that I really want to talk about, right? And that point I will discuss later on. But first of all, this is one of the way how we do the scaling. But again, if I take this particular neural network, okay, let's say this is my neural network, this is my input layer, this is my hidden layer, and this is my output layer. Now you know that this is connected to this, this is connected to this, this is connected to this, and I have this, right? Now here you will be able to see that if I'm doing all the normalization with respect to F1 and F2. Now you know over here we have W1, we have W2, we have W3, we have W4, right? Now in the hidden layer, if I just consider as an example, let's take this as an example. Let's say I will just go ahead and take some house size, right? Area, rooms, how many number of rooms are there? And this will basically be my price, okay? So let's consider these three features I have, okay? The first feature with respect to the house size is, let's say 200 square feet. Now, after I probably do the scaling, let's say I have some values like 1, I'll just put some smaller value, okay? Let's say 0.45, okay? Rooms, I will just convert this into 0.55. And price, I'll keep it like that only, 45 lakhs, okay? Then again, this can be 0.60, this can be 0.20, this can be some other value. Similarly, I'm just putting some values over here, okay? After doing the scaling. And this is my F1, this is my F2, I'm sending this value, okay? Now, you know that when I'm sending F1 and F2, right? So first feature I've given over here as 0.45, and this is my 0.55, right? Now, what is basically happening over here? The first, what I will do for this particular node, we will go ahead and see that the first Z1 that we will go ahead and compute, and here you know that a bias is added, B1, and here bias 2 will be added, and top of that activation function will be applied. So inside the Z1, we will try to apply an activation function. Let's say I'm going to apply a sigmoid activation function. So what is my first feature 1 value? It is 0.45 multiplied by, okay, W1. Okay, so this basically becomes my W1. Then 0.55 multiplied by, what is it? W3, right? Once we do this, then we are adding a bias, right? We add a bias that is B1, right? Now, once we do this entire calculation, we pass it to the sigmoid activation function, we get some value. We will get some value over here. You can go ahead and calculate the value if you want, okay? You can initialize any weights and all, okay? Now, similarly, I will go ahead and do it for Z2, right? Z2 is the output of this. So Z1 is here and Z2 is over here, right? So in the case of Z2, again, I will go ahead and apply sigmoid activation function with respect to that whatever value I'll get. Here I'll add a bias, and this will be my another value, okay? So here I'm getting my value 1. Here I'm getting my value 2, okay? If I probably consider this in the form of matrix, it's very simple. How many weights are basically getting created? 2 cross 2. So here the output that I'm actually going to get is 2 cross 2, right? So here you can see 2, 2, right? So 2 cross 2 will be basically my output, okay? 2 inputs I have. So this is 1 cross 2. Then with respect to this, you'll be able to see that I'm passing it through all the weights over here. So it will come 2 cross 2 matrix, okay? So this is fine. Let's discuss more about this, okay? Now let's observe this. So this is my value 1. This is my value 1. This is my value 2. Now when I have this value 1 and value 2, initially when I gave this F1 and F2, obviously we have done the normalization. But after doing all this kind of multiplication, don't you think this value 1 and value 2 value will change when compared to the distribution of F1 and F2? Right? Whatever multiplications that we are doing over here, does this distribution may change? Does this distribution may change? So here, let me just go ahead and write it over. Here Z1 is nothing but some value, Z2 is some value. Okay. Similarly for all the other inputs, I'll be getting some value. So whatever inputs, whatever calculation that we are getting over here, don't you think this may have a different distribution when compared to this feature 1 and feature 2? Right? It may have a different distribution. And that is what is the problem, right? Because the distribution is getting changed, right? It may have any kind of distribution over here. This and this distribution will definitely get changed, right? And for most of the problem statement, we feel that okay, this distribution should not be getting changed when compared to your input features distribution, right? And it is always good to have a normal distribution at each and every place. But here, what is happening because of so many different types of operations that you have done, that distribution is getting changed over here. Now, because of this, what we have to do is that in order to make sure that the distribution does not change very much in a way that it impacts the entire training of the artificial neural network or any neural network, what we do is that we further go ahead and perform normalization on top of Z1 and Z2. So here we go ahead and perform normalization in every output Z1 and Z2. And this normalization is basically called as batch normalization. So in the case of batch normalization, we take this entire values of Z1, we normalize it. How to normalize it? I will talk more about it. I will just show you the formula over here. Okay. And this Z2. So for this Z1, if I really want to normalize it, what I have to do? I have to go ahead and compute the mu, the standard deviation, let's say mu1 and standard deviation for this. And for every number, we will go ahead and apply the formula. Okay. And similarly for Z2, if I really want to normalize it, again, I will go ahead and compute the mu2 and sigma 2, standard deviation of 2 for that particular Z2. And for every number, I will go ahead and apply my Z score. Right. And that is how the entire normalization probably happens. Right. By doing the normalization, again, our distribution will start matching this particular distribution. Because again, what we are doing when we do some kind of normalization over here with the help of same Z-score value, you'll be able to see that my mean will again be coming to 0 and the standard deviation will be equal to 1 or near to 1. And when we are doing that, distribution will start matching with your features 1 and feature 2. Okay. So this is batch normalization. Now, what is the difference between batch normalization and layer normalization? I will talk about it. Okay. So here, let's say I will also go ahead and talk about batch normalization versus layer normalization. Because if I probably consider my neural network, okay, because if I consider transformer, so in transformer specifically we apply layer normalization. Okay, so let's say over here I have my feature 1, my feature 2, okay, and this was my Z1 output, this was my Z2 output, right? I had some values over here, right? So I had some values over here. So batch normalization says, hey, go ahead and normalize each and every value like this, right? This was batch normalization. Layer normalization says, hey, instead of taking the complete Z1, what you do is that you take layer by layer. You take layer by layer and then you normalize them. So you normalize in this way. For this, you go ahead and compute your mu1, sigma 1 and apply your Z score with respect to x of I minus mu1 divided by sigma 1. X of 1 will be this, x2 will be this. Similarly for this, you go ahead and calculate your mu2, sigma 2. Then you go ahead and calculate your Z score. That is nothing but x of I, mu2 by sigma 2. And similarly for this, you go ahead and compute mu3 and sigma 3. And for this, you go ahead and apply your Z score, x of I, mu3 divided by sigma 3. Okay. And this way, you specifically normalize in layer normalization. This is the basic difference between batch and layer normalization. So guys, I hope you got a basic idea with respect to batch normalization versus layer normalization. Now let me talk about two important learnable parameters that is called as gamma and beta. Okay, these learnable parameters are also used while we are training our models. Okay, now what are these learnable parameters? Why it is specifically used? We will discuss about it. But before that, what is the use of layer normalization that we'll try to see? Let's say over here I have Z1, I have Z2. Okay, and this Z1 and Z2 is what? It is basically the output from here, right? So here we are basically talking about, right? And like that we can have any number of hidden layers. For every hidden layer also, it is a good idea that we actually perform batch normalization. Okay, now let's say with respect to Z1 and Z2, I have different values, and with respect to this, let's say I'm also having some zero values. Okay, let's say over here also I'm having zero values. Okay. Now for this values that I have, what is the use of doing layer normalization? See, in batch normalization, what we do, we take this entire Z1 output, Z2 output, and I say Z1 output. See, I'm basically considering the output of both of them. Okay, both of them in short, sorry, in the form of this particular matrix. So Z1 at one side and Z2 as one side, right? And it is in the form of matrix itself. Okay. Now understand one thing over here. Okay, very simple. If I have many number of zeros over here, if these are zeros, basically the output is not coming up anything, right? When we have this kind of numbers, when we have this kind of numbers, so here we are definitely performing batch normalization, right? We are taking this entire batch and we are normalizing it. Okay. Now once we are doing this, you know that most of the values are zero, but for all these zeros values also, we are still normalizing it, right? And we are normalizing how? By calculating your mean value, sorry, your mean value for this, okay? And then along with this, you are calculating your standard deviation, and then you are applying z-score for each and every number. Now, when you apply the z-score for each and every number, these values are also going to change, right? Some other values will definitely come over here. Similarly, over here you have the zeros. Now, what is basically happening? This zeros is impacting the entire distribution. So this entire distribution will get impacted because of this normalization, right? So usually in ANN and all, we definitely apply batch normalization, but in transformers that we have seen, we specifically go with layer normalization, because in transformer we have this NLP kind of use cases where every word is specifically important considering the context of all the other words, right? So what we do in layer normalization, we go ahead and take each and every combination. We basically take each and every layer's combination, and then we go ahead and normalize it. Now let's say if I have 0, 0, even though we go ahead and normalize this, I know I'm going to get the mean is equal to 0 for this. If I go ahead and calculate, standard deviation is also 0. So no much impact, no values is going to change. Similarly over here also no values is going to change. Similarly if I have 0 over here, no values is going to change, right? This is the most important thing and the basic difference between layer and batch normalization. Now one more question that comes in mind. Is it compulsory that we always have to do this normalization? What if the final output of Z1 and Z2 that we are getting, and this distribution may be important for predicting the output, and that point of time, what if I do not want to do the normalization? Okay, because I'm considering, hey, for my problem statement, whatever distribution I'm getting in Z1 and Z2, that is perfect for my execution. Let's say for my solving my problem statement. So if I do not want to normalize this, so for that we will be using two learnable parameters, that is gamma and beta. And this learnable parameter will be specifically learned and we are training our entire neural network, right? So now let me just go ahead and write again. So Z1, if you're calculating, it will be some function. Let's say I'm going to go ahead and apply my sigmoid over here, right? And this will be W transpose X, whatever transpose you're specifically doing with B1, right? Or whatever B1 weights we are specifically getting. After this step, what happens is that we assign learnable parameters, okay? And this learnable parameters, I'll just write it as Y. Y will be my output. And here I will be using gamma, okay? Gamma. And then I will go ahead and use this X, Z1, okay? Minus mu1. Z1 basically means all the numbers over here. We are going to subtract it minus mu1, which we are going to calculate it. And then along with this gamma parameter, we are also going to use one beta parameter. And these are the learnable parameters. Now you can see that, right? Learnable parameters. Let's say if our distribution is not important over here and we don't need to normalize it, right? Then based on this gamma and beta value, we can make sure that we can tell, hey, do not normalize in this scenario, or normalize in this scenario based on the data that I have, right? So that is the reason we use this gamma and beta value. I will be showing you this entire example by solving a simple problem also as we go ahead. But I hope you got an idea with respect to your layer normalization and batch normalization and how this entire layer normalization is probably taking place. And we specifically use this two important parameters, that is gamma and beta. Okay. Now I hope you have understood till here. Now we can go back over here and you can see why add and normalize is basically coming over here, because after this particular output that I get, okay, it is really important to understand, okay, after this particular output that I am actually getting, once we combine this entire output with respect to the sequence length that we are getting, right, this output is going to get added with this plus this, which I will mention it as x dash. So x dash is going to get added with this entire values, right? And then we are going to apply our layer normalization, right? So here we are going to specifically apply our layer normalization. Okay, perfect. So that is what is all about layer normalization. Now what I will do, I will go ahead and solve a basic problem, okay, just by putting some numbers. And when we use this gamma and beta, these are also called as scale and shift parameters. So this gamma and this beta is also called as scale and shift parameters. Okay. Now let us go ahead and let us take a simple problem. Okay. So I will take a simple problem where I will take an example of cat as a token. Let's say I will denote this cat as token embeddings like 2.0, 4.0, 6.0, 8.0. Let's consider that this is my 4 dimension. And the next parameters that I'm actually going to define is my gamma and beta, because these are the learnable parameters. Initially, this will be initialized. Later on, we'll train them, we'll learn them. 1.0, 1.0. So let's go ahead and initialize this to 1.0. And beta, I will go ahead and initialize to 0.0, 0.0, 0.0, 0.0. The reason is very simple. I've seen the research paper and they have initialized this. Okay. Now we will go ahead and perform step-by-step calculation, like how specifically it happens with respect to the transformer and how this entire process basically happens. Okay. So we will just go ahead and apply this normalization. We will try to calculate, we'll try to find out the normalized vector, then we'll do the scale and shift, and then we'll finally get our y value. Okay, so this entire computation that we'll do. Remember one thing over here, I'm not taking W transpose X, instead I'm directly taking these particular vectors, and how one vector gets normalized. That is what I'm actually planning to show you. How these vectors will get normalized. Okay, normalized. That is what I'm actually going to show you over here. So let's see this in the next video. So guys, now let's go ahead and let me show you an example with respect to all the steps that we have discussed in layer normalization. Okay, so for this example, as I've already mentioned, we will be taking a single token in sequence, going through a layer normalization process within a transformer layer. Okay, so the initial step, we have initialized some values over here. Okay, token embeddings. Let's say this is the token for cat. It is represented by these vectors. We have initialized some parameters. Okay, and this parameters is basically, when I probably say, right, this is this gamma is your learned scale parameter. Okay, and beta is basically your shift parameter. So that is the reason we say it as scale and shift, right? This combiningly is basically called as scale and shift parameters. Now let's go ahead with the step-by-step calculation. So for the first vector, first of all, we will go ahead and compute the mean. Because if you remember, the z-score formula is nothing but z-score is equal to x of I minus mu divided by standard deviation. Okay. So here, if I go ahead and compute the mean, so it will be nothing but 1 by 4. Let us take all the vectors values 2.4, 4.0, 6.0, 8.0, and let's go ahead and compute this by 20.0 divided by 4, which is nothing but 5.0. Okay. Next, let's go ahead and compute the variance. Compute the variance. So variance is nothing but your sigma square. So for that, how do we compute it? It is very simple. Sigma square is equal to 1 by 4. Then we take up each and every numbers. Okay. And we subtract it. Let's say the first number is 2.0 minus 5.0, which is my mean, plus 4.0 minus 5.0 whole square, plus 6.0 minus 5.0 whole square, and plus 8.0 minus 5.0 whole square. So this is how you calculate the variance. So overall, you'll be able to get your variance as 5. Okay. So now here you can see, obviously your mean and your variance looks 5, 5. Okay. So now in the third step, we are going to normalize all our inputs. Okay. Third step, let's go ahead and normalize the inputs. Now in the case of normalizing input, it is xi hat, which is nothing but x of I minus mean divided by just dividing by is root of, what we will be basically doing is that we will also be dividing this by standard deviation, but instead of just writing standard deviation, I will just go ahead and give a new representation, square root of variance plus epsilon value. Okay. Now this epsilon value, we will be using a very small value, let's say 1 e to the power of minus 5. Okay. And this is used to avoid division by 0. Okay. This is basically used to avoid division by 0. So here, if I just go ahead and see and calculate this, it is nothing but root of 5.0 plus 1e minus 5, which is equal to nothing but root of 5.0001, which is nothing but 2.236. Okay. So this is my 2.236 over here, and this is what is my below value that is coming. Now we will go ahead and normalize for each and every values with respect to the numbers. So the first normalized value will be xi bar, okay, let's say, and I will write 2.0 minus 5.0, which is my mean, and here we are just going to divide by 2.236. This is approximately equal to 1.34. Similarly, x2 bar vector that we have, I will subtract 4.0, 5.0 divided by 2.236, which will be approximately equal to minus 0.45. And similarly, coming to the next vector, that is x3 bar, third vector. Here again, we will go ahead and write 6.0 minus 5.0 divided by 2.236, which will be approximately equal to 0.45. And x4 bar will be nothing but 8.0, 5.0, 2.236, which will be approximately again equal to 1.34. Okay. So these are my outputs, and this is my normalized vector. So here I have my normalized vector, but still we need to add something very important. So normalized vector, my x bar will be nothing but minus 1.34, minus 0.45, 0.45, 1.34. Okay. Finally, let's go ahead and apply our fourth thing. Still, we have not applied beta and gamma parameters, which is like scale and shift. So here we will go ahead and apply scale and shift. Now with respect to scale and shift, I will go ahead and write y of I, gamma of I, x of I plus beta of I, right? You know your gamma. Gamma is nothing but 1.0, 1.0, 1.0. So we're just going to scale and shift, okay? Beta is nothing but 0.0, 0.0, 0.0, 0.0, okay? And again, in order to just do the scaling and shifting, obviously just by seeing these particular values, you are going to get the same x bar or final y output, which is nothing but minus 1.34, minus 0.45, 0.45, and 1.34. So in this scenario, when we initialize this particular value, and this is what I explained, if I say here this distribution is important, I will just, this value will be remaining like this itself, and we will be getting the same value. Let's say if you want to change this distribution, some more values will be present over here, and based on that, you can multiply and add that particular values, right? So this was the entire understanding about how a layer normalization work. This we are specifically applied to a specific vectors. I know on these vectors we apply positional encodings, then along with that we go ahead with self-head attention, multi-head attention and all, and then finally whatever output we are basically getting, we add it, right, at the end of the day from this particular architecture that we see. Now similarly, once we do this normalization, you can see over here, we are passing this information to feed-forward neural network, but before that, again we are going to pass this entire signal back to the next add and normalization, where I will be adding this output again back to my output of the feed-forward neural network, and again we'll be performing normalization. So after doing this entire information will probably go to the decoder, which we'll discuss in the later stages. But I hope you got an idea with respect to the entire working, with respect to add and normalization, multi-head attention, positional encoding, input encoding, almost each and everything has been explained. Now in the upcoming video, we are going to discuss about the encoder architecture, what is remaining, and how the entire other operations basically perform. That I will be discussing in my next video. Thank you. Okay, so we are going to continue the discussion with respect to our transformers. Now, in this video, we are going to discuss about the entire encoder architecture. Already, we have discussed about self-attention, we have discussed about multi-head attention, we have discussed about positional encoding, and so many different topics we have also discussed. We also discussed about layer normalization and each and everything. But now, based on the research paper, we'll just try to discuss how the entire architecture is, because this is just one encoder, right? And this is just one decoder. So right now, first of all, we'll focus on encoder. But initially, only I told you, right, based on the research paper, you'll be seeing that there will be 6 encoders like this, right? So there will be not one encoder, but instead of this, there will be 6, like 1 encoder, 2 encoder, 3, 4, 5, 6. Similarly, there are 6 decoders, okay? And with respect to any task like machine translation, you give your input over here, you get your output over here, right? So this is the part that we are specifically going to discuss about, okay? When I say this is just one encoder, that basically means this part can be mentioned in this way, right? If I probably expand this, it is nothing but it is basically this entire encoder part, right? Similarly, you have other encoders also, because after the information is basically coming out of this, it will go to the next encoder, then it will go to the next encoder, then it will go to the next encoder and all, right? So based on the research paper, let me just go ahead and write some very important information. So first of all, the input that you specifically take, right? You convert that into vectors. Then you add a positional encoding on top of that, then you pass through a self-attention layer, right? So if I probably show you the flow, it looks something like this, right? So I'll show you step by step like how things basically happen, and then we will just try to understand like how many embedding vectors is specifically used and all. Okay, so let's say this is your input sequence. So here is my input sequence. Now from this input sequence, what we specifically do, we go to the next step. In the next step, we are specifically going to convert this into vectors, that is through text embedding techniques. It can be any embedding techniques. Plus we add it with positional encoding. Okay. So once we add this with positional encoding, so this is what your input encoding plus positional encoding is basically going on, right? The input sequence, when it is converted into text embedding, so the number of dimensions that is specifically taken for the text embedding, it is nothing but 512. Okay. That basically means every word is converted into a 512 dimension based on the research paper. Okay, so in the research paper it is mentioned, when they tried to entirely create this, initially they used this 512 vectors for every input sequence, right? So positional encoding will also be same, right? Then after we pass through this, what we get our multi-head attention, right? We get our multi-head attention, and this is where your self-attention works, right? Between this multi-head attention. Multi-head attention basically means how many different head attentions you have over here. So if I probably talk about here, you have 8 head attentions like Z2, Z3, Z4, Z5, Z6, Z7, Z8. So this is also based on the research paper. So in research paper, how many attentions head they specifically used? 8. Okay, then before we go ahead and pass this information from multi-head attention, here what we are specifically doing, here we are first of all adding and then normalizing. So that is the reason we say add and norm. right? The normalization technique that is specifically used is layer normalization. So here what we are doing, before doing this, we need to add this information that is probably coming from this layer. And this is what is called as residuals. Okay, this is basically called as residuals. What is the importance of this? Just imagine, before I do the normalization, the output of the multi-head attention is also going, and we are adding the text embedding and positional encoding information. So that basically means we're giving some additional signals, right? So we'll try to understand, I'll write down point by point what is the importance of this. So residuals is basically over here. Then after doing the normalization, we basically send it to the feed-forward neural network. Right? So these are all the steps that we are specifically using. In feed-forward neural network, it will be something like this. This will basically be my input. The input will be based on all these dimensions that we're getting. And then we have one hidden layer. In this hidden layer, we have somewhere around 5 to 12 hidden nodes. Okay. And then I have my output layer. Okay. So this will basically give you the output based on the information that I have, based on the number of vectors that is probably coming up. Okay. So here, that is what is basically happening. And this is the input that is coming from this. Right? All the input that we are specifically passing, and it will get trained. Once I do all these things, then it is sent to the next encoder. And the next encoder will have all the information with respect to all these vectors that I have. Right? But understand, when I say 5 to 12, this is with respect to every word. Every word is basically converted into 5 to 12 dimension of vectors. Okay. Now this is what the basic information, but there's still more information if I go inside self attention, right? Self attention. So what are the parameters that is specifically used, right? There are 3 to 4 important parameters over there also. One is your Q, query key value. So what dimension this query key value is, right? Based on the research paper, this is 64, 64, 64. So you'll be able to see inside self attention when I do the product of query into K, right? Later on, when I normalize and when I have to divide, right? I divide by root of 64, which is nothing but 8. Okay. This is what we are specifically doing, right? We are dividing by 64, and the number of attention of head is basically 8, right? So all this information I've actually mentioned. So these are some of the basic parameters that are specifically used in research paper. Now the question is coming, right? Krish, why 5 to 12? Why so many number of encoders? Because you understand this. The kind of task that you do is kind of sequence to sequence tasks. Sequence to sequence tasks are very complex tasks. They are very, very complex tasks, right? If I probably say language translation, it is a very complex, right? You have one language, then we're trying to convert that into other language. There'll be dialects, there'll be so many different things. Now, if I really want to convert this kind of task, just with one encoder, you'll not be able to get a very good accuracy. So we definitely need to use many encoders over here. According to the research paper, they have used 6 encoders and they were able to get good results. Okay. So this is one of the very important things that we really need to understand. Okay. The second thing that usually comes in your mind, right? And obviously everybody's mind. First of all, why residuals? Okay. Why you need to probably add residuals? Why need to probably provide some information over here and probably give it to the additional and normalization layer, right? This is the next question that many people will specifically ask, right? And the third question that probably comes, Krish, why to use feed-forward neural network, right? So that is also there in your mind because feed-forward neural network, here also we have used one kind of layer. Even though we are doing the backpropagation over here, we are updating the weights of WQ, WK, and all, right? So we'll try to answer step by step all these things. And again, after thorough research, what are the points? What are the things that have basically been there from the researchers? We'll try to note it down. Okay. And as I've already shown you, self-attention. This is what is the operation that is specifically happening. And this is just a 2 example, like encoder 1 and encoder 2. You pass your self-attention, you pass this particular information, your input embedding vectors. So this is basically your 5 12 vectors, right? So this is nothing but 5 12. This is also 5 12. Okay. Then positional encoding will also be 5 12. Then you have to add this. Then what you're doing, you're passing this information to the next layer, that is additional normalization. Then this gets passed to the self-attention. Then after that, a feed-forward neural network. Then for every combination of self-attention feed-forward, you are doing normalization. And why normalization specifically? I've already spoken about it, right? Your input distribution may be different here, and after doing all these operations, your distribution becomes different, right? So what we do, we basically do a layer normalization, which we have discussed in our previous video, right? So let's talk about the residual, right? What is residual over here? Any information that I'm passing it to the next layer. Here also I'm passing, here also I'm passing, here also I'm passing. And if you see in decoder also, here also you're passing. We'll discuss about decoder later on, but let's focus over here in the encoder. Okay. So residual connection, what it is also called as skip connections. Okay, that are used in neural networks. Okay. Now let's understand why residual connection is basically required. Okay. First of all, just imagine, okay, guys, I'm passing this information to the next layer. I'm skipping the self-attention. I'm also passing what was the input. So if I'm passing additional information, if I'm normalizing it, don't you think this layer will be having more information about the input, right? Even though we are able to probably do all the, we are able to convert that into a contextual vector by using self-attention, right? But based on the research paper, there are multiple reasons why it is basically used. So first one is addressing the vanishing gradient problem. Now, why do we say vanishing gradient problem? Because see, guys, here we have somewhere around 6 layers, right? 6 layers of encoders and 6 layers of decoder. During this particular case, you'll be able to see that as the number of layers increases, there are chances the gradient of loss function with respect to the weights can be very small. And this phenomenon is basically called as vanishing gradient problem. Okay. Now, how does residual help you in this? Okay. So I'm just going to write, how does residuals help you in this, or skip connection help you in this? It is very simple. Okay. Here, residual connection create a short paths. Very important part. Gradients to flow directly through the network. Okay. Because of this, the gradient remains sufficiently large. And this even in deep neural networks. Now see what is happening over here. I'm passing this information from here to here. I'm skipping this entire operation of self-attention, right? And I'm passing some additional information. So when this entire information is basically passed, you'll be able to see that we are creating a short path. Because see, in backpropagation, what will happen over here, all the weights will get updated. And here you're passing some additional information, right? So because of this, it creates a short path for gradient to flow directly through the network. Gradient remains sufficiently large. Okay. Now because of this, what will happen? The second very important point that I really want to mention, it improves gradient flow. When I say gradient flow, that basically means my convergence will be faster. Okay. Now, if I don't do this, I may face some vanishing gradient problem. Okay, it may also be exploding gradient problem, because if, let's say, if my weights is initialized in a higher way, right, in a very large values. Okay, so when convergence is faster, then obviously your training will be also smoother, right? Now coming to the third point, this actually enables training of deeper networks. Now here in the encoder, you can see that I'm just not using one encoder. I'm using 6 encoders. So this becomes a very large network, right? So very deep neural network, right? So here, because of this, at every part of this encoder, we are doing this particular step that is called as residuals, right? So this will basically enable training of deep neural networks, okay? So you can basically say that residual connections allow for the effective training of much deep networks by addressing the gradient flow issues and making it easier for the network to learn identity mappings. This enables the model to be very expressive and capable of learning more complex functions, right? So this was about the residual connection that we have specifically discussed. Okay. Now let's talk about over here why we are using this feed-forward neural network. Okay. This also you really need to understand why feed-forward neural network. What is the importance of feed-forward neural network? Because I've just given one example with respect to feed-forward neural network. Obviously, if you know about ANN, ANN is nothing but it is a feed-forward neural network. So here, why feed-forward neural network? Again, based on the research paper, I will try to give you the definition with respect to some advantages. Okay. First of all, see, if you have created anytime an ANN, right? Let's say this is an ANN, and in the ANN, let's say in the output layer, you don't have any activation function. So this basically solves a linear problem, right? Sorry, this solves a linear function problem. But the main aim of feed-forward neural network is basically to capture the non-linear function. It is to solve the non-linear function, right? Now, in the non-linear function, how do we solve this and all? Obviously, we have seen, right? In every layer, we apply an activation function, right? And based on that, it is able to capture the non-linear functions, the most complex properties within a specific data set, right? The behavior and all, right? So similarly, feed-forward neural network will also do that same thing. Obviously, before the self-attention is able to do good tasks, but to capture more information for this complex task, we specifically use this feed-forward neural network. So what it does over here, I will just add one point that it is going to add non-linearity. Okay. Second information, and probably this is even not mentioned in the research paper, but I was reading an article and there I specifically understood about this. Okay, it is nothing but processing each position independently. Okay, now let's talk about this. Why it is important. Now you know that self-attention mechanism captures the relationship between tokens, right? What does self-attention basically do? It captures the relationship. It captures the relationship between the token. It processes the relationship in such a way that each token can attend to every other token, right? That is how it basically captures the relation, right? And that is the reason you don't require further transformation or feature extraction on the representation obtained from the self-attention. Okay. Now, how does feed-forward neural network help? This feed-forward neural network, based on the tokens, whatever context you are specifically able to get, it processes each token representation independently, right? Before, what it used to do, we are sending all the information with the positional encoding. That is how your self-attention will understand which words are probably coming first, which words are probably coming second, right? But if I talk about the feed-forward neural network, this processes each token representation independently. Now you may be thinking, what is so important about this? This means that for each token representation resulting from the self-attention mechanism, the feed-forward neural network applies the same two-layer neural network. As I said, there will be a two neural network, and this helps, since we are taking each and every token and we are trying to retrieve more specific information out of it, this helps in transforming this representation further and allows the model to learn richer representation. With the self-attention, we are definitely able to understand some of the information based on the contextual information. But by using feed-forward neural network, again, we are taking each and every vector for that specific information or for that contextual embedding. And then we are allowing the model to learn more representation from that particular thing, right? It's just like trying to explore more of the specific vectors that are created by the contextual embeddings, right? So this is why we specifically use feed-forward neural network. And if you know about ANN, which is a kind of feed-forward neural network, you can just understand with the help of forward and backward propagation what all information will be able to explore and get, okay? The third important point about feed-forward neural network is that already our network is really deep, right? So feed-forward neural network helps your model, helps your neural network to become much more deeper, right? So it basically adds depth to the model. And one important property about depth is that if you're handling all those vanishing gradient problem and all, as there is more depth, more learnings you will be able to get from the data. More learnings you'll be able to get from the data. So that basically means the neural network will be able to capture more and more information from that particular data. Okay. Now it's not like that you can probably use just 10 layers of feed-forward neural network, but this is doing one thing because the two layers is specifically able to do much more things over there, right? And again, when you say one more very important property with respect to feed-forward neural network, it also increases the model parameters. Okay. And because of it, it will be able to help us to generalize well with the training data and with the test data, which is unseen data. Okay. So this is more about understanding why feed-forward neural network, why this and all. But if I just go with the flow, I have each and every word that is passing to self-attention, add normalization, feed-forward neural network, then again passing through the next encoder. Now again, you may also have a question, Krish, why so many number of encoders, right? Again, as I said, sequence to sequence tasks are more complex. So as we are able to extract more and more information, more better it is, right? Tomorrow, if you're planning to create another kind of LLM models or any other models, you can also change this. You can use 4 encoders if you want and all, right? So after all this information is probably passed, then from here it goes to the decoder. Now in my next video, I'll try to make you understand what is exactly about the decoders. But in this video, I told you about the parameters. So let me revise what all parameters are specifically used. One is for the embedding vectors. Embedding vectors is nothing but 512 dimension. Your QKV is nothing but 64. Your multi-head attentions, how many multi-head attentions you have, it is nothing but 8, right? And then along with this, positional encoding will also be the same thing over here. And all the remaining information I've discussed, right? So yes, this was it from my side. I hope you like this particular video. This was about encoder architecture. I'll see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to transformers. Now it's time to probably understand about the entire working of decoders. Already in our previous video, we have seen about encoders. We have understood the in-depth architecture intuition and how exactly encoder works. Now let's go ahead and let's try to understand about decoder. To cover decoder and transformers, here I will be providing you a plan of action, how we are going to specifically cover these topics. So here you can see on the right hand side, you have this entire decoder working. Now inside just one decoder, you have these 3 important components, okay? Masked multi-head attention, multi-head attention and feed-forward neural network. I hope you know about multi-head attention, how it exactly works in encoder and all. You know that. You also know about feed-forward neural network. But one information that you'll be able to see from the encoders, right? And in the research paper, we know that there are 6 encoders like this. So the output of the encoder is basically passed to the decoder multi-head attention. Okay. So one line you will be able to see it over here. So we will discuss more about this, what exactly it is. Okay. So first of all, let's go ahead and see the definition. So here it shows the transformer decoder is responsible for generating the output sequence one token at a time using the encoder output, and the previously generated tokens. So from here also, we will be generating some tokens. Okay. When I talk about decoder, there are 3 main components, and we will be discussing them step by step. The first main component is masked multi-head self-attention. So we will try to understand about this. How does masked multi-head self-attention works and why do we use this over here? Okay. So this is the first important component. The second important component is multi-head attention. Now, I hope everybody knows what exactly is multi-head attention from the encoder, but we also say this as encoder decoder attention. Encoder decoder attention. So we will also try to understand about this. Coming to the third one, which is basically called as feed-forward neural network. So these are the most important components that you need to know about if you really need to understand about decoders. Just to give you an idea what exactly how does encoder and decoder work over here. So let's say if I'm giving some information to my encoder. So if this is my encoder and you know what is exactly there inside your encoder. So if I'm giving this inputs, let's say I want to translate this entire information, right, into some other language. So what will happen whenever I give some kind of input, this input from this output from the encoders will probably go to the decoder and it should be able to give your output one by one. So this will be my x1 y1 word. This can be your y2 word. This can be your y3 word. This is the basic difference between encoder and decoder. Here, x1, x2, x3, whichever is the words that I'm actually passing in the form of embedding layer, in the form of embedding vectors. These are all passed all at once. Okay, all at once. But when we see with respect to generation, you'll be able to see that my output will be generated based on timestamp. So one word at a time. At t is equal to 1, this will get generated, t is equal to 2, this will get generated, t is equal to 3, this will get generated, right? So that is the basic difference between encoder and decoder. And how this is getting generated, we will talk about this. So we will try to understand the decoder based on 2 mechanisms. One is training mechanism and one is through the inference mechanism. Okay, inference mechanism. Like during training, how this entire decoder is basically trained, and during inferencing, how I will be able, if I give any input to my encoder, how it is basically translating directly to some other words. Because while training, we will also be giving our real output over here, right? So this will, let's say this will be this is y1 hat, y2 hat, y3 hat. No, I will give y1 over here, y2 over here, y3 over here, and we will do some kind of masking also, padding and masking. That is what we are going to discuss about. Okay, so this is what we are specifically going to discuss about. In the next video, we are going to probably start with something called as masking. The first important thing, masking multi-head attention. So let me just go ahead and write down the topics, what all things we will be discussing over here. So here, the first component that we are going to discuss is something called as masked multi-head self-attention. Okay, so we are going to discuss about this topic, which is the first component in decoder. Okay, and remember over here, we will also go ahead and divide this. Let's say the first topic will be input embedding. Okay, and then we will again have this positional embedding. Second step, we will specifically do the linear projection. Now, I hope you know why linear projection is used for calculating your QKV. Okay. Third, we will be doing something called as scaled dot product attention. This also you know why we need to do it. Okay. Then over here, we will do mask application. And this is what is the additional step in masked multi-head self-attention when compared to the self-attention. Fifth step, we will go ahead and create this multi-head attention mechanism. Then coming to the sixth step, it is nothing but concatenation and final linear projection. And coming to the seventh important step is nothing but residual connection and layer normalization. So if you probably see a self-attention model, and if you see a masked multi-head self-attention, if I take multi-head self-attention, see in your encoder also you had multi-head attention, right? Multi-head self-attention. So what is the difference between multi-head self-attention and masked multi-head self-attention? That is, there is one more step which is called as mask application that is getting added. We will try to understand the importance of this, Okay, so in our next video, let's go ahead and explore this masked multi-head self-attention step by step by taking an example and seeing that what is the use of this masked multi-head self-attention. Okay, and here you'll be able to understand the basic difference between this one, right? Because see, over here also you have multi-head attention, here also you have multi-head attention, but what is the use of this masked multi-head attention, right? And we'll try to understand with respect to training mechanism first of all, okay? And then I will also be showing that during inferencing with respect to a new data, how this masking will specifically happen. So yes, this was it from my side. I will see you all in the next video where we'll discuss about all these points. Hello guys, so we are going to continue the discussion with respect to transformers, and in this video we are going to discuss about decoders. Already the plan of action that is probably given in the previous video, we are going to discuss about these 3 main topics, that is masked multi-head self-attention, multi-head attention, which is also called as encoder decoder attention. Why do we say it as encoder decoder attention? We'll try to understand. Then we'll also be understanding about the feed-forward neural network. But now if you see from the architecture, here you have your encoder, here you have your decoder. The differences between encoder and decoder is that instead of just having multi-head attention, here you have masked multi-head attention. So in this video we'll try to understand the importance of this masked multi-head attention, okay? And we'll also be seeing that how this entire transformers will also get trained during the training time, okay? So let's go ahead, and as said, in the masked multi-head attention, if you really want to understand, we will be going completely from the basics, okay? Like how we understood with respect to the encoders. Okay, so here you can see that I have a data set. So this is my data set. Now inside this data set, let's say I have a task which I really need to convert my English text into Hindi text. Okay, so I want to do a language translation from English to Hindi. So let's say there are 3 words like this in English, and for that you have 2 words with respect to Hindi. Now let's just consider one input data. Okay, and with the help of one input data, we'll try to understand. So this diagram that you see, this side is my encoder. Okay, just a single encoder, and this side is my decoder. Now during the training time, what will happen? This parameters, that is x1, x2, x3 will be going from here, right? Then we have our vectors. These vectors will get combined with positional vectors, right? Sorry, positional encodings. Once it is done, then we get this entire input embedding. Here you can see, right? So let me just go and draw this. So once I give my inputs over here, you'll be able to see that I will be able to get the specific vectors, and this is added along with positional encoding. So over here, with respect to the inputs, I will be sending x1, x2, x3, and this will be sent parallelly, right, in the encoder. Similarly, once this entire operation probably takes place over here, where it probably calculates your Q, K, V, it probably goes and find out all the attention heads like Z1 to Z8 according to the research paper, then it will do the normalization. Here it will be passing this information over here, which is my residual, then it will go to the feed forward neural network, and whatever output I'm getting over here, this is ready to go to this multi-head attention. But at the same time, you'll be able to see that my outputs over here, Y1 and Y2 will be going, right? And when we say output shifted right, what does this basically mean? This is a very important word. Now let's say, guys, over here I have 3 words. Here we have only 2 words, right? It is always a good idea that whenever this kind of discrepancy is there, we really need to make sure that we have a fixed set of characters, right? So for this, initially while we are sending output over here, we're going to make sure that we also make this text padded, right? So let's say now my padding will become like Y1, Y2, and over here I will be using a 0 padding. Okay, so let's say that I've used a 0 padding. Why did I use it? Because I wanted to make all the sentences of the same size. In this example, I've just considered 3 words, like kind of thing. The length is actually 3, but again, it depends on the data set, how long also you can actually make this particular sentence. So now when I say I have basically done the output shifted to right, that basically means I've also added 0 padding over here. Now with respect to the 0 padding, again at the last you'll be having 0, I will be getting this embedding. Again, this will go to my positional encoding, will create a positional encoding, will do the summation, and now it will send the data to the masked multi-head attention. So if you see from this particular point, right, in decoder also, this input embedding and positional embedding will occur, but here you're going to specifically do a kind of padding. Let's say, for example, I'm saying 0 padding. Why this is done? To make your sequences length equal. Perfect. Then here you'll be able to see we are going to the masked multi-head attention. Now what happens inside this masked multi-head attention? Let's talk about it. So I'm going to create this specific diagram. This will be masked multi-head attention. Okay, perfect. So here you have masked multi-head attention. Okay. Now with respect to masked multi-head attention, what are the steps that is basically going to happen? That is nothing but it is the combination of all these 3 steps. Okay, linear projection for QKV, this will get calculated. Then you have the scaled dot product attention, it will get calculated. We know this, right, in encoders also. Then we will be understanding about this very important topic, that is mask application. And finally, we'll go ahead and find out the multi-head attentions. We'll understand why this mask application is required. Okay, step by step, we will go ahead and we'll try to do it. Okay, so first of all, let's get an idea about why do we specifically do this masking work, okay? So which is basically a masked multi-head attention, okay? So before that, let me go ahead and take a very simple example. I'll show you with respect to all the steps that is basically happening in the decoder. This is also happening parallelly, okay? First, I will be getting the information over here. So till here, I hope everybody knows, but we need to understand what is basically happening over here parallelly when we are training it, okay? And here also all the information will be going all at once, but with respect to the output, I will be getting one by one output as I get it with respect to words by word, okay? Let's say if I want to get Y1 hat, Y2 hat, so like this, I'll be getting the output one by one, okay? So let's take one basic example, and I'm just going to discuss about this, okay? I'm not going to discuss about this because this is already done, okay? So let's take a very good example. Now in the masked multi-head attention, but before that, first of all, what will happen? Let's say that I have a sequence. Let's say my input sequence is something like this. My output sequence is over here in my data set. My input sequence is something like 4, 5, 6. Okay, and let's say my 4, 5, 6, and I'll go ahead and write 7. Okay, this is just my input sequence. I'm numbering it. Okay, then my output sequence is 1, 2, 3. Okay, so this is my training data that I have in my input and output. Okay, input and output. Now let's do one thing. Okay, let's see what will happen step by step. So first step is nothing but it is called as input embedding. In my decoder, the first step is nothing but input embedding and positional encoding. Now with respect to this positional encoding, what is going to happen? It is very simple, right? So here, let's say I know that my output is specified by this 3 characters, right? 3 characters. I'm going to probably make this into 4. How? I will be making padding over here. Let's say I'm considering the maximum length is 4 over here in all this particular data set. So I will just try to make it as 4. I've done it as 0 padding over here. Now with respect to every characters, okay? Let's say that every number is represented by a 4-dimension vector. 4-dimension vector. So here now how your output embedding will look like. See, output embedding basically, so this output embedding shifted to right, this output embedding. Okay. So here I will just go ahead and write my output embeddings will be very simple. Let's consider that 1 is represented by another vector. Let's say this is 1, 0.1, 0.2, 0.3, 0.4. Okay. Then I have my next embeddings 0.5, 0.6, 0.7, 0.8. Then I have my next embedding 0.9, 1.0, 1.1, 1.2. Okay. Then let's say that final one is 0, right? So 0 padding basically means it will be just 0 only. So I'm just going to write it down over here. So if I just consider this, my entire vector is represented like this. Okay. My entire vector or my entire sentence is represented like this. So this basically becomes my output embedding. Okay. Perfect. Now you know that my output embedding should specifically be going along with positional encoding. Okay, over here. So here you can probably see positional encoding is there. Let's consider that the positional encoding is 0. All the values are 0. So I will be getting the same output embedding. Okay. Now in the next step, what we do, we go to this masked multi-head attention. Now there are some steps that is involved in masked multi-head attention. So the steps line by line I will be saying. The first step is nothing but we go ahead and calculate the linear projection. Linear projection, that is nothing but for QKV. This also we do in encoder. You know the importance of this, right? Then in short, we are just calculating QKV. Okay. So once we do that, then the next step that we have is nothing but scaled dot product, and with the help of this, we calculate the attention. Right, attention scores, right? So that is what we specifically get with respect to the scores. And third step that you'll be able to see is something called as masked application. Masked application. Okay, so this is what we are basically going to discuss. And here we are going to discuss about 2 important mask application. One is look ahead, mask. Look ahead, mask. I will write it down. And this is like one more is basically we did the 0 padding, right? So this is nothing but it is a padding mask. So we will discuss about both the specific mask. What is this mask techniques? Okay, and then probably whatever steps is after this, you know that, right? We finally need to get our contextual embedding. So that the same thing we will be continuing and we'll try to understand it. Okay, so now let's me go back over here. So this is my output embedding, right? Now in the step 2, so this is my step 1, and remember the step 1 is we have added the positional encoding. My positional encoding is nothing but everything is zeros. Okay, so for cross 4 matrix everything is zeros, right? So here based on the same matrix I will be getting over here. Now coming to the step 2. Now in the step 2, what we basically do, we do the linear projection for Q, K, and V. Okay, so let's go ahead and create. What we are doing in this, we are creating query Q, key K, and value V. This vectors we will try to create. How do you create it? By multiplying with W of Q, W of K, and W of V. Let's go ahead and initialize W of Q is equal to W of K is equal to W of V. We will initialize this to identity matrix. So if you are initializing this to identity matrix, so anything that you multiply with identity matrix, so I will just go ahead and calculate Q. This is nothing but output embedding, whatever output embedding. I will just initialize it. See, at the end of the day, we will be learning the specific parameters. This will be multiplied by W of Q, which will be nothing but it will be output embedding only, right? Because this is an identity matrix, right? Similarly, if I go ahead and do the K, this multiplied by W of K, which will be nothing but the same output embedding. Similarly, I have my V, output embedding, multiplied by W of V, which will be equal to the same thing, right? So this is how we calculate the QKV, okay? At the end of the day, the QKV is nothing but it will be the same values. So let me just quickly copy this. So this is my final QKV for the first iteration, let's say. So my QKV is nothing but it is equal to the same thing, right? So till here, I hope everybody's clear. So this is how step by step it happens. And probably when I go to that multi-head attention, which includes self-attention and all, this is the first thing that is going to happen, right? I will be able to calculate it. Now the third step over here, we will go ahead and calculate our scaled dot product. Scaled dot product attention calculation. Okay, so we will go ahead and compute this. Okay, now in order to compute the attention scores, it is very much simple. How do we compute the score? I will just write a shortcut formula. Q we multiply by K transpose, right? And then we divide by square root of D of K, right? In this case, D of K is nothing but 4, right? Dimension of K, that basically means it is nothing but Q dot product with K of T divided by 2, right? We specifically do this, okay? Now, let's go ahead and do the further calculation for the scaled dot product attention calculation. And here, we will be taking the same data of Q, K, and V, okay? So now, what we are going to do is that we are going to go ahead and calculate our scores. Now, in order to calculate our scores, understand when I say Q multiplied by K of T, right? What exactly it is? It is the same matrix multiplied by the transpose of K, right? So this will, like, say if this is Q, okay? And let's say this is K, right? So first of all, I'm just going to probably multiply this with this 0.1, sorry, point. So it should be something like this, 0.1, 0.2, 0.3, 0.4, right? So this will be my K transpose. So that is the reason what we'll do, 0.1 multiplied by 0.1 plus 0.2 multiplied by 0.2 plus 0.3 multiplied by 0.3 plus 0.4 multiplied by 0.4. Then next one will be 0.5 multiplied by 0.1, 0.6 multiplied by 0.2, 0.7 multiplied by 0.3. Then you have 0.4, or sorry, 0.8 multiplied by 0.4. Then again, you will go ahead and calculate the third one. This will get multiplied by this. This will get multiplied by this. Okay. Then for the second time, what you really need to do, you need to take this 0.5 multiplied by this, 0.5 multiplied by 0.1, 0.6 multiplied by 0.2, 0.7 multiplied by 0.3, 0.8 multiplied by 0.4. Then what you'll do, then again, you'll take this entire number and then multiply with the second one, right? So here you'll be able to see I will be creating my separate key pairs, right? So this will be another key transpose where I'll say 0.5, 0.6, 0.7, 0.8, right? So this will be my another key transpose, then another key transpose will be this, then another key transpose will be this. So finally, when you do the specific calculation, and just to give you an idea how the calculation is given, I've probably written down each and every steps over here, but I've done the calculation over here. My final calculation will be nothing but this is simple, right? See, my QKV is all these numbers. When I say Q transpose of K of T, I have to take, this is my one query, right? This is my another query, this is my another query, this is my another query. And similarly, if I probably consider this as my keys, this is my another key, another key, another key, another key. So with respect to everything, I have to probably do the matrix multiplication or dot operation, right? So finally, you'll be able to see that I've already done the calculation. This will basically be my score. The score will be nothing but 0.3. Again, it will be 4 cross 4 matrix, 0.7, 1.1, 0.0. And then we will further do the calculation. 0.7, 1.9, 3.1, 0.0, right? And then I will be having 1.1, 3.1, 5.1, 8, 0.0. Here also, again, you'll be getting 0.0. I have to get this entire 0 because you'll be able to see that last one is just 0, right? Again, in order to show you how the calculation is specifically happening, so I will just make a matrix over here, let's say. So this is my first matrix. My first matrix will be 0.1 multiplied by 0.1 plus 0.2. It is a dot operation, and you should understand this. 0.2 multiplied by 0.2 plus 0.3 multiplied by 0.3 plus 0.4 multiplied by 0.4. Okay. Then coming to the next one, right? Again, what I will do, I will take this 0.1 again, okay, 0.1, and here I will take the same query, right? Same query, and I will multiply with this. So here I will go ahead and write 0.1 multiplied by 0.5, then 0.2 multiplied by 0.6 plus 0.3 multiplied by 0.7 plus 0.4 multiplied by 0.8, right? So this is done. Then what? I will go to my next one. Next one is nothing but, again, if I do the transpose of keys, because I have to, for one token, I have to basically do this multiplication or do this dot operation for all the other tokens, just to understand how much weight it is basically adding. Then this will, third one query of key will be 0.9, 1.0, 1.1, 1.2. So my third one will be something like 0.1 multiplied by 0.9. Then I have 0.2 multiplied by 1.0. Then I have 0.3 multiplied by 1.1 plus 0.4 multiplied by 1.2. Similarly, the last one will be nothing but this will become transpose, right? Then it will become 0.1 multiplied by 0. Then you have 0.2 multiplied by 0. Then you have 0.3 multiplied by 0 plus 0.4 multiplied by 0. So this is done, right? Overall, this is just for one query with respect to all the keys, right? The last key will be nothing but 0, 0, 0, 0. Then what we do, we go with the next query. This we'll try to multiply with the next thing. Then I will be getting my next matrix. Finally, when I do the summation, I'm going to get these values, right? 0.3. So this entire multiplication, if you do, it is 0.3. If I do entire multiplication and addition, this is 0.7. 1.1, 0.4. Then again, the next one, which will be my next one, like this. This will be my next one. In total, overall, you'll be able to see this is also like 4 cross 4, all the multiplication. And finally, you'll be able to get the attention scores. Okay. So this is my attention score, where we have specifically done scale dot product attention calculation. This is the first step. See, inside this, right, after linear projection of QKV, we basically do this, right? Now comes mask application. Now, what exactly is mask application? We're going to discuss about. So let's go ahead and discuss about it. So here, I'm just going to go ahead and write mask application. Now, first of all, you need to understand what is the purpose of masked application. Okay, and this is probably the most important topic, and I'll try to explain you this with multiple examples. Okay, here, first of all, I'll just go ahead and write it helps. Mask application helps managing the structure. Okay, the structure of the sequences being processed. Okay, and ensures the model behaves correctly during training and inferencing. Okay, now what are the main reasons of masking? Okay, so what exactly is masking, you get to know about it, but you can just understand that it helps to manage the structure of the sequence being processed and ensures the model behaves correctly. Okay, now let's talk about the reasons. Why do we specifically do masking? The first reason is handling variable length sequences with padding mask. Okay, now see, yes, as you all know, during the output, right, I told you, right, when I'm actually calculating the output embedding, I'm also making sure that I do zero padding so that both the sequence lengths are almost equal, right? So one of the reasons why we specifically do mask application is that because we need to handle variable length sequence with pad masking. What is the purpose behind this? Okay, you'll understand this. What is the purpose? The first purpose is that to handle sequences of different length in batch. Please just wait for some time. I will explain each and everything what I'm actually saying. To ensure, the second point is to ensure that padding tokens which are added to make sequences of uniform length do not affect the model prediction. So wait, now let's talk about the second point. To ensure that padding tokens which are added to make sequences of uniform length do not affect the model prediction. Now, let me just explain you this particular point with an example. Okay, let's say in my input data, I have a sequence. Okay, let's the sequence is something like 1, 2, 3. And in my output data, let's say this is my sequence 1. In my output, I have my sequence 2. In my sequence 2, I have something like 4, 5, and I have purposely done the padding over here. Okay, so here 0 is nothing but it is the padding token. Okay, we initially need to do the padding. Okay, perfect. Now, without masking, see, if I just give this data like this, okay, then in my data, since this 0 padding is there, this will influence, please note this point, this will influence the attention mechanism. Okay, the attention mechanism. Now you may be thinking, Krish, how? Right now you're just thinking, okay, 1 0 is actually added. But just imagine a real world problem statement when we do padding, right? Let's say I want to probably, I get the maximum length of the sentence is 100, okay, or 100 or 200, right? Let's say. And let's say in one of the output, I just have 2 words, y1, y2, okay? In one of the output, right, I have just 2 words, y1 and y2. So for this, what we'll do? We'll do the padding. And for this, 98 zeros will get added. When 98 zeros are getting added over here, and when we probably send the 0 padding to our self-attention mechanism, don't you think because of the 0, it will influence the entire attention mechanism? And this will in turn, what will happen? Lead to incorrect or biased predictions. Okay, this is the problem. So that is the reason over here we will do some kind of masking, and this masking will be making sure that this token, 0 padding tokens, are ignored. So for this, a kind of masking that we are going to do is something called as padding mask. Okay, so here we are specifically going to say padding mask. This padding mask is basically going to make sure that the tokens are ignored. Okay, so in short, if you really want to understand about the masking over here, masking is done with two important types, in two different ways. One is something called as padding mask, and the other one is something called as look ahead mask. Okay, and in transformer we take the combination of both of them, but we'll try to understand what is the importance of them. Okay, so let's take the sequences. I have 1 2 3 4 5 0. So this is my output in my training data set. This is my input in my training data. This will be sent to encoder, this will be sent to decoder, but we're still focusing on this, right? Now for this, since I have a 0, right, there's a padding token called as 0, right? So for this, how do we apply a padding mask? So what we do over here is very simple. Okay, first of all, wherever I find a sequence of words, if it is not having any padding, right? So what does padding mask does is that since we need to consider all the 3 sequences, so padding mask for the sequence 1 will be 1 1 1. I'm just taking as an example. Okay, so over here 1 2 3, because you don't have any 0 paddings over here, so I will be having the padding mask of 1 1 1. What about sequence 2? So sequence 2 padding mask will be 1 1 0. My 1 1 0, I'll talk about it because this sequences are available. Here I just have a 0 padding, so I'm just going to mention that 1 1 0. Okay, so this is basically my padding mask for my sequence 2. Okay, but we will just not stop here. Okay, we will not stop here. There will also be another type of masking which is called as look ahead masking. So let's talk about this look ahead masking. Then again I'll go back to this padding mask. Okay, so the second type of masking which we specifically use is something called as look ahead masking. You'll understand it. Why we are just using 1 1 0 for 0 padding token. Why we are creating a padding mask of this 0. Okay, because this will probably get added and multiplied. I'll show you. Okay, how things will happen. So in look ahead masking, this is basically called as, and this is used to maintain autoregressive property. Okay, see, one thing that you know, right, in decoder, whatever decoder I have, okay, let's say I'll draw it over here. This is my decoder. Okay, decoder work is to, let's say if this is my encoder, decoder work is basically to, whenever we give any kind of input to our encoder, this information will pass to the decoder, and finally I should be getting my input 1 by 1, right? 1 1 1, like this, 1 by 1. Okay, so let's say if I say, hey, how are you? Okay, so here you should probably in Hindi will say kaise ho aap, something like this. So one word should be coming up from this particular decoder, right? Now you know that in order to find out the output, okay, let's say my 3 words output is over here. If I want to get this word, or if I want to get probably if I want to predict this word, I need to have the information of this specific word, right? I need to have some idea about this specific word, right? I don't require this further word information, and that is how decoder will probably work, right? Similarly, if I want to probably get this specific word, I need to have the context of this particular word itself, right? So a very important point that I'm actually going to write over here. Why look ahead masking is specifically used, and why do we say maintaining autoregressive property? To ensure that each position in the decoder output sequence can only attend to the previous position, but not future position, but no future position. And that is what we want, right? We don't want the future position. We don't want the future information. Instead, from the previous information, I should be able to predict. And that is why we basically use look ahead mask. And why this is necessary? For different sequence to sequence tasks, like language modeling, or you can also say language translation. Right here, sequence is very much important. Okay, and to probably do the prediction, I don't require the information of the future token in my decoder, right? And that is how we predict the current token. Okay, so I hope you have got an idea about look ahead mask. Now let's see some example, and we'll try to find out how masking is basically done. Okay, and then we will again come back to this specific example. But let's see one simple example. Okay, with respect to masking. Okay, so here you will be able to see. I will take an example. Okay, so let's take an example. So example is that let's say I have a sequence like 4, 5, 0. Okay, 0 basically 0 padding. For this, what kind of padding mask I will create? 1, 1, 0. Done. Right. Now let's consider that every token is a 3-dimension. Okay, every token is basically 3 dimension. 4 is represented by 3 dimension, 5 is represented by 3 dimension, 0 is represented by 3 dimension. So that is the reason what we can do is that we can also use this mask padding and we can extend it to 3 dimension. So let's go ahead and extend it. Okay, so guys, now our task is basically to convert this 1D to 2D mask, right? And for that we need to extend padding mask to 2D. Okay, now how do we go ahead and extend the padding mask to 2D? Understand over here, whenever we have this 1, that basically means it is a real token. 0 is nothing but it is a 0 padded token. Okay, now let's take this example 450 I have represented as 110, considering that this is a real token, this is a real token, and this is just a 0 token. Okay, now in order to convert this 1D to 2D mask, you'll be able to see that each row in 2D mask will be a copy of the 1D mask. Okay. Now understand one thing, guys. This is really important to just understand. How do we apply 2D masking? Attention. Okay. So first of all, I've already created my 1D mask. So this is nothing but it is a 1D mask, 1-dimension mask. Now in order to convert 1 dimension to 2 dimension, for each token in the sequence, the mask should indicate which token it can attend to. Okay. Now when I say which token it can attend to, over here, when I am probably doing the encoding for this, if I'm converting this into vectors, 4 should probably take the context of this token, right? Similarly, 5 can probably take the context of this token. They should not take the context of this 0, right? I don't want my vector to get changed because of this 0. Instead, I want my vector to get changed with respect to 4 and 5, right? So these 2 tokens I really want, right? So what we are saying is that for each token in the sequence, the mask should indicate which tokens it can attend to. Okay. So based on this, if my padding mask is 1D padding mask is this, we will just go ahead and repeat this. I know 4 is there, right? So for 4 I will write 110. That basically means 4 the attention can be changed with respect to 5, right? Then if I go, and this is for the first token, right? This is for the first token. Similarly for the second token, I will go ahead and write 110. Why? Because I'm saying that hey, 5 also needs to probably change the attention based on this token 4, right? So both this context should be there. So that is the reason we have repeated 110. This token is basically for 4, this token is basically for 5. And if I probably consider with respect to this can impact this can basically impact this. Okay, this can be a context. I can also basically write over here token 1 attends to token 1, 2. Similarly, token 2 attends to 2, 1 or 1, 2. Right? So this can probably get impacted. Again, I'm telling you what is the exact meaning, why I'm saying it can attend to. Okay, this is important for you all to understand, right? When we say it can attend to, right? In short, we are basically saying that hey, this token 4 can attend to token 5 in the context of attention mechanism. We can change the context, okay, and we can change the representation. But the final one, if I probably see with respect to the token 0, I don't want this to impact anything. So when I convert this 1D mask to 2D mask, this is how it is basically going to look at, right? So this is my token 1, token 2. This both can probably change its own attention. So I'm writing 110. Similarly, I have 110 over here, then 000 over here. Okay. So this is how things work with respect to this, and I hope you got an idea with respect to this particular example. Okay. But we'll not just stop over here. Okay. There are many more things that we really need to probably go ahead and discuss. Okay. And that is nothing but we need to also go ahead and apply one more padding. Okay. And how do we combine both of those padding? We will try to understand that. Okay. But I hope you got an idea over here. So this is my extended padding mask. Okay. Then the next step, what we do is that we will go ahead and create our look ahead mask. Now, how do we calculate this look ahead mask? Look ahead mask is also based on which token can attend. See, this is completely dependent on the decoder output. And here the sequence is very much important. Now, if I really want to create the look ahead mask, I know, right, when I probably get the first token, I will keep it as 1. This will be 0, 0. Because the further context I don't require. Similarly, I will go ahead and write 1, 1, 0. The second token, if I'm probably getting it, it should have the context of first, not the future. And if I try to probably predict the third one, this should probably have the context of all the previous, not the further one, right? So since I'm working with 3 cross 3, so this will be my another 3 cross 3 matrix. Okay. And if I really want to specify this in a better way, it should be better that I create a separate arrays for this or matrix for this. So this will be 1, 0, 0. Then I have the next one, which is nothing but 1, 1, 0. And I have nothing but 1, 1, 1. Okay. Since we are using 3 cross 3, this is how it is basically going to look. Now in this kind of masking, you'll be able to see the top, everything will be 0, right? And in this masking, wherever the token is 0, I'll be making sure that I try to convert that into an extended mask where the 0 will be created in the similar way. Okay. Now the next step will be that we combine padding and look ahead mask. Why do we combine? With the help of padding mask, you'll be able to see that we are removing all the zeros, right? And how do we do this? It is very much simple. It is basically with the help of element-wise multiplication of 2 mask. Okay. Now in this scenario, if I go ahead and combine my mask, so combine mask is nothing but, we will go ahead and do the calculation. It's nothing but it's a simple dot operation. Okay, so here I will just go ahead and write, if you just do the multiplication operation, final output that I'm actually going to get is 1 0 0. Okay, then I have 1 comma 1 comma 0, and then I have 0 comma 0 comma 0. Okay, so this is my final matrix, and that is what we have done. We have done the multiplication of two important metrics, mask matrix in short. Okay, and this is how you have actually got it, right? Then the next step in this will be that wherever the value is 0, please listen to this very, very carefully. Wherever in the combined mask the value is basically 0, there we specify, okay, there we specifically specify infinity. Okay, the reason I will tell you. Okay, why do we specify infinity? But let us do one thing. Let us do all the steps for this particular data that we have created, right? For this data. So here I'm just going to copy this particular data because we are working on this. And here we discussed about mask application. We saw example, and finally we got the combined mask. Now for this data, we will go ahead and compute our mask. Okay, so let's go ahead and compute our mask. So here you can see this was my score, right? And with respect to this particular score, now let's go ahead and find out our look ahead mask. So here I'm going to go ahead and compute my look ahead mask. Now in order to get the look ahead mask, it is very simple. Here, how much I have? 4 cross 4, right? Now, with respect to 4 cross 4, again, this will be 1, 0, 0, 0. Then the next one will be 1, 1, 0, 0. Then I have this 1, 1, 1, 0. And then I have finally 1, 1, 1, 1. Since it is a 4 dimension, right? And here, this is my complete look ahead mask, right? And similarly, if I want to get the padding mask, okay? So in order to get the padding mask, and with respect to the padding mask, I know I need to have this in the extended to 2D format, okay? Single format is very simple, but 2D format, what we really need to do over here is that I'll go ahead and write 1, comma 1, comma 1, comma 0, because this is not important. Then again, I have this is dependent on this, this is dependent on this, this is in turn dependent on this, dependent on this. I'll again go ahead and write this one. Then I will be having my third one, 1, comma 1, comma 0, and then the fourth one will be nothing but 0, comma 0, comma 0, comma 0. Okay, so this is my padding mask, right? Now, when I want to probably create my combined mask, so it is nothing but, if I want to probably find out my combined mask, it is the product of look ahead mask multiplied by multiplication by padding mask. Now, how are we going to do this particular product? It is very simple. It's more like element-wise multiplication. This will get multiplied to this, this will get multiplied to this, like that, right? So finally, if you go ahead and do this calculation, it is nothing but 1 multiplied by 1, 0 multiplied by 1, 0 multiplied by 1, 0 multiplied by 0. Okay. The next one will be nothing but 1 multiplied by 1, 1 multiplied by 1, 0 multiplied by 1, and 0 multiplied by 0. Okay. Then again 1 multiplied by 1, 1 multiplied by 1, 1 multiplied by 1, 0 multiplied by 0. So when we say multiplication, this is nothing but dot-wise multiplication, okay? Element-wise multiplication, sorry. 1 multiplied by 1, 1 multiplied by 1, 1 multiplied by 1, and here I have 1 multiplied by 0. Okay. So finally, this is my output, and the output is very simple over here. I will be getting 1, 0, 0, 0. Then I have 1, 1, 0, 0. Then I have 1, 1, 1, 0. Then I have 1, 1, 1, 1, 0. So this is my final combined padding. This 0 is there basically to ignore all the tokens, padded tokens, and wherever there is 1, those are very important. Okay. Now the next step, which is really, really important, okay, which is about mask scores. We go ahead and compute our mask scores, and it is very simple. The mask score is nothing but wherever there are zeros, that is going to we'll just go ahead and add. You can just basically do something over here. Okay. So let's see this. Okay. Now here I have my combined mask. Okay. Now for getting this combined mask, for applying this combined mask, what we'll do, we'll apply this combined mask to this entire matrix. Okay. And the next step that you'll be seeing after this will be that we will try to convert this into a mask over here. And in this, instead of 0, here we're going to convert this into minus infinity. Why minus infinity? I'll just talk about it in a while. Okay. So here my next step will be converting everything into minus infinity. The reason is very simple, very, very simple to think over it. Till then I will go ahead and write this minus infinity. Wherever there is 0, that will get converted into minus infinity. Okay. So this in turn, I'm actually getting in the form of minus infinity. And again, we do the dot-wise operation with this, right? Wherever there is minus infinity, that will become minus infinity. Okay. So final mask score, you'll be able to see that. I will go ahead and just do the dot operation. So I'm going to get 0.3, minus infinity, minus infinity, minus infinity. Okay. And then you have this 0.7, 1.9, minus infinity, minus infinity. Then similarly, you have 1.1, 3.1, 5.1, and again you have minus infinity. Then you have 0.0, 0.0, 0.0, then again you have minus infinity. So this is your final mask score. Now, the most important thing that you really need to understand is why you need to have this minus infinity. So here you'll be able to see that one minor mistake that I did was that I told, hey, we are replacing 0 with minus infinity. No, minus infinity is getting added to the specific 0 value. Okay, and why this is actually done is that I'll just go ahead and write the reason over here. Okay, when we apply or when we try to add the specific value, okay, it is basically to zero out, or it is to remove the influence, zero out the influence when the softmax activation function is applied. Because the next step is applying softmax activation function. Okay. Now, when we apply softmax to minus infinity, you'll be seeing the answer, what you'll be able to get. Okay, this is crucial. This step is crucial to ensure that certain position, right? Example, if I probably consider padded tokens or future tokens in the case of look ahead masking, do not affect the attention mechanism. Okay, and obviously the impact of zeros will also get removed, right? When we apply a mask, we need to ensure that certain tokens do not influence the attention mechanism. We achieve this by setting the attention score for these tokens to a very high, large negative numbers. When the softmax function is applied to the scores, it converts this entire value will be getting converted to 0. Okay, ensuring that there's no much influence on the attention weights. So attention weights will not get impacted. Right? Because after we calculate the mask scores, what we are specifically going to do, okay, we have to probably convert or apply a softmax activation function. I hope everybody knows that, right? So that is what we are specifically going to do over here. Over here, we are just going to go ahead and apply our softmax. That is our next step. So let's go ahead and do the softmax. Because after this, we'll go ahead and add our values, right? So softmax scores that we're going to get is nothing but softmax, and here I'm going to use my masked scores. Right? Now, with respect to the mask scores, when I apply the softmax, here you'll be able to see that I will get 1.0. I've done the calculation. Minus infinity is basically going to convert into 0. Okay, you can go ahead and write this, and you can also check it out. This will be 0.3, 0.7, 0.0, 0.0. Okay. Then I have 0.3, 0.6, 0.6, 0.0, and then I have 1.0, 0.0, 0.0, 0.0. So this is my entire score that I'm actually getting. Okay, and then as you know in the self attention, the final step will be that we will do the weighted sum of values, right? So every number over here inside the softmax is going to get multiplied by this softmax score. Okay, is going to get multiplied by V. Okay, so here my attention output will be nothing but it will be softmax scores multiplied by the vector V. Okay, so guys, this is the step-by-step mechanism that specifically happens in the decoder, which is similar to encoder, but one additional step that you were able to find out was about masking, right? And what is the importance of masking? I will be giving you in this specific PDF in the word of writing so that you'll be able to understand. Masking in the transformer architecture is essential for several reasons. It helps manage the structure of sequence being processed and ensures the model behaves correctly during training and inferences. Here are the key reasons for using masking. One is basically to handle variable length sequence with padding masking because there will be many number of zeros. To handle sequence of different length in a batch to ensure the padding tokens which are added to make sequence of uniform length do not affect the model prediction. And second is basically to maintaining autoregressive property with look-ahead mask, right? The purpose is very simple, to ensure that each position in a decoder output sequence can only attend to the previous position or itself but not future position. This is crucial for sequence generation tasks like language, modeling and translation, where the model should not have the access to the future tokens while predicting the current token. Okay, so these are some of the important steps with respect to the masking. And now the next step that we are basically going to discuss about is add and normalization, and then what is this exact line and why this particular line is also coming up. Okay, so that is what we are going to discuss about in the next video. So yes, this was it from my side. I'll see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to our decoders. Already in our previous video, we have discussed about this really important topic which is called as masked multi-head attention, and we understood how different types of masking is specifically done and what is the purpose of the masking, right? Then after this, adding a normalization will specifically happen over here, and when I say normalization, layer normalization will basically happen, and this is the same layer normalization like how we discussed in the encoder, right? So from here you'll be able to see a residual connection is basically there, which is also called as skip connection. So this skip connection information is also going, right? So I will also go ahead and say skip connection, okay? And with the help of this, what will happen is that it'll get added to the output vectors that is probably coming from here, right? And how did we calculate the output vector step by step? Each and everything is probably shown in the previous video, right? We went to the softmax and we probably found out the softmax scores, and these were the scores with respect to the vector that I had, right? Now, what we are going to discuss about in this particular video is about encoder and decoder multi-head attention. Okay, so this multi-head attention is also called as encoder and decoder. Why it is specifically called as encoder and decoder? We'll just discuss about it, and you'll be able to see that two of the connection is specifically coming from the encoder output, right? So here from the encoder output, when I say encoder output, from here we are specifically taking the vectors of key and values. Okay, so we are going to probably take the vectors of key and value that is coming outside this particular encoder, and we are going to give it to the decoder multi-head attention. So from here you'll be able to see from the adding and normalization layer what information will be going from here. Whatever query vector is basically generated, right, that will specifically be going. Now you may be thinking, why query from here and why key and values from the encoder output? Okay, the reason is very simple. So here you'll be able to see from the encoder, right, from the encoder output, right, what we are specifically sending. We are sending a set of attention vector K and V, right? And other than this, you'll be able to see when the output from this, right, masked multi-head attention. So the output from masked multi-head attention, here we are sending attention vector Q, which is also called as query vector. Now this query vector is the information that we are specifically doing over here, right? By shifting the outputs to the right, then we are getting the output embedding, then we are probably getting the positional encoding. Okay, and there is one very important thing also I really want to discuss based on your input and output, and just I'll discuss in another 5 minutes. Okay, and why we are specifically doing it is very much simple, because you can understand that these keys and values, these are to be used by each decoder in its encoder decoder attention layer. And why specifically we are doing this? Because this entirely helps the decoder to focus on appropriate places in the input sequence. So during the training time, I know here we will be giving out training output, right? Whatever will be my y, and we need to predict y hat, right? So over here, with respect to what will be the query of y, with respect to this key and values that is coming from the encoder output, that both will be given when a set of three vectors of k, v, and query, which is coming from this masked multi-head attention, it will be given to the multi-head attention, which is also called as encoder decoder multi-head attention. And based on this, whatever is the necessary operation that specifically takes in multi-head attention, right? So in the multi-head attention, what will happen? Self attention will specifically happen inside that. Then you go ahead and multiply the query with keys. Then you apply your softmax. Then you multiply with the values. Then you probably calculate the scores. That exactly we have discussed about each and everything when we have discussed in the previous session, right? Where we have discussed about all the numericals, what is going to happen, right? Same thing is over here that is specifically going to happen. The k and v are going to come from the encoder output, and query is basically going to go from here, right? Then all the necessary operation will take place while the training, and then after this again adding and normalization will basically happen. And again here also you will be able to see whatever output I'm getting over here, right, with respect to the queries, that will be also forwarded to the next layer that is called as adding and normalization. This is just to make sure that more added information is gone to the next layer, right? So by this you will be able to understand that what multi-head attention will specifically do, and the major thing that is important for you all to understand that for this multi-head attention, from where the encoder output is probably coming up, what is the encoder output? That is a set of key value vectors, and the query vectors will probably come from here, right? And why do we do this? See, at the end of the day, when you have a data set, right? So when you have a data set, in this data set you have some input and output, right? In input, let's say you have x1, x2, x3. In the output you have y1, y2, y3, right? So while training, I have to pass x1, x2, x3 over here, right? So when we have this input, so we need to pass the input from here. All the process will basically happen. And with respect to that, while we are training this entire transformers with respect to our input and output, let's say the example that I'm actually going to take is about machine translation. So here also we need to pass the output, which will be my y, right? Y. Again, output encoding will happen, positional encoding will happen. Then after that, masked multi-head attention will happen, right? We have discussed about what masked multi-head attention is all about, right? But when we come over here, we need to make sure that based on this particular vectors, we need to map the key and value vectors for this. So the training mechanism will definitely know that how this query can be matched with this k and v, so that we will be able to focus on the appropriate places in the input sequence to probably predict the next word, right? And this is really, really much important for you all to understand. Okay. Then after that, you have this feed forward neural network and adding a normalization. This is the same thing that what we discussed in the encoder output. Now let me do one thing. Let me go ahead and show you one of the most amazing diagram, and by this you'll get a clear idea how the entire training basically happens. So again, this is the blog from Jalamar, and beautifully transformers has been explained over here. What I have actually done is that I've put up more stress on the research paper to explain you each and everything that's going behind the word. Okay. So see over here. So decoder side, what happens is that we know the components of decoder work as well. Okay. The encoder starts by processing the input sequence. So from here, all the input sequences basically start. The output of the top encoder is transformed into a set of attention vectors K and V. So from here, I'll be getting this K encoder and V encoder, right? Then they are used by each decoder in its encoder and decoder attention layer. Okay. So that is where they're specifically using them inside our decoder, where in the encoder and decoder attention layer, which is nothing but encoder and decoder multi-head attention, which helps the decoder focus on the appropriate places in the input sequence. Okay. Now let's see this. Okay. At timestamp 1, okay, we need to pass this entire information. See. At timestamp 1, this is the word JE. It goes to the encoder. Right? I mean, all these three words, JE, Sui, and then this vector is basically created. Then from this, we derive our K and value encoders, right? And this is passed to our decoder. For every decoder, we specifically need to pass. And initially, we don't pass anything for our training data set. Understand one thing, okay? So this is really important to understand. See, guys, initially, we don't pass any training data set, okay? From the second instance, once we generate this, then we will be passing our training data set, okay? While the training phase, I've also seen in some of the research paper where they say that, hey, the first word needs to be passed, and based on that, some prediction needs to be done. But again, in some research paper that I was seeing, and in some of the blogs that I was seeing, here, a start token will specifically go, okay? So let me do one thing. Let me open my Epic Pen so that I'll be able to explain you here also, okay? And you'll be getting a clear idea, like how things basically happen. But this diagram will actually showcase each and everything. So here I've got my encoder. Okay. Now the next step, this is my K and V value encoder. So here, what will happen? The first state, start token will go. Okay. Now this start token when it goes, again, this will be done with respect to embedding, positional embedding, everything. It will go to the next step. Then in our multi-head attention, right? This KV value will be taken, and whatever query vector is basically generated from here, that will be given to the multi-head attention along with this, right? And similarly, the next step will go. Once I is computed. Now once I is computed, what will happen? For timestamp 2, when we are doing the decoding timestamp of 2, something is going to happen in this way. See this. So for timestamp 2, see, let's start this entirely from starting. Okay, so from timestamp 2, what will happen? I will come. Previous output is I. Then it is going to go, right? Then all the steps inside the decoder will basically happen. This will be your encoding and key and value vectors. But with respect to every word that you're specifically getting over here, positional embedding will happen, and with respect to this particular word, your query vector will be created. Okay. Don't worry about linear and softmax. I'll discuss more about this in the next video, but I hope you are able to understand this, right? In the first instance, I will just pass a start token. It will take this, it will generate a query vector for that. It will take this, it will pass it to our multi-head attention. You know what are the steps in multi-head attention, right? But at timestamp is going to 2. Whatever output is basically generated over here, like I, that will get passed over here. Like previous output will be this, right? Then again for this vector is basically created. Again, key and value vector will be created. Then we go to the next step where our next word will get predicted. Similarly, we'll go and take this previous word, give it to the input into the decoder. Then again the third word, we'll go and give it to the decoder, and finally we'll get the output over here. So this sentence that is probably given over here, it will get converted in this specific way, right? So I hope you got an idea of this, right? So let me just go ahead and explain it once again, okay? So here, let's say this is my encoder, right? You know what is there in the encoder, right? So in the encoder, I pass all my words after doing the positional embedding. Let's say this is my output. From this, we take all our key and value vectors, we give it to our decoder. In the decoder, for the first phase in the training, we give a start token. Okay. Then what will happen? It will go to that masked multi-head attention. Then it will go to the multi-head attention, which is also called as encoder decoder. For this, K and V will be going from here, and query will be going from here, right? Then we go to the next step. So I've just drawn a rough diagram, but I hope you're able to understand it over here, right? So I'll just close this again, and let's do one thing. Let's quickly take this image, okay? So I will copy this image and I will paste it over here, okay? So please make sure that you have this entire steps recorded, okay? So what we do in the first decoding timestamp, we give all the words, we generate all these things, right? We don't give anything from here. Instead, what we'll do some kind of padding, we'll create a start token, right, initially, and then we'll go and generate this output I, right? Then I will be sent with respect to the previous input. Then we'll go ahead and compute the M. So this will be M. Again, M will be sent in my third timestamp, right? Similarly, all the further timestamp things will basically be happening, okay? So over here you can see at timestamp 2, whatever output is basically generated at timestamp 1 I, that is sent as the previous output, okay? So I hope you got an idea with respect to the multi-head attention, and you know what happens inside multi-head attention. I don't need to explain that because already we have discussed this. This is the entire training mechanism. Try to understand in this specific way. Training mechanism, okay? The training mechanism initially what is going to go over here. Then once we generate this particular output, this same output will be going as an input to the decoder for the next timestamp, right? So like that, we go ahead and continue it. So I hope you got an idea with respect to encoder and decoder multi-head attention. Now it's time that we understand the most important thing, that how do we calculate our output probabilities, and that is what we're going to discuss in our next video. So I hope you like this particular video. I'll see you on the next video. Thank you. Hello guys, so finally we are into the last stage of understanding about transformers. I know this entire series now probably is more than 5 hours of content, but you can just understand why this entire architecture is so amazing, right? It looks complex, but if you break down this entire architecture, you will be able to understand each and everything. And that is what, while explaining all these topics, I've actually done, right? So from starting from positional encoding to multi-head attention to feed-forward neural network, here also we discussed about mass multi-head attention, we went to multi-head attention, we also covered about feed-forward neural network. Now it's time to understand about the final layer of the decoder, right? That is nothing but linear and softmax layer. And through this, we basically go ahead and calculate the output probabilities. Now I will try to just make you understand. Again, this entire diagram is from that amazing blog, right, about transformers. And what I will do is that I will also go ahead and share that link with you all, okay? You can go ahead and refer it. So till here, what we have actually seen, we have seen all the kind of operation related to Q, K, V. Here, Q and K is basically going, V is basically coming from here. And again, we also have a lot of multi-skip connections, like from here to here, we are passing some information regarding positional encoding, then other information I'm passing it over here. Now let's finally do one thing. See guys, after this decoder is completed, right, at the end of the day, you're just going to get vectors, right? Now, how do we convert this vector into a word? That is what we're going to see in this session, right? So our main aim of this particular session is that how we will be able to convert our vectors into our output word. And that is what I'm going to discuss step by step. Now, first of all, here you'll be able to see there's something called a linear and softmax. First of all, we'll try to understand what exactly is this linear. So to begin with, this linear, or I will just go ahead and write the linear layer, is a simple, fully connected neural network that projects the vector produced by the stack of decoders. Okay, stack of decoders. And it basically generates some very large vectors, which we also call as that logit vectors. Okay, logits vectors. Now I'll talk about what is the importance of this logit vectors, and this is what a linear layer basically does. Okay, linear layer basically does. So let me go ahead and explain. A linear layer is a simple fully connected neural network that projects the vector produced by the stack of decoders, right? And it basically generates this into a large vector, which is called as logit vectors. Now, what exactly is this logit vectors? Okay, so we'll try to understand this. Let's say if our model, we have a specific model, if let's say our model knows more than 10,000 words, right? Let's say that there are 10,000 unique words, and this is my entire vocabulary, right? So in this case, my logit vectors will be 10,000. Logit vectors will be 10,000 cells wide. So here, instead of just having this many vocab size, we'll be having this 10,000 vocab size, okay, or logit size. Now, understand each and every block that you see in this logit vectors, it corresponds to a score of a unique word. So here, this specifically corresponds to a score of a unique word. What kind of score? We'll talk about it, right? It's just like mapping a vector to words, right? So for this, once I probably get all the vectors from the stack of decoder, I'm going to pass this through the linear layer. It is a fully connected neural network layer. And once we pass through this is going to give us an output of this much nodes, right? This many number of outputs of a vocab size. So number of words vocab, right? So again, over here you'll be able to see, it'll take this particular vector and convert this into logit vectors, okay? Then if you go to the next step, it is a softmax layer. Now you know why softmax layer is used. It is specifically used for multi-class classification. Multi-class classification. And in the case of multi-class classification, what will happen? As soon as I pass this particular vectors, every vector is basically going to give us a log probabilities, right? Now, this probabilities means what? Let's say if this vector has the highest probability, right? Or if this word has the highest probability, then my output will be this specific word. If this word has the highest probability, then the output will be this specific word. Okay. So here, in the second step, what we are basically doing is that the softmax layer turns those scores into probabilities. Now, since it is turning this into probabilities, if I probably do the summation, it will all add up to 1, right? That I hope everybody knows about, because that is the property of softmax layer. Then the cell with the highest probability is chosen as the output, is chosen, right? And the word associated with it is produced as the output, right? For that specific timestamp, okay? Or for that specific timestamp. Now I hope you are able to understand it, okay? So whatever output I get from the decoder, that is passed to a linear layer, which is a fully connected layer, and this output will be based on a vocab size, that many number of cells. And once this passed to the softmax, I will be getting a probability, and whichever has the highest probability, that will be my output word, okay? When we say vocab size, vocab size basically means if there are 10,000 words, for every index there will be one word, okay? So more to talk about, let's go through the entire training process now. So here I will talk about the recap of training, and here also I will take multiple examples. Let's say in my entire vocab size, I have this many number of vocabs. Let's say this many number of words are there. So in my vocabulary, I have A, am, I, thanks, student, EOS, okay? So that is the reason I'm given this as indexing, okay? Now for the first instance, what we do, if I don't just use a simple embedding technique, okay, I will just go ahead and use the simple embedding technique. So for every word, what we will do is that we'll try to use one hot encoding to represent it. So let's say this is my one hot encoding. Okay, this is my one hot encoding for the word M. Okay, so wherever M is present, since the vocabulary size is 6, so I will write 0.0. Where M is present, it will become 1.0, 0.0, 0.0, and 0.0. Okay, now, so during the loss function, what will happen? If I have started training the word, okay, if I have started training the word, and similarly, like if I want to have thanks, then this will become 1 and remaining all will become 0. Let's say that I have a problem statement where I need to convert this mercy, right? Mercy, I think it is in French. We need to convert this into thanks, right? And vocabulary size is over here for me, okay? So what will happen if I have an untrained model, right? My initial output may be something like this. See, I need to get this word, right? Thanks. So I need to get this value as 1.0. But if we see with respect to the untrained model, initially you'll be able to see these are different values. I may get different values for each and everything, okay? So this is how my output should come, but this is how I'm getting the output, right? So after this, what we do, we basically go ahead and calculate the loss function. Okay, loss function. Now this loss function is really important. That is where your backpropagation will specifically happen. Okay, and just to make you understand, let's say I want to completely frame this particular sentence. Okay, so just I'll take an example. Okay, I have a task where I give these words and it should probably form a sentence for me. Okay, so here I have A, M, I, thanks, student. If I really want to know the output, it should be like I am a student, and thanks we can basically write, right? I can basically say thanks. Okay, or let's say I don't want to use thanks even, because thanks will not be a very good thing in that particular sentence. Let's say if I give this particular word, I need to frame a better sentence. So here I can frame one kind of sentence like this: I am a student, and then we should basically get our EOS, right? So in this particular scenario, what will happen is that for positions also, right? For position 1, what will be my target model output and also for the real output, my target output in my output feature will be something like this, right? So my input is something like this. Let's see. I'll just show you over here. Okay. Let's say my input over here in my data set, and this is my output. In my input, I have words like A, M, I, thanks. Okay. Not thanks, student. Let's say I will go ahead and write student. Okay. Now my output is I will go ahead and write I am a student. Okay. Let's say this kind of output I really need to get. Now here, based on this particular actual output, I should be getting, like if I consider my vocabulary size as 6, I should be getting something like this, right? My position 1 should be I, position 2 should be M, position 3 should be position 4 should be student, and then finally end of statement. But what happens is that while we are training, with this particular data set after some epochs, during initial training, you'll be seeing that, hey, my output will not be that good. But after training for some time, let me just go and show you. After training for some time, you'll be able to see over here, I will be able to get something like this. I will become 0.93, then this will become 0.8, 0.9, 0.94, 0.98, right? And this is all because of loss function and epochs. And this all keeps on getting updated, okay? And that is what I really wanted to show you as an example. But at the end of the day, you'll be able to see that we will initially be doing encoding for this. But here we are just using one hot encoding. Different encoding can also be used, right? Untrained model may give you some kind of output, but again, we need to go ahead and compute the loss, and then we will do the back propagation, and then we will go ahead and compute all the weights, right, with respect to all your training data and all, right? So back propagation, the main aim is to reduce the loss, right? So after training from some specific output, initially my training model output will be like this, right? If I convert each and every word into one hot encoding, one hot encoding, one hot encoding, one hot encoding, right? One hot encoding. And this is with respect to position also. In position 1, I is basically having 1 pointer, so this is what is the one hot encoding for this. Then you have this, then you have this, then you have this, right? So once you do this is what is my output that I need to get. But my model, when it initially generates, it can generate something else, right? Then a loss will be calculated between both of them, and it will be reduced till we get this kind of values. And once I get this particular model out, and this is after the, you can probably say with respect to your fully connected layer, right? Over here. So the linear layer, that is what I'm actually talking about, right? And then once you probably compute the loss, you'll again be doing backpropagation. So this was overall the final linear and softmax layer, but I hope I tried my level best, whatever was possible. But just imagine, guys, 34 pages I've actually written just to explain this research paper, broken down each and everything, tried my level best, okay? But yes, there may be, again, some things that you really need to revise from the research paper, but I tried my level best, whatever was possible from my side, okay? But I hope you're quite happy with this explanation. I hope you're able to understand each and everything. So yes, this was it from my side. I will see you all in the next video. Thank you. Now, as you know, from past 2 years, like from 2022 end until now, right, generative AI is really the talk of the town, you know. And with respect to generative AI, if I talk about large language models, open source large language models, OpenAI doing such an amazing work. Now, Cloudy 3 is also there to compete OpenAI, you know, and Amazon is definitely supporting them. So you should know, right, what exactly is generative AI? How is it different from all these terms? Or what is the exact difference between AI versus ML versus DL versus generative AI? So I'll make you understand in this specific video. Probably I'll try to make this video from somewhere between 15 to 20 minutes. I'll be including all simplistic terms, very easy definitions, so that you'll be able to understand it. Because once you have that clarity, right, at the end of the day, right, you really want to probably become an AI engineer, you know, which uses all these technologies to create that AI apps. So let's go ahead and let's understand this thing. Okay, so as usual, when I probably start this session, you know, let us consider the entire universe, and in this field of universe, I would definitely like to call this as AI. Okay, now what is AI? Simple artificial intelligence. The main aim is to build applications that can perform its own task without human intervention. Now, this is the most important definition, right? Without human intervention. So it will be able to perform its entire task without human intervention. So let me just talk about it. Some of the examples, as we know, Netflix, right? It has an amazing AI recommendation system which recommends movies, right? Now here, human intervention is not required to probably provide you some kind of recommendation. Whatever things you're using, you're browsing the movies, whatever movies you're specifically seeing, you know, at that point of time, this AI model is actually helping you to provide you good recommendations so that you can stay for a longer period of time. Self-driving car is another example. Okay, so self-driving car is another example, right? Self-driving car. Now it is able to probably drive itself, you know, whenever turning is coming, everything it is able to do. See, at the end of the day, whichever field you specifically work, right? If I talk about AI engineers, this is very much important. If I talk about AI engineers, at the end of the day, you are actually creating an AI product, right? And this product may be integrated with the software product itself, right? If I say Netflix, it is a streaming platform, movie streaming platform. And if I talk about AI engineers, you know, they are trying to integrate some amazing models, you know, which involves fine tuning, which involves multiple things, so that you integrate in such a way that it is quite scalable. The machine learning engineer task will also come, right? So at the end of the day, we are specifically creating an AI product, and that product is getting seamlessly integrated with some, you can probably say web app or Android app or mobile app or edge devices, something as such. So I hope you got an idea with respect to AI. So it is mostly about building applications that can perform its own tasks without human intervention. Now let's talk about machine learning. Now, whenever I talk about machine learning is a subset of AI. So this is basically machine learning is a subset of AI, and the main aim of machine learning is to provide you stats tools to perform various tasks such as statistical analysis, visualization, prediction, and forecasting, right? So these are some of the examples that I've just written it over here. But at the end of the day, what is machine learning? It provides a lot of stats tools to probably perform the complete life cycle of a data science project that is specifically required. In every life cycle, from data ingestion to probably data transformation, feature engineering, you will be required some of the other concepts with respect to ML techniques, where this is a very important term, specifically if I say about, that is nothing but stats tools, okay? So machine learning is a subset of AI, right? And here, it's providing you stats tools to perform all this task, and this task is usually performed on what? On data. Now, why we do this? So that we understand about the data, right? So that the data will be meaningful. It will be able to convey some information to you, right? So that is where machine learning basically comes into existence. Now, coming to the next part, that is nothing but deep learning. So if I talk about deep learning, again, deep learning is a subset of machine learning. And if I talk about deep learning from 1950s, it's not like deep learning has become just famous right now. It has become famous right now because of amazing things like GPUs, technological advancement, open source libraries, and many more things. But this entire deep learning was built to mimic human brain, right? Human brain. We wanted AI, or we wanted machines to perform like how we human beings used to perform, right? How we human beings used to learn. So that is the reason, as I said, mimicking human brain, and that is where we have something called as multi-layered neural networks, right? Multi-layered neural networks. So I hope you got a clear idea about this. And here, whenever I talk about deep learning, the three important things that we specifically learn, right? Please understand this, because after this only we'll be able to understand about generative AI. So with respect to deep learning, the three important things that we specifically learn, right? ANN, right? CNN, and then we basically say RNN and its variants, right? And this is where, when I say RNN and its variants, CNN and object detection is completely for computer vision purpose, right? So if I talk about task over here, specifically you use computer vision. Over here, you specifically use for what kind of use cases? For text-related use cases, right? Text-related use cases, right? Or you can also use it for time series use cases, because that is how RNN and its variants are designed, right? Time series use cases. So ANN is definitely like how machine learning is basically trained. Similarly, you can train machine learning problem statement with the help of ANN also, right? So overall, most of the things that we specifically learn in deep learning are based on these three things, okay? When I say CNN, object detection, there are techniques like RCNN, many more things and all, right? Similarly, RNN, you have RNN, LSTM, RNN, GRU, then you have encoder, decoder, attention is all you need, then you have transformers and BERTs, right? So I hope everybody's learned from my playlist till here. Everything has been explained along with theoretical intuition and practical intuition. Transformer and BERT are something very advanced, and from here only we will be deriving the next thing, that is nothing but generative AI, okay? Because this is the backbone used in most of the LLM models in generative AI, transformers and BERTs, okay? So deep learning is mostly about this specific thing. At the end of the day, we are trying to mimic the human brain. We're trying to understand how human beings specifically learn. We also learn in the same way. Now coming to the next one, that is nothing but generative AI. Obviously, generative AI is a subset of deep learning again. And here, advanced things. Okay, so I will specifically talk about two types of models that we use in data science industry. Models, or two types of model training we specifically say, right? One is the discriminative. If I just want to say it as that, it's that's mostly like discriminative and generative models. Okay, so if I talk about deep learning models, they are mostly of two types. Okay, this is one and this is the other one. Okay, here you have something called as discriminative models. Here you have something called as generative models. Now you should understand, whenever I talk about generative AI, you should understand one very important thing. Generative AI is more about generating content. Okay, so these are specific models which will help you to generate new content, okay, based on whatever content it has already been trained on. Okay, if I talk about discriminative AI, it is mostly about tasks like classification, prediction, all this regression prediction. So all these tasks you can basically do. In short, over here, your data set that you have, right? This entire discriminative models are trained on labeled data set. You have to really understand this. Okay, labeled data set. Similarly, in the case of generative AI, if I really want to understand about the task, it is nothing but it generates new data trained on huge data set. Okay, if I really want to make you understand, right, in a simple way, if I just take, okay, I'm a person. What I've done is that I have probably learned or read 100 books on cats, right? So I've been trained on this many number of books, huge amount of data, right? Now what I being a person, if anybody asks me any questions with respect to cats, I will be able to answer all the questions in my own way, right? And obviously the answers will be accurate because I've already read 100 books on the cat. So similarly, if I talk with respect to generative AI, there are two types of models that we specifically learn. One is large language models, large image models. Large language model is with respect to text data. Large image model is specifically with respect to images and videos. So here, if a text is given, you can convert that into an image. If a text is given, you can convert that into videos. Here, large language model, if a text is given, it will be able to provide some response in terms of text, right? And if I talk about all the various categories of LLM models, just in some time I'll be explaining you that also. Okay, so generative AI in short, what it is basically doing is that here we have models that is already trained in huge amount of data, and the task of that specific models are based on any input, it will generate a new data itself. Okay, now to make you understand more about LLM models, right? So if I talk about more LLM models, right? Obviously, you know companies like OpenAI, you know companies like Meta, Google, Anthropic, right? And everybody's race in the race, right, to generate the best LLM model. So these companies are already doing really, really well. Anthropic basically comes up with a model which is called as Cloudy 3, right? Right now it is being a fierce competitor of OpenAI GPT-4, right? GPT-4. Then you have in Meta, you have open source models like Llama 2. Google, I hope everybody has heard about Gemini, right? In Google, an open source model has also come which is called as Gemma, right? Now, what are all these specific models? These models are nothing but these are specifically called as foundation models. Okay, these foundation models are also called as pre-trained models. Why we say it as pre-trained models? Because these are trained in huge amount of data, the entire internet data, huge data. It has been trained in huge data, the entire internet data, right? It may be code, it may be multiple things and all, right? Now, we can use this specific model for domain-specific use cases also. Domain-specific use cases also. And that is where a concept, something called as fine-tuning is used, right? And I've already created a playlist about fine-tuning also. I've explained concepts like LoRa, how you can basically do the fine-tuning, how you can do it with open source models and many more things, right? The fierce competition right now is basically to get the best foundation model, right? And right now GPT-4 Turbo, soon GPT-5 is also going to come, right? If I talk about open source model, Llama 3 is there in the pipeline, right? Cloudy has just recently launched Cloudy 3. Gemini is also coming up with Gemini Pro, more variants it is basically coming up. So the main race, if I probably talk about, is to create the best foundation model. Later on, many companies will be able to use this foundation model in the form of pre-trained models, or they will also be able to fine-tune with some own custom data set, right, to solve their use cases. So this was the entire idea about generative AI. Again, this is the video that I really needed to upload early, but yes, many people were waiting, requesting for this specific video. So I made you understand this entire thing by writing in front of you. So for more details with respect to generative AI, LangChain, now if I talk about LangChain, it is a framework, right? LangChain is a framework which will be able to work with all these specific models. At the end of the day, we will be able to generate RAG application, RAG application, retrieval augmentation query, and along with that, we'll also be able to develop some amazing chatbots. That is the main reason, right? Why LLM becoming very famous because of the chances of getting automated, right? We'll be able to automate the entire chatbot response things with respect to it. Not only that, it has a huge scope in multiple sectors also with respect to various use cases. This is mostly about LLM models. LLM models is with respect to large image models. Stability AI is a company which is specifically working in this specific thing, right? So I hope you like this particular video. For more videos related to LangChain, generative AI, LLM models, you can follow my other playlist of LangChain, OpenAI, and all, where you'll be able to see a lot of end-to-end projects. So I hope you like this particular video. I will see you on the next video. Have a great day. Thank you and all. Take care. Hello guys. Before we start implementing some of the amazing generative AI applications with the help of large language models or multimodal, it is very much necessary that you really need to understand how these LLM models are specifically trained. What is the step-by-step mechanism to probably train this particular model completely from scratch? Yes, with respect to practical implementation, it will not be possible because you definitely require a huge amount of resource, data, and many more things. But in this video, what I'm actually going to do is that I'll be taking some of the LLM models like OpenAI ChatGPT models. I'll be talking about Meta Llama 3 models and all, right? And when I read these research papers of all these specific models, they usually follow a specific pattern for training all these LLM models from scratch. And in this video, I will be talking about this entire steps, step by step. We'll try to understand it completely, right? Again, the main aim, the main goal of this specific video is just to make you understand how these LLM models are basically trained. And this is just a theoretical intuition. Practical intuition will not be definitely possible where you'll be training your LLM model from scratch. It definitely requires a lot of resources, right? So yes, let's go ahead and enjoy this particular session, and please make sure that you watch this session till the end because it is important. Thank you. So here I have actually created all these diagrams to just make you understand. But just to understand how ChatGPT was trained, I have explored a lot of research papers from the past month. A lot of different resources, materials that are available in the internet about ChatGPT, blogs. Even I've explored the ChatGPT website, the research paper that was basically generated for this. Everything I explored, and I found out multiple things to probably explain about this. I'll try to break this down. But before I go ahead, There's an amazing article written by Pradeep Menon. You should definitely check out this. I will be providing you the link in the description of this particular video. It looks completely amazing. It's explained in an amazing way. And this last two diagrams that you'll be seeing over here, right? If you probably explore this last two diagrams I've also copied and pasted. So definitely a lot of credit goes to this specific article, which is written by Pradeep. So I will just try to explain you again. Just but not. If you probably read this, you may get some amount of understanding. But currently, what I will do is that I'll give a lot of examples over here, right? So that you will be able to relate it, like how ChatGPT is trained. Now to start with, ChatGPT entire model is basically trained in 3 stages. Okay. The first stage we basically say it as generative pre-training. Okay. And before you probably really want to understand about ChatGPT, you should also check out my video on YouTube regarding transformers, okay? Because this is the base. So if you search for Krishna Nayak transformers, right? So here you will be seeing that I've created a live session over here. This specific video you should definitely refer to, because this is the video that I probably uploaded 2 years back. And if I talk about models like ChatGPT or Bard, they are specifically using transformers architecture, which has an encoder and decoder. Okay, so definitely check out this particular video if you really want to know about transformers. Okay, so in the stage 1, you probably train a generative pre-training model, through which you get a base GPT model. Then in the stage 2, you do supervised fine-tuning. I will be talking about each and everything of this, like how the generative pre-training is basically happening, supervised fine-tuning is happening, and then finally in the stage 3, you basically do the reinforcement learning by using the human inputs, right? So that kind of not human input, but I'll just say human feedback, right? So that is the reason it is written as reinforcement learning, human feedback. And finally, you get a ChatGPT model. Now, this first step that you probably see, the stage 1, right? Generative pre-training. What kind of data is basically required from the entire internet data, right? It can be website, articles, books, public forums, like a website which is they're probably having tutorials, a lot of things, right? So those all internet data is basically taken to train the ChatGPT. So let's go ahead and deep dive and talk about this, okay? But let me just give you a basic example, like what a LLM model looks like. Let's say that I'm a person over here and I am really much interested to know about dogs, okay? So what I did is that I have explored 5-6 different types of this big, huge 500 pages of books regarding dogs, and I've probably read it about it, and so I know many things about the dog. Now you can ask me any questions, so I will try to answer any new thing about that specific dog. That is only present in the book, okay? That is only present in the book. So this gives a brief idea about an LLM model, where you are able to answer something after probably getting trained or reading it from multiple books, okay? So this is just an example. But when we talk about the stage 1 generative pre-training model, so what exactly is basically happening over here? So first of all, let me make this as a full screen. Here you have an internet huge input data, okay? So here you basically have an internet huge input text data. You pass this data to the transformers, okay? Transformers, when you pass this huge amount of data to the transformers, in transformers you have encoder, decoder. I've explained about transformers a lot in my live session. Please do make sure that you watch that particular video. After this particular data, this huge data is basically trained with the transformers. It basically creates a base GPT model. Now, as you know, what all tasks the transformer will be able to do it. Transformer can, like they are able to do this kind of tasks like language translation, text summarization, text completion, sentiment analysis. So this is the kind of task that transformers can easily do. And just by training this huge amount of data, we are able to get this kind of task and we are able to solve this problems, right? Even in transformers, there's a concept called as attention is all you need, right? And based on that, all these tasks can be easily implemented. And I've also shown a practical implementation with respect to that particular live session also, right? Just in Google Colab notebook, right? If you have a good amount of data, you will also be able to implement this. Okay. So once this task is implemented, but our main aim is basically to use this ChatGPT model for conversation, right? What we want basically a conversation chatbot, right? So we want this functionality where we are giving a request and the chatbot is giving the response. That is the functionality we want. We don't want this independent functionality. This functionality can be combined in the response part, right? So in short, when we probably create a generative pre-training model, what we are specifically doing over here is that we are able to get this sub-task kind of task over here, right? All this language translation, text summarization and all. Now we need to convert this task in the form of request and response, right? So that is the reason why 3 tasks are basically required, right? So now what we do is that we go to the next step, that is next stage, supervised fine-tuning. Now what exactly the supervised fine-tuning is with respect to SFT? It is also called as SFT. Now in SFT, what happens is that in one side, a human being will be there, okay? Like say this is a human being over here. Let's say I'm sitting over here, right? And I'll talk about a very important role nowadays, which is very much famous, which is called as prompt engineering role. Okay, we'll also talk about that. Okay, so here on the left-hand side, one human will be there. On the right-hand side, another human will be there, and this human will be acting like a chatbot agent. Okay, so what happens is that whenever this human being sends a request, let's say it asks a question like, "Hello, how are you?" So another human will say that, "Yeah, I'm very good, I'm fine." Okay, some response will be there. Then again, this human will send another request. Then again, the another human will probably send a response. So like this, it will be having the request and response continuously. So these are some real conversations, and these all conversations will be getting captured. So guys, now this kind of real conversation will be converted into an SFT training data corpus, right? Now this SFT training data corpus will basically be in the form of request and response. Request will be your input and response will be your output. Okay, so like this, a lot of requests, a lot of different responses. It can be right for a similar kind of request. There can be multiple responses also. So they will try to first of all create this kind of training data corpus, and it will just not be 1 or 2 records, but millions of records, right? Millions of records. Now once this is basically getting created, you can see request is conversation history and response is the best ideal response itself, right? So this format of training data corpus will basically get created, and then it will then be sent to the base GPT model, right, for the training purpose. Now, once it is sent to the base GPT model for the training purpose, then over here, the optimizers, according to the research paper that is basically being used, the optimizer that is used over here is called as stochastic gradient descent, right? And from this, you are basically getting an SFT chatbot model. What is SFT? SFT I've already written over here. It is a supervised fine-tuning model with respect to ChatGPT, right? So SFT ChatGPT model I will be able to get after I probably do the stage 2 of supervised fine-tuning. Now, still there are a lot of problems with this. Obviously, it will be able to give you the answers, right? But this model, this SFT ChatGPT model, will be able to give you the output based on the data it is basically trained with. If I probably ask some other questions to this particular ChatGPT model that may not be there in this particular training data, then it will start giving you some awkward answers which you may have not been seen also, right? So this ChatGPT will start behaving in a way you'll also not know what exactly it is trying to say. And this all problems was faced also by the researchers when they were actually creating this. And that is the reason they came up with the stage 3, which is called as reinforcement learning through human feedback. Now, because of this step, the model that was now created was called as ChatGPT model. And right now, whatever things you're using with respect to ChatGPT 3.5 or 4 is basically using this reinforcement learning through this human feedback. Now let's understand what exactly is happening over here. And here I'm also going to give you a lot of amazing examples to just make you understand, because the most complex thing is not this. See, data creation is always a task that we probably do as a data scientist. Not this is also not a very difficult step, because there are transformers. We are using the same architecture. We are just taking huge amount of data and we're training with it, right? The most important step is this. Because of this, the accuracy of the ChatGPT has been increased in a tremendous way, right? Now, what exactly is this reinforcement learning through human feedback? So over here, when we have this SFT trained model, let's say a human agent gives a request, then SFT ChatGPT will give some kind of response. Now, similarly, for this kind of request, we may have multiple response also, right? We may have different response. Now, this is based on this particular response over here. You can see these are all my alternative response. Now, when I say through human feedback, where this new human has been put up over here in this, right? So once we probably get multiple different responses, now this human agent, what it will do is that it will try to rank all this response, saying that which is the most suitable response, right? Which is the most suitable response, or which is the best response. Based on that, ranking will get assigned. So here you can see response B is the best, then response A is the best, then response D is the best, then response C is the best. We are ranking all the responses. Now, based on this responses ranking, what we do is that we create a reward model. Basically, the researcher created a reward model wherein based on every response, they probably provide a score, right? For every response, they provide a score, and this score will be based on probability. So it becomes a binary classification. If the probability is high, right? If the probability is very, very high, probability ranges between 0 to 1. If the probability is high, that basically means that particular response is a very good response. If the probability is low, that basically means that for that particular response, the score is less, right? Now, this reward model. Now, obviously, if I'm explaining like this, it's very difficult to just understand. So let me give you an example over here. Let's say that there is a chef, okay? Now, this chef knows how to cook any kind of food, okay? Any kind of food. Now, suddenly in a restaurant, there's a request saying that from a customer, hey, I want to have a very good non-vegetarian food. Okay, it can be chicken, right? Something. I'm just giving some things, right? Like chicken, right? And I want to have it on dinner, right? Now, if probably the chef gets this kind of request, chef will not initially know like what food should I create. It depends, right? If the chef is from India or he's from some other foreign countries, they'll try to create that kind of things that is actually likable by the chef, right? So what chef will do now? It will first of all ask from many people, like what kind of food would you like? So this is the initial response that is taken. So these are all my response that is basically coming up, right? So these are all my response. You will be able to see that I'm picking it up, right? So chef initially will put up all the responses, right? And it will also ask that, okay, fine. Then what will happen based on this responses? It will try to rank it, right? How many people have told that similar kind of responses, right? If many people have told, okay, I like this specific food, obviously it can try to rank it, right? This can be greater than this can be greater than this can be greater than this can be less than this. Now, once we try to rank this specific response, now chef, what it will do is that it will try to create a reward model, and this reward model will be very, very simple. It will be a binary classification. Over here, cross entropy is also used, okay? Cross entropy is used. Now, based on this, what happens is that whenever the chef gives any response, right, it should be able to consider that whether we should go ahead with this particular output or not, or whether should I cook this particular food or not, like that, right? So this is what is the reward model that is basically getting created, and this is based on the feedback. So the feedback is probably coming from the human beings over here, right? So I hope you got the specific idea about it. Now, once the reward model is basically created, the reinforcement is basically applied by a technique which is called as proximal policy optimization. Now, based on this proximal policy optimization, all the things that is basically happening is that reward model, first of all, updates the reward based on the response that is probably coming from the ChatGPT model, right? And then it will also make sure that it will update the specific rewards by using this proximal policy optimization technique. Again, in this technique, if I probably I'll not explain about proximal policy optimization right now, but I'll make a dedicated video about this. But again, understand that this is a reinforcement technique wherein we will be able to improve the ChatGPT response, and based on that, whatever human feedback or response is coming up, it will try to make sure that it will try to increase the reward if the response is properly correct, right? So that is the thing that is basically happening over here. And finally, we basically get a ChatGPT model, and this rewards updation and policy model that is probably getting updated using the proximal policy optimization will happen continuously as the conversation is basically happening, right? And this is how the entire process of reinforcement learning happens through human feedback. See, guys, I know from this, whatever things you know, you are very much familiar with stage 1 and stage 2. You may also know how you can probably create this particular data set, right? That can be a manual approach, but yes, you can definitely do it, right? Only the most complex thing that usually happens is over here. But understand, if you are able to understand things, right, writing a code for this is also very, very easy. Probably you can do it. But it will not just be possible by any companies to do this, because they definitely require a huge amount of data set, right? Hello guys, so in this video I'm going to talk about the evolution of large language model. Right now you may be hearing about various LLM models that have been created by different companies, but to start with, large language models probably initially came up in 1967 called as ELIZA, and this was specifically used to solve some of the NLP use cases. Then in 1970 we had this another model. Then in 1918 we had this Excalibur, and in 1988 from here the advancement started happening, okay, which is with respect to the simple RNN. Then in 1997 you had this LSTM, and if you don't know, in 2014 we had the GRU RNN, right? So in LSTM RNN here you could see that we had a feature that was added with respect to long-term memory and short-term memory, and later on in 2017 this was the amazing breakthrough wherein attention mechanism was basically added in this architecture, which is called as transformers. So after coming into transformer in the next year itself we got BERT, and from this we got this amazing GPT models, okay. Now as we go ahead, in 2019 you got GPT-2, Robert and in 2020 you found out GPT-3, right? And that is where your OpenAI right now, many people are specifically using ChatGPT and all, right? So OpenAI probably came up with this amazing ChatGPT applications by using this GPT-3. Then in 2021 they moved to GPT 3.5. In 2020 still Google also came up with Palm models, Instruct GPT and ChatGPT. So these are some fine-tuned models itself. And if I probably consider with respect to 2023, Meta also came into picture wherein they brought their version of Llama models. Then again OpenAI came up with this GPT-4. Then Palm 2 was there, Bard was there, Dolly was there, and many other models were specifically there, like Falcon. going forward, right now the advancement are still happening, because if I probably consider 2024, so in 2024, OpenAI has already come up with this amazing model, and this time it has come up with this multi-model, and the multi-model is nothing but it is GPT-4o, okay, and with this you will be able to perform tasks with respect to both NLP and images, okay, you'll be able to even generate the images itself, right? Along with this, Google will not be left behind, right? So in 2024, Google already they have come up with its Google Gemini Pro, right? Google Gemini Pro model, so Gemini Pro 1.5, right? And along with that, Google Gemini Pro 1.5 Flash is also there. That specific model is there, and over here also we have somewhere around 3 variants which you can go ahead and serve with respect to Google Gemini models itself, right? Not only this, in 2024, there are many companies who are specifically coming up with this, right? Llama 3 is also there. Then you saw about Anthropic, right? With respect to Anthropic, you have this Cloudy Opus, right? Cloudy Opus models, right? And along with Cloudy, you also have all these models in Hugging Face also. So everywhere this is specifically present, even in Hugging Face, you'll be able to access this particular model. And right now, recently, I guess, Google Gemma 2 model has also been coming, and this is an open source model, right? So Google Gemma 2. If I probably consider Google Gemini Pro, this is a paid model itself, and for some hits or some request, this is given as a free. But if I consider OpenAI GPT-4o, these all are paid models specifically. This is an open source model. So this is just to give you an idea over here, like what all models were there, and the evolution of these large language models. It's like coming from 1967. A lot of research, a lot of development are specifically happening. Now, what we're going to basically do is that in our next video, we're just going to compare the speed and accuracy of all these kind of models, and it is very much important to probably know like which model is best and how the model are specifically doing in the industry, which people are specifically using it, right? And that is what I will be discussing in the next video. Thank you. So guys, already in our previous video, we have discussed about, if you probably see over here, we have discussed about this entire evolution of large language model. I went through this amazing website which is called as artificialanalysis.ai, and here specifically comparison is done with respect to various models that are probably there right now. So here you can actually see with respect to the quality right now, GPT-4o is having the best quality, right? If you see Cloudy 3.5 Sonnet, then you have Gemini 1.5 Pro, then you have Cloudy 3 Opus, then you have Gemini 1.5 Flash, then you have Llama 3 model, which is 70 billion parameters, which is again an open source, right? So here the combination of both open source and paid model has been probably considered. You also have Llama 3, which is an 8 billion parameter. Then you have this Mistral 8 into 70, then GPT-5 3.5 turbo, right? So with respect to quality, right now, GPT-4 is basically having the best. If you see with respect to speed, right now, Gemini 1.5 Flash is having the best speed with respect to inferencing. Then you have this Llama 3. Then you have Cloudy 3 Haiku. With respect to speed, basically means how well optimized the specific models are, and you can probably go ahead and check this. With respect to price, USD per 1 million token, and right now you can see Cloudy 3 Opus is the highest. The best is Llama 3, and this is with respect to again inferencing if it is specifically deployed in a cloud, right? So definitely go ahead and check out this particular website. Here you will be able to get many more information like which all models are basically best in general ability, right? So here from the chatbot arena, this data is taken. GPT-4o is high. Reasoning and knowledge over here, NMLU, GPT-4 is the best. Then with respect to coding, right? Cloudy 3.5 Sonnet is the best, and here you can also see Gemini 1.5 Pro, which is from Google, right? So many companies, right? See over here, and this is nothing but Anthropic. Here also you can probably see different models are specifically there, right? Over here, right? And everybody's competing to probably get the best model out there. Here also you can see with respect to quality and output speed, you'll be able to see Gemini 1.5 Flash, right? If the output is very high, but the quality is a little bit less, right? If I probably consider GPT-4o, if let's say the output speed is somewhere around 90 and your quality general index is very good over here, the value is 100, right? With respect to GPT-4 Turbo, the speed is less, but the quality is really good. So this is specifically with respect to the comparison that you see. Quality versus price, here we already saw Cloudy 3 Opus was really high, GPT-4 Turbo is somewhere here, and remaining all the models are very less with respect to the price. But the quality, I find out this Cloudy 3.5 Sonnet is best. Then you have other models like Gemini 1.5 Pro and all, right? Then output speed, you can see Gemini 1.5 Flash is basically having 165 tokens per second, over here, and then you can probably go ahead and compare with all the other models over here, right? Pricing input and output prices also you can probably see. See, whenever we have this instruct kind of models, right? These are basically fine-tuned models that are available over here. So you can just go ahead and compare this. These are some additional information, and if you just want to see that how many different types of supported models are there, here you have GPT-4o by OpenAI Turbo, GPT-4 3.5 Turbo, 3.5. Then with respect to Google, you have Google Gemini 1.5 Pro, 1.5 Flash, Gemma 2. Gemma 2 is an open source model. See, here you can see the differences between proprietary and open, right? When we say proprietary, this is basically a paid model. When it is open, it is an open source model over here, right? Gemma 7b Instruct is a fine-tuned of Gemma model, so it is also open source. Then you have this Meta. Meta basically comes up with all the models as open source, so here you can see all the open source models. Then you have Mistral, 2 models are open, and remaining all are paid. Then you have this Anthropic, all are paid. Cohere, 2 are open and 2 are paid. Then you also have this Open Chat. This is open right now. Databricks is also open. Reka, here you can see it is proprietary, and all the other things also you can probably go ahead and check. So a good handy website to probably go ahead and check the performance of each and every model. So I hope you like this particular video. I will see you all in the next video.